Hello everyone, I'm Siddharthan. Currently, I'm posting videos on the complete machine learning course, and this machine learning course will be 60 hours in total. In the last 2 weeks, I've posted two parts of this video, and this will be the third part of this particular course. Before getting started with this third part, I'll just give you a quick recap of what we have discussed so far and what you can expect in this particular third part. And this video will be 12 hours long. Okay. So the first part of this course consisted of like four modules. So the first module was on the machine learning basics, where we have discussed like what is meant by machine learning, what is meant by AI, deep learning, and so on. So we have also seen like what are all the different types of machine learning and all those details. So the next module was on Python basics for machine learning, where we have discussed about some of the basics concepts like loops, if conditions, functions, and some of that. And the fourth module was on data collection and pre-processing. So in this module, I explained you where you can collect the data and what are all the different data processing techniques we can have, and how you can process a numerical data set and how to process textual data set and so on. And we have also seen three machine learning use cases. The first one was sonar rock versus mind prediction, and then we have discussed about diabetes prediction, where we try to predict whether a person will be having diabetes or not. And the third was building a spam mail prediction system. So this was the first part of this course, and the second part consisted of two modules. So the fifth module was on mathematics for machine learning, where we have discussed about linear algebra concepts like vectors and matrices. The second was statistics, and finally we discussed about probability. And the sixth module again is a very important module, where we have discussed like how a machine learning model works. So what is like the concept behind it and how it learns from the data, so on. And we have also seen like how model selection works, what is the importance of it, and what is meant by this overfitting, underfitting, and how to avoid these issues. And we have also seen what is meant by this loss function, how to evaluate our model, and so on. And the next topic was about model parameters and hyperparameters. So what is the difference between the two, and so on. And then we have discussed about gradient descent. So these are all the two modules that we have discussed, and then we add like three other use cases of art disease prediction, Boston house price prediction, and loan approval prediction. Okay, and this third part contains one module, and this module is all about building machine learning models from scratch. So in this module, I have explained you about four models. So I couldn't add like the other model due to the length of this video. So there will be four models such as linear regression, logistic regression, support vector machine, and lasso regression. So each models will be having multiple videos where I have explained you about intuition of a particular model, math behind a particular model, and how to build this model from scratch, and how to implement this with a sample data. So each of this model will be having like multiple videos, so you can go through them. So in the next part, I'll try to add the videos for the model k nearest neighbors, so you can like watch that as well. Okay, so these four things will be covered in this video. So this may sound a bit complex and tough, but trust me, I explained you all the details in a more simpler way, so you will try like you can understand that well. So and also there will be like Python sessions where we will try to build these models from scratch in Python. Okay, so it will be a very good exercise for you. So I hope that you have a good time watching this video. Okay, so yeah, learning model, and there will be three videos for each machine learning model. So the first video will be on understanding the intuition behind a machine learning model, and the second video will be on understanding the math behind the model, and in third video, based on this understanding, we will try to build a model from scratch in Python. Okay, so this will be the structure for our course moving on. So in today's video, we are going to understand what is the intuition behind a linear regression model. Okay, so before getting started, in case you are watching my videos for the first time, in this YouTube channel, I'm making a hands-on machine learning course. And if you want to learn this course from the beginning, I'll give the link of my course playlist in the description of this video, and you can check that out. With that being said, let's get started with today's video. So before going into linear regression, I'll just give you a quick recap on how does a machine learning model works. So when it comes to machine learning, we have two main things attached to it, two main pillars that supports machine learning. One is the data, and the second one is the machine learning model. So what does a machine learning model does is we feed it with lots of data, and this particular machine learning model will try to learn from this data. So learn in the sense it tries to find the pattern present in this data. So based on this understanding, or based on this learning that the model has done, if we give new data, it can try to predict new values. Let's say, for example, we want a machine learning model to find the blood sugar level of a person. So in that case, what we will do is we will take a suitable machine learning model and we will train this model with lots of data related to diabetes. Okay, so once the model has learned from this data, if you give a new set of data, it can find what is the blood sugar level of a person based on some medical parameters. Okay, so this is how machine learning works. So there is a machine learning model and we feed this model a lots of data and it tries to learn this data. Okay, so this is how every model works. And now let's try to understand how does a linear regression model works. So let's try to understand this with an example. Let's say that we have a set of data. So we have totally 5 data points in this case, and in this case we have the experience in years. Let's say that there is a software engineering role, and let's say that we have 5 people, and we have the data as the number of years of experience for each person. So totally we have 5 people, and their salary based on their years of experience. Okay, so a person with a 0 years of experience, so this person can be a fresher, and the salary he makes is about 2 lakhs or 200,000 rupees per year. Okay, so for a software engineer role. So there is another software engineer and he has about 2 years of experience and he makes a salary or he makes an annual income of about 4 lakhs or 400,000, and a person with 4 years of experience makes a salary of about 800,000 or 8 lakhs, and a person with 5 years of experience make a salary of about 10 lakhs, and a person with 6 years of experience make a salary of about 12,000. Okay, so this is the data set that we have, a very small data set. And based on this data set, based on this particular data, we need to find what would be the salary of a person with 3 years of experience. Okay, so we have a set of data, and based on this data, we need to find this particular answer. So what is the salary that a person makes if he has 3 years of experience? So how we can find this particular answer? Think about this. So we can use a graphical method in order to find this answer. So let's try to draw a graph and let's try to plot these data points. So we have two axes, x-axis and the y-axis. And in the x-axis, we are taking the years of experience. Okay, so number of years of experience for a particular person. And in y-axis, we have salary of the person. So the annual salary of a person in rupees. Okay, so here we have a 0 years of experience, 1 year of experience, 2 years, 3 years, and so on up to 7 years. And here we have the salary of the person as 2 lakhs, 4 lakhs, 6 lakhs, etc. So in the x-axis the unit is 1 year, and in y-axis the unit is like one unit is equal to 200,000 or 2 lakhs. Okay, so the value increases by 2 lakhs. So this is the graph that we have, and we try to plot this particular data. So a person with 0 years of experience make 2 lakh rupees salary, right? So if we try to plot this, we will get the plot here. So 0, the x-axis value is 0 and the y-axis value is 200,000, and the second data point is 2 years of experience and the salary he makes is about 400,000 or 4 lakhs. So similarly, we have 4 years of experience and 8 lakh salary, and 5 years of experience, 10 lakh of salary, and finally 6 years of experience and 12 lakh salary. Okay, so the annual income. So this is the data points that we have, and we have plotted these data points in a graph. Now we need to try to fit this data to a particular curve or a particular model. So if you look at this plot, we can say that there is a linear relationship between x and y. Okay, so the x value and y value. That means if the value of x increases, the value of y also increases. So it is not the case where at a point the value increases and then it decreases. So there is no randomness here. So there is only an increase in the value. When the x value increases, the y value also increases, and there is no other trend. So we just have only one trend, that if the years of experience increases, the salary also increases. So for this particular case, we can fit all these data points in a simple straight line. So if you try to find a best fit for this particular data points, it will be something like this. So we cannot draw a line which fits through all the data points. So it is not possible to draw a line which fits through all the data points, because this is kind of an outlier. So this is not an outlier exactly, but this data points is kind of different from these data points, and this is the best line that could fit all these data points, right? Because these data points are closer to this line. So totally we have about 5 data points, and 4 out of these 5 data points are closer to this line except this second data point. Okay, so this is the line that fits this data. Now what we can do is, so we know that we need to find what is the salary made by a person with 3 years of experience. Now we can come to this x-axis, and we know that this is the number of years of experience. So we need to try to see where this point meets in the y-axis. So I'll just make a dotted line here. So this is the person with 3 years of experience, and based on this data, we got this straight line which fit through all these data points. And for a person with 3 years of experience, so this is the point where it is meeting the line, right? So if you find the corresponding y value, it will be looking something like this. So this value would be around 6,50,000 per year. Okay. So from this, we can conclude that based on this data, we can say that a person with 3 years of experience will make a salary of about 6,50,000. Okay, so this is the interesting insight that we are getting. So what we are trying to do is we are trying to plot the data in a graph, and we are trying to find a line or a model which could fit through all these data points, and then we are giving an x-axis value. So now if you give a x value, you can find the corresponding y value. Similarly, let's say that there is a person who is making a salary of about 14 lakh rupees per year. So in that case, we can try to join this, y-axis or y value to this particular line, and we can find the corresponding years of experience they might have. So this is the important application of this line. So this model is called as a linear regression, where we try to fit the data points to a normal straight line. Okay. So the application of this is we can find the y value given the x value. Here, x is the independent value and y is the dependent value, because the value of y depends on the value of x. Okay, so hence x-axis value or the years of experience is the independent value, and salary in rupees per year is a dependent value, because most of the time the person's salary will be based on the experience that they have, right? So this is one main thing that you can do. There is also another way where you can try to find this particular value or particular thing. So this is how machine learning model works, as I have told you before. So a machine learning model tries to learn from this data. Here this normal line has found the trend between the data, that there is a linear relationship between them, and if one value increases, the other value also increases. And this is how machine learning model works. They try to fit to this particular data set to find the trend between them. So this is how you can find this particular value graphically. And now let's try another method where we can find the equation of this line, and we can find the similar values. So now let's say that we have different set of values. So we have x-axis value and y-axis value, and the if the value of x is 1, then the value of y is 5, and the value of x is 2, the value of y is 7, and so on. And the value of y depends on the value of x. So y will be the dependent value and x will be the independent value, and whatever the value of y is, it is dependent on the value of x. Okay, so now let's again try to fit this in a graph. Okay, so we have plotted the data points in a graph. So we have x-axis values in the x-axis and y values in the y-axis. Okay, and let's try to plot these values. So 1 comma 5, the coordinate 1 comma 5. So the x-axis value is 1 and the y-axis value is 5, and we will get the plot here. And the second data point is 2 comma 7. So 2 comma 7 will be here, where the x-axis value is 2 and the y-axis value is 7, and so on. So totally we have about 5 data points. Now let's try to fit this data points to a curve. In this case also, we can say that we can use a simple straight line in order to fit all these data points, right? So you don't need to use a very complex model. You just need a straight line to fit all these data points. Okay, so now we need to find the equation of this line. So from our primary school, we have studied that the equation of a line is y is equal to mx plus c. Okay, right? So we would have studied this in our high school. So it is very simple equation. So y is equal to mx plus c, where m is the slope of the line. So x represents the x-axis value, y represents the y-axis value, and m represents the slope of the line, and c represents the intercept. Okay, so let's understand about the slope and intercept in the next slide. So I'll explain you how this slope and the intercept works, but just try to understand that this is the equation of a line, which is y is equal to mx plus c. Okay, so different lines will have different values of m and c, and based on these values of m and c, y value depends on the value of x. Okay, so if you have a value of x, and if you plug the value of x in this particular equation, you will get the value of y. Now let's try to see how we can find the value of this particular slope and intercept. Okay, and then we can try to find the equation, the actual equation of this particular line. So this is the general equation of a line, and we need to find the specific equation for this particular line. Okay, so let's try to do that. So we have the plot here, and this is the line that joins all these data points, and we know that the general equation of a straight line is y is equal to mx plus c, where y is the y-axis value and x represents the x-axis value, and m represents the slope and c represents the intercept. So now let's try to find the values of m and c. So m represents the slope. Slope represents the orientation of the line in this graph. So if you have a different slope, so what happens is, So I'll just show this in the previous slide. So if you have a different slope, your line would look something like this. Okay, so the slope of, so consider this is a straight line. So the slope of this line is different, and the slope of this particular line is different, and the slope of this line is different from this one. And if you consider the slope of this particular line, this is different. So the slope basically represents the orientation of the line. Okay, so this line has some particular orientation and it depends on the slope of the line. And now we have the intercept. Okay, so I'll just remove this. So you just need to understand that slope, if you change the slope of a line, then its orientation changes. So that's what you need to understand. And what is this intercept? So you can see that there is a difference between the origin. Okay, so this is the point where the line is starting, and this is the origin, right? And this particular distance is called as the intercept of the line. Okay, so this distance, so you can see that this distance is 3, right? So if you just look at this y-axis value, so 0, 2, and 4. So between 2 and 4, we have 3. So the intercept value or the C value is 3. So intercept value is the distance between this origin and from where the line is starting. Okay. So now let's try to find the value of M and C, the slope and intercept, based on the data points that we have. Okay. So the data points that we add are these values. So 1 comma 5, 2 comma 7, 3 comma 9, 4 comma 11, and 5 comma 13. So these are the data points that we have, and based on these data points we are going to find the values of M and C. So let's take 2 points, two data points, P1 and P2. Let P1 be this second data point, which is 2 comma 7. So the x-axis value is 2 and the y-axis value is 7, and the second point is 3 comma 9. So this is the, let's take this as P2 or the point 2, and this is 3 comma 9, where the x-axis value is 3 and the y-axis value is 9. And there is a formula to find the slope of a line or the orientation of this line. So the slope formula is M is equal to y2 minus y1 divided by x2 minus x1. Okay, so here we know that the point 2 is P2 and the point 1 is P1. So we need to take the later point as P2 and the smaller point as P1. So this will be our point P2 and this will be our point P1. Okay, so now this 2 represents the value x1. So just look at this formula. So we have x1, x2 and y1, y2. Here 2 represents x1 and 7 represents y1, and 3 represents x2 and 9 represents y2, right? So you understand this, right? So p1 represents the values x1 comma y1, and p2 represents the coordinates x2 comma y2. Now you need to substitute these values. So this is the formula for slope, which is y2 minus y1 divided by x2 minus x1. Now we need to substitute the values. As I have told you, 9 is y2 and 7 is y1. So it is 9 minus 7 divided by x2 is 3 and x1 is 2. So we just need to substitute the values here. Now it will be 9 minus 7 is 2 and 3 minus 2 is 1. So you will get the slope value as 2. So it will be 2 divided by 1, which is equal to 2. So the slope of this line is 1, sorry, 2. So what does this slope represent? So it represents that for if the x-axis value changes by a unit of 1, then y-axis value will change by a unit of 2. So that's the importance of slope. If the x-axis value is 2 and 3, so there is an increase in the value of x, right, by a value of 1. And for each increase in value of x by a factor of 1, the y-axis value will increase by a factor of 2, as you can see here. So if we increase the value of x by 1, so we are just adding a 1 to this data point 2, and you will get a value as 3, right? And similarly, when you add the value 1, you will get the slope value or the y-axis value by the value will be added by the value of 2. So that is meant by this slope. So I'll just explain you this in a different manner. But before that, let's try to understand the intercept of this line. So we found the slope of the line to be 2, which is m is equal to 2. And now we need to find the intercept of the line. So I'm just taking another point 4 comma 11. So I'm taking this fourth point, which is 4 comma 11, where the x-axis value is 4 and the y-axis value is 11. Okay, so now we need to substitute in this particular equation. So we found the value of the slope to be 2. So I've just substituted the value of m as 2 in this equation. So y is equal to 2x plus c, and we need to substitute the values of x and y. So we know that the value of x is 4 and the value of y is 11. Now if you substitute all the values, so 11 is equal to 2 into 4 plus c, you will get the value of intercept as 3. So it is nothing but c is equal to 11 minus 8. So you will get the intercept value as 3. So which we have seen in the previous case as well. So as you can see here, so we found the intercept to be 3, right, graphically, and we have found using these equations and these formulas that the value of intercept is 3 and the value of slope is 2. So we can write this equation of this line here. So we found the equation to be y is equal to 2x plus 3, because we know that the value of slope is 2 and the value of intercept is 3. Okay, so you can take any 2 points. It is not compulsory that you need to take these 2 points. So you can take this particular first point and you can take this fourth point, and in that case also you will get the value of the slope as 2. Okay, so this particular line represents the slope. So this triangular part represents the slope, and you can also represent this slope as y is equal to dy by dx. So we know that this is nothing but the differential equation, right? So dy by dx. So dy means change in y and dx means change in x. Okay, so you understand that, right? So dy is the change of y and dx is the change of x, and dy by dx represents what is the change of y when x changes. So from this, we have found that if the value of x changes by a value of 1, then y will change by a value of 2. So that is the value of, this same, which is equal to 2. So you can also consider this. So if dx is 1, then dy will be 2, which represents the slope of the line. So the important so the another factor which we have discussed about is the intercept. So c represents intercept from where the line starts, right? So if you have the intercept as 4, then your line will start from this point 4. If you have the intercept as 7, your line will start from here. So in this case, we have an intercept of 3, and hence it starts from here. So the important inference that we are getting here is the above line equation is a function that relates x and y, right? So we get an equation, and this equation relates x and y. Okay, and for a given value of x, we can find the corresponding value of y. So similarly, let's say that we have a value of 3.5, and if you just draw a dotted line here and see where this line joins, and the corresponding value will be the value of y when your x value is 3. So this is the same thing which we have done with the years of experience and the salary example. So we try to find the salary of a person with 3 years of experience, right? So similarly, for a given value of x, you can find the given value of y. So this is machine learning. So machine learning is very simple. So you don't need to complicate things. So we are just trying to fit a curve or a line to a data, and we are trying to find the corresponding y value. So this is all about machine learning. So the only difference is that in all the cases we cannot use a straight line, so we may use a very complex model. So line is also a model. So this is a linear model, and we call this as a linear regression. So similarly, you can have a polynomial model and different kinds of models. So the model changes, but the concept remains same. Okay, so this is how a linear regression works, where we have two sets of data, the x value and y value. So we cannot have more number of dimensions. So we can have only one x value and one y value. So in that case, you can use a simple linear regression model or a simple line in order to fit those data to a straight line. Okay, and once you do that, your machine learning model or your linear regression model will learn from the data, and you can use this learned model in order to make new predictions. Okay, so this is all about linear regression, and this is how linear regression works. So now there is also a few other things which I need to explain you. What if there are more than two variables? So in the previous case, we have x value and y value. So we have two variables which are x value, x variable, and y variable, right? And I have told you that x is the independent variable and y is the dependent variable, because the value of y depends on the value of x. Now, what if there are more than two variables? What if there are more than two independent variables? So in that case, what you will do is you will use a multiple linear regression. So this is an example for a simple linear regression where we just have two variables, and the multiple linear regression is one where you will have more variables. So this is the definition of a multiple linear regression. So multiple linear regression is a model for predicting the value of one dependent variable based on two or more independent variables. Let's try to understand this. In the previous example of salary and years of experience, we just considered one variable, right? So the one variable here is years of experience, and the dependent variable is salary. Now, what if the salary of a person not only depends on the year of experience, but it also depends on his educational qualification? Let's say that the salary of a person depends on both the years of experience and what degree he has studied. So let's say that one person has studied B.Tech, so he has studied Bachelor of Engineering or Bachelor of Technology in Computer Science, and there is another person who has studied Master of Technology in Computer Science or Master of Engineering in Computer Science, and both of these people are 2 years of experience. So one person has studied BE Computer Science, and the another person has studied ME Computer Science, but both of them have 2 years of experience. Now we can logically say that the person who has completed ME with 2 years of experience will get a more salary, right? So in this case, there are three variables. So the one variable, the dependent variable, is salary, and the other two independent variables are years of experience and their educational qualification. In that case, you will need to use a three-dimensional model. Okay, so this is the example of a multiple linear regression. So this is not a line anymore. This is a plane, and if you want to be more accurate, this is called as a hyperplane. Okay, so when you have more than two variables, in that case, you will be using multiple linear regression where it tries to fit to the data by means of a plane. Okay, so you can consider this one axis as salary and this axis to be the number of years of experience, and this line represents the qualification, educational qualification of that person. Okay, so this is how the equation of the line looks. So this is the equation of a simple linear regression, which is, this is just the similar to y is equal to mx plus c, where instead of m we have represented b1, and instead of x we have represented x1, and b naught is nothing but the intercept c. So y is equal to c plus mx. So it is similar to that equation of a simple line. And this is the equation of a multiple linear regression, where b naught is similarly the intercept, and x1 is the one variable and x2 is the another variable. So similarly, you can have any number of variables you want. So often in machine learning, the data set that we have will about tens of features or even hundreds of features. So in that case, you can use a multiple linear regression where we have multiple number of features, and in that case we have multiple number of parameters. Okay, so the only difference is that you can use a simple linear regression, a straight line, when you have one dependent variable and one independent variable. And in case if you have one dependent variable y and there are multiple independent variables as x1, x2, x3, etc., and in that case you will use a multiple linear regression. Okay, so this is the difference between a simple linear regression and a multiple linear regression. And finally, let's try to understand about what are the advantages and disadvantages of this linear regression model. So linear regression is model is very simple to implement. So we don't need a lot of features. So we use linear regression when we have only two features. So we don't need a lot of parameters. We just need the value of the slope and the intercept. So that is enough for us. So that is one main advantage. So it is very simple to understand and implement. And the second advantage of linear regression is it performs well on data with linear relationship. So we have discussed an example where we tried to find the salary of a person based on the years of experience, and there is a linear relationship between them, which is if the x value increases, the y value also increases. So in that case, you can use a very simple linear regression. So you don't need to use a very complex machine learning model like random forest, or you don't need to use a very complex deep neural network in order to find this particular relationship. You can just use a simple line when there is a linear relationship between them. So these are the two main advantages when it comes to linear regression. And there are also some disadvantages to it. So as this model is very simple, and it is not suitable for data having non-linear relationship. Okay, so let's say that we have data something like this. So here you can see that this data is in the form of a sine curve, right? So there is an increase in the value of the data points, and then there is a decrease in the value, and again there is an increase, and so on. So here we have the value as t. So this can be time and this can be the y value, or you can just consider this as x value. So what happens here is when the value of x increases, the value of y first increases then decreases, and when the value of x further increases, the value of y increases and it again decreases. So this is an example of a sine curve, and this is not a linear relationship. So this is a non-linear relationship, and to be precise, this is a sine relationship between t and y or x and y. So you cannot use a straight line in order to fit this particular data. So no matter what line you have, you cannot fit all these data points to a straight line. So you cannot use a linear regression to the data points which does not have a non-linear relationship, and that is one main disadvantage. Okay, so a lot of real life problems, a lot of real life data won't be linear, so there will be a more complex relationship between them. So in those cases, you cannot use a linear regression. And another disadvantage is there will be a lot of underfitting issues in the case of linear regression. So we know that underfitting is something where a model cannot find the pattern present in this data, because a model is very simple, very general. So it leads to underfitting issues. So if you are not sure about underfitting, just go to my sixth module, and that module is on machine learning models, and that I have explained about what is meant by this underfitting and how you can rectify this underfitting. So you can watch that video. For now, I'll say that underfitting is when your model doesn't fit to your data better. Okay, so there is a lot of bias in your data. So that is called as underfitting, and linear regression often leads to this underfitting issue where it fails to find the relationship between the data. Okay, so that is example of an underfitting. So let's try to fit a straight line to this sign relationship. I'll explain you about underfitting here. Let's say that we are just drawing a horizontal line. Okay, so now we call this straight line as an underfitted model because it doesn't fit this data in a proper way. Okay, so hence we call this as an underfitted model, and there is a high chance that linear regression model will underfit. Okay, so that is one main disadvantage. And finally, sensitive to outliers. So when there are a lot of outliers, your linear regression model will be very sensitive to it. So outlier is nothing but when, let's say that there are about 10 data points, and out of these 10 data points, 8 data points are similar. Okay, so whereas the two data points are not similar to each other. Like if you consider this particular example, so there is some trend in this data. And what if there are points like this? So there is a point here and there is a point here. So this data doesn't represent other data well, right? So these are outliers, or these are noise in the data. And when there are outliers and noise in your data, and your linear regression model will change, the parameters will change based on those outliers. So when you have a lot of outliers in your data, and it is not very suitable for you to implement a linear regression model. Okay, so that's another thing which you need to keep in your mind. So the reason or I'm explaining this advantages and disadvantages is that you need to weigh all those advantages and disadvantages when you are choosing a model. So let's say that you have a data set and you need to find which model suits better. So if there is a linear relationship between the model, and if there is a linear relationship between the data points, and the data point doesn't have a lot of outliers, in that case you can go with a simple linear regression model. So you need to understand the advantages and disadvantages of all the models in order to make a better model selection. Okay, so you need to understand the advantages and disadvantages for that particular decision. Okay, so that's it about linear regression model, and I hope you have understood all the concepts about how a linear regression model works, how it fits to the data, and the two parameters which are the slope and intercept. And I hope you have understood about multiple linear regression which we use when we have multiple parameters. And I hope you have understood all the advantages and disadvantages of linear regression. Description of this video, you can check that out. With that being said, let's get started with today's video. So as I have told you earlier, in the previous video, I have explained you what is the equation of a line, which is y is equal to mx plus c, and the two parameters of the line, such as the slope and intercept. So as you can see here, we have a set of data here. So totally we have 5 data points here, which are represented as a small blue colored circles. So, and we have joined all these data points by means of a straight line. And we know that the general equation of a straight line is equal to this y is equal to mx plus c, where m is the slope. Okay, so it is the slope of this line, which is represented by this dotted triangle, and x is the x-axis value, y is the y-axis value, m is the slope of the line, and the c is the intercept. So c is this particular distance, the distance from origin to this particular point where the line is starting. Okay, and m is the slope. So there is a simple way to find the intercept of this line. You just need to substitute the value of x as 0. So when you substitute the value of x as 0, you need to find what is the value of y. In this case, if you substitute the value of x as 0, so you can see here the y-axis value in this particular case, in this particular point is 3. So it's between 2 and 4, and this particular point is 3. So when you substitute y is equal to 3 and x is equal to 0, you will get the c value as 3. Okay, so intercept is nothing but the value of y when the value of x is 0. So that is called as the intercept. And in this case, intercept is c, which is the value of c is 3. So in the previous video, I have explained you how you can exactly calculate the intercept value and the slope value. So here m is the slope of this line. So if you change the slope of this line, the orientation of the line changes. So what it means is, what is the change in y when you change the value of x? So as you can see here, We can also represent this particular slope as m is equal to dy by dx. So dx means the change in x and dy means the change in y. So the slope means that for a change in value of x by 1 unit, so we can see here that we have 2 and 3, and if the value of x changes by 1 unit, what is the change in the value of y? So this is called as slope. So for every change in x, we need to measure what is the change in y. So these are the two main parameters of the line, which are slope and intercept. Okay. So if you haven't watched my previous video, so you need to watch that video so that you can get a better understanding, and then you can move on with this particular video. So now let's try to understand the other aspects of linear regression. Let's say that we have a data and we have x and y axis here, and we have some data set and we are trying to plot this data set. So these are the different data points that we have. So this can be the number of years of experience for a person and the salary of a person. Okay, so let's say that there is a software engineer and there is a company, and this company provides the salary based on their work experience. Okay, so in this case what we will do is we will take the number of years of work experience in the x-axis and salary in the y-axis, and we try to plot the data points. So it's like, let's say that let's take this particular data point. So let's say that the corresponding x-axis value is 2, which means the person has 2 years of work experience, and the corresponding y value is, let's say that it is 2 lakhs. That means the person earns about 2 lakhs or 200,000 when he has a work experience of 2 years. So this is the data set that we have. Okay, so linear regression is nothing but a straight line. So we want to fit the data set to a straight line. So in this case, you can see here there is a linear relationship between x and y, which are in this case the number of years of experience and the salary, which means if x increases, the value of y also increases. So in other words, how you can say this is, if the if a person has more number of years of work experience, then the salary is probably going to be more, right? So when x value increases, y value also increases. So in such cases, you can fit your data points by means of a straight line. So in this case, the best fit would be a line like this, right? So this line doesn't pass through all the data points, but it is close to almost all the data points, right? So we need to build a linear regression model which is close to this particular line. So, but it is not easy to do that. So we can manually look at this data in this particular graph and we can draw this line, but it is hard for a machine learning model or a linear regression model to find this best fit in the first try. So a linear regression model cannot find which is the best fit. Okay, so this is also a line, right? So this is also a line which is the best fit for us, and this green color line also represents a straight line, and this is also a line, and this is also a line. So a linear regression model has to know which is the best fit for this particular data set. So it is, we can see here clearly that this line is not a best fit because it doesn't capture the trend in this data point. So in this case, so if x value increases, y value increases, and it is not represented by this line, right? So we have different lines here, and we need to find which line is the best fit for this particular data set. So totally we have about 4 models, and we need to find this. So each line, so we have different lines here, and each line has different slope value and different intercept value. Okay, so that is one main thing that you need to note. So with the change in the slope and intercept, the orientation and the position of the line also changes. So that is one main thing which you need to take note of. So totally we have 4 models here, and now we are going to understand how does a linear regression model finds a best fit. Okay, so that's the main goal for us in this particular video. So this is where loss function comes into play. So in our previous module, I have explained you what is meant by a loss function and how we can calculate the loss function. So I'll give the link of the loss function video in the description of this particular video as well, so you can check that out. So I'll just give you a quick recap of what is meant by loss function. Loss function measures how far an estimated value is from its true value. It is helpful to determine which model performs better and which parameters are better. Okay, so there are two values. One is the estimated values. So you can also call this as the predicted value, the values predicted by our model. So in this case, the model we have is our linear regression model, and the true value is the actual data points. So we need to find what is the distance between the true value and the estimated or predicted values. So the other main use of loss function is it tells us which model performs better and which parameters are better. So in the previous case, so totally we had 4 lines, right? So all these 4 are all these four lines are the same model. So it is a linear model, but the parameters are different. The parameters such as slope and intercept are different. And when you calculate the loss function of all these models, you can understand which is the best fit. So the best fit model will have a very less loss function. So we will go deep into that, after this slide, but let's try to understand that. So these are the same model, same linear model, but they have different parameters. And now we are going to see how to find this loss function of the model so that we can tell which model is the best fit for this particular data points. Here, as I have told you, there are two values. One is true value and the another one is estimated values or the predicted values. So let's say that we are taking this particular model and this is our linear regression model that we found. So this blue color circle represents the actual data set that we have, the actual data points that we have. And this red color line represents our model. And you can take any corresponding values. So let's say that we take x is equal to 2. So x is equal to 2 means the person has 2 years of work experience. So if you draw a straight line here, so I'll just change this here. So what I'll do is, so this is 2 years of work experience. So let's say that I'm just drawing a dotted line here. So in this case, so you have a point in this line, right? So let's say that this is a point in our line, which is our linear regression model. So this blue color circle in the 2 years of work experience is the true value, and this particular point is the predicted value. And similarly, you can take another thing here. So let's say that we take a line here. So in this case, what happens is this is the true value and this is the predicted value. So let's say that there is a point in this line. So this is the predicted value. So we need to find what is the distance between the true value and predicted value for all these data points. So when you do that, you will get the loss function of this particular model, and then we can find which is a good fit. So that's what we are going to do now. So totally we have about four models in this case. I'm going to show you how a linear regression model fits to this particular data set. So I've explained you what is meant by this loss function. And this is the formula for loss function. So loss is equal to 1 by n summation of yi minus yi cap whole square. Okay, so yi means the true value. Okay, and yi cap represents the predicted value or estimated value by our machine learning model. In this case, we are using a simple linear regression model. So y cap means the values predicted by our linear regression model, and yi is the true values. So what we will do is we will try to find the difference between the y value of both true value and the estimated values for each data points. Okay, and we try to find the difference between them and take square of this. And once we do this for all the data points, we will divide it by the total number of data points we have. Let's say that we have 10 data points. So in that case, what we will do is we will take all the 10 data points, the true value of all those 10 data points and all the 10 predicted values, and individually we will try to find the difference between them. And we will square all those differences separately and add them. So once we add them, we need to take the average of it. So in this case, n is equal to 10, because I told you that there are totally 10 data points. Okay, so this is how you can find the loss function of a particular model. So let's try to do that. Let's say that the model randomly assigns parameters as m is equal to 3 and c is equal to 2. So how does a linear regression or any model works is, so as I've told you before, so I just remove this 1 second. So we have different lines here. So this is an example of a linear regression as a normal line, and then this is also a line. This is so totally we have about four lines. So how does a model works is it will randomly assign parameters to this model. Okay, so that is the first step, which is to randomly assign values. In this case, we have two parameters which are slope and intercept. So let's say that our linear regression model assigns the random parameters as m is equal to 3 and c is equal to 2. So this is the data set which we have discussed before. So we have this data set and we need to find how this linear regression fits to this data point. So it has randomly assigned some parameters to the model. And if you just draw a line based on this parameter, so that would be y is equal to mx plus c. So that can be written as y cap is equal to 3x plus 2, right? So let's say that this is the line that we get based on these parameters. So y is equal to mx plus c, we know that. And I told you that y cap is the values predicted by our model and y is the true values, which is this blue colored circles. So y cap is equal to 3x plus 2, where 3 is the slope, so m is equal to 3, and intercept value is 2. Okay, so 2. So this is they are randomly assigned values for the parameters, and based on these parameters we have drawn a line like this. Now what the model will try to do is find the loss function. So we know that the loss function is the distance between the true values and the predicted values, and this value should be very less so that the model can be better fit. So if the loss function value is very high, that means the model is not a good fit for this particular data set. If the loss function is very low, the loss function value is very low, that means the line or this particular model is close to almost all the data points. So that is meant by the loss function. So let's say that this is the first parameters given by the model to this linear model. So this is a randomly assigned parameters. Now it will try to find the loss function. So these are the values of y and y cap, and based on this we will find the loss function value, because I told you that for finding the loss function value we need the true value, which is yi and yi cap. Okay, so in this particular example we have a lot of data points, so but we cannot calculate all these data points manually, so I'm just taking 5 data points in this case. Okay, so but this is not what actually happens. So in the actual case all the data points will be calculated. So the difference for the true value and the estimated value for all these data points will be calculated. But for demonstration purpose, I'm just taking these 5 data points. Okay, so we have x value, y value, and y cap value. So here this is x represents the value of x, and y represents the true values. So this blue color data point. So I'm taking just 5 values, and y cap is the value predicted by our model. Okay, so as I've told you, so with this dotted line, right? So these are the values. So when you substitute the x value in this particular equation, which is y cap, you will get this y cap value. So let's take this first data point. So in this case, x is equal to 2. So let's substitute the value of x is equal to 2 in this equation. So it will be 3 into 2, which is 6, plus 2, which is 8. And then we have 3. So 3 into 3 is 9, and 9 plus 2 is 11. Similarly, 4 into 3 is 12. 12 plus 2 is 14, and so on. So you need to substitute all the values individually. So once you do that, you will get all the values for y cap. So if you plot x and y cap, you will get this red colored line. Okay, and if you plot x and this blue colored value, this y value, you will get all these blue colored circles. So y is the true value, and this is our linear model, which is built using this randomly assigned parameter. Okay, so we need all the things that we have for to find the loss function, and in this case we are just taking 5 values. Okay, but in reality we will calculate the difference for all the values. So in this I'm just taking 5 values. So now we need to find the loss function. So this is the table that we have, and this is the loss function formula. So now we need to substitute the values in this particular formula. So we need yi, which is this particular value. So yi means all these individual values, and yi cap I, which is these values. So you can call this y cap or y at anything you want. Okay, so now let's try to find this loss function value. So yi minus yi cap. So we need to take for all the data points that we have individually. So first data point is 2, so x is equal to 2. So for x is equal to 2, y is equal to 10, and y cap is equal to 8. So you just need to substitute these values here. So it will be 10 minus 8 whole square. So there is a square here, right? So it's 10 minus 8 whole square. So we are taking summation, so we need to add it in this case. So and then we need to find the difference between 14 and 11, and we need to square the difference. And then we have 18 and 14. So again you need to find the difference and square the difference. And similarly it will be 22 minus 17 whole square, and 26 minus 20 whole square. So we need to find the difference between each predicted value and the true value. Here y cap is the predicted value and y is the true value. So you need to find the difference and square it. The reason we are squaring this is, so sometimes what happens is there can be negative error. Let's say that the y cap value is 14, or the y cap value is 15, and y value is 10 in this case. So in that case there will be a negative error. So we don't want positive errors and negative errors to cancel each other out. So for that we are just squaring these values, so that the positive and the negative error won't cancel out. So we will just remove the sign. So that's the reason for squaring this. So we also call this as a mean square error formula. Okay, so you just need to find the difference between them and square it and divide it by the total number of data points that we have. So in this case we totally have 5 data points. So once you find this, you need to divide it by 5. So when you subtract these values, you will get, so we know that So 10 minus 8 is 2 and 2 square is 4. Similarly, 14 minus 11 is 3 and 3 square is 2. So 18 minus 14 is 4 and 4 square is 16 and so on. So we need to find the difference and square them, and this is what we will get. So 4 plus 9 plus 16 plus 25 plus 36 divided by 5. So when you solve this, you will get the loss function value as 18. Okay. So this is how you can find the loss function value of any model. So here we need to understand one thing. So as I told you earlier, higher loss function means the model is not a good fit. So the loss function value should be as low as possible. So it should not be high. So if the loss function value is low, that means the predicted values and the true values are very closer to each other, which means our model is very accurate. Okay. So you need to make note of this, as low loss value means a very high accuracy, and high loss function value, which means low accuracy. So in this case, the loss value is 18, which is quite high, and we can say that this model is not accurate. So you can also see this from this graph. So this particular line is not close to all these data points in the upper side, right? So we cannot say that this is a good model, and this is represented in this loss function. So loss function of 18 is quite high in this case. So we cannot say that this is a good fit. This particular red line is a good fit. So what happens in this case is, so once the model understands that the loss function is more, it will try to reduce this loss function. So how the model can reduce the loss function? So what it will do is, it will try to change these parameters of 3 and 2. Okay. So and this process will go on. So there will be multiple iterations. So iteration, so what is meant by the word iteration? Iteration means repeating something, so doing some work repeatedly. So the model will try to fit to the data again and again, and it will try to find the loss function value or the error value. So as long as the error value is very less, so once the error value or the loss function value is low, then the linear regression model can understand that the model is a very good fit. So when this process continues, we will get a plot something like this. Okay. So we can say that this is a best fit because it is in the middle of all these data points, and it kind of fit to all these data points. So previously we had a randomly assigned parameters, and we get a model something like this, which is not a good fit. When you compare this model with this particular model, so we can say that this is a better fit than that, right? So this is how linear regression model works, where it will try to assign the random values for the parameters which are slope and intercept, and once it does it, it will try to find the loss function. So loss function is nothing but the distance or the difference between the true values and the predicted values. So if the loss function value is more, we what happens is, it will try to change the parameter values, and the process goes on. So we can also manually set the number of iterations we want, and what is the loss function value we need to give on such things. So that is more advanced case. So this is how linear regression model works, and this is how linear regression model fits to the data. Okay. So I hope you have understood all the things covered in this video, and that's it for this video. And in the next video, I'll explain you how we can build a linear regression model from scratch using Python. Okay. So that will be an hands-on video. So you need to have a clear understanding of the previous video, which is linear regression intuition, and this mathematical understanding, so that we can go on with the hands-on part, where we will try to build the linear regression model from scratch parameters for our model. So in today's video, let's understand what is meant by model optimization, and how we can use gradient descent algorithm in order to optimize our model, and how we can implement this gradient descent for linear regression. So once we understand this, we can build a linear regression model from scratch in Python. Okay. So this is the agenda for today's video. First of all, let's try to understand what is meant by this model optimization. Optimization refers to determining best parameters for a model such that the loss function of the model decreases, as a result of which the model can predict more accurately. So I have already made videos on what is meant by loss function. So loss function is a measure that tells us how far is the predicted value and the actual value. So it is like the distance between, or it is the difference between the predicted values and the true values that we have. And if the value of loss function is high, that means our model is not predicting correctly. So there is a huge difference between the values predicted by our model and what is the true values that we have. Okay. So we should have very less loss function value, and for this we need to have the best parameters. So I'll explain you this with an example. So what is meant by these parameters, and how we are going to optimize these parameters. So let's say that we have a set of data points. So we have x-axis and y-axis, and we have plotted some data points here. Now let's try to fit these data points to a curve. So if you look at this data, we can say that if x value increases, the y value also increases. So there is a linear relationship between x and y. So we can fit this data using a simple straight line. So this is a straight line, and let's say the equation of this particular line is y is equal to m1x plus c1. Okay, where m1 and c1 are the parameters of the line, where m is the slope and c1 is the intercept. So we have already discussed about this. So we have totally 8 data points here, and for this particular red line, these 4 data points are closer to this line, but these 4 data points are far away from this line. So if you measure the distance between all the data points and this particular line, it will give you the loss function value. Now let's try to fit this data points to a different line. Now let's say that we are using this line, and this line is closer to the 4 data points that are present here, but it is far away from these data points. And the equation for this particular line is, let's say that y is equal to m2x plus c2, and this m2 can be this m2 is the slope value, and again c2 is the intercept value. So the slope value for this line and the slope and intercept value for this line is different from the slope and intercept value for this line. So now let's try to find another line which fits to all of these data points. So if we take a line like this, it is closer to both of these data points, whereas in the previous two cases, the line was only closer to only the 4 data points. But in this case, it is actually an optimal model. So we can say that it is a best fit. So let's say that the parameters of this particular line is m3 and c3. So the equation of this line becomes y is equal to m3x plus c3. So we know that the equation of a line is y is equal to mx plus c, right? So that is the equation that we have here. And we can say that m3 and c3 are the best parameters because they are closer to all the data points that we have. Whereas in the previous cases, so the line is not closer to 4 data points, so which is similar to the first model that we have. So we can say that this third model is the most optimal model, and it has the best parameters that we have. So in order to find this best parameters, we need to optimize this model, and this is where we are going to use gradient descent. Now let's try to plot the parameter values and the loss function values. So in the previous case, we had three set of models. So the first model that we had parameters of m1 and c1. The second model has the parameters of m2, c2. Similarly, the third model has a parameter of m3, c3. Similarly, we are taking different set of parameters and we are trying to find the corresponding loss function value. Okay, so when you plot the parameters and the corresponding loss function value, you will get a curve like this. So let's try to understand a U-shaped curve like this. Now let's try to understand what is the significance of this curve. So whenever we are trying to plot the data, or whenever we are trying to fit the data points to a model, we will randomly initialize the parameters for the model. Okay, so let's say that we are randomly initializing the values for our linear regression model. So we know that for linear regression, the two parameters that we have are m and c, right? So we are randomly initializing the parameter values as m1 and c1. Okay, so let this be 1. So m1 and c1. For this set of parameters, we get a loss function as this. Okay, so this is the corresponding loss function value, and from this curve we can say that this loss function value is very high. So we need to find a point in this curve where the loss function value is very minimum. So the minimum point in this curve, the deepest point in this curve is this, right? So at this point, the loss function value is very less. So this point is called as global minimum. So a global minimum is the point in this curve where if you choose the parameters at this particular point, you will have a very minimum loss function. Okay, so that is the point called as global minimum. So this global minimum is the point which will give us the optimum set of parameters. So the loss function value is very less for this particular set of parameters. Let's name this as m3 c3. Okay, so m3 c3, because in the previous case also we have discussed, right? So m3 c3 is the best fit for our model because this has the very less loss function. So this will be our optimum model. So let this be 3. So I'm not good at writing in the PPT, just bear with me. So this is the global minimum. So from this point, we need to reach to this particular point. So we do that by reiterating over the data. So we will try to change the parameters values. So we will try to constantly update the parameter values from M1, C1 to try to find which is the optimum parameters. So we will reiterate to over the data. Reiterate means we will make our linear regression model to go through the data again and again. So once we do that, at a particular point, we will reach this global minimum, and at this point, our model can understand that we have a minimum loss function value, and in that case, it will choose this particular parameters. So the significance of this curve is, if you go beyond this parameter, if you change or if you increase the parameter values beyond this point, then the loss function value increases. If you reduce the parameter values below this point, then also the loss function value increases. So you should not increase or decrease your parameter values beyond this global minimum. So this is our most important parameter, or this is our best parameters. Okay, so that is what we will do when it comes to gradient descent. So we will try to minimize this loss function by constantly updating the parameters, by constantly changing the parameters and trying to find which parameter has the minimum loss function. So let's try to understand this mathematically, how this gradient descent works. So gradient descent is an optimization algorithm used for minimizing the loss function in various machine learning algorithms. So it is not only used in linear regression, it is used in any kind of linear machine learning models, and it is also used in the case of deep learning as well. So we will try to minimize the loss function by constantly updating the parameters of the learning model. So in this case, we have constantly tried to update the model, right? So by constantly updating or changing the parameters, we will try to minimize the loss function value, and this is called as gradient descent. So we will do that by this particular formula. So this formula is very important for us because we will try to implement this formula in Python. So m is equal to m minus l dm, c is equal to c minus l dc, where m is the slope and c is the intercept, and l is the learning rate, and dm is the partial derivative of loss function with respect to m, and dc is the partial derivative of loss function with respect to c. Now just pause for a moment. Now let's try to understand what is meant by each of these terms. So this m is the initial value that we took. So let's say that this particular point is m1 and c1. So I'll just write this as m1 and let this be m2. So let this be m2 and let this be c1 and let this be c2. And let's come back to this particular graph. Now let's say that this is the second set of parameters that we have, and I'll just draw a dotted line here, and let's say that the corresponding parameter value for this second set of values m2 and c2. Okay, m2 is equal to c2. Now we need to change the value of m1 c1 to m2 c2, where m1 c1 is the slope and intercept of the first model, and we are changing this model in order to reduce the loss function, and the second set of parameters that we have is m2 c2. Now come back to this formula. M2 is equal to m1 minus ldm, and C2 is equal to C1 plus LDC. So this is M1 C1, this is M2 C2. Now we need to reach to this point. So we will reach that point by subtracting this M1 value with L into DM. So L is the learning rate. So learning rate is means like how much you want to change your parameters. So do you want to change your parameter by unit of 10? So let's say that you have a slope value of 1000. Okay, so the slope value is 1000 and your intercept value is 500. Let's say that you want to change your slope value each time you iterate over the data by 50. Okay, so 50 units. So what it means is, so let's say that your m1 value is 1000 and c1 value is 500. Now you need to reach to m2 and c2. Now let's say that we are choosing the learning rate as 50. So in that case, what we will do is, it will change the parameter by a value of 50. So that's called as learning rate. Just try to understand that learning rate is something, so it is the magnitude of the change that you are willing to make on your parameters. Okay, so we have two parameters m and c, and learning rate is the magnitude of the change that you want to make on these parameters. So that is given by L, and dm is the partial derivative of loss function with respect to m. So that means how much your loss function changes when you change your slope value, and dc represents how much your loss function value changes with respect to c when your intercept changes. Okay, so if you come to this curve, now we are coming to m2 and c2 from m1 c1, right? So when you change the values from m1 c1 to m2 c2, what is the change in loss function value? This is very important because we are constantly trying to reduce the loss function value, so we need to find this partial derivatives. So what is the change in loss function when you change m, and what is the change in the loss function value when you change your c? So that is represented by this equation, which is m2 is equal to m1 minus ldm, and C2 is equal to C1 minus LDC, where M2 and C2 are the updated parameters and M1 and C1 are the initial or the previous parameters. But we won't do this, subscript in Python. So we won't use this subscript. We will just use as m1 is m is equal to m minus ldm and c is equal to c minus ldc. So we won't use this subscript in programming. Okay, so now let's try to understand how we can find this dm and dc. So dm is the differential or differentiating cost function with respect to slope, which is m, and dc is differentiating cost function with respect to c. So now the cost function is synonymous to loss function. So there is only a small difference between them. So you can just go to Google and search what is the difference between cost function and the loss function. The answer is very straightforward. So you can search for it. So for now, just understand that cost function and loss function are very similar to each other and they have the same formula. So this is the formula to compute the cost function or the loss function. So it measures what is the distance between your true value and the predicted value. So if you don't understand what is meant by loss function or cost function, I'll give the link for my video which I already made on this loss function concept. So just watch that video. So for now, understand that this is the formula for loss function or cost function, which is 1 by n summation of yi minus yi pred whole square. Okay, so we need to differentiate this cost function with respect to m first, and then we need to differentiate the cost function with respect to c. So these are two partial derivatives. So when you add these two, it becomes a complete derivative, and these are partial derivatives because we are differentiating cost function first with respect to m, and then we are differentiating with respect to c. Okay, so now what I'm trying to do is I'm replacing this yi prediction with mxi plus c because this is the model that we have. So m3x plus c3. So this is the model that we have, right? So instead of this red color line represents my predicted value, which is yi prediction, and blue color data points represents yi, which is true value. So that is represented by this particular equation. So yi means the true value, which are the blue color circles that I've shown you, and yi prediction is the red color line that we have created, the linear regression that we have created. So I'm replacing this yi prediction with mxi plus c, the equation of the line, so that we can do the we can do the differentiation, right? So we cannot differentiate y with respect to m, so we can differentiate m with respect to m only. So I'm replacing this yi prediction with this particular equation. So you just need to implement this, and what you need to do here is just need to square this. So this is a minus b whole square formula. Okay, so you just need to take this so this is very simple. First you need to square this particular thing. So like what you need to do is, this is a minus b. So just think about this as a minus b formula. So a minus b whole square, and when you do that, you will get yi square, and this will be whole square, and then it will be 2ab. So 2ab will be 2 into yi into mxi plus c. So that is what given here, and then you need to implement a plus b whole square formula. So I'll just explain you this again. So we have yi minus mxi plus c whole square. So what you need to do is, first you need to implement a minus b whole square. Just consider this entire term as b. Okay, so let this be a minus b. So this entire term in this bracket is b. So you need to implement a minus b whole square formula. Once you do that, you will get a term as mxi plus c whole square. Then you need to again do a plus b whole square formula. So if you do that computation, you will get an equation something like this. Okay, now we need to integrate this equation by means of m. And when you it is not integration, it is differentiation. So you need to differentiate your equation with respect to m. So when you differentiate your equation, you will get the formula as something like this, which is minus 2 divided by n xi into yi minus mxi plus c. Okay, so this 2 comes from this yi square. So if you this m2xi, so if you differentiate this, it will be 2mxi, right? So it comes from it. So you can just calculate this. So this is very simple differentiation. So you will get a formula like this, which is, so just highlight this. So it will be minus 2n summation of xi into yi minus yi prediction. So this is something you will get if you differentiate this particular equation with m. And similarly, you need to differentiate the cost function with respect to c. Okay, so we are just using the a minus b whole square formula, and then we are again need to use a plus b for whole square formula for this particular term, and we need to differentiate this. In this case, we need to differentiate it by c, which is intercept. Previously we have differentiated it with means of slope, and now we need to differentiate it with means of intercept, and you will get a equation, or you will get the formula as like this. Okay, so the first formula, or the dm formula we have, is dm is equal to minus 2n summation of xi into yi minus y prediction, and dc is equal to minus 2n uh, divided by n yi minus yi prediction summation. Okay, so these are the values of dm and dc, and if you substitute the values of dm and dc in this case, you will get the updated parameters of slope and c. So this is how you can update your parameters. So previously I've explained you, right? So we need to reach to this global minimum point, right? So we reach that point by updating the parameters using this formula, and we have discussed what is meant by this dm and dc. So the most important things which we need are these two formulas and these two formulas. So we need to implement these two formulas in Python. So these two formulas and the third updating formula. So once we update the slope and intercept, we will create a gradient descent that can find the minimum loss function value and the corresponding parameters value. So this is the process that we will do. So we will randomly initialize a slope value and intercept value, and using gradient descent we will try to find the dm and dc, which is the partial differentiation of the loss function with respect to slope and intercept, and we will try to update the parameters constantly. So we will create a for loop, and inside this for loop we will reiterate the data using a linear regression model, and we will constantly update the parameters. So it's okay if you don't completely understand this. It's completely fine because we are going to implement this in Python using in our hands-on session. So in that case, you will get a better understanding of this. Okay. So for now, understand that this is the formula that we use for gradient descent, which we use to minimize our loss function value by updating our parameters. So that's it for this gradient descent video, and I know that this can be huge for you to take. This will be a bit difficult for you to understand, but just feel free. So I'll just also make a separate video on this as a detailed explanation. But just make note of these formulas, which is m is equal to m minus l dm and c is equal to c minus l dc, and how you can find this dm and dc. Just take a note of this. So that is fine for now. So we can use this in order to implement our linear regression model from scratch. So that's it for this video, and I'll see you in the next video where we will try to implement all these things which we have learned in Python, and so that we can build a linear regression model from scratch. So I hope you have understood all the things covered, and that's the seventh module of our hands-on machine learning course. And this seventh module is all about building machine learning models from scratch. So the first model that we have chosen is a simple linear regression model. And in my previous videos, I have explained you what is the intuition and math behind the linear regression model, and how to deduce the gradient descent for a linear regression model. So in this video, let's try to implement all those things in this Python code, and let's try to build a linear regression model from scratch in Python. So this is the agenda for today's video. So once we create this model, once we complete this model, we will use a sample dataset in order to try this model out. So here I have this salary dataset. So I'll just open this in a notepad. So this particular data set contains some amount of data. It contains about 30 data points. So it contains years of experience. So the number of years of experience for a person and their corresponding salary. Okay. So what is their salary per month? So a data set like this. So once we create our model, we will use this data, and we will try to fit our linear regression model to this data, and we will try to make new predictions. Okay. So this is what we are going to do. So once we train our model, we will try to plot the model with the test data. So this is the thing that we will do. Now let's go into this linear regression code. So as we know that we have discussed previously that the equation of a line is y is equal to mx plus c, where m is the slope of the line and c is the intercept of the line. So you should watch my previous videos if you don't understand those things. So I'll give the link of those previous videos where I've explained you about linear regression. So you can watch those videos before coming into one, so that you can have a better understanding of this video. So it's y is equal to mx plus c. So here I have replaced m with w, and I have replaced c with b. So we know that m is the slope, and instead of m I have used w, and instead of c intercept I have used b. So I'm just changing the notation. So this is because in machine learning we often deal with this kind of notation, which are w and b, where w means the weight of the model and b is the bias of the model. Okay. Now, there is a separate explanation for weights and biases. So in my next video, I'll explain you what is meant by this weight and bias. But for now, for linear regression, just think that weight is nothing but the slope of your model and b is your intercept of your model. So we will be having a deeper explanation in the next video. But for now, just think the weight as the slope of your line, and b as bias as the intercept of the line. So that's enough for now. So y will be our dependent variable. So in our data set, the dependent variable is salary, because we are finding the salary based on the work experience. So salary will be our dependent variable because it depends on the years of experience, and the x will be our independent variable. In this case, the independent variable is years of experience, the number of years. So it will be like salary is equal to W into number of years of experience plus B, which is the bias. So this is the equation of a linear regression model, and we need to build this equation in Python so that we can build a linear regression. Now, in my previous video on gradient descent for machine learning, I've explained you how you can get the best parameters. So these two are called as the parameters of the model, the weights and bias. So in that video, I explained you how to get the best bias and weight for your model, or how to get the best parameters of your model, so that you have a very less loss function. So this is the formula for gradient descent. Gradient descent is an optimization algorithm used for minimizing the loss function in various machine learning algorithms, and it is used for updating the parameters of the learning model. So in this case, the parameters are weight and bias, or it is slope and intercept. Okay, so we need to find the best parameters. So how we will find the best parameter is, we will try to deduce, or we will try to measure the loss function for different kinds of parameter, and we will try to see which parameter, which set of parameters that has the least loss function or the cost function. So I just go to my PPT, which I have explained you last time. So loss function is what is the distance between your predicted value and your true value. Okay, so what we will do is, we will start with a random initial value of slope and intercept, and then we gradually try to step down the curve where we have a minimum loss function value. So this point is called as the global minimum, and at this point we have a very less loss function. So I have explained to you all these concepts in my previous videos. So we use this gradient descent algorithm to start from this random parameter value, and we will come to this optimize in the best parameter value, where we will have a very less loss function. So that's what I have mentioned in this gradient descent definition, and this is how we will update our weights. So weights and bias. So W is equal to W minus alpha into dW, where W is the initial parameter, and this W is the W in the left hand side is the updated weight. Okay, and alpha is the learning rate, and dW is how much your loss function changes when your weight changes. So I'll explain you in a minute what is meant by this. First, let's try to understand about this learning rate. So learning rate is a tuning parameter in an optimization algorithm that determines the step size at each iteration while moving toward a minimum of a loss function. So let's come here. So in this gradient descent curve, so when you plot the parameter and loss function, you will get a U-shaped curve, and we need to step down this curve in order to reach this global minimum. So an optimum learning rate is required to create this step. So if you have a very a larger learning rate, so this step will be drastic. So you will move from this point to this point in a very faster way. So whereas if you have a very small learning rate, the movement from this point to this global minimum will be very less. Okay, so it is very important for us to have an optimum learning rate. So the learning rate will often be in the magnitude of 0.1, 0.01, or 0.001, and so on. So it depends on the data set that we have and the model we have. So it is generally the magnitude that we use, which is about 0.01 or something. Okay, so that is about learning rate, where we will try to step down the curve to reach the global minimum. So that is given by this alpha. Now let's try to understand about dW and dB. So this is the formula to get a dW and dB. So now, so dm is nothing but dw, because we have replaced m with w, right? So it is the differentiation. So we need to differentiate cost function with respect to slope. It is how much your cost function changes when your slope changes, and so on. So refer my previous videos for a detailed explanation, so I cannot go into deep into these concepts. For now, just understand that this is the formula for dw, and this is the formula for db. Okay, so yeah, so dw is equal to minus 2 divided by n summation of xi into yi minus yi prediction. Here xi is the feature that we have. In this case, the feature we have is the number of years of experience, and yi is the salary, the true salary, and yi prediction is the prediction made by our model. So we use our model to make predictions given the years of experience. So we need to find the difference between, so this yi prediction and yi, and we have to multiply it with xi, which is the number of years of experience, and we need to do the summation for all these data points. So totally we have 30 data points, right? So we need to find the difference for all the 30 data points, so the predicted value and the true value of salary, and we need to multiply it with x. So in this case, x is the number of years of experience, and we just need to multiply it with 2 and divided by n. Okay, so after taking summation, so this is the formula for w, and this is the formula for b. So this is weight, or the slope of our model, and this is b is the bias, or the intercept of our model. So we just need to implement these three equations. So first is the equation of the line. Then we need to include this formula or this equation, which is updating the parameters of our model. So in this case, the parameters are weights and bias. And finally, we have to set some learning rate, and then we have this dw and db. So this is how much your cost function changes when your w changes and so on. Okay. So now let's try to build this model. So first I'll import my NumPy library. So NumPy library is the only library that we will use to build this model. So importing NumPy library. Okay. So let's import NumPy as NP. So NumPy library is very useful for creating NumPy arrays. So I'll run this. So this is in Google Collaboratory. I hope you know about Google Collaboratory. So we will do all our Python programming in Google Collaboratory. So in order to run this cell, you just need to press Shift plus Enter. So this will run this cell and go to the next one. And now let's create our linear regression model. So I'll just make a text here as linear regression. Okay. So we will create this linear regression in a class. So just a second. Okay. Now what we are going to do is we are going to create linear regression as an object. So how we will create how we will do that is by using the keyword class. So class linear regression. So let's name our model as linear regression. So I'll just name this as linear underscore regression. So it should be a single word. Now class in Python is used in order to create the template for your object. Okay, so just understand that. So in Python we can create objects using this class keyword, and we can include multiple functions within this class. So whenever we are training our machine learning model, let's say that we are importing a logistic regression. So what we will do is we will import logistic regression from the sklearn library, and then we will use logistic regression.fit or logistic regression.predict and so on. Similarly, within this linear regression, we need to include some functions like fitting the linear regression model and predict function and so on. So that's what we are going to do. So inside this linear regression, we need to include all those functions. So the other way of calling the function is methods. So functions and methods are both are the same. Okay. So now we need to include these functions. So we need some set of important functions. The first function that we need is init. So init means initiation function. So in this, we need to initiate some parameters for our learning algorithm. So this is the first function that we will deal with. And the next function that we will deal with will be a fit function. So this fit function is used to train our linear regression model with the data set that we have. So in the case of that we have taken, so here the data set we have is years of experience and salary, right? So we will fit this data to our linear regression model, and we will do that part of the code in a diff fit. So def means define. So it is defining a function. So this is defining fit function, and we need to mention the parameters in this parenthesis. So let's come to this parameters things later. So let's first discuss what are the functions that we need for our linear regression model. So first is the init function, which is to initiate the parameters. Next is the fit model, sorry, the fit function in order to fit the data to our model. And then we need uh, updation function. So def update weights. So in this case, we will update our parameters. So as you can see here, we have this gradient descent formula, right? So which is used to update the parameters, the weight and bias, and we will create that function in this update weights function. And finally, so there should be okay colon here. Now the last function that we have is predict. Okay, so this is the function that we will use, where if you give the number of years of experience, our linear regression model can give you the salary that the person makes. So these are the four functions that we need for our linear regression model. So 1 second. Okay, so here there should be a parenthesis as well. I just missed it. So there is, so we have this linear regression class or linear regression object, and we have these four functions. So first is the init function, which is to initiate the parameters, and then we have the fit function, which is used to fit the data to our model, and then update weights function, which is used to update the weights based on the gradient descent, and finally we have the predict function, which is used to predict the salary of a person depending on their numbers of years of experience. Now what we will do is let's try to complete these functions one by one. So the first parameter which you should have in all the functions within your class is self. So you should include self as your first parameter in all the cases. So init self and fit self. So I'll explain you in a minute what is meant by this self. So update page self and define predict self. So whenever we are creating a class, within the functions of this class, we need to include this self as our first parameter within this function. So what is meant by this self? So I just go to the next cell. So let's say that we are importing our logistic regression model from sklearn. So what we will do generally is, so we will create an instance of a logistic regression model. Let's say that model is equal to logistic regression. Okay, so logistic regression, and you can import logistic regression from sklearn dot linear model import logistic regression. So this is how we will use logistic regression model, which is already pre-made in sklearn. So in this case, we are going to build by ourselves the linear regression model. In this case, we are using a pre-made logistic regression model. So we will import this logistic regression model from sklearn.linear model. Then what we will do is we will take one instance of this logistic regression model. So I have created a variable here called as model, and I'm loading the instance of this logistic regression. So once we complete this linear regression code, what we will do is, so we will create some instance of this model. So we will do something like, just a second. So we will create an instance as model is equal to linear regression with parentheses. So this is how we will call our linear regression model. So model is equal to linear regression. So this is nothing but one instance of this linear regression model. Now this term model, so or you can call this as the value of your instance. So this value, which is model, will go into this self. So whenever you call this a fit function, so the class will understand it as define fit model. Okay, so it will take the parameters from this model. So just try to understand one thing. So we are importing the function, or we are importing the object using an instance, and this instance value is given in the self. So that's what you need to understand. So hence we need to include this self as the first parameter in all the functions that we create in our class. So I'll just remove these things. Now let's create our parameters. So the parameters we need are the learning rate and the number of iterations that we are going to do. So let's come to this init function. So self comma learning rate. So I have explained you what is meant by this learning rate. So this will be our second parameter, and the third parameter will be number of iterations. Okay, so what is meant by this number of iterations? So whenever we are doing gradient descent, what we will do is, so in order to reach to this global minimum, we will try to run our model through the data again and again. So the model will go through the data again and again. So that is called as iteration. So iteration is nothing but doing something repeatedly. So we want the number of iterations. So we need to mention the number of times the model has to go through the data. So this will be one parameter, and this will be the learning rate. So I have already explained you what is meant by this learning rate. So it is a tuning parameter which determines the step size of the iteration. So these are the two parameters that we have. So this learning rate and number of iterations are called as the hyperparameter for our model, and this weight and bias or slope and intercept is called as model parameters. So these two are the model parameter, whereas the learning rate and the number of iterations is called as the hyperparameters. So that is model parameter. So these two are model parameters and these two are hyperparameters. So we will set this manually. So we will manually set the learning rate and the number of iterations for our model. Let's say we can give the number of iterations as 100. So 100 means the model will go through the data 100 times, or you can also set it to 1000. So 1000 means the model goes through the data 1000 times. So we also manually set the learning rate as 0.01 or 0.001 and so on, but we cannot set the weight and bias or the slope and intercept manually. So this is determined by our model based on the data set that we have. So these are called as the model parameter, and these are called as the hyper parameter, because these are the things that are given manually out of the model, whereas these two parameters are within the control of the model. So these are model parameters, and hence these are hyper parameters. So these are the two parameters that we have, and we need to initiate these parameters in this class. Now what we will do is, So we need to mention this as self dot learning rate. So self dot learning rate is equal to learning rate, and the next one is self dot number of iterations is equal to number of iterations. So this is how you initiate the parameters. So the parameters here are learning rate and number of iterations. So self dot learning rate means model dot learning rate is equal to the learning rate value, and the self dot number of iterations is the number of iterations that we are going to give. So this is the first function that we need. So we won't explicitly use this init function. So we won't be using this init outside this particular class. So we will use only this fit function and predict function outside this class in order to train our data. But this init and this update weights will be used implicitly within this class. Okay, so that's what you need to understand. Fit and the predict are the function which we will use outside this particular class. So these are the first two parameters. So this is the first part of our code, which is to initiate the parameters that we have, which are the learning rate and the number of iterations. Now we need to create this fit function. Okay, so I just make statement here as initiating the parameters, initiating the parameters. So in this case, the parameters are the learning rate and the number of iterations. Okay, so this is the first function that we created in it. So it should be preceded with two underscore, and after the init word we need to include two underscore. So this is how you will create any class. So this is our first step, and now let's try to create the function for fitting the data to our model. So this will be, so it shouldn't come here. Okay, one second. Okay, now we need to fit our data to our model. So here the parameters that we, or here the parameters that we should include are self comma x and y, where x will be our number of years of experience and y will be our salary. So whenever we are fitting the data, we need to give both the x-axis values and the y-axis value, right? Here the x-axis value will be years of experience and y-axis value will be salary. So we need to include those two parameters inside this fit function, which are x and y. Now let's try to carry on with this. Now we need to mention the number of parameters and the number of features that we have. So number of training examples and number of features. So what is meant by this number of training examples? So number of training example is the number of data points that we are going to use for the training. So that is very important. So we need to mention here that how many data points that we are using from this data set. So that is given by this number of training example, and the number of features is the number of x that we have. So in this case, we have only one feature, which is the years of experience. So in several data set, there will be multiple features. So you will have 10 features, 20 features, and so on. Let's say, for example, let's say that we are building a machine learning model to measure the blood sugar level of a person. In that case, we have several features like what is their blood glucose level, or what is the, like what is the amount of food that they eat, and what is the calorie intake they have. So that can be one parameter, and the other parameter can be, or other feature can be, whether they do exercise or not, and so on. So these are called as features of the data. So in this case, we have only one feature, but in more in several data sets we have multiple features, so we need to mention them as well. So number of training examples and a number of features. Now we need to mention them as self.m and self.n. So m will be our number of training examples, and n will be the number of features. So if let's say that we have 30 data points in our data set, so we are using 30 training data points. So in that case, m will be 30 and n is the number of features. So in this case, the number of features we have is only one, because like we don't include salary as the feature. So salary is the target variable, whereas this years of experience is the feature. So in this case, n will be 1. So m is the number of training example we have, the number of data points that we are going to use, and n is the number of features. So this is given by x dot shape. So x will be our training data features, and it will be in the form of an array. So just look at this first column. So here, what is the shape of x? So the shape of x will be 30 into 1. Let's say that there are totally 30 data points. So just forget about this salaries. Just think that this salary is not there. So this first column will be taken as your x, and your second column salary will be taken as your y. So what is the shape of this x? So the number of rows in your x will be 30, and the number of columns your x has is only one. So it will be 30 cross 1 matrix. Like it is like 30, that means it contains 30 data points, but it contains only one features. So that is the x dot shape. So you can just, I'll just make a statement here as it is the number of rows and columns, where the number of rows represent m, which is the number of training examples that we have, and n is the number of columns we have. So in this case, we have only one column, right? So it is number of rows and columns. So m represents the number of rows or the number of training example, and n represents the number of columns or the number of features that we have. Now we need to initiate the weights. So I have explained you, right? So we will randomly initialize the parameters for our model. So the parameters are nothing but the slope and intercept, or you can call it as weight and bias. So we need to initiate this value, so this particular point. So let's do that now. So this is initiating the weight and bias of our model. So you just need to include self. So it's self dot. So self is nothing but model. So if you don't understand why we are using this self, just don't worry. I'll just complete this code completely and explain you in a recap on why we are using that self. So at that point, it will make more sense. So it's self dot w. So w will be our weight. So self dot w is equal to np dot zeros self dot n. So I want to create a matrix, or I want to create an array with these many features or these many columns. So n is the number of columns, right? So I want to create a matrix with n number of columns, and all the values in this array should contain zeros. So that is how we will initiate values. So often we initiate the parameters with the value 0. So now let's initiate the value of bias as 0. So self dot b is equal to 0. So if you just look, take a look at this clearly. We are creating a numpy array for weights, but we are just giving only one single value for bias. It's like creating an array or a matrix for w, but we are just creating only one value for bias. So the reason we are doing this here is, as I have told you earlier, a data set may contain different number of features. So it may contain 10 features, 20 features, and so on. And each feature has a weight associated with it. Hence, the weight will be a matrix, whereas a model has only one bias value. So this weight can be a matrix, whereas the bias can be 0. Sorry, the bias can be only one value. So we are initiating the weights in the form of a numpy array, and we are initiating the bias value as only 0. Now we need to mention self.x. So self.x is equal to x, and self.y is equal to y. So x and y are the data set that we are going to give. So this will be, so this first column will be x and the second column will be y. So we need to mention that here. And now let's try to implement our gradient descent algorithm for optimization. So implementing gradient descent. So for this we need to create a for loop. So for I in range self dot number of iterations self dot update weights. Okay, so self dot update weights parenthesis. Now what we are doing is we need to create a for loop so that the model does the iteration. So as I have told you earlier, we will mention the number of iterations. So number of iterations means the number of times the model will go through the data. So if we just give the number of iterations as 50, that means it will the for loop will have a value of 50. So the for loop will run 50 times, and each time the model will go through the data, and 50 times the parameter value will be updated. So that's why we are including this self dot update weights. Now we need to create this update weights parameter, sorry, update weights function. I'll just remove the spaces here. So now we are going to include these formulas. So w is equal to w minus alpha into dw, b is equal to b minus alpha into dw, and these two formulas. So we are going to incorporate these four formulas into our update weights function. So now we need to mention y prediction is equal to self dot predict self dot x. So this is the predict function. So we haven't done this predict function yet. So this function is here. Now let's try to complete this predict function. So this is what we do in class. Sometimes we will use a function that is not yet created yet. So now let's try to create this predict function. So define predict self x. So the purpose of this particular predict function is that if you give the value of the number of years of experience, it can calculate the salary of the person. So we just need to give only one parameter. So in this case, the parameter is 6, which is the number of years of experience. Now, if you give that value, it will try to plug in the value to the formula that we have. So here the linear regression formula is y is equal to wx b, right? So we will try to plug in the values of x in this particular formula, and we will try to find the value of y, which is salary. So now let's try to incorporate this formula to our Python code. So define predict, which is return x dot dot. So we are creating a dot product of x and w. So self dot w and self dot b. So just look at this particular line of code. So it is x dot self dot w. So it is the dot product. So as we know that we have created a w, or we have created this weight as a numpy array. So we need to include numpy multiplication, an array multiplication, or a vector multiplication. So this is the dot product of the two vectors, which are x and w. So here x is also one vector. So x is a 30 cross 1 vector, right? So we need to multiply this 30 cross 1 vector with the corresponding weight value. So it will be x dot self dot w plus self dot b. So this is nothing but the formula y is equal to wx plus c, wx plus b. So instead of writing this, we are just writing this in a different manner as x dot self dot b plus self dot b. So we are including this dot product because this is an array. Now we need to create an array called as y prediction. So all the predictions made by your model will be stored in this y prediction, and we need to compare the loss function for each different parameters. So I'll just write some set of lines of code, and then I'll explain you what I'm doing here. So once I complete all of those things, so now we are going to calculate the gradients. So first is dw. So dw is equal to, so you can refer the formula here, which is minus 2 by n summation of xi into yi minus yi prediction. So here n is the number of training examples. So in this formula, the number of training example is represented as n. But in the case of our code, we have taken the number of training example as m. So in this formula, you need to replace n by m. So it is just a change in the notation, so nothing more there. So you just need to replace this n by m. So let's try to write this formula in Python. So dw is equal to minus 2 into self dot x. So we need to make a transpose of this x, so that it can multiply with uh, other values. So I'll just explain you in a minute. I'll just complete this line of code. So it's dot t dot self dot y minus y prediction divided by self dot m. Okay, so now just look at this formula. So it is minus 2 by n. So this I have represented this minus 2 by n as minus 2 whole thing divided by m. So here m is the number of training examples. So as I've told you, we have replaced this n by m, and now it's xi into yi minus yi prediction. So xi is nothing but our capital Y, which is the number of years of experience. So that is written as self dot x. So we cannot multiply it directly with this term. So we need to find the transpose. So we know that it is in the form of 30 into 1, right? 30 rows and one column. So we need to make the transpose of it. So if you take a transpose of it, it will be like one row with 30 columns. So I'm just creating a transpose of this dot self dot y minus y prediction. So this is nothing but yi minus yi prediction, where yi is the true salary value and the yi prediction is the values predicted by our model. So that is the first line, and the second line will be db is equal to minus 2 by n, this particular formula. So this is very simple than this. So next will be db. So db is the weight or a bias value. So db is equal to minus 2. So minus 2 into np dot sum self dot y minus y prediction, and this whole thing should be divided by self dot m. So m is the, okay, y prediction divided by self dot m. Okay, so this is the formula given here. So this is the formula for db, which is minus 2 by n summation of yi minus yi prediction. So that's what we have done here. So it's 2 minus 2 into np dot sum self dot y minus yi prediction self dot m. So now we need to update the weights. So the formula for updating the weight is this particular formula: w is equal to w minus alpha into dw, and b is equal to b minus alpha into db. So we have created this dw and db. Now we need to update the weights. So updating the weights, self dot w is equal to self dot w minus self dot learning rate, so which is represented by alpha. So learning rate into dw, and the next is self dot b is equal to self dot b minus self dot learning rate into db. Okay, so just a second. Learning rate, okay, so this is our linear regression model. So I'll just run this once and I'll explain you what this entire thing. Okay, now I'll explain you completely how this linear regression model works based on the code that we have done. So the first thing that we have done here is initiating the hyperparameters. So in this case, the hyperparameters are the learning rate and the number of iterations. So learning rate is nothing but the step size that we are choosing. So how much step the parameters should change. What should be the magnitude of the change in the parameters? Okay, so it should change by a small value, or the parameter should change by a large value. So that is given by this learning rate, which we will manually give some amount of value. So this can be 0.01 or 0.001, and it depends on the model that we use and the data that we have. And then we have the number of iterations. So this is the number of times the model has to go through the data points. So this is also, we can set this manually. So you can set the iterations as 100, in which case the model will go through the data 100 times again and again, or you can set this number of iterations to 1000, where your model will go through it 1000 times. So that is the first part. So first is initiating this hyperparameters. The next thing that we need to do is fit our data to the linear regression model. So we have used several models already. So we have used several pre-made models in sklearn a lot, and we used to use this model.fit functions. And then in this case, we are trying to build that fit function. So define fit self comma x comma y, and self is nothing but your instance. So as I've told you, we used to write this line as model is equal to logistic regression, or a model is equal to linear regression. So that model So this is, self takes that value model. So it is nothing but the instance value. So that is the self value is nothing but the instance value. So define fit self comma x and y. So x and y is nothing but the data that we have. So in the example that we have here is, so I'll just open this. Yeah. So years of experience and salary. Here, years of experience is X and salary is Y. So now what we need to do is we need to give both this X and Y in order to fit, because let's go to this curve. So if you want to fit the data points to a line, you need to give both x-axis value and y-axis value. Then only you can plot a data point. Otherwise, you cannot plot a point. So you need two coordinates. You need x coordinate and y coordinates to plot this in this x-axis and y-axis. So we need to give both x value and y value. So that's what we are mentioning here. So whenever you are using this fit function, you need to give two values. So one value is x and the other value is y. So in our projects, we have used the function define fit, and we will use to give the parameter as x train and y train, right? So these are nothing but x train and y train. So now what we need to do is we need to extract the shape of x. So in the example that we have, so this data set contains 30 data points. So 30 total data points, and it contains two columns. Here we have only one feature and one target column. Here salary is the target column and years of experience is the feature. So the number of features that we have here is 1. So this one feature is nothing but the years of experience, and the total number of data points we have is 30. Now we need to extract this shape. So self.m comma self.n is equal to x.shape. So when you do this, the shape of your x will be extracted. So in this case, the shape of x is 30 into 1, which means 30 rows and 1 column. So m in this case is the number of training example, and n in this case is number of features. Okay. So that is one main thing you need to take note of. So we are extracting the shape. So the reason we are doing is this dataset contains only two columns, but generally the dataset that we deal in machine learning will contain 10 features, or it may also contain 100 features and so on. So we need to create an array in this case. So let's say that our dataset contains 30 features. In that case, your n value will be 30, and let's say that there are about 10,000 data points. So there are 10,000 data points and 100 features. So let's say that, so there are totally 1,000 data points and there are 100 features. So in that case, the value of m will be 1,000 and the value of n will be 100, where n is the number of features we have in our data set, and m is the number of training examples or the data points that we have. Now we need to initialize the weights and bias. So in our gradient descent curve, I have told you that we will randomly initialize the value, right? So we will randomly initialize the parameter and we will try to come to this global minimum. So this is the point where if we choose this parameter, it has the less loss function, but we cannot find this parameter value directly. So we need to randomly initialize the value, and we need to find this gradient descent. So we need to implement this gradient descent algorithm so that the model can find which is the optimum parameter. So the next step is to initiate these parameters. So we initiate the parameters using this line of code, which is self.w is equal to np.zeros, self.n, and self.b is equal to 0. Now, as I've told you, this particular data set contains only one feature. So here there is no problem. So here what you can do is you can just instead of writing this np.0, so what you can do is you can just put self.w is equal to 0. So you can do that, but often we don't have data set that has only one feature. So we often have data set that contains many features. So we need to create a numpy array. So if a data set contains 10 columns or 10 features, each of this feature has a separate weight value, each of this feature has a separate slope value. Hence we are creating an array for w instead of just putting w is equal to 0. So we are creating an numpy array with all the values as 0, and the shape of this numpy array is given by n, where n is the number of features. As I've told you, each feature will have a separate w value, and you need to create a numpy array based on the number of features we have. So in this case, the number of features is n. So you need to create a numpy array which contains all the values as zeros, and the shape of this array should be n. Okay, where n is the number of features. So that's how you can initiate the values of w. So the initial parameter values is w, and you b. So no matter how many feature you have, always the bias will have only one value. So you can just come to this particular equation. So w can be w size is equal to the shape of x. So if we have 10 features, then we have 10 value for w. But in all the cases, no matter how many features are there, b will be only one value, the bias will be only one value. Hence we are just putting self.b is equal to 0. So you don't need to create a numpy array, because a bias is a single value, an integer value. So we are initiating the bias value as 0, whereas we are initiating the weights value as np.0, which is an array. So that is the next step, where we are initiating the weights and bias, weight and bias. So this is self.x. So x is nothing but our feature and y is nothing but our salary. So we need to mention that. So this is our next step. Now we need to implement our gradient descent. So gradient descent is something where we will try to reach to this point from this point by comparing the loss function of different parameters. Now let's try to do that. So here we are creating a for loop. So for I in range, self dot number of iterations and self dot update weights. Now what we need to do is we need to mention the number of iterations. So as I've told you, if the number of iterations is equal to 100, that means the model will go through the data again and again for 100 times, and each time it goes through the data, it will try to change the weights and bias. It will try to change the parameter value and see whether the loss function value is less or whether the cost function value is less. So the loss function and cost function are very similar to each other. So you can just call it anything you want. So you can use that synonymously. Now the model will go through the data again and again for these 100 number of times, and each time it will change the parameter. It will change the weights, and we call this as updating the weights. So for I in range self number of iterations, so for each time it runs through the data, it will update the weights. Now we need to create this update weights function. So that's what we are doing in our third function, which is a define update weights. So update weights, so like here there is no second parameter. So this is a function that we are using implicitly within this class. So we don't need to give any parameter values in this case, only this self is enough. Okay, now let's see what we are doing here. So inside this update weights, we are creating an array called as y prediction. So y prediction is equal to self.predict self.x. Now let's try to understand this. So let's say that we have randomly initialized our weights and bias value, and this is the first iteration of our model. For this particular first iteration, the value of weight is a numpy array which contain all the values as 0, and the bias value is 0, and based on this value it will create a line, a linear regression model with the weight value as 0 and bias value as 0. Now our model will try to find the value of salary, the value of y, based on the model that it has. So in this case, the model will have the equation of the model will be like something like this: 0 into x plus 0, because the weight value is 0, right? So we have initiated the weight value as a 0 and the bias value as 0, and y is equal to 0x plus 0, where the first 0 represents the weight w and second 0 represents bias value 0. Now what the model will try to do is it will take only this first column, years of experience column. So that's what we are mentioning here. So self dot predict. So now let's come to this predict function. So we have created this predict function here, which returns some value. So this predict function will return some value, and this value is x dot dot self w plus self b, which is the equation of the line. Okay, so this is the equation of the line, which is y is equal to wx plus b. So this particular predict function will return the value of y, which is the salary if you give the years of experience. Now I have just written this particular equation in a simple way in this case. Now let's come back here. So this is what this predict function will do. So it will give the value of x to this equation, and it will try to find the value of y, and all the values predicted by our model will be stored in this array called as y prediction. Okay, so I hope you are clear up to this. So once we randomly initialize the value, once we initialize the weight value and bias value, the model will try to find the predicted values, will try to predict the values, and now it will compare these two values. So you can come to this formula here. So we are subtracting the true values yi minus yi prediction, right? So in this case, the yi prediction is nothing but this array y prediction, and yi is the true values. True values are the columns in the values in the second column. So this is the salary value, and these are the true values. Now we need to compare the true value and the estimated value or the predicted value, and this is called as the loss function, right? So now we have yi from this particular data set. So we got the yi, which is the true value from the data set, and y prediction is the value predicted by our model. Now what happens is, once it finds this value, it will try to find the values of dw and db. So this is the formula for it. So dw is equal to minus 2 by n summation of xi yi minus yi prediction. So this is how much your parameter value will change. So this is the value of dw db, and we are implementing these formulas in this two equations. So dw is equal to -2 into self x dot t, and so on. So this is this exactly this two equations. We have written these two equations here. Now the model has to update the weights. So it will update the weights based on the difference that okay. So now we have the true value and we have the predicted value. So based on this, the gradient descent can calculate what should be the updated weights. And this is the formula for updating the weights. W is equal to W minus learning rate into dW. So yeah, this formula. So W is equal to W minus this formula, and B is equal to B minus alpha into dB. And we have calculated this dB and dW based on our yi, the true value, and the yi prediction value. Okay. So once it does that, it will again come back to this for loop, because this is where we have used this update weights, right? So this process will be continued for 100 iterations. So if we give a number of iterations as 100, it will try to do these iterations for again and again for 100 times, and it will try to update the weights for 100 times. So this is how linear regression model will work. So first of all, it will try to get the value of the learning rate and number of iterations from the user, and then it will try to randomly initialize the parameter values, which are the slope and intercept value, and it will we have initiated the values with 0, and then we try to update the weights based on the difference between the y prediction and the true value. And once the number of iterations is complete, we will reach a point called as convergence. So convergence is a point beyond which your model cannot perform better. So it is the most it is the point where your loss function is very minimum. So it is the global minimum point. So this point is called as convergence. And if once your all your iterations are completed, your model will reach that point. Okay, so this is how linear regression model works, and I hope you have understood all the things covered in this video. So if you don't understand a few things, it's completely fine, because in the next video what I'll do is, so we will take this particular data set and we will try to train our linear regression model with this particular data set, and we will try to make predictions. So in that case also, I'll explain you practically how we will use this data set and how this data set will go through this particular linear regression model, and we can make predictions. So I hope you have understood all the things covered in this particular video. And if you have any doubts, please mention in the comments. And that's this seventh module is all about building machine learning models from scratch. So the first model that we are working on is a linear regression model. And in my previous videos, I have explained you what is the intuition and math behind a linear regression model, and how you can deduce the gradient descent of a linear regression model. And we have also discussed how we can build a linear regression model from scratch using Python. So that was our previous video. And if you haven't watched those videos, I suggest that you watch those videos before watching this one. Okay, so after that only this video will make sense to you. So we have did all these codes in the previous video, where we have built a linear regression from scratch, and we have built this linear regression in a class format, right? So we have did all the things. So we have initiated the parameters, and then we built the define fit function, which is used to fit the data set to our model. And then we use this update weights in order to update weights using gradient descent. And then finally we built this predict function. So we have done all those things, and I hope you are clear up to this particular point. Okay, so now what we will do is, in this video we will try to implement this linear regression that we have built. Okay, so this will be on implementing linear regression from scratch in Python. Okay, so we have a sample data set. So this data set is about the salary of a person. So I'll just show you. So I'll just open this with a notepad. So this particular data set, so this is a very small data set, and it contains two columns. One is the number of years of experience of a person, and the salary that that particular person makes. So totally we have 30 data points in this particular data set. Okay, so that means 30 different people, and what is the salary that they are making. So we don't have much information about this particular data set. So let's assume that this salary is in the form of Indian national rupees, and it represents the salary per month. Okay, so let's say that a person with 1.1 years of experience makes about 39,343 rupees, and a person with 1.3 years of experience make a salary of about 46,205 rupees, and so on. Okay, so as you might know, this is a linear. There is a linear relationship between years of experience and salary, which means if the years of experience increases, the salary of the person also increases. So in this case, we can use a linear regression model, as there is a linear relationship between them. So this is the data set that we are going to use. So now what we will do is, we will fit this data set to our linear regression model that we have built in Python. And once our linear regression model is learned from this data, we will give new data set and a new data points. So we will give a new values for this years of experience and see what is the value of the salary that our model can predict. Okay, so our model will predict the value of the salary given the experience of the person. So that is what we are going to do in this particular video. And as I've told you, we already have this linear regression class written in code in Python. Now let's see how we can implement this. So I'll just make a text here as using linear regression. So using linear regression model for prediction. Okay, so let's make this text here. So I'll explain you what are the steps that goes on within this particular linear regression model. So I have made this notepad file. So let me explain this to you. Okay, so this is the workflow of a linear regression model. So the first step is we will manually assign the value for learning rate and number of iteration. So in the previous video, I explained you what is meant by this learning rate. So learning rate is the amount of change we want in our parameters like weights and bias. So what is the change in weights and bias you want to give in each iteration of your gradient descent. So if you don't understand what is meant by this learning rate, so I give a particular video in the video description. I have already made videos on this learning rate and number of iterations, so you can refer that one. So first we will set manually what is the learning rate and the number of iterations that we want. Okay, so we can change these values anything we want, and then we will initiate the random weight value and bias value. So in our code we have initiated with the value 0. Okay, so as you can see here, so in this init part we have initiated this is the learning rate and number of iteration. Now this is so these two lines represents initiating the weight value and bias value. Okay, so as you can see here, we have initiated weight value with np.0 self.n. Okay, so we are creating a numpy array with the zeros, and we are initiating with weights. So weight will have an array, and all the values in this weight array will contain the value 0. And bias is an integer value. So there is another main thing you have to note. So weight can be an array, but bias will always be an integer in most of the cases. So we are initiating bias value as 0, and weight we are creating a numpy array. This is because so the number of weight that you have in a model changes. So it changes according to the data set that you have. So if you see this particular data set, the salary column is the target column and years of experience column is the feature column. So you can call this years of experience as X and the salary as Y. So the number of weights you have in your model is equal to the number of features that you have. So in this case, you have one target column and one feature column. So in this case, we will have only one weight value. Okay. Whereas in some other dataset, we have multiple features. Say, I'll show you the diabetes dataset. We have already worked on this dataset in our YouTube channel. I have made a video on diabetes prediction. So if you see this particular dataset, so I'll just open this in Excel file. Okay. So now, as you can see here, this particular dataset contains many columns. It contains many features. So the final column is the output column, and the remaining column are the features. So let's see how many column that we have. So 1, 2, 3, 4, 5. So, okay, so totally we have 8 feature columns and 1 target column. So as I've told you, the number of weight values that you have is equal to the number of features that you have. So in this case, we have totally 8 features. So if you use this particular data set, you will need 8 weights. So there will be a particular weight value for each column. Okay, so that is the one main thing that you need to note. So that's why we are initiating weights as a numpy array instead of a number, whereas bias is just a single integer value, so we are initiating with 0. So that will be the first step in our linear regression model. So first we will set our learning rate and the number of iterations, and then we need to initiate some value for our weight and bias. So you can give random weights, but generally we will initiate with a 0 as the value for weights and bias. So after we did this, we will build the linear regression equation, which is we know that it is y is equal to wx plus b, where you can consider this w as your slope or weight and b as your bias or intercept. Okay, so it is similar to the equation y is equal to mx plus c, where m is the slope and c is the intercept. So instead of that, we are using this particular notation, which is y is equal to wx plus b. So we have built this particular equation in our define.predict function. Okay, so as you can see, a define.predict return x dot self w plus self dot b. So this is nothing but wx plus b, which is the equation of the line. So that will be our second step. So we will give this random value for this weight and bias, and then we will build this linear regression. Now with this weight and bias value, the model will predict the value of the salary. So if we come back to this data set again, so now we will give the value of this X alone, the years of experience alone, and our model will predict the value of our salary. And that is the role of this predict function. So in this predict function, we will give the value of this X, and this function will find the value of Y using this particular formula, which is X dot W plus B. Okay. And now once it has found this Y value, now what it will do is, so all the values predicted by our model, we will store it in the array called as Y prediction or Y pred. So it will be stored here, and so find the Y prediction value for given X value for the corresponding weight and bias. So first we add a random weight value and bias value. So now with this random weight and bias value, so if you think about this, so let's say that we know that the weight value is 0 and the bias value is 0 as well. Now if you substitute those values in this Y is equal to WX plus B, the equation you will get will be Y is equal to, or the salary is equal to, weight is 0, so 0 into X, and plus bias is also 0, B is also 0, right? So this will be your equation. Now with this equation, your model will try to find the value of salary. Why? By using this particular equation. So it will just substitute the values of X. So as you can see here, the first column values in this equation, and it will try to find the value of Y. And now all these values will be stored in Y prediction. Now what we need to do is, then the model tries to check the loss function. If the loss function is I, that means our model is not working fine. That means our model is inaccurate. So loss function is nothing but the difference between Y prediction and true value of Y. So true value of Y is those values given in this particular data set, and the Y prediction value is the values predicted by our model. So it will try to find the loss function, and if the loss function is I, if the value of the loss function is I, it will try to update the parameters. So it will change the value of this weight and bias. So obviously we know that if we give the weight value and bias value as 0, our model is not going to predict well, because for all the values it will predict the value of Y as 0. So it is not the correct weight and bias value. So now the model will update the parameters using gradient descent. So that is the role of the gradient descent in linear regression. Okay. Now it will update the values of weights and bias, and that's what we are doing in this define update weights function. Okay, so and the number of iterations we have given already. So if you just go to the step 1, so we are already assigning the value for learning rate and number of iterations. So now the model knows how many iterations it should run. So we have made a for loop here with number of iterations. That means, let's say the number of iterations is 100. That means the model will go through the data again and again for 100 times, and each of these 100 times the weight and bias value will change, and the model will try to reduce the loss function. So that's the idea behind gradient descent. Okay, and this steps will be carried out again and again. This step 3, step 4, and step 5. So the model will try to update the weight and parameters. Again it will try to find the value of Y prediction with the new weight and bias value. Again it will find check the loss function. So this will be carried on till it reaches a point where the loss function is minimum, and this is called as the training of the machine learning model, where we try to minimize the value of the loss function by updating the parameters such as the weight and bias value. Okay, so finally we get the best model, that is the best weight and bias value, as it has a minimum loss function. And this is the process that is going to happen in the linear regression that we are building. So I hope this is clear to every one of you, and every one of you understand how this linear regression model works. And now we can implement this straight away. So I'll just close this, so you can take a note of this if you want. So this is very important. So I'll come back to my Google Collaboratory. So I have connected my system, and I have also uploaded this salary dataset. So I have showed this salary dataset, right? So I have uploaded this dataset in Google Collaboratory. So now we will be doing processing in this dataset. So the first step will be to import the libraries. So I'll just make a comment here as importing the libraries. So we need some libraries for data processing. So for that purpose, we are importing some libraries. And for this linear regression, we have already imported the numpy function. So numpy library as np. So now we need to import pandas, sklearn, and matplotlib. So those are the 3 libraries that we need now. So first I'll import pandas. Sorry. So first is importing the dependencies. Dependencies are nothing but the libraries. Okay, so the first library that I'm going to import is pandas. So import pandas as pd. So pandas is very useful for creating data frames. So data frames are nothing but tables. So it is easier for us to process the data and analyze the data if it is in a more structured form in a table rather than in the form of a notepad file or a text file. So that's why we are importing this pandas. So I'm just importing it in the short form as PD. So most of you might know it, but some of you may be new to this. So that's why I'm explaining all these small things. So every time we don't need to use this pandas, as a lengthy word. So we can just abbreviate it as PD. So this is the general convention that we use, and we import numpy as np, and it is also the general convention. So we have we are importing the pandas library, and now let's import train test split function. So from sklearn dot model selection, we are going to import train test split. So the purpose of this train test split is, so we have this data set, right? So this data set contains 30 data points, and some data points may contain 500 data points, 1000 data points, or 10,000 data points. So it depends on the data set that we have. And whenever we are training our machine learning model, we will train our machine learning model with the training data, and then we will evaluate our model, or we will test our model with the test data. So this is like the evaluation to check the accuracy score of the model. So that's why we need to split our original data set into training data and test data. So that is the purpose for this. And then now let's import the matplotlib library. So at last we will do some visualization procedures also. So that's why we need matplotlib library. So import matplotlib.pyplot as plt. So pandas is used for making pandas data frame. sklearn.model selection. So sklearn is a very important library which has functions like train test split. It also contains a lot of models like linear regression, logistic regression, etc. It is also a very important model. And matplotlib library is used to make plots. Okay, so in this matplotlib library, I'm just importing this pyplot module, and I'm importing it in the short form as plt. Okay, so that's what we are doing in the first step. So we have okay, so there is invalid syntax. So I should give this as from import, sorry. So from sklearn dot model selection, import train test split. Okay, so the next step will be some data processing. So we generally, what we do in machine learning is we will try to see whether there is any missing values in our data set, and some simple procedure like this. So I'll name this as data processing. So this process is called as data pre-processing. So I'll name this as such, data pre-processing. Now, what we will do is we will try to load our data, which is in the form of a CSV file. CSV means comma separated values. As you can see, this data set, all the values are separated by comma. So now we will load this CSV file into a pandas data frame. So that will be the procedure. So this step will be importing or loading. So it will be more appropriate to say loading the data from CSV file to a pandas data frame. So that will be the next step. So I'll name this data frame as salary data. So salary data is equal to PD. So we know that PD means pandas. PD.read CSV. So this read CSV is the function which is used to import the CSV file into a pandas data frame. And now you need to mention a quote here. So opening quote and closing quote. And now we need to copy the path of the salary data. So if you want to upload your dataset file in Google Collaboratory, what you need to do is you need to go to this files option, and there you will find this upload option. So upload to session storage, or you can just come to this part and right click. So you will find this upload option. So you can use any of them. So once you give this upload option, you can upload the dataset from your system to the Google Collaboratory session. So I have already uploaded my salary data here. So now I'm going to copy the path. So you can see this three dots, which is the options menu. And from there, you can copy the path of this particular file. Okay. Now we need to paste this in this quotes. So just a second. Okay, so I have pasted this code. So now what happens is this function pd.read CSV will read this CSV data, and it will load it to a pandas data frame. So I'll run this. So you can press shift plus enter to run this cell and go to the next one. Okay, so this has successfully loaded our dataset into a pandas data frame. Now let's try to see the first 5 columns in our dataset. So printing the first 5 columns of the data frame. So we have named the data frame as salary data, as you can see here. So salary data dot yet. So this yet function will print the first 5 rows of the data frame that we have. So I'll run this. As you can see here, these are the first 5 rows in our data set. So it contains two columns, which are the years of experience and the salary column. And you can also use salary data dot tail. So this function, so you need to mention the parenthesis, so that's very important. So you can also run this in order to get the last 5 columns of the data set. Okay, so it says 29 because numbering in Python starts from 0, so that's why we have 29. So totally we have 30 data points, as the numbering starts from 0 instead of 1. We have 29 here, so that's not an issue. So this salary dot tail data will print the last 5 rows of the data frame. Okay, so I'll run this. So it is used for us to understand what is the magnitude of the data and what the data looks like. So that this is the general procedure that we do in every machine learning process that we do. Okay, so that is our next step. Now what we will do is, let's check the number of rows and columns that we have in our data set. So in this particular data set, we know, because I told you, right, that it contains 30 rows and 2 columns. But some data set may contains, as I've told you, it may contains 1,000 rows, it may contains 100 columns, and so on. So it is important for us to know how many rows and columns are there in our data set. So that will be our next step, which is to print the number of rows and columns in the data frame. So we can find that by salary data dot shape. So in this case, you shouldn't use a parenthesis like that. So if you use a parenthesis, you will get an error called as tuple object is not callable. So you just need to remove this parenthesis. So it is in the form of your output will be in the form of a tuple, which is an example of a data type. So those doesn't support this parenthesis, so you need to remove that. So yeah, you will get a tuple which contains 30 and 2. The first value represents the number of rows you have, and the second value represents the number of columns you have. So this is similar to the shape of a matrix. Okay, so whereas in the previous cases, as you might know, we have included parentheses, but whenever we are using this dot shape function, we shouldn't use parentheses like this. Okay, so you need to remove that. So we have found that this particular data set, this data frame contains 30 rows and 2 columns. So that is our next step. Now let's check whether there is any missing values in our data set. So that is another main thing. So if you have any missing values, what we will do is, we will generally remove those rows and columns that are if it has a lot of missing values, or we can do some processing like imputation. And I have already made a video on this. You can go to the 4th module in my machine learning course, and in that module I have explained you how you can process those missing values, so it might be useful for you. So this step will be checking for missing values. So we need to mention the data frame name, which is salary data dot isnl dot sum. So isnl parenthesis dot sum. Okay, so I'll run this. So null means missing values, and we are checking whether there is any missing values. That is meant by this is null, and dot sum. So we need to count how many missing values are there. So that's why we are using this sum function. So this is the summation function. So we are counting the number of missing values that we have in each column. So as you can see here, the value is 0 for both the columns that we have. That means there are 0 missing values in years of experience and 0 missing values in salary column. So we don't have any missing values, which is a very good thing. But generally we will have a lot of missing values in the data set that we use for our predictions. So you have to know like what are the processes that we do in order to operate with this missing value. So that's very important. So this particular data set doesn't contain any missing values, which is a good thing. Now what we will do is, we will separate this feature and a target. As you might know, in this dataset contains only one feature and one target variable, whereas several dataset contains multiple features. There can be 10 features, 20 features, or even 100 features. So the diabetes dataset that I have shown you contained about 8 features in one target column, right? So the next step will be to split this dataset into feature and target, where the feature is the years of experience, which is the x-axis value or the x value, and salary is the target column, which is the y column. So now let's separate this x and y column, or the feature and target column. So I'll just make a text here as splitting the feature and target. So if you just come to this linear regression equation, y is equal to wx plus b, here y is the dependent variable and x is the independent variable, because the value of y depends on the value of x. So if you consider this particular data set, here the x-axis column is x value is years of experience and y value is a salary, right? So you can say that the salary of a person depends on the years of experience of that person. So similarly, hence we call that this target column is dependent on the feature column. So we call this y as dependent variable because the value of y depends on the value of x, and value of x is independent. It does not depend on any factors. So we call this as an independent variable, and we write this linear regression equation as y is equal to wx plus b. So you can call this x as feature and y as target. So that's what we are doing here. So we are splitting the feature and target. And now let's store them as x and y. So let's store the feature in the variable x, and let's store the target in the variable y. So now I'll mention the data frame name, which is salary data dot ilog. So we are just choosing particular columns. So that is used by this, that is done by this particular function ilog. So, and here we need to mention the column names. So I'll just mention this as -1. Okay. So I'll tell you what this means just in a moment. So salary data dot ilog square bracket to 1. Okay. Dot values. Now I'm going to take this this salary data frame, and I'm going to separate this years of experience values alone and salary values separately. So that's what I am doing here. Here, the first value, like it represents the column number and the row number, and this I have mentioned that there is a colon, a comma, a colon, and -1. This basically means I am just separating this last salary. So I'm just removing this salary. So if you just represent it as let's say, okay, so you can represent it as, let's say, 1 is to 10 is to 1. Okay, so what this basically means is, let's say that we have a data set that contains 10 columns, and in that we just need the first column, third column, fifth column, seventh column, and the ninth column. So you just have a step size of 1. So the next column will be basically removed. So that is represented by this particular line. So totally we have 1 to 10 columns, and I'm having a step size as 1. So if you run this particular code in a data set that has 10 columns, so your first column will be printed and the second column will be removed because you have given the step size as 1, and this process will be carried on until you reach the 10th column. Okay, so this is called as the step size. So similarly, we are just removing the last column. So this is another way of doing this. So I'm just -1 in the sense I'm just removing this salary column. So that's what we are doing, and the next part will be separating the salary column. So I'm taking this years of experience and storing it in x. So that is done by this first line of code, and in the second line of code I'm just taking the second column, which is salary data. So I'm just taking this. So the first column is represented by 0 and the second column is represented by 1. As I told you earlier, in Python, numbering starts from 0 and not 1. So the first column has the value as 0 and the second column has the value 1. So I'm mentioning the second column value as 1. So in X, we are taking all the years of experience values, and in Y, we are taking the target column, which is the salary column, and those values. So that's why I'm mentioning dot values. So this will split our data set into features and target, or the years of experience and salary. Now you can just print and see your X and Y separately. If you print X, you will have 30 values, which contains only the years of experience values, and if you try to print Y, you will have the salary value. As you can see here, we have all the salary values. So that is our next step. Now what we will do is, as I've told you earlier, we need to split our entire data set into training data and test data. This is because we will train our machine learning model with the training data, and we will test or evaluate our model with the help of testing data. So that is one main important thing. So this step is common in all the projects that you do, all the use cases that you do. So this is very important step, and this will be splitting the data set into training and test data. Okay, so for this we have already imported the function called as train test split function from the library sklearn. So from sklearn.model selection, we have imported train test split. So now we need to use this train test split function. So now I have to create four arrays. So first is x train, x test, y train, and y test. So what they basically mean is, so we need to separate this x and y, and this data set will be separated into two data sets. So one is training data, and the second one is test data. So if you just see this x, we know that it contains all the value of x. So this all the values of x will be separated into two groups. One is the training data, and the second one is test data. Now let's say that we have two groups of data, so two groups of x, and the corresponding values of x will be stored in y. So we have some set of values for x train. So all the x values, so sorry, not all the x values. You will have all the training data x value, and the corresponding y value for this training data will be stored in y train. Similarly, you will have few values for your test data. The values remaining from this x train. So the values other than this x train data will be stored in x test, and the corresponding salary value will be stored in y test. So that is what we are doing here. So we are creating four arrays where x train contains all the training data for features, and y train contains all the labels or target for this x train, and the x test contain all the test data features, and y test contain all the target values of this particular x test. So these are the four arrays, and now we are going to use the train test split function. So train test split, and now we need to mention x and y. So because we know that we have splitted this features and columns, features and targeted as x and y, right? So from this x and y, we need to separate x train, x test, y train, and y test. So we need to mention x and y in this particular train test split function. And we have other parameters as well, which we need to mention. Test size. So let's say that the test size is equal to 0.33. So it is almost 30%. And I'm mentioning random state as 2. So random state is equal to 2. So what this test size means is like what percentage of data do you want in your test set. So 0.33 means out of this 30 data points that we have, out of the total data set that I have, I want 30 percentage of the data to be the test data, and the remaining 70 percentage of the data will be training data. So in generally speaking, we will take 10 or 20 or 30 percentage of data as test data. So the test data size will be less, and the training data size will be more. So in this case, we are just taking 33 percentage or the 30 percentage as our test data, and that is mentioned by this parameter test size, and I'm taking random state is equal to 2. So random state is a very interesting parameter. So the purpose of this is, if you, let's say that you are practicing this particular code, and if you give the random state value as 2 as I'm giving now, your data and my data will be splitted in the same way. But let's say that if I am giving the random state value as 2, and if you are giving the random state value as 1, then your data will be splitted in a different manner. Like your x train will contains different values, and your x test will contain different value compared to my values. But if you just give the random state as is equal to 2, then both your data and my data will be split in the same way. Your x train and x test will have the similar values as my x train and x test will have. So that is the use of this random state parameter. So it is just to reproduce the code exactly that we are doing. So that is the purpose of random state, and you can give any number you want. So that is not a problem here. So you can give any number you want for random state. So it is just for reproducing the code. So now we can train our linear regression model. So as you might know, we have built this linear regression model in the previous video. So we have built this in this class. Okay, so this linear regression, now we are going to train this linear regression model using the data set that we have. So we will first train our data with this x train and the corresponding salary value y train, and then we will feed this x test to our trained linear regression model, and it will try to predict the value of y, which is the salary. So now let's see how we can train our linear regression model. So I'll just make a text here as training the linear regression model, and let's create a variable called as model. So model is equal to linear regression. Okay, so this linear regression is nothing but the class that we created. Yeah, so this is this linear regression, and we need to give certain parameters to it. The parameters that we need to give are learning rate and number of iterations. Okay, so we call these values as these parameters as hyperparameters, because like these parameters are outside the model. But there are other parameters called as model parameters. So the model parameters are nothing but the weight and bias. W and B are called as the model parameters, and the learning rate and number of iterations are called as hyperparameters. So we need to give these values manually, learning rate and number of iterations. So let's see what we can do here. So I am loading this instance, one instance of this linear regression, model to this variable called as model. And in this parenthesis, you need to mention the values of the two parameters, which are learning rate and number of iterations. And you cannot assign the values for weight and bias. So the weight and bias will be calculated by the model itself by going through the data. So it will try to learn from the data, it will try to fit to the data, and it will try to determine the weight and bias value. So that will be done by our model, but you need to give the value for learning rate and number of iterations. So that is another main thing that you need to take care of. So now let's give the value for learning rate. So let's give the value for learning rate as 0.02. So you can give 0.01. So you can basically tweak these values and see which values yields you better result. So this is the general magnitude that we use. So I'm not saying that in all the cases we can use this number. So it depends on the data set that we have and the magnitude of the values that are present in the data set. So it basically differs. So it is nothing but what is the amount of change that gradient descent applies to your parameters. So if you see the gradient descent for linear regression video, so you will understand about learning rate. Okay, so that is not a problem, I think. So I'm giving the learning rate value as 0.02, and now let's give the number of iterations as number of iterations is equal to 100 or 1000. So let me give 1000. So 1000 is a good number of iterations, so you can give 100 and check whether your model is working fine. If you don't see that your model is working fine, then you can change the number of iterations to 1000. So you basically can change these values of learning rate and number of iterations and see whether your model is working fine. So I'm just leaving that to you, so you can try different values of this learning rate and number of iterations, and that's one exercise I'm giving you. So now let's run this. So this will load our linear regression model to this instance called as model, and this it contains two parameters, learning rate and number of iterations. So I'll run this. So linear regression is not defined. Okay, so I haven't one second. Linear regression, I think I didn't run the code. Okay, so we need to run all these codes, so I just failed to do it. So let's run on the previous cells. So I'll run this linear regression class. Okay, so now we can run this line. So you should do that first itself. So this has successfully loaded our linear regression model. So I didn't run this particular cell, that's why it showed an error. So that's not an issue. Now what we can do is, now we can fit our linear regression model. So if you come to this linear regression class, we have built a function called as fit. So this is the very important function that we have in our linear regression model. So this is the part where our model will learn. So I have already mentioned you all the steps that goes in a linear regression model, right? So the 6 steps that I have made here. So all these process will be carried out in this fit function. Okay, so it is used by the model in order to learn from the data. So it will try to fit to the data, and it will try to find the loss function, and if the loss function is more, it will try to update the weights. So that is what the process that is going on in this fit and update weights. And yeah, now we can fit the data set. So for the fit, we need to give two values. So one is x and one is y, because like if you want to fit a line, you need to give both the x-axis value and the y-axis value. So you need both the x coordinate and y coordinate, and the two values will be our x train value and y train value, so which we have splitted using the train test split function. Okay, so now I'll fit my linear regression model to training data, which is x train and y train. Okay, so now I'll run this. So this process will fit our linear regression model to the data set that we have. Okay, so this process is completed. So this basically takes a very long time. So this data set contains only 30 data points, which is not a huge number. So this training process takes only a few seconds. But if your data set contains say 1000, 10,000 or more data points, in that case your learning process may take a lot of time. And even deep learning models take even more time because they are computationally more strong. There are a lot of things happening there, and you generally have a very large data set whenever you are using deep learning models, or deep learning in the sense neural networks. So in that case, the training may even takes place for several hours or even may weeks. It may occur. Okay, so this is a very small data set, so it doesn't take much time. So it just takes few seconds. So this will fit our training data to our model. So fitting is nothing but so just go here. So it will try to randomly initialize the weight and bias value, and it will try to predict the y value, and again it will see whether the loss function value is minimum or not, and this process will be continued again and again until you reach a minimum loss function. So that process is called as fit, or you can call this as the learning process for the model. Now the model has reached the optimum weight and bias value. Now let us see what is the weight value and the bias value that our model has assigned. So the first step which we did is, yeah, so we have assigned the weight value as 0, np dot zeros, and bias value as 0. So that is our first initial value. Now our model will go on changing this weight value and bias value, which is called as the updating weights, which is done by gradient descent. Now let's see what is the final weight value and bias value for this linear regression. So this process is printing the parameters in the sense weights and bias. Okay, so let's do this. So print, so just make a text as weight. So weight value is equal to, so you need to mention model.w 0, and the next thing is print bias. So bias is equal to model.b. Okay, so model is nothing but linear regression. So we have loaded this linear regression to this variable called as model, and we know that w and b represents weight, right? So we have mentioned here. So yeah, in this case, so self dot w is equal to np, so 0. So this is nothing but our weight and bias. So if you want to print these values, you need to mention model dot w. So this self is nothing but model. So it basically means this instance that we are giving. So we are giving the value as model, right? So this self will take the value model. So if you want to print the value of the weight that you are giving, weight you are getting, so you need to mention model dot b w and model dot b. Okay, so now let's see what is the value of weight and bias that we are getting. So this is the final value for our weight and bias. So 9514 point so on, and bias value. So this is our weight and bias. So how will be our linear regression equation is, so if we substitute this weight and bias value, let's come here. So y is equal to wx plus b, which is linear regression equation. And now our trained linear regression models equation will be like this. So it will be y is equal to 9514 point so on. I'm just I'm not considering this decimal. So into x plus b. So bias value is 23697. Okay, so 23697. So this is how our linear regression, trained linear regression models equation will look like. Or you can also say that it may look like this. So y is nothing but our salary. Okay, so y is our salary, and x will be our years of experience. So I'll just name this as experience. So our x will be salary. So salary is equal to 9514 plus 2369. So this is how our trained linear regression model will look like. So now when you give a new value of value of the experience, it will try to substitute that value here, and it will try to find the value of salary. So this is how machine learning works. So this may now seem very simple to you, right? So basically, this is how a machine learning model works. So it can be any complex model. So what it actually does is it will try to find this basic equation, and whenever you are giving the value of x, it will try to find the value of y. So that's what happens in machine learning. So it can be a very complex model. So it can be a logistic regression model or support vector machine or any model. So only this equation change. So this is the equation of the line, which is y is equal to wx plus b, and different models will have different equation. But the process that the machine learning does is it will try to get this equation, and then it will put in the values of x, and it will try to find the value of y. So this is the process that takes place in any machine learning model. So it's actually very simple to understand, but the thing is we just need to understand it. So we don't try to understand what's been going on under the hood. So if you try to do that, it will be very interesting for you. So now we can see that this is a very simple step that has been going on, right? So that's one thing that you can appreciate. So this is what happens in your linear regression model that we are building. Now what we can do is, so as I've told you, we have splitted the data set into training data and test data, right? And we have used this X train and Y train to train our data, and now we are going to test our model with the test data. So now what we will do is, let's try to find the value of Y given the value of X. So for this we have also created a function called as define predict, right? So this predict function, so whenever you give the value of X, it will find the value of Y. So this value will be predicted by this particular equation. Okay, so that's what we are going to do. And one more thing, as you can see here, I have mentioned W and the square bracket 0. This is because, as I've told you earlier, bias will be an integer value and the weight will be uh, a numpy array. So that's why I'm mentioning a square bracket is equal to 0. So that's one main thing, because we have created weights as a numpy array, right? A numpy array which contains all the values of 0, but bias is a single value. So that's why I'm mentioning this W as square bracket 0, which is addressing a numpy array. So the first element in this numpy array, and the first element is nothing but this particular value. Okay, so that's another thing which you need to take note of. Now let's try to predict the salary value for this X test data. Okay, so this part will be predicting the salary value for test data. Predict the salary value for test data. Now I'll just store all those predicted value in an array called as test data prediction. So test data prediction is equal to model.predict X test. Okay, so what basically happens here is, now we are giving all the values of X test, and our model will try to find the value of Y, which is the salary. Okay, so Y test is the true value, and our model will predict all those values, and it will store it in the in the array called as test data prediction. So obviously it won't be very accurate or very equal to the Y test value. There will be some difference between the test data, the original Y value, and the value predicted by our model. So it's obvious, right? So this is because our data set is a very small data set, and it can't do the learning process very efficiently. If you want a very accurate model, in that case your data set should be very huge. So if you have a more data set, or if your data set is large, then your model can make better prediction. So that's one main thing. But now let's try to understand how this process works. So the reason I'm telling you this is, the purpose of this video is to show you how we can build this linear regression from scratch and how we can implement this. So the accuracy score and the loss function value are not important in this particular video. So the idea here is to try to understand how we can implement this and how we can build this from scratch. So don't worry about the accuracy values and other evaluation scores and all. Now let's see how we can predict this value. So we have already defined this predict function in our class linear regression, and as you might know, we have loaded this linear regression into this variable called as model, and that's why instead of calling linear regression, I'm just using model.predict. So they are basically the same thing here. So model.predict x test. Now given the value of X, our model will try to find the value of Y, which is using this particular equation, and it will store all the values in this test data prediction. Now I'll run this. Okay, so now you can try to print all the predicted values. So print test data prediction. Okay, so you can try to print these values, and these are the values predicted by our model. So now what we will do is, let's try to visualize the data set that we have. So I'll just make a text here as visualizing the predicted values and actual values. Okay, so I'm just going to create a matplotlib chart or a graph in which we are trying to plot the X test value with the linear regression model that we have. Okay, so plt, which is the matplotlib library.pyplot, plt.scatter. So I'm going to create a scatter plot X test and Y test. Okay, so X test and X test, Y test, color is equal to red. So I'll explain you what we are doing in this particular part of the code after completing this. So just give me here 2 minutes. So plt.scatter and then plt dot plot x test comma test data prediction color. So let's give a different color here. So color is equal to blue. So we are basically comparing the true values. So we know that the true value that is present in the data set is nothing but y test, and the values predicted by our model is this test data prediction. So we are just basically comparing these two. So sorry, so we are just basically comparing the true values and the values predicted by our model in the form of chart. So because in the case of regression problems, it is easier to do this way, because like there are two types of problems. One is classification and the other one is regression, and I hope you know about this. Classification is one where we try to find it basically means the output is one or the other. So if you consider the diabetes data set that we have, the output will be whether the person has diabetes or not, or the person is healthy. Okay, so you have two classes here. So it is predicting an yes or no kind of a question. So those are called as a classification, and the other type of problem is called as regression, which tries to predict some accurate value. So if you consider this in this data set that we have here, we are trying to predict a numerical value, right, which is salary. So these kind of problems are called as regression. So if you try to predict the classes, it is called as classification, and if you try to predict some values, it is called as regression. So this is an example of a regression problems. And in the case of classification problem, you can use accuracy score as your evaluation metric. Okay, so like if you don't know what is meant by this accuracy score, classification and regression, so you can watch my machine learning project videos. I have did a lot of classification and regression problems as well. So in that I have shown you how you can find this accuracy score and all that. So that is not important for this particular video. I'm just explaining what we basically mean. So for classification problems, you can use accuracy score as your evaluation metric, and for regression problems, you can use mean square error, mean absolute error, and so on. Okay, so and another interesting way to evaluate this model is by visualizing the true value and the predicted value. Okay, so the predicted value is the one which is found by our model, and the true value or the actual value which is present in the true data set. And now instead of using those metrics like a mean absolute error or a mean square error, I'm just going to plot these values. So you can also try to find those values as well. It is simple, and you can see my regression project videos like house price prediction and so on, in order to like if you want to understand how you can find those mean square error and other values as well. Okay, so just a second, I've got some connection issues, so I'll just give me a minute. Mm, okay, so I'll just run all the lines here. Okay, so what I'm basically telling is you can try to find those mean absolute error and mean squared error and so on. So now we are going to visualize the true value and actual values. So let this run. So as my runtime is disconnected, I need to run all these codes. So because they won't be saved. Okay, so I'll just remove this as now. Okay, so now we are going to plot this. So I'll explain you how this particular plot works in a minute. So plt.x label work experience, and our y-axis value will be plt.y label salary, and let's name this plot as plt.title, which is salary versus experience, which is the work experience. Okay, so now plt.show. Okay, so now we can plot it. So basically what we are trying to do is first we are creating a scatter plot. Scatter plot is nothing but these dots. So we are plotting the values as dots, and we are plotting x test and y test. So you can see the x test is nothing but our test data features, and y test is nothing but our test data salary values. So now we are plotting those two values in the form of dots. and that is done by this first line of code. So we are doing a scatter plot, and we are plotting the x test value and the y test value, and we are plotting it in red color in the form of a dot. So scatter plot is nothing but all these dots, and now we are plotting a line plot. So for this we are using plt dot plot and the x test comma test data prediction. So and we are plotting this in the form of blue color. So now we are plotting a line, and this line is nothing but the value of the values predicted by our model. So we are to see the difference, we are just plotting the true values, which is y test in dots, and the predicted value in the kind of line. So if the line and the dots are closer to each other, that means your model is working fine, or your model is making somewhat good predictions. If this line is very far away from your these true values, in this case, as you might know, this line is nothing but our values predicted by our model. Like, say for example, if we give the work experience as 4, you can just come to the point where it reaches this blue color line, and if you see the corresponding salary value, so that will be our value predicted by our model. And for the same work experience, this red is the true value. Okay, so that is the difference between this red color dot and blue, where the blue is the predicted values and red color dots is the true values. Okay, so if the line is closer to all the data points, that means our model is good, that means it is making better prediction. And if this line is not closer to these data points, these red color dots, that means our model is not working fine, it is not making good prediction, and it has a very high loss function. So that is very interesting insight that you can do. So in the case of regression, instead of finding the mean absolute errors or mean square errors, we can use this plot, which is a very interesting metric. So you can visually see what is the distance between the true values and the predicted values. So it is a very good exercise for you. Okay, so you can see here most of the points are closer to the line, but as you can see here, these 3 points may not be closer to it. That is because this is a very small data set, and your training won't be that efficient. So if you need a very good working model, you need a lot of data. Okay, so but this model is actually fine because most of the data are close to it. So it is not possible to build a model where a line fits to all the data points. So that is not possible. So we cannot build a linear regression that fit to all these data points. So that is not possible. So you just need to see whether the line where the predicted value is closer to the true value. So that is one thing that you need to note. And now what you can do is you can just change the learning rate values and iteration values. So now what you do is just change the iteration value as 100. Okay, so I'll just change this value and 100. I'll show you how this works. Okay, so instead of 1000 iterations, now I'm just giving 100 iterations. That means our model will go through the data again and again for only 100 times, and our weights and bias value will be updated for only 100 times. And now, as you can see here, our weight value and bias value has changed a lot, right? Because in the previous case, we had 1000 iterations. So I'll just run all the codes again from this particular part. Okay, so now we get different. Okay, this data predictions. So I think it's basically showing the same thing. Okay, so now the plot is somewhat different, right? So if you change this number of iterations to 1000, let's see whether it is giving. No, see this line and see. Let's see whether there is any change in it. I'll run this. As you can see here, there is a change in the line. So your number of iterations and the learning rate actually influences how your learning takes place. So generally, if you have more number of iterations, you will have a better working model. But you shouldn't keep on increasing your number of iterations. Like if you keep on increasing it, there is a problem of overfitting. So you need this optimum values for this number of iterations and learning rate. There are also several procedures to arrive to this particular rate, but let's discuss about this at a later point. So that is called as model optimization. So we will discuss it about later. So what I just wanted to do is just try different values for this learning rate and number of iterations and see how much this changes. So what is the distance between the line and the true values, which is red colored data points, and so on. Okay, so that is one thing that you can take care of. So that's it. How you can implement the linear regression from scratch in Python. So there is one more thing that I need to show you. So before that, I'll just give you a quick recap on what we basically done here. So in the previous video, as you might know, we have built a linear regression model and in the form of a class. And then we have imported some basic libraries like pandas, sklearn, and matplotlib. And then we have loaded the salary dataset, which is in the form of a CSV file. to a pandas data frame, and we did some processing. So we checked the first five rows in the data frame and the last five rows, and next part we have checked how many rows and columns are there in the data frame, and then we checked whether there are any missing values in the data frame, and then we splitted the data into feature and target. We stored the feature in X and the target in Y, and we printed X and Y separately. And then the important step is that we splitted the data set into training data and test data, and we have loaded this linear regression into the variable called as model, and we have fitted the training data, which is X train and Y train, to this model, and we have checked the weight value and bias value and so on. And then we have finally predicted the value for salary given the value of years of experience using this X test data. And then we have visualized what is the distance between the true value and the predicted value, where blue color line represents the values predicted by our model, and red color dots represent the true values. Okay, so I hope everyone of you is clear about this. And there is another way we can do this. So instead of just having this float, let's say that I don't like this particular part, this is very huge, right? So now what you can do is you can just store this linear regression code separately. Let's say that you want to use this linear regression code for multiple projects, and you don't want to write the same code again and again, right? So in that case, what you can do is you can store this linear regression code in a separate Python file, and then you can call your or you can load this particular code afterwards. Like we have imported this library separately, right? So instead of writing the function for train test split function, we have a ready-made function that has been there in the sklearn library. Similarly, what you can do is you can store all this linear regression code in a separate Python file, and then you can use that code in your multiple projects or multiple use cases in order to use the linear regression. So let's see how we can do that. So it will just take a few minutes. So I'll just copy all the codes in this particular line. Okay, so I'll just copy that, and I'll create a Python file. So for this, I'm using Notepad++. So you can download and install Notepad++. So this is a very useful app for programming. So I suggest that you create this or you install this app in your PCs. So I just open this, and now I'm going to print, the paste all the linear regression code that I have. Okay. And now we also need one more thing here. So in this linear regression, we have used this NP, right? So NP is nothing but our NumPy library, but we have imported this NumPy library separately. So if you just see this, this doesn't contain the NumPy library, right? So we need to include this line as well. So I'll just copy this line also, as we are using NumPy library in this linear regression class. Okay, so you need to include this at the start. So at starts, let include this import numpy library as np, and the linear regression, the same thing that we have built in our previous video. Now what you can do is you can, in this notepad plus plus, go to file and just save the file. So you can save this file as, so now I'm going to save this as a Python file. So you can come to this save as type, and you have a different file formats. So you won't see this in a normal Notepad app. So you just need this Notepad++ app for this. And if you just come down, you will see the option for Python file. Okay, so Python file ends in the extension .py, as you can see here. So I want to store this as in the form of py, and I'll just name this file as linreg. Okay, so I'll just give a short form for this linear regression model as maybe linreg model. Okay, so this will store all this code in a Python file, and this is the name of the file. Okay, so this is our Python code. Now as you can see here, this has gave some indentation, and now this notepad plus plus basically recognize this is a Python file. Now I'll just close this, and I have another code built in. So it is basically the same thing. So it is basically the same code. The only difference is that this particular cell won't be there. Okay, so this linear regression code won't be there, and I have imported all the libraries in the starting. So your code will start from this particular point. Okay, so you don't need this class now. So instead of just writing this, what I'm doing here is, so I'll just import my data set, which is salary data set, salary data, and now I need to import my linear regression Python file, which contained the class linear regression, the model that we built. So this is the file linreg.model. Okay, so now you can import this particular file. So you can so that's what I'm doing here. So linreg, so the name should be the same for this file and here. So similarly, so we know that we can import numpy libraries, pandas, sklearn, and so on. So similarly, you can store this linear regression in a separate file, and you can call that file here. So linreg model is the name of our Python file, and this code now will import this linear regression model. Okay, so now you can go on running this file. So these steps are basically the one which we have seen before. So these steps are nothing but the same. Okay, so I'm just instead of having the linear regression class, I'm just loading it in a Python file. So all the steps are basically the same, and the only difference is that, so while loading the model, so previously we add this linear regression class, right? So we just use this model is equal to linear regression, and just we gave the parameters. Now what you need to do is, in order to load this linear regression, you need to mention the name of the Python file. So we have imported this linear regression model, right? Lin underscore reg underscore model, which is the name of our Python file, and we know that inside this Python file we have the linear regression model. So you need to call this particular Python file here, which is, you can basically call this as a module. So linear regression model, so this R should be caps. Okay, so linreg model dot linear regression. So this linear regression is nothing but just a second. So if we go there to this Python file and let's open this with okay, so notepad plus plus, as you can see a linear regression, so linear underscore regression. And so we have uploaded this file in our collaboratory session, right? So we have uploaded this. So you need to mention this Python file, which is reg.model, the same as you have entered here. Or else what you can do is, you can just import this as I've told you, you can just import this in the short form as LR. Okay, so now what we will do is, we will just use LR in this case. So you can try that one also. So that is also an efficient method to do that. And so in this case, we can have, yeah, so linreg model dot linear regression, which is a linear regression class, and you can have this number of iteration and learning rate. So you can try the 100 iterations, and then you can try 1000 iterations, or any number of iterations you want. So you can run this same code, and you can see what is the true value and the predicted value and so on. So by this way, you don't need to build this linear regression model every, once in a while you are working in a project. So you can just store this in a separate Python file, and whenever you are working in a use case or a project, you can just import that Python file and you can do your processing. So this will be a very simple steps. So this is how you can save your model, the code of your model separately, and you can use it for multiple projects. Okay, so that's it from my side, and I hope this particular video is very useful for you. And if any you have any doubts, please let me in the comments. I'll try my best to reply to your comments. And it's all about building machine learning models from scratch. So the first model that we have discussed was linear regression, and the second model that we have now is logistic regression. So logistic regression is one of the most important models in machine learning that we use very often in several projects and use cases. So in the upcoming videos, I will be explaining you what is the intuition of the logistic regression, and what is the math behind it, how we can build a gradient descent for logistic regression, and finally how you can build a logistic regression from scratch. So this will be the upcoming videos, and in this particular video, let's try to understand what is the intuition behind a logistic regression. So what is the function that it depends on, and some basic things about it. Okay, so that is the agenda for today's video. So first of all, let me explain you some of the features of logistic regression that we have to be aware of. So these are very basic things, but you need to be very clear about these things. Okay. So first, the logistic regression is a supervised learning model. I hope everyone is sure about what is meant by supervised and unsupervised learning. And logistic regression is an example of a supervised learning model. So supervised learning is something where we use labeled data. So I'll give you an example. Let's say that we have a set of data with images of dogs and cats. So there are two data sets that we have, and in the first data set, each images have labels. Say for example, all the dog images have the label as dog, and all the cat images have the label as cat. So as you can see here, and there is another set of data where there is only images and there is no label. Okay, so these data sets are called as unlabeled data, and whenever we use labeled data set in machine learning, and that type of learning is called a supervised learning, and there are specific models for it, like logistic regression, support vector machines, etc. And in the case of unlabeled dataset, we use a special type of algorithms which comes under unsupervised learning, like k-means clustering and other clustering algorithms. So supervised learning model is one which uses labeled dataset, and logistic regression is an example of the supervised learning model which uses both the data as well as the labels associated with it. Okay, so that is called as the supervised learning, and the logistic regression is one of them. And the second important point about logistic regression is that It is a classification model. Although the name suggests regression, it is mainly used for classification, where classification is something we just group the data, or we classify the data into different classes. As you can see here, we have two kinds of data points here. So one set of data are in green color triangle shape, and the other set of data is blue color, which is circular in shape. So let's call these data as class A, and these data points as class B. Now we have two classes of data, and whenever your data contains class like this, then we use a classification kind of a model. Say for example, you can think about predicting whether a person has a diabetes or not. In that case, one class that we have is a person with diabetes, and the other class of people that we have is those who doesn't have diabetes. So that is one example. And the other example is, you can also classify your mails, whether they are spam mails or normal mails. So that is another classification model. Or otherwise, you can also think about whether a news is fake or not. So in all those cases, we classify the data into different classes. Okay, so there is another type of problem called as regression, where we will try to find the accurate value. Say for example, if we want to find the salary of a person based on their work experience, in that case we are predicting the salary, which is a number, and those problems are called as regression problem. And in classification, we just classify data points. So logistic regression is a classification model. So the other feature about logistic regression is this point is very important. So logistic regression is best for binary classification problem. So some data set contains only two classes. So if you see this particular example, we just have two classes, right? Class A and class B. So these kind of data sets are called as binary data, because there are only two classes, and logistic regression is best suited for binary classification problem. So you can also do multi-class classification, but we just add to need we need to add some more features to it. But we can say that logistic regression is best for binary classification problem in most of the time. Okay, so some of the time you may need to use some other models, but generally speaking, so logistic regression works best for binary classification problem, where we will try to classify the data into two classes. So that is about logistic regression. And finally, it uses a sigmoid function. Okay, so we know that in linear regression, it uses a simple line function, right? So we know that the equation of a line, or the function of a line, is y is equal to mx plus c, whereas this logistic regression uses a sigmoid function. And when we plot using a linear regression, you will get a line like this black line. But whenever you plot a sigmoid function, you will get a plot like this. So it will be a S-shaped curve. Okay, so hence this is called as a sigmoid curve. So this is how a sigmoid curve looks, and this logistic regression is based on this sigmoid function. And whenever you plot this plot your logistic regression model, you will get a curve like this. So these are the four main features about logistic regression. So we know that it is a supervised learning model, and it is used for classification, and it works best in the case of binary classification problem. And finally, it uses sigmoid function. Okay, so now let's try to understand more about this sigmoid function, and how a logistic regression uses it, and what is the equation behind it. What is the equation of a sigmoid function? So those are the things now we are going to discuss. So let's say that we have this sigmoid curve here. So let's say that this is our logistic regression curve. And if you see here, your y-axis value will range from 0 to 1. And your x-axis value can be negative to positive. So that's another important thing you need to note. So I'll just say this once again. So your y value will be between 0 and 1, and your x-axis value will be from negative to positive. So that will be a sigmoid curve, and exactly at the midpoint you will have the y value as 0.5. Okay, so this is the part which separates this curve into two equal halves. Okay, this is 0.5 exact midpoint. Okay, so the data points which comes under this part takes the label as 1, and the data points which comes under this part takes the label as 0. So this is about a sigmoid curve. And now let's try to understand what is the equation of a sigmoid curve. So let's say that we in the x-axis we take the values as z, and in the y-axis we take the values as y cap. So I'll explain you in a minute what is meant by this z and y cap. Just for now, understand this. In the horizontal axis we are taking z values, and in the vertical axis we are taking y cap values. So y cap values will range from 0 to 1, and z can take values from negative to positive. So I hope everyone is clear up to this point. And this is the equation of a sigmoid curve. So y cap is equal to 1 by 1 plus e power minus z. Okay, so this is the equation of a sigmoid curve. And now we need to understand what is meant by this z. So z represents w dot x plus b which represents the equation of a simple line, right? We know that the equation of a line is mx plus c, where m represents slope and c represents intercept. Similarly, this also represents the equation of a line, which is wx plus b, where w represents weights and b represents bias. So let's try to understand what all these terms represent. Okay, so as you can see here, y cap represents the probability that y is equal to 1. Okay, and say for example, if you get the value y cap value as 0.8, it means that there is a 80% chance that your y value will be 1. Okay, and let's say that your y cap value is 0.2. That means there is only 20% chance that your y value will be 1, and there is a 80% chance that it will be 0. So that is represented by y cap. So in the case of linear regression, we would have written it as y is equal to mx plus c. But in the case of logistic regression, we won't take y. We won't take the actual value of y, but we will take the value of y cap, because we are just finding the probability of y being 1. Okay, whereas in the case of linear regression, we try to find accurate values. Say for example, in the salary example that I have given you, we will take the y value as salary, and you will get some salary value of y. That is some number, right? That is some numerical value, whereas this y cap is in probability, and in logistic regression we will try to find this probability, this y cap, which represents that y is equal to 1. What is the probability of y being 1? Okay, and you can also write this probability that y is equal to 1 in a different way, and that is represented by this equation. So y cap is equal to p of y is equal to 1 bar x, where y cap, we know that it represents the probability, and p represents p means probability. So how you can read this particular line is y cap is equal to the probability of y is equal to 1 for a given value of x. Okay, so this is how you can read this. So this is y cap is nothing but probability of y being 1 for a given value of x. Now what is meant by this x? So we know that x's are input features. If you think about your diabetes data set, you will have several features, like what is the blood glucose level of a person, what is the age of the person, and what is their weight, height, and so on, right? So these will be our input features, and the final outcome, whether that person has diabetes or not, will be our output value. Okay, and x will be our input features, which I hope you know the difference between features and target. Target is something which we are trying to predict. So in the case of diabetes, we are trying to predict whether the person has diabetes or not. So that will be our outcome, and the remaining columns and the remaining data represents the features. So it can be the age of the person, height of the person, weight of the person, and so on. Similarly, you will have different number of features in your data set, and there will be one target column. Okay, so this x represents our input features, and the w represents weights. So I have already made a detailed video on what is meant by weights and biases in my channel. So that videos I'll give the link of that particular video in this video description, and if you are not sure about weight and bias, so please go watch that video. Okay, so w represents w represents weight, and b represents bias. And another main important thing that you need to note is the number of weight value that we have in a model is equal to the number of input features you have in a data set. Say for example, let's say that we have this diabetes dataset, and this diabetes dataset contains about 8 features and one target column. So the number of weight values you will have will be equal to the number of input features that you have. So in this case, let's say that we have 8 input features. So this particular model will contain 8 weight value. So let's say that our dataset contains 100 feature, and it contains one target column. In that case, there will be 100 different weight values, each for each feature, and there will be 100 input features. So what I'm trying to say is the number of weights will be equal to the number of input features you have in a data set, and this is a very important thing that you need to remember. And bias is a single real number value, so it is an integer value, whereas the weight will be in the form of an array, because it can take multiple values. Multiple value in the sense it can take the number of values the input features have. So in most of the cases, we will have the weight value in the form of an array, and the bias value will be a single number. So this is a very important thing that you need to understand. Okay, and finally, we can also write this sigmoid equation as y cap is equal to sigma into z, and this sigma represents this particular sigmoid function. Okay, now if you just see this z, so z is nothing but wx plus b, and we just wanted to write this in a confined manner. That's why we are just representing this entire term as z. Okay, so z is nothing but wx plus b. So you can just substitute the z value here as well. So it will be 1 by 1 plus e power minus wx plus b. Okay, so that's how you can write this sigmoid equation. So that is all about logistic regression. So it is nothing but y cap is equal to 1 plus e power minus z. So your z can have any numerical value, but when you put that z value in this particular equation, and this equation will always give you the values ranging from 0 and 1. Okay, so your y cap value will always be in the range of 0, between 0 and 1, and that is the speciality of this particular sigmoid equation, and that's why we have the values from 0 to 1 in this y-axis. Okay, so your value won't exceed beyond the 0 and 1. So that is another thing which you can take note of. So y cap is equal to 1 by 1 plus e power minus z, where z is equal to wx plus b, where w represents our weights, x represents our the input features that we have, and b represents bias, and we are just using a sigmoid function where y cap represents what is the probability that y is equal to 1. Okay, so generally speaking, if your probability that y is equal to 1 is greater than this 0.5, then we take the label as 1. If let's say that the probability is less than 0.5, we take that the label is 0. Say, for example, let's say that a person with diabetes, so we are labeling all the people with diabetes as label 1, and all those people who doesn't have diabetes as label 0. In that case, we will try to find what is the y cap value. So if the y cap value is greater than 0.5, then we can say that the label is 1, which represents the person has diabetes. If the probability value or the y cap value is less than 0.5, then we can say that the y cap value is 0. That means the person does not have diabetes, and your data will be in this particular region, either in this region or in this region. Okay, so we have a clear distinction by this 0.5 midline. Okay, so this is about logistic regression, and I just wanted to tell you about one more thing. So I'll also explain about this in the next video, but I'll just give you an interesting idea about this sigmoid function. So if you see this equation, your z can have a larger a positive value, or it can have a larger negative value. Let's see how your y cap value will be for different z values. Let's say that you have a larger z value, larger positive z value. So in that case, let's say that your z is equal to 8. Okay, so if you substitute z is equal to 8 in this particular equation, you will get 1 by 1 plus e power minus 8, right? Because we have a minus sign here, and let's say that z is equal to 8. If you put that value here, your e will be e power minus 8 because of this negative sign. Now e power minus 8 is close to 0. Okay, so e power negative number, e power negative power is close to 0, and let's say that this term is equal to 0. So in that case, your denominator will be 1. So y cap is equal to 1 by 1, and you will get the y cap value as 1. Okay, and if you see here, if your z value is a large positive number, you will get the y cap value as 1. Whereas if you take some negative value as minus 8, let's say that we are taking the value as minus 8, in that case, if you substitute z is equal to minus 8 in this particular equation, it will be e power minus of minus 8. In that case, your minus and minus will become a plus, and your equation will be 1 by 1 plus e power plus 8. And e power plus 8 is a large positive number. Okay, so let's say that this will become a large positive number, so it will be 1 divided by 1 plus large positive number, and this particular value will be closer to 0. And if you see here, your y cap will be 0 for a larger negative value of z. So that is another important thing that you need to know. So if your data has a larger positive z value, then your label is going to be 1. And if your data for a particular data point, if your z value is a larger negative number, in that case your y cap value will be 0. Okay, so you can also just check this in some uh, e value calculator. So you have this e power x calculator, so you can find online several calculators like this. Let's try to find the value of e power 8. Okay, so let's give the value of x as 8. So this will calculate the value of e power x for the given value of x. So I'm just giving the value as 8. So as you can see here, e power x is okay. So I'll just give minus 8 first. So e power minus 8 is equal to 0 because it is like 0.00034. So that's what I have mentioned. If you have the, if you just take, yeah, if you take this z is equal to 8, and this equation become e power minus 8 because of this negative sign. So e power minus 8 is nothing but a value which is very closer to 0. If you just put that 0 here, your equation will be 1. Whereas if you take e power x is equal to 8, your value will be a very large number, so 2980. And if you come here, if you take this minus 8, z is equal to minus 8, and if you substitute here, So minus minus will get cancelled and you will get e power 8. So this will be a large positive number as we have seen, which is around 2900, right? So this large positive number, so 1 divided by a large value will give you a value which is closer to 0. So we can say that if z is a large positive number, then your y cap value will be closer to 1, and if your z value is a large negative number, then your y cap value is close to 0. Okay, so that is a very important thing that you need to be that you need to understand moving forward. So I hope everyone is clear up to this point. Everyone is clear about the sigmoid equation and how this sigmoid equation, this y cap value changes for different values of z. Okay, so this z value is found by this particular equation, which is wx plus b, where w represents weight and x represents the input feature and b represents the bias. Okay, so that is all about logistic regression. Now, as the final part in this video, let's try to understand some of the advantages and disadvantages when it comes to a logistic regression model. So these are the advantages and disadvantages of some of the advantages and disadvantages of logistic regression. First is, it is a very simple model to write, and it is very easy to implement, right? It is not as simple as linear regression, because you just have a simple equation as y is equal to mx plus c. So it is not as simple as linear regression, but it is relatively easier than other complex machine learning models. So we can say that it is very easier to implement, and it is also very efficient for a binary classification problem. So that is one advantage to it, and it performs well on the data with linear relationship. So if your data can be separated linearly, then you can use this kind of a model. But some data points may have a complex relationship. You cannot find a linear relationship between them. Say for example, if I just yeah, let's take this example. So as you can see here, there is a linear relationship between them, and we can just separate the values by just a simple line. So we can use logistic regression whenever there is a linear relationship between the target and the input features. But some data points will have a very complex relationships, and we cannot use logistic regression in that case. So that is another advantage. So this is actually an advantage as well as a disadvantage. So one is, it performs well on the data with linear relationship, which is an advantage, and it is less prone to overfitting for low dimensional data set. So low dimensional data set in the sense, if your data set contains a less number of input features, then in that case you won't get the problem of overfitting. So we have already discussed what is meant by overfitting. So if your model is overfitted, you will get a very high accuracy value for your training data, but when you test your model with the test data, your accuracy value will be very less. So your model won't perform well on new data. So that concept is called as overfitting. And if you are using a low dimensional data set with a logistic regression model, then there is there is a less chance that we will get overfitting. So in most of the cases, we won't see any overfitting issues. Okay, so that's another important advantage. So whenever there is a low dimensional data, we don't get overfitting when we use logistic regression model. So these are some of the advantages of logistic regression model. And if we talk about the disadvantages, just the opposite to what we have discussed here. So high dimensional data causes overfitting. So as I've told you, low dimensional data, no problem with it. We don't get overfitting. But if you have a high dimensional data, so dimension represents the number of input features that you have. If you have a large number of input features, in that case, your model may not work fine, and your model tend to overfit, where it will have a high accuracy on your training set, and it will have a low accuracy on your test set. And it is difficult to capture complex relationship in a data set. So this point is just opposite to the second point. So some data set may be very complex. So in that case, we may need to use different models, different classifiers like support vector machine classifier, random forest classifier, and so on. Okay, so in that case, we cannot use a simple logistic regression model. We can use whenever there is a linear relationship between them. And the third disadvantage that we have with the logistic regression is that it's sensitive to outliers. If your dataset contains some of the outliers, then it might affect the performance of your logistic regression model. Your model may not give good outputs. So that is another disadvantage. And it needs a larger data set to give accurate predictions. So if you have a very small data set, then it might be harder for your logistic regression model to understand the patterns in the data set. And if you have a larger data set, and in that case, you will get better accuracy values and so on. And it is not easy task to get a larger data set every time. So it is a disadvantage that we need to have a larger data set. So these are the advantages and disadvantages when it comes to a logistic regression model. And I just wanted to explain you about these advantages and disadvantages, because whenever we are choosing a model, we try to see whether we can use that particular data set for this model. So we just try to weigh the advantages and disadvantages. If the advantages are more for a particular model, we will go with it. Let's say that we are comparing linear regression and logistic regression for a particular model, for a particular data set. If that data set is best suited for linear regression, we go with it. If it is best suited with logistic regression, then we will go with logistic regression model for a classification or whatever task we are doing. So we try to weigh the advantages and disadvantages, and we go with the model which has more number of advantages for a particular data set. Okay, so that is all about the advantages and disadvantages of logistic regression. Okay, so I just made a mistake here, so it should be logistic regression, so it is not a linear regression. So that's a mistake from my side. So I'll just okay, so let's do that later. But just for now, understand that these are the advantages of logistic regression model. So that's it from my side, and I hope you have understood all the things that we have covered about the intuition of a logistic regression model. And it's all about building machine learning models from scratch. So the first model which we have worked on was a linear regression model, and the second model which we will be dealing with is the logistic regression model. And in the previous video, I have explained you what is the intuition behind a logistic regression model and what are the advantages and disadvantages of a logistic regression model. And in this particular video, let's discuss about what is the math behind a logistic regression model and how does a logistic regression model predicts our label values like 0 or 1. So this will be the agenda for today's video. So let's get started right away. So I have explained this in my previous video. I'll just give you a quick recap. So a logistic regression model curve would look something like this. So you can call this curve as a sigmoid curve or an S-shaped curve. So this is the example of a sigmoid curve, and we will take the x-axis value as generally z, and your y-axis value will be y cap values, and your y cap values will range from 0 to 1. So this is where your y cap values lies between 0 and 1, and your z values can range from negative values to positive values. And I'll explain you why we get this kind of a curve and what is the significance of this. And now let's try to understand what is meant by this y cap and z and so on. So this is how the formula of a sigmoid function looks like, or the equation of a sigmoid curve looks like. It's y cap is equal to 1 by 1 plus e power minus z. So this y cap value depends on the value of z. Okay, so this is the relation of the sigmoid function, and now we need to know what is this z. So z is nothing but z is equal to w dot x plus b, which is similar to the equation of a straight line, which is y is equal to mx plus c, right, where m represents the slope and the c represents intercept. And we generally instead of slope and intercept, we use weight and bias as our notation, and we can write the equation of the line like this. So wx plus b, which is equal to a line equation or a linear regression equation. So we have discussed about the linear regression in the previous video, which is similar to this. Okay, so once you find this value of z using this weight value, bias value, and x value, you can plug in the values of z in this particular equation in order to get y cap, where your y cap will be the probability that y is equal to 1. So whenever you're doing, or whenever you're working with logistic regression, in most of the cases you're trying to predict binary classes. Say for example, you will be trying to predict whether the output will be 0 or 1 or an yes or no answer, like if a person has any heart disease or not. So you are just predicting some classes, or it can be whether a news is a real or fake. So there will be two classes in most of the cases, which is called as a binary classification problem, and the one label will be given the label 1. Let's say that if a news is fake, then we can call it as y is equal to 1, and if news is real, then we can say that y is equal to 0. So we just label whether the news is real or fake. So we will do this in all the binary classification problem, and y cap is nothing but what is the probability that y is equal to 1. Say you get the y cap value as 0.8. That means there is a 80% chance that your y cap value is 1. So which means there is a 80% chance that your news is fake. So that is meant by this. And let's say we get the y cap value as 0.2. So 0.2 represents there is only a 20% probability that your news is fake. So we can say that it is a real news. So this is how we interpret this, and we generally take this 0.5 as the midline. If your y cap value is greater than 0.5, then we take the y value as 1. If your y cap value is less than 0.5, then we take the y cap value as 0. Okay, so if it is less than 0.5, it's 0. If it is greater than 0.5, you will get the label as 1. Okay, so this is meant by this sigmoid function and y cap. And you can also, instead of writing that probability that y is equal to 1, you can write this particular statement in terms of probability. So p represents probability here. We can read this particular line as y cap is equal to probability that y is equal to 1 for a given value of x. Okay, so where x is our input features, say we are predicting whether a person has a heart disease or not. So in that case, we will have to we have to give some features. So features can be what is the age of a person, and whether that person doing some good amount of exercise or not. So we will have several features, and our model will predict whether the person has any heart disease or not based on these features. So these features are called as input features, and we generally represent input features as x. So you can have one input feature, or you can have 10 input features, or you can have 100 input feature, and it differs based on the data set that we have. So once we have this input features, we can plug in those values in this particular equation to get z, and we can substitute the value of z in this sigmoid equation to get the value of y cap, which will lie between 0 and 1. And then we have the weight value. So w represent weights, and I have already made a video on weights and bias, which is a vast topic. So if you are not aware of this weights and bias, you can go to the 6th module of my channel, or else I'll give you the link of this weights and bias video in this particular video description. You can check that out. So weights, so one main thing that you need to remember is that you will have the number of weights equal to the number of input features. So let's say that you have 10 input features. In that case, you will have 10 weight values, whereas bias is a single real number. It is a single value, whereas weight can be an array which contains as many number of input features as there. Let's say that we are having a data set, as I've told you, where we are trying to predict whether a person has heart disease or not. So in that case, we will have the input features as age, the BMI of a person, and so on. Let's say that there are about 10 input features. So you will have for that particular model, you will have 10 weight values. If you have 100 input features, you will have 100 weight values, each one for each column or each feature. Okay. If you have only one input feature and one target variable, then you will have only one weight value. So that is one main thing that you need to note, which I have mentioned here. Okay. So you can take note of this. And B is the bias value. So I recommend you to watch the weight and bias video if you are not sure about these steps. Okay, so that is meant by this W and B, and then y cap is equal to sigma of z. So sigma is z is nothing but this particular equation. So it is just a short form of writing this equation. So we know that we can write an equation like y is equal to f of x, right? Where we can say that y is y is a dependent value on x, or y as the function which is dependent on x. Similarly, we can say that y cap is equal to sigma z, which where sigma represents a sigmoid function which is given by this particular equation. So I hope everyone is clear up to this point. So y cap is the value which we are trying to predict, whose values lies between 0 and 1, and it will be our label, and it is basically the probability value. So now what happens is, when we train our machine learning model, first of all, it's try to predict, or not predict, it will try to find what is the optimum value for weight and bias. We cannot have the same weight value and bias value in all the cases. So the weight value and bias value changes depending upon the data set that we have. So the model works in order to find what is the best weight value and bias value, so that it can make accurate prediction. So this step is called as training the machine learning model. So this is the so-called learning process, where it will try to find the parameters. So W and B are nothing but the parameters of the model. So it will try to find these models. So once the model has fitted to the data and it has found the optimum weight and bias value, and now we will find the value of z, and then we can find the value of y cap with that. Okay, so we won't be going in detail about how we will find this weight value and bias value in this video, but I will be explaining that on how the machine learning model finds the weight value and the bias value in the next video, where I will explain you this using gradient descent. So using gradient descent, the model finds the optimum weight value and the bias value, which we have discussed in linear regression as well. So there is a slight changes in how gradient descent works in linear regression and logistic regression. So we will discuss that in the next video, but just for now, understand that weight value and bias value is determined by the model using several steps using gradient descent, and we will arrive at some optimum weight value and bias value. Okay, and now we need to substitute the values in these equations. Let's say that we have some data set, and we have fitted our data set to our logistic regression model, and it has found the optimum value for weight and bias, which can give you accurate prediction. Let's say that weight value and bias value are 5 and 10. So let's say that weight value is equal to 5 and bias value is equal to 10, and let's say that this particular example dataset contains only one input feature. So in that case, you will have only one weight value, which is 5, and you have bias value as 10. So this is just an example value. I'm not telling that this is the value we will get every time. So that's not the case. We are just taking some example value, and assume that we have trained our machine learning model and it has arrived at this weight value and bias value. Now what we can do is, if we have the new data sets and if we have the new values for x, we can substitute the value of x here, and you will get the value of z for that particular new data point. And once you fill in the values in the z, you will get the y cap value, which will lie between 0 and 1. So I'll manually show you how we can calculate these values, and this is what happens in the logistic regression model. Okay, so let's try to do that. So these are the new values that we have. So previously we have trained with the data set, and our logistic regression model has learned from it. Now we have the new data set, and now we are going to discuss how the model finds the y cap value. So it's just very simple. We just need to plug in the values. So we have two formulas. The first formula is for z. So first we have to find the value of z using this particular equation, and then we need to find the value of y cap. So let's take all the five values, all the x value and the y cap x value. So we have x is equal to -9, x is equal to -8, x is equal to 0, x is equal to 8, and x is equal to 9. So that is a very interesting thing that I'm going to tell you once we calculate all these values. So it is a very important thing that you need to remember. So let's see what is that. So now just plug in the value of x in this equation and find the value of z. If we do that, we will get the values like this. So if you put the x is equal to -9 in this case, you will get z is equal to 5 into -9 plus 10. And if you solve this, you will get 5 into 9 is 45, minus 45 plus 10 is -35. So it is very simple, right? A simple mathematics. And if you put x is equal to -8, you will get z is equal to -30, minus 40 plus 10, which is equal to -30. And if x is equal to 0, your z value will be equal to 10. And if x is equal to 8, and your z value will be equal to 50. And finally, when your x value is equal to 9, your z value will be 55. So we have arrived at our z value, and now we need to plug in this z values separately for each of these x values in this y cap equation, which is the sigmoid function equation. Okay, so let's do that. So y cap is equal to 1 by 1 plus e power 35. So we have z value as -35, and if you substitute the value of z is equal to -35 in this particular equation, this minus and this minus will be changed to a plus, right? So minus into minus is plus. So you will get 1 plus e power plus 35. So that's what I have written here. And now let's calculate this y cap value. So you can just go to your Google Chrome. So just a second. So I'll just show you how we can calculate this value. Scientific. So you can just search a scientific calculator online. So you will get this calculator, which is very useful for us in this case. So the equation that we have is 1 divided by 1 plus e power 35. Okay, so I'll just write this equation here. 1 divided by 1 plus e power. So for power, you need to give this x power y. So e power plus 35, right? So plus 35 is the value that we got, and your value will be 6.3 and so on into e power minus 16. So this value is very closer to 0. Okay, so it is e power minus 16. So it is very closer to 0, and hence we can say that your y cap value will be 0. Okay, so it will be very close to 0. Hence we can write it as y cap is equal to 0. And now let's calculate the same for z is equal to -30. And when you put -30 here, you will get 1 plus e power plus 30. And when you do the same, it will also be the similar case. So I'll just clear this. 1 divided by 1 plus e power plus 30. Again, this value will be very closer to 0. So e power minus 14 some number. So this is very close to 0. And then we have z value is equal to 10. So if you just plug in similarly the value of z value here, you will get y cap is equal to 1 by 1 plus e power minus 10. So this is very important, because in the previous cases we had z value as a negative number, whereas in this case the z value is plus number. So you will get 1 plus 1 divided by 1 plus e power minus 10, and 1 power e power minus 10 is a very large negative number. Okay, so let me show you. So you will get the value closer to 1. So I'll just clear this. So let's write 1 divided by 1 plus e power 10. So sorry, minus 10, right? So minus 10 is the equation that we have. So e power minus 10, and the value you get will be very close to 1. So as you can see here, it is 0.999 and so on. So we can write this particular value as 1. So that's what I have written here. So whenever you have z value as negative, you will get the y cap value, which is closer to 0. And whenever your z value is a large positive number, in those cases you will get the y cap as 1. And if you do the same for this particular equation here, the z value is a very large positive number, right? So I'll just show you this one alone. So this is actually a very good exercise for you. You can try other values as well. So 1 divided by 1 plus e power 50. Okay, so yeah, 1 power 50, sorry, minus 50, I think. Yeah, it's 1 plus e power minus 50, and your value will be 1. So the if similarly if you try to find the y cap value for this particular z value, which is z is equal to 55, again you will get the y cap value as 1. So this is a very important thing that you need to remember. So whenever you are having the z value as a large negative number, your y cap value will be closer to 0, which I have shown you using this particular equation. And whenever you are having a large positive number as the value of z, you will get a y cap value of 1. So we can say that we will get two labels as either 0 or 1. So this can be anything depending upon the data set you have. It can be whether predicting whether a news is real or fake, where we can give the label as 1 for fake news and 0 for real news. And whether a person has diabetes or not, where like a person with diabetes, you can give the label value as 1, and for a person without diabetes you can give label value as 0, and so on. So similarly, this is how you can use the sigmoid function, which is basically the logistic regression. So logistic regression is built based on the sigmoid function. So you will get these label values. So that is all about the math behind the logistic regression, and this is how it will find the y cap values which lies between 0 and 1. So this is not exactly 0, but it is very very close to 0 when you have negative number, and when it is a positive number, the value will be very very close to 1. So we can say that whenever your y cap value is greater than zero point 0.5, you can say that the y cap value is 1, and whenever it is less than zero point 0.5, you can say that the y cap value or the label value is equal to 0. And we have already discussed what is the sigmoid function, and using this z, which is equal to wx plus b, we can derive this y cap value. Okay, so the important inference that you need to remember here is, if z value is a large positive number, this number will be very close to 0, so which we have seen before. So if it is a large positive number, then it will be e power minus z, because like plus into minus is minus, so you will get a value. So e power negative some number is very close to 0, so you will get 1 by 1, which is equal to 1. So you will get the y cap value as 1, and whenever your z value is a large negative number, so that negative and this particular negative before the z will cancel each other, and you will get a e power larger positive number, and e power a large positive number will be a very huge number. So that's what I have written here, 1 divided by 1 plus large positive number. So this large positive number is nothing but e power plus z, and this is e power minus z, and so on. So when you have a 1 divided by a very large number, your your final value will be very closer to 0, which we have discussed before. So this is the important inference that we need to remember. And this is how our model can predict using the sigmoid function what is the y cap value, where y cap is the probability of whether you will get a y cap value as 1 or 0. So 1 represents there is an 100% probability that your y cap value is 1, and 0 means there is a 0% chance that your y cap value is going to be 1. Okay, so this is how we can infer logistic regression function, and in the next video I'll explain you how we can find the loss function of a logistic regression model, and how we can use that in order to deduce the gradient descent for logistic regression. So it is slightly different from what we have seen in the linear regression case, and once we have done that, so we can move on to building a logistic regression model from scratch in Python. Okay, so that will be the next series of videos, and I hope you have understood all the things covered in this particular. And this 7th module is all about building machine learning models from scratch. So the first model that we worked on was a linear regression model, and now we are currently working on a logistic regression model. In my previous videos, I have explained you what is the intuition and math behind a logistic regression model, and in today's video, we are going to discuss how we can find the loss function and cost function for a logistic regression model, and this is the agenda for today's video. So let's get started right away. So as I told you in my previous video, I have explained you what is meant by this logistic regression, where we will use it, and so on. I'll just give you a quick recap about this logistic regression model. So if you plot a logistic regression function, you will get a curve like this, and we call this curve as a sigmoid curve or a S-shaped curve because of this particular shape. Okay, so in this curve, we will if you see this graph, we will take z values in the x-axis and y cap values in the y-axis. So if you notice the values in the y-axis, you can see that this y cap value lies between 0 and 1. Okay, so your y cap value cannot exceed 1, and your y cap value cannot decrease beyond 0, whereas your z value can have negative values all the way up to positive values. So it can have any values, but y cap values will lie between 0 and 1. And how we will find this y cap value is by using a sigmoid function. So this is called as a sigmoid function or a sigmoid equation. So it is given by y cap is equal to 1 divided by 1 plus e power minus z. So this is called as the sigmoid equation, and now we need to know what is meant by this z. So this z is nothing but z is equal to wx plus b. So if you just look into this equation closely, you can realize that this is nothing but the equation of a straight line, right? We know that the equation of a straight line is y is equal to mx plus c. Similarly, this is wx plus b, where w represents the weight and b represents the bias. So we have already discussed about what is meant by weights and bias in the previous videos. If you are not sure about these terms, I'll give the link of the weights and bias video in this video description. You can check that out. Okay. So hence we can understand that z is equal to wx plus b, and y cap is given by this particular equation, where y cap depends on the z value, and we know what is the z value. So whenever you substitute the value of z in this equation, your y cap value will lie in this range. Now we need to understand what is the significance of this y cap and why we are using this logistic regression. Okay, so these are the terms that we have used in this equation. So y cap is the probability that y is equal to 1. So in logistic regression, the problems we work on will be a binary classification problem. Binary classification in the sense we will try to classify the data points as two classes. It can be either 0 or 1, or it can be like predicting whether a news is real or fake. So in all of these cases, there are only two classes or two types. So we will try to classify our data points into these two classes, and generally we give labels to our data points. Let's say that we are predicting whether a news is real or fake. Let's say that if a news is fake, we can take that y is equal to 1. If a news is real, then we can say that y is equal to 0. So now we have two classes and we have two label values, which are 0 and 1. And now we need to find whether a news is real or fake. In other words, we will try to find whether the y value is equal to 1 or 0. So this is where y cap is useful. So what we will do using logistic regression is we will try to find the probability. What is the probability that y is equal to 1? So now look at this values. Let's say that you get a y cap value of 0.8 using this particular equation. So 0.8 basically means that you have a probability of 0.8 that y is equal to 1. So how you can say in other words is that there is a 80% chance that y is equal to 1. So what y is equal to 1 is nothing but the news is fake, right? So we can say that there is a 80% chance that the news is fake. Or if you get the y cap value as 0.2, that means there is only a 20% chance that the news is fake. So you can say that it is most probably it is a real news. So this is how logistic regression works. It tries to classify binary values. So this is why we use it in a binary classification problem, where we will try to find the whether y is equal to 1 or 0, and we won't find it precisely. So we won't calculate y is equal to 1 or 0, but we will try to find the likelihood or the probability that y is equal to 1. So that is given by this sigmoid equation y cap. Okay, so in other words of reading this probability that y is equal to 1 is, you can write this particular line like this. So y cap is equal to p of y is equal to 1x. So how you can read this line is y cap is equal to the probability that y is equal to 1 for a given value of x. Now what is meant by this x? So x is our input feature. So let's try to understand this with another example. So whenever you are training your machine learning model, you need to give it features. Let's say that we are predicting whether a person has diabetes or not. In that case, we need to train our model with features like what is the blood glucose level of a person, what is the BMI of a person, what is their weight, and so on. So all these are called as input features. So once we feed these input features and train our machine learning model, whenever you are giving new values, it can predict whether that person has diabetes or not. So x will be our input features, and this is what this z is equal to wx plus b represents. So this x is our input feature, and w will be our weights, and b will be our bias. So if you consider a linear regression problem, so weight is similar to the slope of the line, and b bias is similar to the intercept of the line. So if you have watched my videos on linear regression, you will understand all these topics. So if you haven't, please watch those videos as well. Okay, and now the other thing which you need to remember is that the number of weights is equal to the number of input features that you have. Let's say you have 10 input features. In that case, you will have 10 different weights for each of these input feature, whereas you will have only one bias value. So bias is a one real number value, but you can consider these weights as an array. So this is all about logistic regression, where we can say that our model will try to find what is the probability that y is equal to 1. And it is mainly used in binary classification problem, and we know that the y cap value lies between 0 and 1 because it is a probability value, and probability value can lie only between 0 and 1, and this is the sigmoid equation, and this is the equation of z. And I hope you are clear up to this point. Now the reason for let's try to understand why we need to understand about loss function and cost function for a logistic regression model. So it is quite different from the loss function that we will use for a linear regression. So we won't be using the same loss function equation that we have used in linear regression, but we need to use a different one. Let's try to understand what is the significance of this loss function. If you look at this equation, z is equal to w x plus b. This W and B are called as the model parameters. So model parameters of this logistic regression model. Now, our machine learning model will try to find the optimum value for weight and bias, W and B. It will try to find what will be the best value for weight and bias, so that it can accurately predict the Y cap value. Okay, so if your weight value and bias value are not proper, they are not optimum, then you won't get proper Y cap value. So what happens in that case when you don't have proper weight value and bias value is that if your news is real, your machine learning model may predict that that particular news is fake. So it may predict wrongly. So that is what happens when you have improper weight value and bias value. So our machine learning model will try to find the best value for weight and bias, and this is not a single step process, and it will take in multiple steps. And this is where we use an algorithm or a method called as gradient descent. So in the next video I'll explain you how we will use this gradient descent. But for now, in order to calculate this gradient descent, loss function is very important. Okay, so in order to find which parameters W and B are important, like which parameters are optimum, we need to find the loss function of the model. So, and other thing you need to remember is that the weight and bias value changes in each case. So you won't get the same weight value and bias value in all the projects that you work on. So these values differ based on the data set that we have. Okay, and these values, we don't manually give these values to the model. So these values will be determined by our model by learning from the data set that we have. So we need to find which is the optimum value. Now let's discuss what is the importance of loss function and how does it influence this weight value and bias value. So loss function measures how far an estimated value is from its true value. So if you just look at this particular statement, we have two values here. One is the estimated value and the another one is the true value. Estimated value is the value predicted by our model, which is represented by this yi cap, and the true value is the true value given in the data set. Okay, so this is the actual value. So we have two values. One is the predicted value, which is predicted by our model, and the another one is true value or the actual value. And this loss function is nothing but what is the difference between these two values, the estimated value and the true value. If the difference between the true value and the estimated value is very high, that means our model is not working fine, right? Because let's say that we are predicting the salary of a person based on their years of work experience, and the true value of the salary of a person is, let's say it's about 50,000 rupees per month, and let's say our model has predicted their salary as 30,000 per month. Now there is a huge difference between the true value and estimated value, right? So the difference is about 20,000 rupees, and the difference is too huge. So you don't want that much difference between the estimated value and the true value, and that is represented by this loss function. So what is the difference or the distance between the true value and the estimated value? And this is given by the loss function. So this is the kind of loss function we will generally use in regression problems, like regression models like linear regression, where we will try to predict a particular value. So if you think about the salary example, we are trying to predict some numerical value, which is the salary. But in the case of logistic regression, as I've told you before, we will try to predict whether y is equal to 1 or 0. So we cannot use this kind of a loss function. So we need a different kind of a loss function. Okay, but the loss function definition remains the same. It is just to measure how far the estimated value and the true value are. So we cannot use this kind of loss function. And if you use the same loss function which we have used for linear regression, so if you remember, we have used this loss function for our linear regression model, and if you use this kind of loss function, your gradient descent won't work properly. So you will get a gradient descent curve something like this, and we call these as a curve with multiple local minima. Okay, so gradient descent with local minima, and we know that we generally take loss function or cost function. So I'll explain you what is the difference between loss function and cost function in the upcoming slide. But just for now, remember that in the y-axis we will take a loss function or the cost function, and in the x-axis we will take weight value and bias value. So we will try to find what is the loss function value for different parameters. So we will keep on changing the weight value and bias value, and we will try to see for which parameter value the loss function is very less. So we know that if the loss function value is less, then that means our model is working accurate, right? So we need to have minimum loss function. So we will try to see for which parameter. So this is the different parameters that we have took on x-axis. So for different parameters, we will try to take the loss function value, and if you look at this curve, there are multiple minima. So these points are called as minima, and these are called as local minima. But how does an optimum gradient descent model looks like is like this? Okay, so you will have this kind of a curve is called as a convex curve, and convex curve are really important for us in gradient descent. So then only you can reach this global minimum. So global minimum is the point. So at this point, if you just come to this x-axis, you will have some parameter values. So your parameters will be some things. Okay, so the weight value and bias value for this particular weight value and bias value, your loss function value will be very small. Whereas if you take the weight value and bias value, let's say that we are taking initial weights. Okay, so let's take at this point, and we are taking the weights and bias value in this particular point. And if you just come to this y-axis, you can see that the loss function value is very high. So wherever you start your initial weight, we need to reach this global minimum, and it is the point for this weight value and bias value or the parameter value, your loss function will be very minimum. And for this particular action, we need a convex curve like this. You cannot have multiple minima, but you just need one single global minimum. So this is the problem with using this kind of a loss function, because logistic regression is not a convex function like and but if you take the log of this loss, you will get this kind of a convex curve. So you will understand what I'm trying to say. Just hang in there. So this is the reason we are not using this particular loss function, because of the problem of local minima. Now, for this particular purpose, we need to use a different kind of loss function, not this particular equation, but we need a different loss function. And now let's try to discuss that particular loss function. So this loss function for logistic regression, we can use a loss function called as binary cross entropy loss function, and it is also called as log loss. So we are going to take log of the loss function, and the equation will look something like loss function of y comma y cap. So we know that loss function is the difference between estimated value and true value, right? Where your y will be the true value and y cap will be your estimated value or the predicted value. So loss function is the function of the true value and estimated value. So you can write the loss function as L of y comma y cap, and L of y comma y cap is equal to minus y log y cap plus 1 minus y log of 1 minus y cap. So this is the log loss equation or the binary cross entropy loss function. So this is a very important loss function formula, and you need to take note of this. And if you see this closely, you have two terms in this equation: y log y cap, and this is the first term that we have, and the second term is 1 minus y into log of 1 minus y cap. Okay, and this negative sign is common for both these terms. So this is a very important equation, and I'm not going to go detail into how we derived this particular loss function. So you can just search on internet if you want that, but we don't have to go into that much detail in this case. Okay, so this is the loss function that we have. Now we need to find out will be the loss function value. So we have already discussed that we need a very minimum loss function, and if we have a very minimum loss function, that means our weight and bias value are working fine, right? Now let's see how this loss function works. So we know that we can have only two values for y. One is 1 and 0, right? So we have this is a binary classification problem. So hence you can have only two labels, either 0 or 1. And now we are going to put the two values. So we are going to try when y is equal to 1 and y is equal to 0. And we know that y cap value lies between 0 and 1, right? So I have explained this in the first slide. So y cap value lies between 0 and 1 because it is the probability, and we get this by the sigmoid equation. So I hope you understand this part. So if you just look at this equation, your y can take the values of either 1 or 0, and your y cap can take any value between 0 and 1. So this is how your equation is. And now what we will do is, let's try to substitute the value of y is equal to 1 and then y is equal to 0. So let's do that separately. Now we are going to give y is equal to 1. Let's say that a news is fake, and for fake news, we are going to give the label as 1. So what happens is, in this case, if you substitute the value of y is equal to 1 in this equation, so this will be 1 into log y cap, and this will be 1 minus y will become 1 minus 1, right? And this particular part becomes 0 now. So 1 minus 1, and because of this particular term, the second term will become 0, and you will have only this first term, which is log y cap. So 1 into log y cap, which is equal to log y cap. So that's what I have written here. So L of 1 comma y, whenever that y value is equal to 1, your loss function will be minus log of y cap. Okay, so this will be our log value. So I'll just remove this or else. Okay, so now So we have two terms, and whenever y value is equal to 1, this second term will be 0, and you will have only this term, and this y value is equal to 1. So you will get a loss function of 1 comma y cap is equal to minus log y cap. And whenever y value is equal to 0, we need to discuss that as well. So whenever y is equal to 0, if you substitute the value of y as 0, you will get L of 0 comma y cap. Now this particular term will become 0 because we are substituting y is equal to 0. Therefore this term, because of 0 into log y, so 0 into any number is 0, so this particular equation will become 0. And now 1 minus 0, so we are substituting y is equal to 0, so therefore this 1 minus 0 will be 1. Okay, so this is the second term. Now you will have this first term will be 0, and you will have only this second term, which is negative log of 1 minus y cap. So this negative sign comes from here. So as I've told you, this negative sign is common for both first term and the second term. So this is the loss function you will get whenever y value is equal to 1 and y value is equal to y cap. Now let's try to understand what is the significance of this. So why we need this kind of a loss function value. So our goal, so I'll just remove this just a second. So our goal is to have a minimum loss function value, right? So as I've told you, minimum loss function means there is not much difference between the true value and the estimated value. So we always want a minimum loss function. And now we need to understand when this loss function value will be minimum. Just look at this term minus log y cap. For what value of y cap your loss function will be minimum, and in this case for what value of 1 minus y cap your loss function will be minimum. So that is the important inference that you need to get in this case. So we always want a smaller loss function because that means our model is working accurately, right? So we always want a smaller loss function, hence y cap should be very large, so that negative log y cap will be a large negative number. So large negative number means it is a very small number, right? So large positive number is a large number and a large negative number is a very small number, and we know that it is basic math. And if you want a very large negative number for loss function, this log y cap value should be very huge. For log y cap value should be huge, this y cap value should be very large. So that's what I have mentioned here. So if you want a smaller loss function, your y cap value should be very large, and if your y cap value is very large, this minus log y cap will become a very large negative number, which means your loss function value is very minimum. It is a very small number, and we know that our y cap value can lie only between 0 and 1. So whenever I'm saying that a y cap value should be very large, it is nothing but it is closer to 1. And whenever in the case of y is equal to 0, we always again want a smaller loss function. In this case, the y cap value should be very small. So when the y cap value should be very small, your 1 minus y cap value will be large, and your negative log 1 minus y cap will be a large negative number. So this is just opposite to it. So this is log of y cap, but this is 1 minus y cap. So it is just quite opposite to it. Because if you have a larger number, so a number close to 1 for y cap, the difference between 1 minus y cap will be very small. So let's say that you are having the y cap value of 0.9, so 1 minus 0.9 is 0.1, and if you have log of 0.1, it is a very small number, so we don't want that. So whenever y is equal to 1, we want the y cap value should be large, which is closer to 0, and whenever y is equal to 0, you want your y cap value should be very small. I'll just show you how this what this basically means. Let's try to take different value for y cap for this equation and y cap for this second equation. So first is negative log of y cap. So I'll just go to my Google Chrome, so you can just type in scientific calculator, where you can just calculate some basic values. So I'll just give negative log of some number. So we know that for y is equal to 1, we want a very large y cap value. So what I'm going to do is a large y cap value, in the sense it should lie between 0 and 1. So the large number should be very closer to 1. So I'll just give 0.9. Okay. So if you give 0.9, your loss function value is 0.045. So this negative log of y cap is nothing but our loss function, right? So loss function is equal to minus log of y cap. And if you see here, if you take a larger number like 0.9, you get a very small loss function value, which is 0.045 and so on. Now what we are going to do is, we are going to take a very small number. So we are going to take this equation and we are going to take a very small number, and now we are going to check the loss function value. So negative log of smaller value, in the sense which is closer to 0. So I'm taking 0.1. So in this case, your loss function value will be 1. So 1 is a very huge number, right? When compared to the 0.04. So previously we have calculated the log, like negative log of 0.9. So 0.9 is a larger number than 0.1. So whenever you are taking the y cap value, so this 0.9 and 0.1 represents y cap value. So whenever you are taking a larger y cap value, your loss function will be minimum in this case, and whenever you are taking a small number, your y cap value will be very large. Okay, so you can compare these two numbers. Now, this is what I have mentioned in this particular inference part. So these two lines are the inference that we get from this particular equation. So when y is equal to 1, you will get the loss function equation like this. And for this equation, y cap value should be very large, so that it will be a large negative number and so on. Now, the thing is, uh, as I've told you, for loss function to be minimum, y cap value should be very large, that it is closer to 1, which is similar to y is equal to 1. So this is what the loss function will try to do. So whenever your y value is equal to 1, it will try to push the y cap value to 1 as well. Whereas whenever your y value is equal to 0, it will try to push the y value to 0 as well, y cap value to 0 as well. Now let's see. Now we have negative log of 1 minus y cap, and let's try the similar part here. So I'm taking negative log of 1 minus y cap. 1 minus y cap. So we need a very small value in this case. So it's just opposite to it. So whenever you take a very small value, your loss function value should be minimum. And when you take a larger value, which is closer to 1, your loss function value should be large. So let's try that. So I'm taking a very small value like 0.1, which is closer to 0. So if you will get a value something close to this, so 0.045. But when you take the log value, the y cap value is negative log of 1 minus y cap, and now I'm going to take a larger number like 0.9. So in this case, you will get the loss function value as 1, which is very large. So these two are just opposite to it. So as you can see here, so these two cases are just opposite to it. So whenever your y value is equal to 1, your loss function will be minimum, and it will try to push your y cap value to 1. And whenever your y value is equal to 0, your loss function value will try to push your value to 0. So this is what happens in a loss function case, and we will try to use that in the gradient descent. And now we need to understand what is the difference between this loss function and cost function. So this is a very important part. A lot of people may still have ambiguity on what is meant by this loss function and cost function, and I think I have mentioned in one of the videos as well. So what is the difference between them? But I'll just try to explain this to you again. So if you think about loss function, we will try to find the difference between the true value and the predicted value for only one case, for only one data point. So let's say that there is a person and he makes a salary of about 50,000 rupees, and the machine learning model had predicted the salary of the person as 30,000 rupees. And now we try to find the difference between the true value and the estimated value. And now we are doing this for only one data point, right? So whenever you do the difference, you do the estimation of the difference between the true value and the predicted value for one data point, it is called as loss function. And the cost function is something when you do the same thing, when you try to find the difference between the true value and the predicted value for the entire data set, it is called as the cost function. So that is the difference between them. It is basically very simple, right? So loss function mainly applies for a single training set as compared to the cost function, which deals with the penalty for a number of training set or the complete batch. So the basic things of loss function and cost function are basically the same thing. They try to find the difference between the predicted value and the true value, but loss function is concerned with only one value, whereas cost function is concerned with all the values or all the data points in a data set. So that is the difference between them, and this is a very important point, and you may be asked for this particular question in your interviews related to machine learning as well. So please remember these points, or you can take a note of it as well. Now there is a quite change in this loss function and cost function, okay, because of the difference in their definitions and their understanding. So your cost function will be slightly different from this loss function. So let's try to understand how the cost function looks like. So we know that this is the loss function equation, which is L of y comma y cap is equal to minus y of log y cap plus 1 minus y log of 1 minus y cap. And now what we need to do is, for cost function, we need to take the summation of all the loss functions of all the data points that we have in a data set. So it is actually the same equation. You just need to take the summation of all the data points, and you need to divide it by the total number of data points. So let's say that M denotes the number of data points in the training set. Let's say that we have about 100 data points in a data set. So we have salary data for 100 different people in a data set, and M denotes the number of data points that we have. Okay, so that is the importance of M, and your cost function equation will look something like this. So this equation may look very big complicated long, but it is actually very simple. This is basically the same equation. You just need to include the summation and this average. So we are just taking the average of all the loss function. Okay, so this cost function is represented by j of w comma b, whereas loss function is represented by L. So w and b are nothing but weight and bias value. So we always represent cost function as a function of weight and bias value, because like your cost function value changes depending on the weight value and the bias value that you have, as I have told you in the gradient descent part. Okay, so as you can see here, so for different weight value and bias value, your cost function value will change. So we always represent our cost function as the function of weight and bias. Okay, so that's why I've represented it as j of w comma b, and j of w comma b is equal to 1 by m, where m denotes the total number of data points, summation of all the loss functions. So how we will find the cost function is, our machine learning model will try to find the loss function for all the individual data points. So once it tries to find the loss function of all the data points, it will take the average of it. So it will try to sum it up and take the average of it, and it is called as the cost function. Okay, so it is cost function is nothing but the mean average of loss function, so nothing more than that. So if you have 1,000 data points in a data set, so your model will try to find the loss function for all these 1,000 data points, and once it found the loss function of all these data points individually, it will try to take the average of it, and that average is called as the cost function. So that is the simplest definition I can give you. So j of w comma b is equal to 1 by m summation of L of y comma y cap. So you can just represent this as I just missed it here. So you can just write it as m. So let's say this is m and I is equal to 1. So this is how we represent summation, right? So 1. So similarly, you can do the same thing here as well. So at the top of the summation, we represent the total number of values you have, and I is equal to 1. So I is equal to 1. So this should come on top and below the summation part. So everyone knows this. Okay. So summation of loss function of yi and yi cap. So yi is nothing but all the individual values. So we are trying to take the summation of all the individual values. So this equation basically remains the same. The only difference is we will try to find the values for all the different data points and take and sum it up. So that's the difference. So it will be is equal to minus 1 by m. So this minus comes from here. So 1 by m, where m denotes the total number of data points, summation of m and I is equal to 1. So yi, which is represented by this. So y log y cap will become yi log y cap I plus 1 minus y will be 1 minus yi cap log of 1 minus yi cap. So these two equations are basically the same. They are actually similar. We just need to sum it up. So that's the difference, and we will do this for all the data points individually. So that's why we are represented I here. So I is nothing but the individual data points. So individual data points that we are taking from the start to the end of all the data points that we have in a data set. Okay, so this is how the cost function looks like in a logistic regression model. So this is very important for us. So you can take note of this cost function equation and loss function equation, because we are going to use these equations in our logistic regression model. So while we are building our logistic regression model from scratch in Python, we need to build the gradient descent for the logistic regression as well. And in order to build the gradient descent, you need this cost function equation. Okay, so the gradient descent works based on the cost function, because it tries to check the cost function value for different weight value and bias value until it finds the optimum weight value and bias value. So this is the importance of cost function, and I hope you are clear up to this point. And if you have any doubts, please mention in the comments. And this 7th module is all about building machine learning models from scratch. So the first model that we worked on was a linear regression model, and then we moved on to a logistic regression model. We know that logistic regression is one of the most important models that we have in machine learning. And in my previous videos, I have explained you what is the intuition and math behind a logistic regression model, and what is the loss function and cost function for a logistic regression model, which is very different from the linear regression, right? So in today's video, let's try to understand gradient descent, particularly for logistic regression. So there will be quite a change in gradient descent and the derivatives for logistic regression when you compare it to a linear regression. So in this video, let's try to understand that. So once we are clear with all these concepts, in the next video, we can move on to the hands-on part, where we will be building a logistic regression model from scratch in Python. Okay, so let's get started with today's video. So I'll just give you a quick summary of what we have discussed so far about logistic regression. So we know that logistic regression is a supervised learning model. So we know the difference between supervised and unsupervised learning model, where in the case of supervised learning model, we use labels and targets, whereas in the case of unsupervised learning, we don't use any labels. So you can think about this as classifying an image as either dog or a cat. So whenever you are using a supervised learning model, you need to give the images of dog and cat, and you need to tell the model that these images represent dog and these images represent cat. So these annotations represents the labels, and the data is your image. Okay, and your model will try to find the pattern between the image and the label. So this kind of models which uses both data and the labels are called as supervised learning models, whereas in the case of unsupervised learning, we don't give any labels, we just give the data alone. So that is the difference between supervised and unsupervised learning. And the logistic regression is a supervised learning model where you need to give that label, and it is a classification model. So classification models classify the data points into different classes, whereas a regression model tries to find some particular value. So you can think about regression problem as finding the salary of a person or predicting the temperature of a day and so on, where you are trying to predict some numerical value, whereas the classification models try to predict the classes. You can think about this as I've told you before, you can try to classify the image as either dog or cat. So here you are just classifying the images, or you can predict whether a news is fake or not, or you can predict whether a mail is a spam or not. So these are called as classification problems, and logistic regression is mainly used for classification problems. Okay, so hence it is a classification model. And then it is best suited for binary classification problems. So there are cases where we have multiple classes. So when you compare working of a logistic regression for that multiple classes and with binary class in the sense there are only two classes as a yes or no question, or you are predicting whether a person has diabetes or not. So there is only two classes. So these are called as binary classification problem, and the logistic regression works best for binary classification problem. So we can also use logistic regression for multi-class classification also, but it is more efficient in binary classification. So for multiple classification we need to implement, or we need to add some changes to the model. So that is the difference, but you can remember that it is best for binary classification problem, and it uses a sigmoid function. So in the previous videos I have explained you what is meant by the sigmoid function and how this comes and so on. So we know that sigmoid function is given by this particular equation. So y cap is equal to 1 divided by 1 plus e power minus z, and your y cap value lies between 0 and 1. So y cap is nothing but the probability. What is the probability that your y value is equal to 1? So if you are not sure about what all these things means, you have to watch the previous videos, and I'll give the link of the previous videos in this video description. So please watch those videos before coming to this one. Okay, so this is our sigmoid equation where we will try to find the y cap, which is the probability of y being 1. So it is given by 1 by 1 plus e power minus z, where z is equal to wx plus b, where x is our input feature. So whenever we are training a machine learning model, we will give input features as well as the target column. So x represent our input feature. Say for example, if you are trying to predict a person has diabetes or not, you need to give the input features such as the weight of the person, the BMI of the person, their blood sugar level, age, so on. So these will be our input features, and our output value will be predicting whether a person has diabetes or not. So that will be our target column, and the other remaining columns are called as features, or the input feature, which is represented by x. So w and b represents weights and bias, which we have already discussed before. So this is our sigmoid function, and here so this y cap depends on the value of z, and this z is nothing but wx plus b. So this is our sigmoid function, and logistic regression works on the sigmoid function, and hence you get this sigmoid curve or a s-shaped curve. Okay, and the final point is it uses a binary cross entropy loss function or a log loss, whereas linear regression use a least square error kind of a loss function, whereas logistic regression uses a binary cross entropy loss function or log loss. And in the previous video I've shown you what is this log loss function looks like, and we have also determined our cost function, which looks something like this. So j of w comma b represents our cost function. So your cost function changes when you change the weight and bias, which are the parameters of the model. So your cost function, we can write them as a function of weight and bias. So j of w comma b is equal to 1 by m, where m is your total number of training examples. So loss function. So loss function is something which we try to find for only one data point. Say you are trying to find the difference between the true value, which is y, and the predicted value y cap given by your model. If you do that if you try to find the difference between the true value and predicted value for only one data point, then it is called as loss function. And if you take the average of all the loss function for all the data points in your data set, and then it is called as your cost function. Okay, so this is formula for determining the cost function, and this is nothing but our log loss. So your cost function would look something like minus 1 by m summation of yi log y cap plus 1 minus y log 1 minus y cap. So in my previous video I explained you in detail about how this cost function works and how we can find the cost function value for different value of y. So far we have discussed all these things. Now we need to come to gradient descent. So what is the purpose of using gradient descent? So once we feed our data to our model, it tries to learn from the data. So what this learning means is it will try to find the weight value and bias value. So this weight and bias is called as the parameters of our model. Okay, so these are the model parameters, and we need to find the optimum weight value and bias value, and for this the model uses gradient descent. So gradient descent, so we randomly initialize some weight value and bias value, and our model reiterates over the data. It tries to go through the data again and again until it finds the best value for weight and bias. And now we need to know what is the best value, what is the best value for weight and bias, and that is where cost function comes into play. If your cost function is very high, cost function, it will be a numerical value. If your cost function value is very high, that means there is a huge difference between your true value and your predicted value given by your model. Then that means your model is not working fine, it is not accurate. But if your cost function value is less, then that means your true value and your predicted value are close to each other, then your model is working fine. So what our logistic regression model will do is it will randomly assign a weight and bias value, and it will try to find the cost function respective for that weight and bias value. If the cost function value is high, then it will change the parameters, that is weight and bias, by a certain amount, and again it will try to find the cost function value. So this process will be repeated again and again till it reaches a minimum cost function value. And this algorithm or this method is called as gradient descent. And now let's see how this particular gradient descent works. So if you plot the weight, if you take a weight in the x-axis, you can take a cost function in the y-axis. So this is, the gradient descent is the same for all the models, only some terms changes within the gradient descent. So I'll explain you what is meant by that, but this is very similar to our gradient descent works on a linear regression model. Okay, so if you understand that, you can understand this easily as well. So let's take weight in the x-axis and the cost function value in the y-axis, and we know that this cost function value should be minimum. And if you plot your cost function for different weight value, you will get a U-shaped curve like this. You can also call this as a convex curve. And so let's say that we take a random weight value. So in this, throughout this x value, we have different weight values, and we are taking different weight values. Now we will randomly take some initial value for weight. Let's say that this weight value can be anything. So it can be 5, 10, or sometimes we initiate the weight with 0. So in most of the cases, we initiate weight and bias with 0. So let's say that we are randomly initializing the value of weight. So we are giving some value for weight, and for this particular weight of our model, our cost function is very high. So if you come here, we have this weight value and bias value. So consider that we are giving some random initial value for weight value and bias value. Now the model will find the value of z using this particular equation, and then it will plug in the value of z in this equation to find the y cap value. And from this y cap value and the true y value, it can substitute it in this cost function, and it can find the cost function value. Now let's say that for this random initial value, our cost function value is very high because this point is at the upper part of the y-axis. Now what we need to do is we need to find for which weight value your cost function value will be minimum, and that is this particular point. So you can call this as the global minimum. Okay, so we need to reach to this point from this point, where if you take the weight value in this particular point, so if you just take a point from here and you come to the x-axis, you have some weight value here in the x-axis. If you take this weight value and bias value, you will have the minimum cost function, because this point is closer to the lower part of the y-axis, which is a lower value for cost function. So we need to reach from this point to this point, which is called as the global minimum. So global minimum is the point at which, if you take those parameters at the global minimum, the parameters in the sense weight and bias value in the global minimum, you will have minimum cost function. So we need to reach to this point from there. So that is what a gradient descent algorithm does. It will try to change your weight value and bias value. So it will try to effectively change your parameter value until it reaches the global minimum. Okay, so this is what we are doing in a gradient descent algorithm, and we do this for both weight and bias as well. So in this case, it's a 2D curve. So I have mentioned only weight and cost function alone. If you take both weight and bias, your gradient descent curve will look something like this. So it will be a 3-dimensional curve like this, where we take weight and bias in one axis. Okay, so weight in one axis, bias in another axis, and your third axis will be your cost function with respect to weight and bias, and this will be your global minimum point, where at this point, if you take this parameters of weight and bias, you will have the minimum cost function. So this is how gradient descent works. And now we need to understand what is the equation, what is the formula that's behind this gradient descent. So gradient descent is mainly based on differential calculus, and This is how it finds that global minimum. So if you want a definition of gradient descent, it is given here. So gradient descent is an optimization algorithm used for minimizing the cost function in various machine learning algorithms. It is used for updating the parameters of the learning model. So we know that it is an optimization algorithm. What we are optimizing here is nothing but the parameters of the model. So we need an optimized weight value and bias value so that we get a very less cost function, which will give us an accurate model. And the purpose of this gradient descent is that we know that its purpose is to minimize the cost function value, and it is used in several machine learning models. So it is used for updating the parameters of the learning model. So if you come to this particular curve, so this is the first weight value you have taken, and we need to change this weight value in consecutive steps, right? And this is called as updating weights. So we have this initial weight, and then we are changing our weight value some by amount. Okay, and this is called as updating weight. So we keep on updating our weights till we reach the most optimized weight and bias value, and that's what is given in this definition. This second statement, which represents, it is used for updating the parameters of the learning model. So in this case, the parameters are weight and bias. So this is how the formula looks like. So W2 is equal to W1 minus L into DW, and B2 is equal to B1 minus L into DB, where your W represents the weight of the model, B represents the bias of the model, L represents the learning rate. So learning rate is nothing but what is the amount of change that you want to give to your weight and bias. So it's like, so we are we are starting at some random initial weight value, and now we are changing our weight value to some other weight value, right? So this is the second weight value that we are taking. So we need to mention what is the amount of change that you need to give to your parameters, how much change you need to give to your weight. So that is represented by the learning rate. So that is represented by L. Okay, and the dw and db, so these are partial derivatives. So dw is the partial derivative of cost function with respect to w or the weight, or db is the partial derivative of cost function with respect to b. So we are just taking the derivative of cost function with respect to weight, and then we are taking the derivative of cost function with respect to b. So the idea behind this is we need to check how much your cost function changes when you change your weight and bias value. So if you come to this curve, we know that we are changing the weight value by some amount. So when you change your weight value by an amount, what is the amount of change that is happening to your cost function? So how much your cost function value decreases. So that is nothing but our partial derivative of cost function with respect to weight. And if you find how much your cost function changes with respect to bias, then it is called as db, which is the partial derivative of cost function with respect to db. And when we implement this, we can get this kind of a gradient descent model, where we can keep on updating our weights till we reach a minimum point. So no matter where we start our parameters, like in this case, we have started from this initial value, and we kept on changing the weight value till we reach a global minimum. So if you take a different weight here, so let's say that we are taking a weight value which lies here, and if we implement gradient descent, and then it will again try to reach this global minimum. Okay, so it will keep on doing this until it reaches this global minimum. Okay, so think about what this weight means and this weight means. So we have the weight in the x-axis, and this weight means we are taking an increased value of weight. So let's say that this is the global minimum. Let's say that this weight value is 5. Okay, so let's say that initially we are taking the weight value as 0. Now the weight value should increase, right? So the gradient descent will keep on increasing the weight value till it reaches the global minimum. And let's say that if we have mistakenly taken the weight value as 10, which is a larger number compared to the optimum number, in that case it will again try to reduce the weight value till it reaches the global minimum. So no matter at what point of the curve you start, it will try to reach this global minimum. So that is the important aspect of a gradient descent model, and that is given by this equation. So when you implement this, we can get that kind of a result. So your W2 will be your new updated weight, the second weight that we are updating, and this process will be continued again and again based on the number of iterations we give. So we can give 100 iterations, 1000 iterations, so on, and your model will repeat the iteration until you reach a minimum cost function. So W1 will be your initial weight, W2 will be your updated weight, and your updated weight is equal to initial weight minus learning rate into dw, and your bias updated bias value is equal to initial bias value minus learning rate into your db, which is the partial derivative of cost function with respect to b. Now we need to know what is this dw and db. In order to find this, you need to differentiate your cost function with weight. So if you do that, you will get this dw value, and if you differentiate your cost function with respect to bias value, you will get this db value. So your dw and db will look like this. So dw is equal to 1 by m into y cap minus y dot x, and db is equal to 1 by m into y cap minus y. So this is your dw value and db value. So if you remember, our cost function equation is this. Okay, so this is our cost function equation. So we need to differentiate this so this equation by dw once and then by db. So when you do that, you will get the dw and db value, and we use something called as chain rule of differentiation here, and I'm not going detail into how we derived this particular equation. So it is a long procedure, and it is out of scope of this particular video. So if you want, I'll just make a separate standalone video for how to determine the derivatives dw and db, but we cannot do that in this particular video. Okay, but you need to, this is like very important, so you need to remember this dw and db equations. So because we will use these two equations in our code. So if you want, I'll just derive and show you in a later part of the course how we will get a dw and db. But for now, remember that your dw is equal to 1 by m into y cap minus y into x, where x is your input feature, where y is the true value, y cap is the predicted value, and your db, the partial derivative of cost function with respect to bias, db is equal to 1 by m into y cap minus y, where m represents the total number of data points in your data set. So if you have 100 data points in your data set, your m value will be 100, and it if you have 1000 data points, it will be 1000, and so on. Okay, so this is the equation for dw and db. So this is very important. So w2 and b2, so these two equations and these two equations are very important for us, because we will write these equations in Python while we are building our logistic regression model. Okay, so I hope every one of you are clear up to this point. So we use gradient descent in order to find the optimum weight value and bias value, and this is how we can use gradient descent to do that. So now I'm going to show you what are the equations that we need for building our logistic regression model, and we will do this in the next video. Okay, so the things that you need are, first is the sigmoid function. So we know the sigmoid function, which is y cap is equal to 1 divided by 1 plus e power minus z, and z is equal to wx plus b. So we know this. This is the first thing that we need for building our logistic regression model. And the second thing that we need is the equation which we use in order to update the weights through gradient descent. So this is the equation which we have discussed. So w2 is equal to w1 minus l into dw, where l is our learning rate, and b2 is equal to b1 minus l into db. So we mentioned the learning rate while creating the model, so we can manually change this learning rate value, so it's not an issue. So learning rate is nothing but how much change do you want to impart to your weight and bias. So that's our learning rate. So this is the second important thing we need, which is the equation for updating the weights through gradient descent. And the third equation that we need is the derivatives. So the derivatives are nothing but dw and db. So we know the equations for dw and db, where dw is equal to 1 by m into y cap minus y into x, and db is equal to 1 by m into y cap minus y. So these are our dw and db, and we will be using all these equations. So totally we have 6 equations, right? So we will be using all these 6 equations while building our logistic regression model from scratch. So before going to that, you need to be clear about all these equations. Okay, so this is all the things that we need in a theory perspective before going on to logistic regression, practical part where we will build it in Python. So I hope every one of you is clear up to this point in the 7th module of our hands-on machine learning course. And this 7th module is all about building machine learning models from scratch. So previously we have worked on a linear regression model, and we have seen how we can build a linear regression model from scratch in Python. And currently we are working on a logistic regression model, and in my previous videos I have explained you what is the intuition and math behind a logistic regression model, and how you can find the gradient descent of a logistic regression model, and so on. Now let's incorporate all those concepts related to logistic regression, and we will try to build a logistic regression model from scratch in Python. So we have discussed all about the logistic regression equation, so the sigmoid function, the gradient descent for logistic regression, and its derivatives in the previous videos. So if you are not sure about these things, and if you are not sure what these topics means, so please refer the previous videos, and I'll give the link of those videos in this video description, so you can watch those videos before watching this one. Okay, so this is our sigmoid equation, and we know that y cap is equal to 1 divided by 1 plus e power minus z, and this z is equal to wx plus b. So this y cap, or you can call this as y at. So y at is the predicted value, the value predicted by our model. So it is nothing but what is the probability that your y value is equal to 1. So we know that we use logistic regression predominantly for binary classification. So binary classification in the sense we will try to classify the data points into two classes, either 0 or 1. So you can think about the 0 or 1 as a person having diabetes or not, or you can think about this as whether a news is real or fake. So you just have two classes, and we want to classify the data points into two classes. And your let's say that our y can take only two values, either it can take the value as 1 or it can take the value as 0. So y cap is what is the probability that your y value is equal to 1. So if your y cap value is equal to 0.8, then that means there is a 80% chance that your y value will be 1. So y cap is a probability, and we know that all the probability values lies between 0 and 1. So your y cap value or your y hat value will lie between the range 0 and 1, whereas your y can take only the values 0 and 1, but y cap values lies between 0 and 1. So that is the difference between them. And we know that this z, so z is equal to wx plus b, where w is your weight and b is your bias, and x will be our input feature. So what is meant by this input features? So we have already worked on the diabetes prediction in our channel. So I have already made a project video where we try to predict whether a person has diabetes or not, and we have used this data set. So we have multiple columns here, and this final column, this output column, is the target column. So here 1 represents a person having diabetes and 0 represents a person does not have diabetes. So this column is called as the target column, and the remaining columns are called as, so as you can see there are totally 9 columns, and if you just ignore this outcome column, so totally you have 8 columns here. So these 8 columns from A to H, so these columns are called as the features, or you can call them as input feature. And the final column, 8th column, is your ninth column will be your or target column. Okay, so totally we have 8 input features here. So these are nothing but your x. Okay, so which I have represented here. So x represents your input feature. This x can be one set of values, so it can be one column values, or it can be multiple column values. So you can think about x as a matrix. Okay, a matrix with multiple rows and columns. If you come here, you will have let's see how many rows we have. So this particular data set contains about yeah, it contains 769 rows. Okay, so it contains 769 rows and 9 columns, and out of that the ninth column is the target column, and the remaining 8 column are the feature columns. So that is represented by x. And the important thing about weight bias is that the number of weight value you have is equal to the number of input features you have. So if you come to this data set, so totally we know that totally we had 8 input features. So you will have 8 different weight values. So you will get one weight value for each column, for each input feature. So if you have 8 feature, you will have 8 weight value. And if you have let's say that we have 20 input features, so in that case you will have 20 different weight values, each for each input feature. Okay, so that is one main thing that you need to note. So this z is equal to wx plus b. So I have already made videos on weight and bias. If you are not sure about this, I'll also link that video as well in this video description. You can watch that as well. So this is our logistic regression equation, or our sigmoid function. And now we need this gradient descent. So the purpose of this gradient descent is to find the best weight value and bias value. So whenever we are using a logistic regression model to fit to a data set, it cannot find the proper weight value and the bias value at one step. So it is a multiple step process. So this weight value and bias value changes depending upon the data set that we have. So our model has to find what will be the best weight value and bias value, so that your model can make accurate predictions. For this purpose, we use a gradient descent model, or a gradient descent algorithm. So gradient descent is an optimization algorithm used for minimizing the loss function, or you can also say cost function, in various machine learning algorithms. So it is used for updating the parameters of the model. So we know that a loss function or cost function is something which is the difference between the true value and the predicted value. So your loss function or the cost function value should be very minimum. So your gradient descent algorithm will try to minimize your cost function value by changing the weight value and bias value. So this will be a multiple step procedure. So it will take some random initial value for weight and bias, and it will try to find your loss function. If your loss function is more, it will try to change the weight value and bias value. Again, it will try to find the loss function and the cost function. So this process will be continued till your cost function value is minimum. So this is called as gradient descent, and the formula for updating weight is this. So w, the updated weight, is equal to, updated weight, so the w in the left hand side is the updated weight, and the right hand side, this w represents the initial weight. So updated weight is equal to previous weight minus alpha into dw. So this alpha is our learning rate. Okay, so similarly we have the formula for bias. So for updating the bias, we have b is equal to b minus alpha into db. So this alpha is called as the learning rate. So as I've told you, the gradient descent will try to change the weight value and the bias value, right, in order to reduce the loss function or the cost function. So learning rate represents how much change do you want to impart to this weight and bias. So that is called as the learning rate. So learning rate is a tuning parameter in an optimization algorithm that determines the step size. Step size in the sense how much change you want to give to your parameters at each iteration while moving toward a minimum of a loss function. So the ultimate goal is to minimize our loss function. So as I've told you, loss function is how much your true value and your predicted value differs. So the difference should be very less. If your true value and the predicted value, the difference between them is very high, that means your model is not making accurate prediction. So we want a minimum loss function. In order to do that, we will use this gradient descent, and this learning rate is the amount of difference you want to give, the amount of change you want to give to your weight and bias. So that is meant by this learning rate. And finally, we have the formula for dw and eb. So dw is nothing but the partial derivative of the cost function with respect to weight, and db represents the partial derivative of cost function with respect to bias. So you can get this formula for dw by differentiating cost function with respect to weight, and you can get the second equation by differentiating the cost function with respect to bias. So these are the things that we have discussed in our previous videos, and now we need these 6 equations: this y cap, z, and this w and b and dw db. So these are the 6 equations that we need, and we are going to write these 6 equations in Python in order to build this logistic regression model. So this is very simple. So we just need to figure out how we can do this. So that's all. Okay, so let's get started with coding part. So I'll just make a text here as importing the dependencies. So importing the dependencies. So we will be using only the NumPy library here for creating this logistic regression. So I'll just make a text here as importing NumPy library. Okay. So the purpose of this NumPy library is to create arrays. So these arrays are called as NumPy arrays. So import NumPy as NP. So we can import this NumPy in short form as NP. So this is the general convention that we use, and most of you would know this. So okay, so I'll run this. So in order to run this cell, you can just press Shift plus Enter. Okay. I'll create a text here as logistic regression. So in this part, we are going to write the code for building logistic regression. So what we are going to basically do here is create a class, and we can name this class as logistic underscore regression. So you can name this anything you want related to regression, but it should be a single word. Okay, so we should mention parenthesis here. So you can just join this logistic and regression by underscore, or you can just simply remove this, but it should be a single word, and you cannot just have a space like this. Then it will show an error for us. So you can join this with an underscore. So we are creating a class as logistic regression, and within this class we need to mention some functions. So I'll just complete these functions and explain you what this means. So we need 4 functions here. So the first function is the init function, and the second function we are going to write is a fit function. So at the end of each function, you should mention the parenthesis, and within this we will give the parameters for each of these functions. So the third function that we are going to write is update weight function, update weights. And finally, the last function that we need is predict function. So define predict. So let's try to understand what is the purpose of these 4 functions. So first we have the init function. So no matter what class you are creating, so it can be any object. So in all the cases, we will be using this init function. So this is common for all the classes. So this is basically initiating the parameters for the class that we are creating. So in this case, we are creating a logistic regression function. So similarly in Python, we will create different objects using this class in different cases. And in all those cases, we should mention this init parameter or init function. So this is nothing but the parameters that we want to give to our object. So this will be our first function, and the second function that we have for logistic regression is the fit function. So the purpose of this function is to fit the data set that we have to our logistic regression model. So if you look at our diabetes data set, so we have totally 9 columns, and out of these 9 columns, the first 9 columns are the first 8 columns from A to H. So these are the input features. So based on these features, our model will try to predict the outcome. So outcome value will be 1 or 0, where 1 represents a person with diabetes and 0 represents a person without diabetes. Okay, so these first 8 columns will be our input column and I will be our output column. So we will basically try to fit our data set to this X. So all these 8 columns represent X, and this I column, the ninth column, represents the Y column. Okay, so we need to fit this X and Y to our logistic regression model, and for that we need this fit function. So we will be mentioning this X and Y within this parenthesis, which are the parameters of this fit function. And then we have the update weight. So we know that we use gradient descent in order to update the weights and bias, because we will randomly initiate some weight and bias value, but these weight and bias value won't be the optimum value, so our model won't work fine. So we include a gradient descent algorithm which tries to update the weight and bias by minimizing the cost function. So for this we need this gradient descent model, and for that we use this update weight. So this update weight will keep on changing the weight and bias value so that we get a good model. Okay, so that is the purpose of this third function. And finally we have this predict function. Let's say that we have trained our logistic regression model with this diabetes data. So once the model is trained, if you give all the X values, let's say that we are taking all these 8 X values, and once you give all these values, your model will predict the Y value, which is either 0 or 1. So it will tell you whether the person is diabetic or not. Okay, and that is the purpose of this predict function. So given the value of X, your model will find the value of Y. Okay, so these are the 4 functions that we are going to write within this logistic regression class. Okay, so first we have the init model, which is used to initiate the parameters for logistic regression. Then we have the fit function, which is used to fit the data set to our model, and then update weights, which is used to update the weight and bias value, and finally predict a function which will give us the Y value, whether it is a 0 or 1, based on the X value we are giving. Okay, so these are the 4 functions we need, and let's work on these 4 functions. Okay, so I'll just give you a quick thing about this. So these are the steps involved in a logistic regression model. So the workflow happens in this way. So first thing that we need to do is set the learning rate and number of iterations. So we know that learning rate and number of iterations are called as the hyperparameters, because these are the parameters which are outside the model. Okay, and then we have once we have set the learning rate and number of iterations, then we will initiate the values for weight and bias. So if you see this code here, so we have this init function, right? So within this init function we will include the learning rate and number of iterations. Okay, and after that we will initiate the weight value and bias value for our model. Then we will build a logistic regression function. So we know that logistic regression function is nothing but a sigmoid function, which I have written here, which is y cap is equal to 1 divided by 1 plus e power minus z, and this z value is wx plus b. So then we will write that particular the logistic regression equation, and after that we need to write the gradient descent algorithm, where we will try to update the parameters of the model. So once this process has been carried out, so we will give the number of iterations. So let's say that the number of iterations that we are giving is 100. So that means our model will go through the data 100 times again and again, and each time it will update the parameters using gradient descent. So once the number of iterations is complete, we will get a proper model which has a best weight value and bias value. So you can change the number of iterations depending on your accuracy score of the model. So we can change this value. So we can change the learning rate and number of iterations value. So once we do that, we will get an optimum model which has best weight value and bias value. So best weight value and bias value in the sense, the model will make good predictions, and it will have a minimum cost function. Cost function means the value predicted by your model and the true value are very close to each other, which means your model is working accurately. Okay, so and finally we can build this predict function. As I've told you, when you give the X value, it will give the output as Y value, which is either 0 or 1. So these are the steps that we are going to follow. Okay, so the first step is setting up the learning rate and number of iterations, and then initiating the weight and bias value. Okay, so now let's try to understand what is the importance of class and why we need to create a logistic regression as an object. So we know that Python is an object-oriented programming language, and everything is an object in Python, and we will try to program other things around this object. So again, we are trying to create logistic regression as an object, and in order to create an object, you need a template for that object, and this template is created using this class keyword. Okay, so template in the sense, every object has its own characteristics, properties, and functions related to it. So the characteristics and properties of logistic regressions are nothing but this sigmoid equation, the gradient descent, derivatives, etc. So we need to include all these properties and functions within this logistic regression object. So that's what we are going to do. So the purpose of doing this is, so you can also write this logistic regression model without using class and functions, but the reason we are doing this is, we don't want to write the logistic regression every time we are using it. Say for example, we are having 10 different data set and we want to use logistic regression for all these 10 projects. So we cannot write this logistic regression code every time we want to implement it. So what we will do is we will create the logistic regression class, and whenever we want we can use this logistic regression. So it will be like a ready-made code for us. So I'll give you a simple example for this object and class, because this object and class is a very important concept in Python. Let's say that we are creating a car. So the car that we are creating is called as an object. In order to create that car, you need a blueprint for that particular car, or you need a prototype for that car. So in that you may mention that a car should have an engine, and should the engine should perform in such way, and a lot of things. So the car should have four wheels, brakes, and so on, right? So that template which we are creating for our car can be considered as the class, and the car itself which we are creating is called as an object. So here the object that we are creating is in logistic regression, and the template for it is created by using this class. So that is the importance of class and objects in Python. Okay, so let's work on this. So I'll just give some space here. So the other thing which you need to keep in mind is, so we have four different functions. So def represents define, and this is used to implement, in order to write some function in it, and we need to mention some parameters inside this parenthesis. Okay, so when you are creating a class, or when you are creating an object using this class, the first parameter that you need to give within this parenthesis is self. Okay, so I'll create this self, and so it should be given in all the four functions. I'll explain you what is meant by this self. Okay, now let's say that we have completed our logistic regression model. Okay, so let's say that we have completed our code, and now we want to implement this logistic regression to fit to a data set. So what we will do after completing it is, so we will try to load an instance of this logistic regression. So how we will do that is, we can create some variable. Okay, so I'll say that I'm creating a variable called as model. So I'm naming this variable as model, and within this model I'm going to load this logistic regression code. So I'll mention this particular name, which is logistic underscore regression. So I'll write here as logistic underscore regression and parenthesis. Okay, so here I'm creating, or I'm loading an instance of logistic regression, and the instance I'm loading is model. Okay, so this is the instance of logistic regression I am creating. And after that, what I will do is, so I will just simply use model dot fit. So here model dot fit represents logistic regression dot fit. So it will come to this logistic regression class, and it will search for the function fit. So if you go through this, you can see that we have the function fit. So this is how the model will work. So we will fit our dataset to this logistic regression model. Now, as you can see here, this model takes the value logistic regression because it is an instance of this logistic regression. The reference of this particular instance is called as this self. So this self and model are, actually they are the same thing. So this self is nothing but the reference of this instance. So we use self because we use it within the class. So whenever you are using, or you are mentioning the instance of the code or instance of the class within the class itself, we call it as self. So this is nothing but the reference of the instance. So you can remember like that. So I'll just remove this. We don't need this. We just need this for the implementation purpose. I just wanted to explain you the purpose of self. Okay, so the self is nothing but the reference of the instance that we are creating. Now we need to mention the parameters within these functions. So as I've told you earlier, the purpose of this init function is to create, or in order to initiate the hyperparameters learning rate and number of iterations. So we will initiate weight and bias separately, but we will initiate the learning rate and number of iterations first, and we will do that in this init function. So init stands for initiation. So I'll just make a text here as initiating, instead of initiating, I'll write declaring. Okay, so declaring learning rate and number of iterations. Okay, number of iterations. So these two parameters are called as the hyperparameters. So hyperparameters, whereas the weight and bias are called as the model parameters. So I have already made a video on weight and bias and this learning rate and number of iterations. You can watch that one as well. Okay, so we are declaring the learning rate and number of iterations, and as you know, the learning rate is the amount of change that we want to give to our weight and bias. So when we are implementing gradient descent, as I've told you, we will keep on changing the values of weight and bias till we reach an optimum value for these two parameters. So learning rate is the amount of change that we want to give to our weight and bias. So which I have given the definition for it here. Okay, so that will be our learning rate, and number of iterations is like the number of times you want your model to go through the data. So these are the two hyperparameters, and let's initiate or declare these parameters. So first is learning rate. So self dot learning rate is equal to learning rate, and self dot number of iterations is equal to number of iterations. So we need to mention these parameters in this parenthesis as well. So learning rate and number of iterations. So you should do this first before doing these two lines. So number of iterations. Okay. So what we are doing here is we are declaring the two parameters which are learning rate and number of iterations. So when we are loading an instance of logistic regression, say we have completed this code and I am creating an instance for logistic regression as model, and I am loading the logistic regression model. So logistic regression, and within this parenthesis, I need to give the value for this learning rate and number of iterations. So what I will do is I will mention the learning rate as something like, let's say it's 0.01. So you can give any values, and let's say that the number of iterations is, let's say it's 1000. Okay, so totally we have 1000 number of iterations. So this is how we will declare the value of learning rate and number of iterations. So you can manually change these two values, learning rate and number of iterations. And so these two are the parameters of this class logistic regression. And whenever you call this logistic regression, along with this, you need to mention the values for the learning rate and number of iterations. So if you just call the logistic regression function, sorry, the logistic regression class without mentioning the learning rate and number of iterations value, your code won't work properly. So you will get an error. So you should mention the parameters which are represented in this init function. So these are so what we are basically doing is initiating the two parameters which are learning rate and number of iterations, and these two are the important parameters for the logistic regression class. Okay, so this is our first step. As you can see here, the first step is setting up the learning rate and the number of iterations, and then we need to give the random weight value and bias value. So let's get into this later, but for now understand that we have set the learning rate and number of iterations. Okay, so we have declared these two parameters. So this will be our first step. So the purpose of this define init function. Okay, so now what we are going to do is the second function that we have is the fit function. And as I've told you earlier, the purpose of this fit function is to fit the data set to the model that we have. The model in this case is of course the logistic regression. So I'll just make a text here as fit function to train the model with some data set. Okay, so in order to fit a function to a model, you need two things. One is the x-axis value and the y-axis value, right? So you cannot fit a model without these two values. So these two values should be there. So the x-axis value is nothing but all these 8 columns, and the y-axis value is the last I column. Okay, so you can call these 8 values as x and the last column as y. Okay, so this is basically is nothing but a matrix. So x is nothing but a matrix, right? So what I'm going to do is we need two parameters here. One is x and the another one is y. So I'm just taking this data set as an example data set. So once we complete this code, you can use any data set that you have. So I'm just taking this as an example. Okay, so a to h will be x, and last column y, the ninth column will be y. So whenever you are calling this fit function, so whenever you are calling this model.fit function, you have to give two parameters along with it. So one is x and the another one is y, where x will be your input feature and your y is the output feature, which outputs either 1 or 0. So this is the purpose of fit function. Now what we need to do is, so there are a few things that we need to do within this fit function, and the first thing that we need to do here is determine the number of data points in your data set and determine the number of input features in your data set. Okay, so let's try to understand these two terms. So I'll just remove this. So we don't need this outcome right now, so let's remove this for now. Let's ignore it. So now we have the 8 columns here. So all these 8 columns are called as input features. So as you can see here, we have the number of pregnancies for a woman, what is their blood glucose level, blood pressure, skin thickness, insulin, BMI, diabetes, age, etc. So based on this, our model will try to find whether the person has diabetes or not. So these 8 columns are called as input features. So we can say that totally we have 8 different input features. Okay, and we need to find how many data points are there. So data points in the sense, so each row represents data for individual. So the second line represents the data for one individual, third line represents the data for another individual, and so on. So if you just go through this data, totally we have about 769 data points. Okay, so as you can see here, so totally there are about 769 data points, and or you can also consider it as the number of rows. So the total number of data points is equal to the total number of rows, and the total number of input features that you have, which is the columns, is equal to 8. So totally we have the data for 769 different people, and the total number of input features is 8. So we can write the shape of this matrix as, so you can consider this as a matrix. So we can write this as, just show you, this is an example of a matrix with 769 rows and 8 columns, right? So ignore the output column, which is the outcome column. So this is the shape of the matrix that we have. Now this first value represents the total number of data points, or you can consider it as the number of rows. So this will be your m value. And this 8, the second value, the number of columns, represent the total number of input features that you have, and this will be n. So m represents the total number of data points. In other words, you can say it is the total number of rows, and 8 represents the total number of input features that you have. In other words, it represents the total number of columns that you have. So it is as simple as that. So this is our x. So x is nothing but the input data. So this is our input data, and our output data will be outcome, which we have ignored for now. Okay, so we need to determine these two values, and for that what we are going to do is, I'm going to mention self.m comma self.n. So m and n are the parameters of this model, of this logistic regression, and as I told you before, we are representing these parameters within this class, and whenever you are doing that, you need to mention self. So whenever you are using this outside the logistic regression, so what you will do is, you will represent it as model.m. So if you print the model.m, you will get the value of this m. Okay, whereas whenever you are doing this particular code within the class, you need to represent it by self, as we know that model is nothing but it is an instance, and self is the reference of this instance. Okay, so when you are mentioning it within the code, you need to mention it as self.m and self.n. So we know that m and n are nothing but the shape of x, where the shape of x is 769 into 8, right? So it is nothing but self.m and self.n is equal to x dot shape, where your x is all these data. Okay, so excluding the output data, the outcome column, so all the things are x. So when you use this x dot shape, it will return an array with the value 769 into 8 when you are using this particular data set. So different data set will contain different number of data points and different number of total number of features. So we can say that there can be another data set which may have let's say that a data set that have 1000 data points or 1000 rows, and it may also have, let's say, 20 columns or 20 input features. In this case, this 1000 will be your m value. Okay, so I know that this handwriting is horrible, but just tolerate me, I'm not good at this. So this 20 will be your n. So m is the total number of data points or the total number of rows, and n will be your total number of input features. So the reason I'm explaining you this is, this value is not constant in all the cases, and this value differs based on the data set that we have. So different data set have different m value and n value, and so we are mentioning it generally as self.m and self.n is equal to x dot shape. So when you run this code, you will get the values of m and n. Okay, so that is the purpose of doing that. So I'll mention a text here as number of data points in the data set. So this is actually equal to number of rows, right? So number of rows, and so this will be our m value, and then number of input features in the data set. So this will be the number of columns. So in the example data, diabetes data I have shown you, there are totally 8 different columns, right? So this will be the number of columns, and this value will be our n value. So I'll write this as n. So when you run this code, self.m comma self.n is equal to x.shape. So your m will take this value. So your m will take the first value, which is the total number of data points, and your n will take the second value, which is x.shape, and that second value is the total number of columns that we have. So this is the first step that we are doing in this fit function. Now you may think that what is the purpose of finding m and n? So you may ask that question. Okay, so the reason that for the reason for finding this is, if you come to this formula, as you can see here, this is the derivative formula which we need for gradient descent. So dw is equal to 1 by m into y cap minus y into x. Here this m represents the total number of data points. So in order to find this m, you need to run this particular line of code. So if you don't create this line, you won't find the value of m. So this is the reason we are finding the value of m. And the importance of the value of n is that, so we have weight and bias value here. The number of weight value that you have for a model is equal to the total number of input features that you have for a model. Okay, so let's say that we have this data set, and we know that this data set contains 8 input features. So ignore the output column. So apart from the output column, we have 8 input features. So if you have 8 different input feature or 8 different columns, you will have 8 different weight values. Okay, so if in a data set you have 100 different input features, so let's say that you have 100 different columns, in that case you will have 100 different weight values. So each column will have a different weight value. Okay, so that is the purpose of finding the value of n, because so we need to find how many weight values can be present in that particular model. So that is the reason for finding this n value, because n value represents the total number of weight values that we are going to have. And when you are initiating the weight value and bias value, as I told you, we need to initiate the weight value and the bias value. So in order to initiate this weight value, you need to know how many weight values do we have. Okay, so that is the reason for finding the value of n. Okay, so I hope everyone is clear up to this part. And the next thing which we are going to do is initiate weight value and bias value. So initiating weight and bias value. So we will do that by self.w is equal to w, sorry, so self.w is equal to np.zeros. So I'll just complete this and explain you what this means. So self.n and self.b self.b is equal to 0, and self.x is equal to x, and finally self.y is equal to y. Okay, so let's try to understand this. So as I've told you, the next step will be initiating random weight and bias value. So we need to initiate some value for our weight and bias, and we generally initiate the value with 0. Okay, so as you can see here, I have for weight, I have represented a numpy array. So np stands for numpy, as we have imported the numpy library. So np.0 will create a numpy array with all the values as 0. Okay, and in the parenthesis I have mentioned self.n. So self.n is nothing but, so let's say that in this data set the value of n is 8, right? Because we totally have 8 different columns. So this will basically take the value as np.zeros, in the bracket, in the parenthesis it will take the value 8. So this np.zeros with parenthesis 8 will create a numpy array with 8 values of 0. So I'll show you this. So I'll just remove this particular code. So let's create an array as weight. So weight is equal to, let's say that np dot zeros, and within this parenthesis I'm giving 8. So let's print this weight. So np is not defined, so I think I haven't run this particular code. Okay, okay, so we can run this now, and I'll print this weight. Print weight. So this will create a numpy array. So this is an example of a numpy array, and this array will contain 8 values, and all the 8 values will be 0. Okay, so we have given 8 because this dataset contains 8 different input features. So in the other example which I have shown you, this particular dataset contains 20 different input features. So the n value will be 20. So if you give the value as 20 here, you will get a numpy array with 20 values as 0. Okay, so this is what we are basically doing here. So we are initiating the weight value. Here weight will be a numpy array. It won't be a single value because we will be having multiple weight values which is equal to the value of n. So we are creating numpy arrays with the shape n. Okay, so that is the reason for doing it. Whereas the bias is a single value. So weight is a numpy array. Weight can be considered as an array because it contains multiple values. So you can just consider it as a list. So you can consider weight as a list which contain n number of values, but bias is a single number value. So it is a single real number. So we are just giving the value as 0, whereas as you know, weight is an array or a list. So we are creating a numpy array with all the values as 0. So this self.x represents our input data set x, and this y represents the output column. So the output column is nothing but your outcome column. So this I column is our y, and all the other 8 other different columns are x. So we are representing x and y here. So that's what we are doing here. So this is our next step. So the first step was to initiate the hyperparameters, which are learning rate and the number of iterations, and the second step was to initiate the weight value and the bias value. Okay, so we have completed these two steps successfully. Okay, so next what we are going to do is, so now we need to create our logistic regression. Sorry, we are going to create our gradient descent algorithm. So the reason we are doing it here is we are just randomly giving the weight value and bias value as the value 0, but this model won't be accurate because we cannot take weight value and bias value as 0. So now what we are going to do is we are going to create the gradient descent algorithm, so that let's say that we are giving the number of iterations as 1000. So our model will go through the data 1000 different times, and each time it will change this bias value and weight value. So this weight value is 0 and bias value is also 0, we know that, and these values will be changed again and again till we reach a point where the model works efficiently. So at this point your model will have a very minimum cost function. Okay, so for this purpose we need to create a gradient descent algorithm, and for this we need to create a for loop. Okay, so I'll just put a text here as function. So sorry, just going to create as implementing gradient descent. So we are going to implement gradient descent here, and the purpose of gradient descent is for optimization. Okay, so implementing gradient descent for optimization, and for this I'm going to create a for loop. For I in range number of iterations, I'm going to update the weights. So self dot update weights. Okay, so this is my next part of code. So let's try to understand what we are doing here. So I'm creating a for loop, and the range of this for loop, for I in range number of iterations. So this number of iterations can be anything. So let's say that we are giving the number of iterations value as 100. So if you give the number of iterations value as 100, so we will do that later in a later part, where we will give model is equal to logistic regression of learning rate and number of iterations, as I have told you before. So we will give some number of iterations. If this value is 100, then this for loop will run 100 times. If you give the number of iterations value as 1000, then this for loop will run 1000 different times. Okay, and in each step and in each time your for loop runs, your weight value will be updated. Not only weight, your weight value and the bias value will be updated, and that is the purpose of this purpose of using this for loop. Okay, so now what is meant by this update weights? So we know that in order to update weight, we need these four formulas. So W is equal to W minus alpha into dW, where the W in the left hand side represents the updated weight, and W in the right hand side, this W represents the previous weight. Okay, and alpha is your learning rate. So we know what is meant by the learning rate, and dW is your derivatives, and we have the derivative function here. So dW, and the formula is same for bias as well. So updated bias is equal to previous bias minus learning rate into dB, and dB formula is this, where y cap minus y. Okay, so this is our gradient descent formulas, and this is the formulas in order to update the weights, and we are going to incorporate all these weights, all these equations, WB equation and DW and DB equation, in this update weights function. Okay, so that is the next step which we are going to do, and this process process is called as our gradient descent algorithm. Okay, so and another thing we need before going into that is, so if you see this formula, so let's see what are the values that we have. So we have this weight value. So now the value which we are trying to find is this W, the updated weight and the updated bias. So we will be having this previous weight value. So this previous value is nothing but the value that you have initiated, which is np dot zeros and zeros. Okay, so this is your initial weight, and we also have the learning rate value, because we will while calling the logistic regression class, we will give the learning rate value and the number of iterations value. So you have these values as well. So you have the previous weight, we are trying to find the updated weight, so learning rate value is also there. And now the thing that we need to do is find the dw value and db value, right? And this is the function for formula for dw and db. Here we have the x-axis value, sorry, the x value. The x value is nothing but all the 8 columns, the first 8 columns that we have here. The input column is our x value. If you look at this formula, the one thing that we are missing is y cap, right? So we also have the m value. We have already calculated the m value, which is x dot shape, so self dot m will be your m value, and y is nothing but your outcome column is your y. Okay, so we have all the values in these equations, but we don't have this y cap value. And now the step which we are going to do is find this y cap value. Now what is meant by this y cap? This y cap is nothing but your sigmoid equation. So y cap is equal to 1 divided by 1 plus e power minus z, where z is equal to wx plus b. So the next step would be to write this equation. Okay, so once we write this equation, we can write the dw and db formula, and after that we can write this updating weight functions. Okay, so it is very simple, and I hope you know what is meant by this y cap. So we have already discussed this in our previous videos. So y cap is nothing but, so it is the probability that y is equal to 1. So we know that y can take only two values, and these two values are either 0 or 1. Okay, so we can only take two values, and y cap is what is the probability that your y value is equal to 1. So if you get the y value as 0.8, then it means that you have a 80% chance that your y value is equal to 1. If you have the y cap value as 0.2, then it means you have only 20% that your y value will be 1. So that is the property of this y cap. And the important thing that you know to note here is y cap can have only the values from 0 to 1. Okay, so that's the other important thing that you need to keep in mind. And now we know that this y cap is derived from the sigmoid function, and this z is given by this equation, which is wx plus b. Okay, so now let's try to write this y cap equation. So that will be our next step. So just a second, I'll just have some water. Okay, so let's try to write the y cap equation first, and then we can write the dw and db formulas, and finally we can write the updating weight formula. So that is the process which we are going to follow. So the next step will be, I'll write this as y at, so I'll represent this y cap as y at formula. So this is nothing but the sigmoid function. Okay, sigmoid function which will give you the y cap value or the y at value. So I'll call this as capital Y at. Okay, so Y at is equal to, just write this equation. So 1 divided by 1 plus e power minus z. So Y at is equal to 1 divided by 1 plus np dot exp, and inside this parameter parenthesis I'm going to mention minus z. Now we need to understand this particular equation. So y at is equal to 1 divided by 1 plus np dot exp. So np dot exp is nothing but your e value, your exponent value. Okay, so e value you can just write it separately as well. I just remove this. Okay, so if you just print np dot exp, your value will be, okay, so I'll just give the value here as np dot exp1. So what this basically means is, we'll go to the scientific calculator online. So we know that the sigmoid function has the term e, right? So this e is represented by this np dot exp. So if you want to cross check, just go to the scientific calculator and just give e. Okay, so e power. So if you just click this particular button, you will get a power value. Okay, so let's try to check the value of e power 1. So e power 1 is 2.718, and in order to find the e power 1 value, you need to mention np.exp, and inside this parenthesis you need to mention the power which we are trying to give. Let's say that we want to find the value of e power 1, so give the power value inside this parenthesis, and you will get the value of e power 1. And let's say that we want to find the value of e power 5. Okay, so I'll just create text here as e power 5. So you can find this e power 5 value by np.exp, and in parenthesis mention the value as 5. Let's run this, and you will get the value for e power 5, and you can cross check this here. So e power 5. So you can compare these two values. So this is nothing but the E that we have in our equation. So you can find that exponent value by using np.txt, and we have this value within the numpy library. So it is easier for us to write that particular value there. So I'll just remove that. So that's what I have written here. So y at is equal to 1 divided by 1 plus e power minus z, and instead of that e I'm using this np.ext, which is basically the same thing. Now what I'm going to do is I'm not going to use z, but instead of this z I'm going to substitute this equation, which is wx plus b. So your equation will become y cap is equal to 1 divided by 1 plus e power minus wx plus b. So I'm just substituting the value of z here. Okay, so I'll just remove the z, and now within this parenthesis let's mention wx plus b. So we cannot represent wx plus b as such, so we can write this as self dot x dot self dot w plus self dot b. So this is nothing but the same equation, which is wx plus b. Okay, so I'll just leave some space so that it is clear. Okay, so what we are basically doing here is, so we know that it is wx plus b, but the important thing is w and x are not single integer values. So they are arrays, they are a matrix, right? So the shape of this x is 769 into 8, right? So similarly, your weight value is, it contains 8 different values because it is equal to the total number of input features. So this is basically a matrix multiplication. So this is not the multiplication between two numbers, but it is a matrix multiplication, and hence we are using this dot. So this is nothing but dot represents product of these two matrices. So self dot x into w. So this is similar to, so I'll just write here as this particular part. This second part of code is nothing but it is similar to wx plus b. Okay, so that's what we are basically doing here. So the next thing which we are going to do is, I hope you are clear about what this particular line means. So this is basically this equation. We are just substituting the value of z here, and we are just representing this w into x as a matrix multiplication. So b is a simple integer value. So we know that simple b is an integer value, whereas w is an array, right? Array or a matrix, and hence we need to do matrix multiplication or vector multiplication kind of a product here, and we can just add b. So this is what we are doing here. So the next step is to find the derivatives. Okay, so we have the y at values, and then now we can build these dw and the db formulas, and once you find these formulas you can also build these two equations in order to update your weights, and that will be your final part. So the next step is to build the derivatives. So you can call this as derivatives or gradients. So dw is equal to, we know that it is 1 by m. So we are mentioning this 1 by m within this logistic regression class. So we need to mention it as 1 divided by self dot m. So we know that we need to mention it as self dot m into np dot. So dot represents dot product, or it's basically the matrix multiplication. Self dot x dot t. So we are taking the transpose, and y at minus self dot b, self dot y. So I'll just complete this and explain you what this means. So db is equal to 1 divided by self dot m into np dot sum y at minus y, sorry, self dot y. Okay, so let's try to understand what we have done in these two lines of code. So I've just written these two equations, these two formulas here. So that's it. So it is nothing but 1 by m into y cap minus y into x, and db is equal to 1 by m into y cap minus y. So if, if you see this dw, so we have written it as 1 divided by self dot m. So we know that it is nothing but 1 by m into np dot dot. So we are taking we are taking product of x and y at minus self y, because we know that we need to find the difference between y cap and y, and we need to multiply it with x. Our x is nothing but this particular data. Okay, so the data without this y column is our x. So we need to find the difference between y cap. So y cap is nothing but the value you found using the sigmoid equation, and the y is nothing but the outcome column. Okay, so we need to find the difference between them, and we need to multiply it with x, and after that we need to multiply it with m. So this particular part, this y at minus self dot w represents this term. Okay, y cap minus y is represented by this term, and we need to multiply this with x. Okay, so that's what we are doing here. Self dot x, the important thing that we need to note here is we are taking transpose of x. Now you need to understand why we are taking the transpose of x. So I have already made videos on matrix multiplication, and the important point about matrix multiplication is that if you take two matrix and if you try to multiply these two matrix, the number of columns in the second matrix, which is this value, so the number of columns in the first matrix should be equal to the number of rows in the second matrix. Then only you can do the multiplication. So you can see the rule here as well. So the number of columns in the first matrix should be equal to the number of rows in the second matrix. So the resultant matrix will have the same number of rows as the first matrix, as the same number of columns as the second matrix. So what will be the shape of the resultant matrix is this. So 2 into 2, these two. So the important thing to note here is this value and this value should be same. So if you see this particular example, the number of columns in the first matrix is not equal. So this is not equal to the number of rows in the second matrix. So in this case, you cannot do the matrix multiplication. So it is basically the same thing. Okay. So let's try to find the shape of x and y at comma y. Okay. So what is the shape of x? So if you look at this, we know that the shape of this x is 769 into 8, right? So I'll just remove this. So the shape of y, just a second. So let's remove this, and yeah. So let's try to find the shape of x. So we know that the shape of x is 769 into 8, right? So 769 rows and 8 columns. And now let's try to find what is the shape of y. The shape of y is nothing but, just look at this last column. So it contains only one column, but it contains 769 rows, right? So therefore this will be our y. So the shape of this y is, so y shape will be 769 rows into one column. So it's 769 into one column. So if you just look at this, so this will be our y, and a to h will be your x. So the shape of x is 769 into 8, and the shape of y is 769 into 1. Okay, so now we cannot multiply these two. As I've told you, if you want to multiply two matrices, this value and this value should be similar. So that's the reason we are taking the transpose of x. So if you take the transpose of x, your x transpose will have the shape as 8 into, so when you take the transpose, your number of rows and columns will interchange. So you will have 8 rows and 769 columns, and you will take the y matrix as such. So your y will be 769 into 1. Okay, 769 into 1. Now as you can see here, this value and this value is a similar. Now you can multiply these two values. So the important insight or important takeaway is that you cannot multiply x and y directly, but you can take the transpose of x and you can multiply it with y. So that's what we are doing here. Okay, so if you come to this particular part, so that's what we are doing here. So y at and y will basically have the same shape, so that's why we are subtracting them. So once you subtract that, so we cannot multiply x and y as such. So we need to take the transpose of x, and then we are taking we are just multiplying it with this y at minus y. So we know that it is y cap minus y into x, and this is the same thing that we are doing here. The only difference is that we are taking the transpose of x, because you cannot multiply x as such, because there is some problems with the shape of the matrix. x. So we need to take the transpose. So we have successfully created our y at equation, and then we have created our dw and db equations, right? So the next thing that we need is this gradient descent equation, which is used for updating the weights, which is w and b. Now this is the last step, and it will be to write this w and b equation. And now let's write this. So this is our updating weights part. So updating the weights and bias using gradient descent equation. Okay, so the equation is w is equal to w minus alpha into dw, b is equal to b minus alpha into dw. So whenever you are mentioning w and b, we need to write it as self dot w and self dot b, as we are writing this within the class logistic regression. So self dot w is equal to self dot w minus self dot learning rate into your dw value. Okay, so just give some space here. Okay, so your db equation is self dot b is equal to the same, it is basically the same thing. So self dot b minus self dot learning rate into db. Okay, so these are all the equations that we need. So first we found the equations of this y at. Once we found the equation of this y at, we have used it in this dw and db equations, and after that we have substituted this dw and db equation in this updating weights equation, which is w is equal to w minus learning rate into dw, and b is equal to b minus learning rate into dw. Okay, so this is so the part, so this will be our part to implement gradient descent. So what basically happens is, if you look at this for loop, your for loop is runs the number of iterations we are mentioning. So if it is 100, this for loop will run 100 different times, and each time it will update the weights. And how it will updates the weight is based on this particular function. Okay, so first we are finding the y at value using the equation x dot w plus b, so that 1 divided sigma, basically the sigmoid equation. After that we are finding the dw and db values, and using these values we are updating the weight and bias value. Okay, so this is our next step. And finally, once we found the optimum value of weight and bias, we can come to this predict part. And this part is to find the value of y given the value of x. So how we will do that is by creating again the sigmoid equation and then setting a decision boundary. Okay, so this will be writing the sigmoid equation and the decision boundary. So let's discuss what is meant by this. So as I've told you before, this y cap is what is the probability that your y value is equal to 1. Okay, and your y can take only two values, which is either 0 or 1, but your y cap value can have any values between 0 and 1. But the output that we want is either 0 or 1. So we just want to find whether a person has diabetes or not. Let's say that 1 represents a person with diabetes and 0 represents a person without diabetes. So your output value cannot be 0.2, or it cannot be 0.8, it cannot be 0.4, and so on. So we just take a decision boundary, and it is nothing but if your y cap value is greater than 0.5, then your output value should be 1. If your y cap value is less than 0.5, then the output value should be 0. So it is very simple as that. So your y cap value is nothing but the probability that y is equal to 1, and if your y cap value is greater than 0.5, you will take the y value as 1. If the y cap value is less than 0.5, your value will be 0. So that's what we are going to do in this last part of the code, which is define predict. Okay, so let's create a variable as y prediction, so or y pred. Okay, so y prediction represents y pred represents y prediction. So now we need to write the same y at equation, because we just need to find the equation of y at, right? So I'll just copy and paste this equation here. So y prediction is equal to 1 divided by 1 plus np dot exp, and this is basically the sigmoid equation. So we are trying to find the equation of the value of y cap, and if the value of y cap is greater than 0.5, it should be 1. If the value is less than 0.5, it should be 0, right? So y pred, I'm going to write this as y pred is equal to np dot var y pred greater than 0.5, in that case the value should be 1 or it should be 0. Okay, so this is like a simple if condition, so it is similar to this, and I just want to return ypred. So let's try to understand what is meant by this. So we are just writing the same equation, the y at equation here, and instead of y at I'm representing this as y pred, which is y prediction. So y prediction is equal to 1 divided by np dot ex, this the same equation that we have here. So this y cap equation, and we know that if y cap is greater than 0.5 it should be 1, and that's what I have written here. So np dot var, so your y prediction value will take the value 1 if your y prediction value is greater than 0.5, otherwise it will take the value of 0. So that is the use of this np dot var function. So this is very useful for creating conditions. So here I have given a condition, right? If the condition is that the y prediction value is greater than 0.5, then your y prediction should get the value as 1, otherwise it should get the value as 0. So it is basically saying the same thing here. Y cap greater than 0.5, then take the value as 1. If it is less than 0.5, take the value as 0. So it is as simple as that. So when you give the value of x, so you need to mention the parameter x, okay? Because when you give the value of x, your final output should be 1 or 0. So your final output will look like, so let's say that we have trained a logistic regression model, everything is done. So let's say that we are taking all these 8 values. Okay, so we are taking all these 8 values. So when you give all these 8 values, your logistic regression model will find whether your output is either 1 or 0. So you cannot have any decimal values here, you can have only 1 or 0, the binary values, but the output that we get will have the values between 0 and 1. So in order to set that decision boundary, we are setting it as 0.5. If the value is greater than 0.5, take it as 1. If it is less than 0.5, then take it as 0, and that is what represented by this equation. Okay, so that is all for building the logistic regression model in Python. Okay, so we have created a class, so I'll just give you a quick recap. So I hope everyone is clear up to this point. Okay, so that is all that is related to building logistic regression from scratch. So what we have done is, so you can just come to these steps again. So the first step is setting the hyperparameters, learning rate, and the number of iterations, which we have done in the define init function. And after that, we need to initiate our weight value and bias value, and we have initiated with the value 0. After that, we need to update the weight and bias. So we will create our logistic regression function, which is the sigmoid function. So once we get that, we will build our gradient descent function, right? So gradient descent equation. So we will try to find the value of y at. After that, we try to find the value of dw and db, and finally we have written the equation for updating the weights and parameters. So this process will take place again and again. So the model will go through the data again and again based on the number of iterations that we are setting. So if you give 100, it will go through the data 100 times. If it is 2000, it will go through the data 2000 different times, and each time it will change the value of weight and bias using this gradient descent algorithm. Okay, so after the number of iterations, we will get an optimum model which has the best weight value and bias value. And once the model is trained from the data, you can use this predict function to determine the class of the data point. Class of the data points in the sense it is either 0 or 1, and for this we have set a decision boundary as 0.5. Okay, so that is all that we have done in our logistic regression model. Okay, so these are the equations that we have. So the sigmoid equation, the equation for z, and the gradient descent equation, w is equal to w minus alpha into dw, where your dw and db are given by these set of equations. And after that, we have imported our numpy library, and then we have created the object as logistic regression. And inside this, we have 4 different functions. So first is the init function, and fit function, which is used to fit the data to our model. And the third function is updating the weights function, where we have used gradient descent. And finally, we use this predict function. Okay, so these are the 4 steps. And in the first step, in the init function, we have declared the learning rate and number of iterations, which are the hyperparameters. And whenever you are mentioning the parameters within this class, you need to mention it with using this keyword self. So the second function is fit, and it is used to fit the x and y to our logistic regression model. And for that, the first step is finding m and n, where m is your number of rows or the number of data points that you have in your data set, or you can, and the value of n is the number of columns, or in other words, you can say it is the total number of input features. So we have found that by x dot shape, and then we initiated the weight value and the bias value as zeros. So weight should be an array, so we have created a numpy array with all the values as 0. Bias is a single value, and we have declared x and y, which is our data set. And then we have built this for loop in order to go through the data multiple times. And then we have set up this gradient descent algorithm, where we try to find the y at value, and then dw and db value, finally the formula for updating the weight and bias. Okay, and the last part is making this predict function, where we try to round the values. If the values is greater than 0.5, round it to 1. If the value is less than 0.5, round it to 0. So when you run this predict function, you will get the value as either 0 or 1. So this is how we can build the logistic regression model from scratch, and I hope everyone is clear up to this point. Please practice these codes, so then only it will be helpful for you. And in the next video, I'll show you how you can use this code, how you can use this logistic regression code in order to learn from a data set, and how you can predict new values. Okay, so that will be the next video where we will try to implement logistic regression model from scratch. Okay, so this seventh module is all about building machine learning models from scratch. In my previous videos, I have explained you what is the intuition and math behind a logistic regression model, and the last video was on how to build a logistic regression model from scratch in Python. So in that video, I have shown you how you can write this code for logistic regression using class, where we have created logistic regression as an object. So in today's video, let's try to use this model. Let's try to train this model using a data set, and we can make predictions with it. Okay, so that is the agenda for today's video, and for this purpose, we are going to use the PIMA diabetes dataset. Okay, so this is one of the standard datasets that we often come across in machine learning. So we will use this particular dataset to train our logistic regression model, where if we train that model, we can find whether a person has diabetes or not. So that is the end goal of this particular dataset. So let's try to understand this deeply. So I'll just give you a quick recap of what we have done in this logistic regression code. So first we have imported this NumPy library, and we know that NumPy library is used in order to make NumPy arrays, and we need to create arrays in multiple steps of our code. So that is the reason for importing this NumPy array. And here we are creating the class as logistic regression, where we are giving a template as logistic regression. Okay, so if you want a deeper understanding of this code, you can watch my previous video on this. So I'll just give the link for those videos in this video description. You can check that out before watching this video. Okay, so let's discuss about this. So first we have initiated the parameters for this logistic regression, where the two parameters are learning rate and number of iterations. Okay, so these are the two hyperparameters for our model, where learning rate is something that we give to our model. Like when our model is training with the data set that we have, it will go through the data multiple times. Okay, so let's say that we want our model to go through the data 1,000 times. So in that case, we will give the number of iterations value as 1,000. So each time the model will try to change its parameters. So the parameters are nothing but the weight and bias of the model. So we have discussed all this before itself. So we need to change this weight and bias value repeatedly during this 100 iterations. Okay, and in each step, we will change the value for weight and bias, and the amount of change that we want to give to our weight and bias is nothing but the learning rate. Okay, so these are the two hyperparameters of the model, which are learning rate and number of iterations. So in this define init, we will try to initiate these two parameters. Okay, so that is the first part of the code. Then we will try to build the fit function. So the purpose of this fit function is to train the model. So we will try to fit the data set that we have to our model. So in this case, the model is logistic regression. So it is just like plotting a curve with the x-axis value and y-axis value. It is as simple as that, where your x-axis value will be the features, and your y-axis value will be your target column. Say for example, in the diabetes data set, you will have various features like what is the age of the person, what is the blood glucose level, what is their BMI, and so on. So these are nothing but the features which we will take as x, and y is a target column. So target column is whether the person has diabetes or not. Okay, so that is our target column. So when you give these two values, your model will try to fit to this data. So that is a second step. So here m represents the number of data points that you have. Let's say that you have about 700 data points in your data set. So we will represent that 700 as m, and n represents the total number of features. So as I told you before, there will be features like age, BMI, etc. Okay, so you can consider this m as the number of rows in your data set, and n as the total number of columns in your data set. So I have mentioned all these things here. And then we will initiate the weight and bias value of our model. So generally we will initiate with the value 0, and this x is nothing but the data that we have, the feature. So x represents the feature and y represents our target column, and then we will implement our gradient descent algorithm. So gradient descent is used in order to arrive at the most optimum weight value and bias value. So for this we will create a for loop, and as I told you before, we will give some number of iterations. So this iteration number can be 100,000 or whatever number you want. Okay, and based on the number of iterations, the model will go through the data again and again for that specified number. Okay, and it will try to update the weight and bias. So it will try to change the weight and bias to check which weight value and which bias value is the most optimum one. So that is this part of the code, and then we finally write this update weight, which is used to update our weight and parameter of the model. And we know that this y-at equation is nothing but our sigmoid equation. So we know that logistic regression is based on this sigmoid equation, which is given by y cap is equal to 1 divided by 1 plus e power minus z, and z is equal to wxd. So that is our next step, and we will try to find the derivatives dw and db, and this dw and db is used. So this is the formula for dw and db, and this is used in order to implement gradient descent. So we will try to write these four equations in Python. So these are that four equations. Okay, the four equations that I've shown you. And once you do all those things, so once the for loop has run with all these code, it will find the optimum value for our weight and bias. And finally we have the predict function. So this predict function is used to give us the value of y, that is whether the person has diabetes or not, that class. So it will try to predict that class given the value of x. So if you give all the features like the age, bmi, glucose level, etc., it will tell you whether that person has diabetes or not. So that is the purpose of this predict function. And as you might know, this y cap is what is the probability that your y value is equal to 1. Let's say that if a person has diabetes, in that case your y value is equal to 1. If a person does not have diabetes, in that case the y value will be equal to 0. So we are just labeling the output. So your y cap is the probability. So what is the probability that your y value is equal to 1? So that is your y cap. So your y cap value can lie between 0 and 1, because we know that probability values generally lie between 0 and 1. Okay, whereas your y can only take two values, either 1 or 0. So we are trying to find this y prediction, which is nothing but basically the y at value. And once we find this, if your y cap value is greater than 0.5, we will take that as 1. Okay, if your y cap value is less than 0.5, we will take that as 0. So these are the labels for our prediction. So that's what is represented by this part of the code. And if you don't understand things clearly in this particular code, so you should watch the previous video. Okay, so I have given a detailed explanation on this. So that's what we have did in this class logistic regression. This is the code that we have written. So there are two things that I need to mention you. So there are some errors in this code. So as you can see here, in this for loop, while we implemented gradient descent, we need to give self dot number of iterations. Okay, so I have missed that in my previous video. So you need to do this particular change. So self dot number of iterations, as we are mentioning this, so we know that number of iterations is one of the hyperparameters of the model. So we are using this parameter inside this logistic regression class. So we need to precede it with this self keyword. And here in the second part, in this predict function, here this self shouldn't be here, because here we are taking a different x. So we are giving a new x, and we are trying to find the value of y. So in this case the self shouldn't be here. So these are the two errors that was in the previous video. So just make a note of it. So before this number of iteration, there should be a self, and there shouldn't be a self before this x in this predict thing. Okay, but in this case, so in this y-at, there should be self dot x, but in this predict function we should not include the self. So that these are the two things that I wanted to mention in this particular video. Okay, so I hope everyone is clear up to this point. And now we are going to use this model to train our diabetes data set. Okay, so for this we need to import some libraries. So I have already made a detailed video on this diabetes prediction project, and in this particular video we won't be going in detail about the data processing and how to clean the data and such things. So because I have already made a video on that, and if you want a clear understanding of this diabetes data set and how you can use it, you can watch my diabetes prediction project video. I'll give the link for that video as well in this video description. So for now, the purpose of this particular video is to understand how we can implement the model. Okay, so that's it. So we won't be going detail about this project. So our idea here is to learn the implementation. So first thing we need to do is in any project is to import the libraries, import the dependencies that you want. So dependencies is nothing but the libraries that we need for our project. So we are importing the pandas library, sklearn or pre-processing. So sklearn library is very important. So pandas library is used to create data frames. So data frames are nothing but they are like structured tables. So it is very useful for us in order to make data processing and other such kind of things. So for data analysis, so for these purposes, pandas will be very useful, because the data set that you have will be in a CSV format. So if you just open in a notepad file, so your data will look something like this. Okay, so we cannot do any analysis or processing in this structure. So we will load this CSV file in a structured pandas data frame. So that is the reason for importing the pandas library and then sklearn library. So sklearn library, we have some functions like standard scalar, train, test, split function, accuracy score, etc. So I'll explain you what is the purpose of these functions. So for now, just understand that we are importing these functions. Okay. So and then the second step is data collection and processing. And in this you can get this data set in sklearn.datasets, or you can also find this data set in Kaggle. So I'll give the link for this data set file in my video description. You can download it from here. Once you download it, you can upload it, you can upload the data set in your collab environment. So just click this files option. So you will find this upload option here. So from here you can upload your diabetes.csv file. So I have already uploaded it. Now we can do some processing on it, and we can use this to make predictions. Okay. So the next step is to load the CSV file into the pandas data frame. As I've told you, it is hard to analyze the data from a CSV file. So we are loading this in a pandas data frame, and pd.read CSV is the function for it. So I'll run this. So I'll just run the previous cells as well. So you can just press shift plus enter to run this one. So I'll run this logistic regression code as well. And we will be using this code in order to train our model. So now I'll run this libraries cell where we have tried to import some libraries. So now we will load our CSV file, the diabetes.csv file, to a pandas data frame, and let's name this data frame as diabetes.data. Okay, so I'll run this. So the next part will be printing the first 5 rows of the data set. So this is something we do while processing all the data sets. So we generally do this in order to check what are the different columns that we have. So this is like the sample of the data set, and we will try to print what are the first 5 rows in our data set. So as you can see here, we have the columns like the pregnancies. So this PAMA diabetes data set is mainly used to predict whether a woman has diabetes or not. So the first column represents the number of pregnancies that they had, and the second column is their blood glucose level, and then we have the blood pressure level, skin thickness, insulin level, BMI, and we have this diabetes prediction function, age, and finally outcome. So this outcome is a target column where 1 represents a person with diabetes and 0 represents a person without diabetes. So the next step will be to find how many number of rows and columns are there in a data set. In other words, we are trying to find how many data points in the in the data set and how many features in the data set. So features are nothing but all the columns except this output column. So these are called as our features, and the total number of data points is nothing but let's say that we have 500 different people, and we have the data for 500 different people in this data set, and each line represents the data for each individual. So we have tried to find what is the shape of the data set, which is nothing but the number of rows and columns. In other words, you can think about it as nothing but the total number of data points and the total number of features that you have. So this is nothing but your m and n, where your m is the number of data points and n is the number of features. So that is our next step, and after that we will try to use this describe function. So these are some data analysis part where we will try to find the mean of the mean in each column, what is the standard deviation, minimum value, percentiles, etc. And then we will try to find how many values are there for the target 1 and the target 0. So for the target 0, we have totally 500 data points, and the target 1, we have 260 data points, where 1 represents a person who is diabetic and 0 represents a non-diabetic person. Okay, so I'm not going detailed into this part. As I've told you before, if you want a detailed explanation, watch the diabetes prediction video. Okay, and the next step is to group the data based on their mean values. Okay, so we have grouped the data points of 0 and 1, person with diabetes and without diabetes, based on the mean value for all the columns. You can find all the mean values here. So the one main thing which you can note here is a person without diabetes, who is represented by 0, has a lower glucose level compared to a person with diabetes who has a higher glucose level. So it is obvious here, right? And you can also see that the age of the person is less for a non-diabetic person, and the age is slightly more for a diabetic person. So these kind of things, so it will help us to draw a clear distinction between person with diabetes and without diabetes, and that is the reason for grouping the data based on the mean value of individual columns. So the next will be separating the features and the target. As I've told you, the last column is our target column. This output column is our target column, and the remaining columns are the feature, are the input feature. So we need to separate these features, and we need to separate this target. So for that, we will use this particular code. So where we will use this drop function in order to drop the last column, and we will store this target column, this outcome column, in this target variable. Okay, so the remaining columns will be stored in this feature column. So I'll just run this. and you can now print the features and the target separately. Now as you can see here, the target column is separated from this features. Okay, so the reason for this is your features represent x and your target represents y, so we need to give these data separately, so that's the reason for separating them. So the next what we will do is, if you look at this data, so if you look at this input features that you have, the pregnancies have the values in single digit numbers, 2 3, so on, but the glucose level value is in the range of hundreds, your blood pressure value is in the range of 60s and 70s. So similarly, different values are in different range. So if your diabetes prediction function, it is in some kind of decimal value, so 1 and 2 and so on, so that is the range of this particular column. So we need to standardize this data in order to have all the data in a similar range. So for that, we will use the standard scalar function, where we will standardize our data. So we are loading the standard scalar function here, which we have imported from sklearn.preprocessing. As you can see here, from sklearn.preprocessing, we are importing the standard scalar function. With this standard scalar function is used to standardize the data that we have. Okay, and sklearn is one of the most important libraries in machine learning. So it contains a lot of data pre-processing functions like standard scalar, train, test, split, etc. And it also contains all the different machine learning models ready-madely available for us. So the next step is loading the standard scalar function, and we are naming a variable, and we are loading this instance of the standard scalar to this variable. So I'll just run this. Now we will fit the features. So we know that we need to change this feature value, right? So we need to standardize this value. So we will fit those feature to the standard scalar, and we will transform it. So we don't need to transform the target column, as we know that there are only two possible values, which are 1 and 0. So you don't need to do that in this case. You just need to standardize the features columns alone. So I'm fitting the scalar function to this features, and I'm transforming the features. So as you can see here, scalar dot transform features. So we are transforming the data, and you can now print the standardized data, and almost it is in the same range now. Okay, so this is the purpose of standardizing the data. And again, I'm saving the standardized data in my features, and the target remains the same. Okay, now this feature will change to this feature, which is a more standardized value. So you can just print features and target separately. So this is our standardized values, and this second part, this target, is our outcome column. Okay, and the next step is to split our training data and testing data. We know that in machine learning, we generally train our machine learning model with training data, and we will test it with our test data, right? So this is the step for it. Just a second. Okay, so here we are doing that, and for this we are going to use the train test split function. We have also loaded this train test split function from the sklearn library. So sklearn.model selection, we are importing train test split function. Okay, so in this train test split function, you need to give the what is the features that you have, and what is the target, and what is the test size. So test size is equal to 0.2, means I want the 20% of data to be in the test size. So let's say that we totally have 100 data points, and if you give test size is equal to 0.2, then in that case, the 20% of data, which is 20 data points, will go to the test data, and 80% of the data will go to a training data. So this test size is nothing but how many data points do you want in your test data. Okay, so these are the different code, and random state is a very simple thing. So if you give random state is equal to 2, your data will be splitted in the similar way as my data is getting splitted. If you give different random state value, your data will be splitted in a different manner. So this is a very simple thing which is used to reproduce the code exactly. So this is not big of a concern. So you can give any values you want for this random state. So I'll just run this, and this will create four values, four arrays: x train, x test, y train, and y test. So these are the four arrays that we will get. So x train is nothing but your training data features, and your x test is your test data features. So y train is the label for your training feature, and y test is label for your test feature. So you can also find how many data points are there. So out of the 768, your 80% of data, which is 614, go to your x train, and 20% of data goes to your x test, because we have given test sizes 0.2. So that will be our next step. And now we are in the more important thing of this particular video, where we are training our logistic regression model. As you can see here, so I have created an instance as classifier, and I'm loading the logistic regression which we have created before. As you can see here, we have created the class as logistic underscore regression. So I'm calling this logistic regression 4. So here we are going to train our model. So logistic regression, as I told you, we need to manually give the values for learning rate and the number of iterations. Okay, so you can manually tweak the values of learning rate and number of iterations and see when you are getting good accuracy score and when the model is performing well. So I'm giving a learning rate as 0.01 and the number of iterations as 1000. 1000 means our model will go through the data 1000 times. So this is how you can train your data. Okay, so first of all, I'm loading this logistic regression to a instance called as classifier. Okay, so I'll just run this. Okay, now we need to fit our data to our logistic regression model. So we know that we have created this define fit function, right? So this define dot fit function, and within this fit function, you need to give two parameters, x and y. Okay, so your x is the features and y is the target, and we know that we need to train our model with the training data. So we will be giving x train and y train. So x train is your training data feature and y train is your training data target. Okay, so we are fitting the model, logistic regression model, to these data set. Let's run this. So this will complete the training process. So now once the model has learned from the data, now we can find the accuracy score, or even we can use the model to make new predictions. Okay, so now we will do the model evaluation where we will try to find the accuracy score. So accuracy score function also you can get it from sklearn.metrics. Okay, so from sklearn.metrics we are importing accuracy score, which is used to calculate how many correct values our model is predicting and how many wrong values our model is predicting. So I'll just run the code for it. So classify.predict xtrain. So we have already created this predict function, right? As you can see here, define predict. So when you give the value of x, your model will find the value of y pred. So y pred value will be either 1 or 0. Okay, where 1 represents a person with diabetes and 0 represents a person without diabetes. So, and I'm predicting the value for x train. Okay, and I'm storing all those values in this x train prediction. And this x train prediction is the value predicted by your model. So this is the predicted value, but the true value is y train. So we need to compare these two and check how many values are predicted correctly and how many wrong values are predicted. So that is the purpose of this accuracy score. So we need to compare the true value. So here the true value is y train and the predicted value is x train prediction. So I'll just run this. Now we can print the accuracy score. So I'm storing this accuracy score in the variable called as training data accuracy, and now we are printing the training data accuracy here. So the accuracy score is about 0.77. So 0.77 means it is almost 77%, which is not a bad metric. So if you even use the logistic regression from sklearn, you will also get the accuracy score close to this. Okay, so you can also try that. You can load the logistic regression model from sklearn, and again you can do this training part and find the accuracy score. And this is for the test data accuracy. As you might know, we have splitted our data into training data and test data. So now we need to find the accuracy score on the test data. So I'll run this, and the test data accuracy is about 0.76, which is 76%. So it is close to the training data accuracy. So we can tell that our model didn't overfit. So overfit is a condition when your accuracy score on the training data is very high, but the test data accuracy is very less. So that is called as overfitting, and I've already explained you what is overfitting. So we have already made video on that, and I assume that you know all those things. Okay, so our model didn't overfit, so we don't want our model to overfit. So this model is working fine. And finally, you can make a predictive system. So where you will if you give the values, so these are nothing but the values from the pregnancies all the way up to age. So if you give all those values, your model will predict whether the person has diabetes or not, where 1 being a person with diabetes and the 0 being a person without diabetes. So our model predict the label as 1, and 1 represents a person who is diabetic, and if the value is 0, it will tell you that a person is non-diabetic. Okay, so this is the code for it. So I'm not going to explain all these things because we have already worked on this in our diabetes prediction project. So if you haven't watched that video, please check out the link in the description. So you will clearly understand all those things. So what we are doing from the start to end. So I have detailedly explained all the things in that particular video. Okay. So this is how you can implement this logistic regression model. So the important part which you need to understand from this particular video is from this classifier all the way up to this accuracy score and this making predictive system. So these are the most important part of the code in this particular video, where we will try to load the logistic regression model that we have built to this classifier. So you can also name this anything. You can name this model or classifier or anything. And then we have fitted the data, the x train and the y train data, to a classifier which is logistic regression, and then we try to find the accuracy score for this. So this is how you can train your logistic regression model with the data set that you have. Okay, so that is another way of doing it. So we don't want to write this logistic regression code every time we want to use it. Let's say that we have about 10 different data set and we want to use the logistic regression code for all these 10 data sets. So in that case, we cannot go on and write the same code again and again. So what we can do is we can store this code in a separate Python file, and we can import that Python file and we can use it ready-madely. So I'll show you how we can do that. So we have actually seen that in our linear regression video as well. So I'll just show you how you can do that. So copy this part. So copy this logistic regression code. So I'll just remove this thing. So as I've told you, we have two errors, which is incorporating this self in this line. So I'll just remove this comment, also this comment. Okay. So make changes in those two lines, where in one case you need to include this self, and in the second case you need to remove the self before this x. Okay. So now I want to copy this logistic regression code along. So this cell, I'll copy this and I'll go to my notepad plus plus, and I'm going to create a Python file. Okay. So I'll paste the code here. So please, you can download and install notepad plus plus. So this is a free software and it is very useful for writing the scripts and all. So I have pasted my logistic regression. As you might know, we have imported numpy library as well, right? So we need to write that code as well. So in the first line, I'll import numpy library, import numpy as np. Okay, so now we have the code for our logistic regression model, and now I'm going to save this as a Python file. So you can go to this file and give save as. So I'm going to save this in my desktop as, sorry, it's not. Okay, so file, save as. I'll go to desktop and I'll name this file as log_reg, so which is the short form for logistic regression, and save as type. So you need to save this as a Python file. So come to this save as type, and if you scroll down, you will see the option for a Python file. Yeah, Python file is this, which ends in .py. Okay, so logreg.py, where logreg represents logistic regression. So you will now get the syntax of this Python in your notepad plus plus. So I'll close this. So this is my logistic regression Python file. Okay, so this is the code for it. Now what I can do is, if I have a new project, if I have a new data set, I can just upload my logistic regression code and use that code in order to do the prediction. So it is basically the same code. So the same diabetes prediction code. So I've just removed this logistic regression part. Okay, so other things are just the same. So the data processing, making the prediction, all the things are same. Now what we are going to do is upload our logistic regression Python file. So the diabetes.csv data file is already here. So I'm going to upload my logistic regression.py file. Okay. So the file is uploaded, and now we need to import this Python file. So you can do that by coming to this importing the dependencies section, and I'll import logreg. So you need to mention the name of this Python file, which is log_reg, which stands for logistic regression. So I'll run this, and everything is the same. The only difference is that while implementing the code, while training the code, so we know that this logistic regression is nothing but I'll just open this with notepad plus plus. As you can see here, so I'm calling this logistic regression, and within this logistic regression, let's do that. Okay, so I'm going to load the instance of this logistic regression from classifier. So in order to do that, you need to mention the Python file that we have imported. So the Python file that we have imported is log_reg, which stands for logistic regression. So just mention it here. So log_reg dot logistic regression. So basically what we are doing here is, okay, so we are calling this Python file, and within this Python file, I want to load this logistic regression class. So that's what I have mentioned in this second part. Okay, so logistic regression, and then we need to give the learning rate and number of iterations. So now this classifier assumes the value of logistic regression, and we know that logistic regression dot fit will train our machine learning model, right? So for that we have mentioned this fit function. So everything is same after this. So this code and this code is, everything is the same. You just need to mention it in a different way, the loading the logistic regression. Okay, so I'll just run all the cells now. So you can go to this runtime and give run all. So all the cells will be executed in order. So similarly, so your training data will be splitted and everything will go on in the same way. and now you can find the accuracy score for training data and test data. So this is basically the same thing. So the only different thing here is we don't need to write this logistic regression code again and again. So we have just stored this in a file so that we can use anytime we want. Okay, so we have stored it in a Python file which is .py, and once we upload it we can just import it directly and we can use the logistic regression code. So this is how we will basically work. So once we create this model, we will store it in some kind of file and we can just load it as such. So I hope everyone is clear up to how we can implement this logistic regression code. And this seventh module is all about building machine learning models from scratch. In my previous videos, I have explained you what is the intuition and math behind a linear regression model and logistic regression model. And we have also seen how we can build these models from scratch in Python. So the third model which we are going to discuss is a support vector machine classifier. So this support vector machine is one of the most important models that we deal with in machine learning. So let's try to understand about this model. So first we will try to understand the intuition behind a support vector machine classifier, and in the upcoming videos I will be explaining about what is the math behind it and how we can build this SPM model from scratch in Python. Okay, so that will be the order of the upcoming videos. So let's get started with today's video where we will discuss about the intuition of a SVM classifier. Okay. So first of all, let's discuss about some of the basic things about a support vector machine model. So as we know that it is an example of a supervised learning model. So supervised learning model in the sense these models requires data as well as labels. Say for example, let's say that we have the images of dogs and cats and we want to train a machine learning model that can recognize whether that image is a dog or a cat. So when we take a supervised learning approach, what we will do is we will feed all the images of dogs and cat to our machine learning model or a deep learning model, and then we will also give the labels in the sense, so all the dog images will be labeled as dog and all the cat images will be labeled as cat. So now the model, the supervised learning model will try to find the relationship between all those images and their respective labels. Whereas if you take an unsupervised learning model, it won't require the labels for the data set. So we just give all these images, but we don't mention whether it is a dog or a cat. Okay, so what does the unsupervised learning model does it tries to group the similar images. So all the dog images will be grouped into one group and all the cat images will be grouped in another group. Okay, so this is the difference between supervised learning model and unsupervised learning model, where supervised learning model use the labeled data set where all the data will be labeled, whereas unsupervised data set uses data set that is not labeled. Okay, so some examples of supervised learning model are logistic regression, support vector machine, and some examples of unsupervised learning model are k-means clustering and other clustering algorithms. Okay, so support vector machine is a supervised learning model, and we know that there are two types in supervised learning. One is classification and regression, and both for classification and the regression purpose, support vector machine model can be used. Okay, so it can be used for both the cases, but it is predominantly used for classification. So we will be discussing about the support vector machine classifier, okay, and not regressor. If time permits, let's discuss about regression in the later videos, but for now let's discuss about a classification model that we can build using support vector machine. Okay, so and it is also mainly used for binary classification problems and not multi-class classification. So binary classification in the sense we will try to classify the data points into two classes. Say for example, let's say that we are predicting whether a mail is a spam mail or a normal mail, or we are predicting whether a person is going to get a job or not. So we are just classifying into two classes or two types. So this is called as a binary class classification, whereas multi-class classification is the one where we have multiple classes. Say for example, we have 10 different colors and we are looking at an image and trying to find which color that particular image is. So in that case we have totally 10 classes, right? So these kind of problems are called as multi-class classification, whereas binary classification is one where we just have two classes, and support vector machine is predominantly used for binary classification. So we can also use support vector machine for multi-class, but we have to do some adjustments and other processes. Okay, so let's not go detail into that, but for now understand that support vector machine is mainly used for binary classification. And the other two important things about support vector machine is that there are two terms called as hyperplane and support vectors. So these are the very basic things about support vector machine. So let's discuss about what is meant by this hyperplane and what is meant by the support vector. So these two are the more important factors when we are working on the support vector machine, and these two are the things which define the support vector machine model. Okay, so now let's try to understand this. Let's say that we have a data set and this data set contains two features, and we need to classify the data points into two groups or two classes based on these two features. Okay, so this x1 and x2 can be anything. So it can be, let's say that we are trying to predict whether a person has diabetes or not. So we are taking two features for this. So one feature can be their blood sugar level, and the other factor can be the BMI and so on. So we are taking two features. So now we will try to plot the data points in these features, and as you can see here, there are two different classes, right? So this group of classes given in blue colored data points, and this data points are given in green color. So sometimes we can draw this clear differentiation between the data points, so there is clearly a grouping between them, right? So now what a support vector machine classifier will try to do is, it will try to find a hyperplane that can separate these two data points. Okay, so as you can see a line here, so this line is called as a hyperplane. Now if we give a new data point, this support vector machine model will try to find whether the new data point lies in this group or this group. So based on that, it can tell you what kind of class it belongs to. Okay, so this is how support vector machine classifier works, and this line is called as the hyperplane. So here we have only two dimensions. Okay, so x1 and x2, and you can see the 2 points here, 1 and 2. So I have named this point as 1 and 2, and these 2 points are called as support vectors. So support vectors are nothing but the data points which are very close to this hyperplane. So the nearest points to the hyperplane are called as support vectors, and if the position of the support vector changes, the position of the hyperplane also changes. So the position of the hyperplane mainly depends on the position of the support vectors. Okay, so this is the basic explanation of how a support vector machine classifier works. So it will try to find that hyperplane that can separate the data points into two classes, and the 2 points which are very close to each other are called as support vectors. So one from this group and the one from this group is called as support vectors. Okay, and this is how a support vector machine model works. And now let's discuss more about this. So, and so here, as you can see here, we have only two dimensions, right? But it is not possible to separate the data points into two classes when we have only two dimensions. So let's take this example. As you can see here, we have a two-dimensional plot here. So x1 and x2. So x1 and x2 can be any features, and now you can see the two types of data points here. So one set of data points are circle in shape, which is blue in color, and the other data points are triangle shaped and they are red in color. So you cannot draw a line that can separate these two data points, whereas in the previous case we have easily drew a line that can separate these data points, right? But we cannot do the same here. So we cannot draw a line here. So now what we can do is, one thing that we can do in order to separate them is increasing the dimensions. So if you have a three-dimensional structure like this, there is a possibility that we can separate these data points. So this is what we need. So it is not always that we will be using a two-dimensional space as we have used in this case. So some data points, when you have two dimensions, we can easily separate them, but it is not possible all the time. So in that cases, we may need to increase our dimensions. Now you can see here, this is a three-dimensional space. This is a 3D space, right? So we have three dimensions, x1, x2, x3, and these are nothing but three features. So in this case, we have only two features, and you can see this grayish plane. So this is called as the hyperplane. So this is why it is basically named as hyperplane, whereas in this case you can see that it is basically a line, yet we call this a plane, right? So the reason is that most of the times we will be dealing with multiple dimensions and not two dimensions. So we will be creating a hyperplane. So if you have more number of dimensions, then we have to take that multiple dimensions as well. So if you have two dimensions, the plot will be in a two-dimensional plot where you can have the hyperplane as a normal straight line. But if it is a three-dimensional space, you will have a 3D plane. Okay, so this is how you can use a support vector machine model to classify data points. And the one main thing you need to remember is that we have a hyperplane that separates the data points, and then we have the support vectors which are the nearest points to it. And we often try to increase the dimensionality. Dimensions are nothing but the different features that we have in a data set. Okay, so I hope everyone is clear up to this point. So I'll just give you a clear definition of hyperplane and support vector machines, support vectors in this slide. So hyperplane is a line when we consider it in a 2D space or a plane that separates the data points into two classes. Okay, so it is basically a line or a plane that separates data points, and it basically separates them into two classes. So when you consider a two-dimensional space, it will be a straight line like this. When you consider a three-dimensional space or a multi-dimensional space, it will be in the form of a plane. Okay, and what is meant by the support vectors? So support vectors are the data points which lie nearest to the hyperplane. If these data point changes, the position of the hyperplane changes. Okay, so this is one of the main concepts of support vector machine. So you can refer this diagram as well. This black colored line is the hyperplane of our support vector machine, and you can see these data points here. So these are named as support vectors for class 1 and support vectors for class 2. So these are the two groups of data. So one is this blue colored circle, the other group of data is the red colored squares. Okay, and the support vectors are mentioned here. So support vectors are nothing but the data points which are closer to the hyperplane. So these support vectors must be as far as possible from the hyperplane. Okay, so if they are as far as possible, then this support vector machine can draw a clear differentiation between them. Let's say that I'll just mark it here. If the data points, let's say one data point lies here and another this blue color data point lies here, so in that case, if there is not a clear distance between them, our model cannot classify the data points easily. So the support vectors must be as far as possible from this hyperplane, and if the position of the support vector changes, the position of the hyperplane also changes. Okay, so that's another thing that you need to remember. So, and another term which we can remember is the margin. So, the margin is nothing but the distance between one support vector. So, support vectors of one class and the support vectors of other class. So, this distance is called as the margin. So, how a support vector machine classifier works is it's try to fit to the data set multiple times, and it tries to find which can be the optimum hyperplane. So, once it's found this optimum hyperplane, when you give a new data point, it will try to see whether that data point goes into this class of data points or this class, and based on that it will tell you what kind of class it is. So these classes are nothing but whether a person is having diabetes or not, or it can be a male is a spam mail or a normal mail, and so on. So those kind of binary classification problems, and these are the definitions of hyperplane and support vectors. Okay, and finally let's discuss about what are the advantages and disadvantages of support vector machines. So understanding these advantages and disadvantages will let you choose the best model for your problem. So like when you are working on a data set, we need to try to understand which model suits for that particular data set. So we need to understand the advantages and disadvantages of each model in order to select a model properly. Okay, and this process is called as model selections. And in our previous videos also, in a linear regression and logistic regression also, I have explained you what are their respective advantages and disadvantages. And for now, let's discuss about the same for this support vector machine classifier. So it works well with smaller data sets. So this is one of the main thing. So support vector machine model is one of the best model for binary classification when you have a smaller data set, when you don't have a large number of data points. So in that case, we can use a support vector machine, and it works efficiently when there is a when there is a clear margin of separation. So clear margin of separation is nothing but there should be space between the support vectors of one class and the support vectors of the other class. As I have showed you, if there is not a clear margin, that is the distance between these two support vectors, the red colored one and the blue colored one, if the margin is very low, then the support vector machine cannot draw a clear separation between them, so and it cannot classify the data points clearly. So there should be a clear margin of separation, and there should not be any overlapping. That's the idea. So the two classes should not overlap in the sense the two classes should not have any similar values. So that is another main advantages. So you can also consider this as an advantage and as well as a disadvantage. Okay, so when there is a clear margin of separation, then we can say that SVM is best we can use. Okay, and the other advantage is it works well with high dimensional data. As I've told you before, we cannot classify the data points when there is only two dimensions. So if you have higher dimensions, then support vector machine model works well. But this is not the same in the case of the models like logistic regression. So those models require lesser number of dimensions, because if you have higher dimensions, those model will tend to overfit. But support vector machine works well with high dimensional data. So high dimension in the sense when you have a lot of features in your data set, that is nothing but the columns you have in your data set. Okay, so whenever you have that more number of features, you can go with support vector machines, and when you have a low number of column and a larger data set, you can go with logistic regression. So this is how you can select a model. If the model is very small and it has a higher dimensions, you can go with the support vector machine, and it can also find the complex relationship between them. So if the relationship between the data points is linear, then we can use the models like logistic regression or linear regression. But when the relationship between the data points are very complex, in that case we can use support vector machine classifier. So these are some of the advantages of SPM classifier. And now let's discuss about its disadvantage. So it's not suitable for larger data sets as the training time is higher. So this is the reason. If we have a larger data set, and if the data set has more number of dimensions, then the training is going to take a lot of time. So training this SVM model will take a lot of time, and hence we don't generally use SVM when we have a very large data set, but we will use it when we have smaller data set. And the other disadvantages is that not suitable for noisier data set with overlapping classes, the one which I have explained you. So in some cases the two classes will have the data points which almost overlap with each other, and in that case the margin will be very low, the distance between the support vector of one class and the other class. So in that case the model cannot clearly define the separation between them. Okay, so that is one disadvantage. So when you have overlapping classes, it is not easier. Noisy data set in the sense the data set which contains a lot of outliers and mistakes. Okay, so these are the advantages and disadvantages, and whenever you are choosing a model, you need to weigh this advantages and disadvantages of different model in order to choose the best one. Okay, so I hope everyone is clear up to this point, and that's it for this video. The main takeaways for this particular video is that support vector machine is a supervised learning model which is mainly used for classification. So it can be also used for regression, but it is mainly used for binary classification. And we have two main terms such as hyperplane and the support vector. So hyperplane is the line or a plane that can separate these two classes, and the support vectors are the data points which are closer to this hyperplane. Okay, so I hope everyone is sure about this, and in the upcoming videos let's discuss about the math behind a SPM classifier, and then we can move on to the hands-on part where we will try to build this SPM classifier model from scratch in Python. The seventh module is all about building machine learning models from scratch. In my previous video, I have explained you what is the intuition behind a support vector machine classifier, and in today's video, let's try to understand what is the mathematical basis of a support vector machine classifier. Okay, so let's get started. I'll just give you a quick recap of what we have discussed in the previous video. So we know that a support vector machine or a SVM model can be used in both classification as well as regression tasks, but it is mainly used in classification problems, but that too in binary classification problems. So binary classification in the sense the model will try to classify the data into two groups. So you can see the two groups here. So one type of data is represented as blue colored circles, and the other type of data is represented as red colored squares. And now we are going to use a support vector machine classifier in order to classify these data points. So what does a SVM classifier tries to do is it will try to draw a hyperplane that can separate these two data points. Okay, so you can see this black color line. So this line is called as hyperplane. So even though this is a line, let's call this as hyperplane. I'll explain you why we do that, but for now remember that it will try to draw this hyperplane which is represented as this black colored line. So this line will separate these two data points. And now we have other important term called as support vectors. So support vectors are the data sets or they are the data points present in a data set which lie closer to this hyperplane. So you can see this three red colored squares, right? So these three data points lies closer to this hyperplane, hence we call them as support vectors. Okay, and you can also see these two blue colored circles, so they also lie closer to this hyperplane, and we call this as support vectors as well. So it is not the rule that there should be one support vector, so that's not the case. So you can have multiple support vectors in a data set, so you can remember that. And then we have something called as margin. So this margin is the distance between the line that is drawn drawn from the support vector. So if you draw a dotted line that joins all the support vectors from one side, and another dotted line that can join the support vectors from the other side. So if you measure this distance, and this particular distance is called as the margin, and your hyperplane lies exactly in the middle of this margin. Okay, so this is how we will try to draw this hyperplane. So we will try to find the support vectors, and we will try to find this margin, and we will try to draw this hyperplane in this middle part. And now the one thing you need to remember is that this margin should be as far as possible. So this margin distance should be greater so that our SPM model can make good predictions. So the reason we are creating this margin is to have some tolerance value, or to have a cushion to make predictions. So if we have just this hyperplane alone, then our model cannot make good predictions because some data points may overlap. But if you have this tolerance, if you have this margin, let's say that there is a data point which lies in this space. So let's say that we have a new data points, and we try to plot this data point, and it lies at this point. Now the SVM model can see that it lies in this part of this margin, and then it will try to classify this data point as one of those red colored squares. Okay, and if you have another data point which lies in this space, it can try to classify this data points as one of the blue colored circles. So this is how this margin works. So we need this margin should be as long as possible, so the distance should be greater so that we can have a good cushion or a good tolerance value. Okay, and now if you have a new data set, and let's try to plot this new data set. Let's say that this green colored square is the new data set, and if we try to plot this, it comes in this place. So we can see this visually and say that this is one of the type of this red colored squares, right? Because it lies in this part of the hyperplane. If another data point lies in this space, we can call this, let's say that there is new data point which lies in this space. So in this case, we can say that this particular data point is one of the blue color data points. Just a second. So we can say that this data point belongs to one of those data points, and this data point belong to these red color squares, right? So this is how we can visually say that SVM can classify the data points. But now we need to understand how a SVM classifier can mathematically determine this. How it can look at this data point and say that it is belong to this kind of data. So that's what we are going to deal with in this particular video. And you can see that this is a linearly separable data set. So that's what I have mentioned here. So which means this data set can be separated by a straight line, right? But in real world, there are a lot of data set which cannot be separated by a straight line. In that case, what we will do is, let's consider this example. Let's say that we have two features, x1 and x2, and in this data set we are trying to draw a SVM classifier. So no matter what, you cannot draw a straight line that can separate this red colored triangle and blue colored circles, right? So these are the two data points you have, and you cannot use a straight line to separate them. In that case, what we can do is, if we have a third feature, in that case we will try to plot this data points in a three-dimensional space, and in that case we can separate these two data points using a plane. So you can see this plane here, which is represented as a gray colored space. So this is how you can build a support vector machine classifier by increasing the dimensionality. So in this case you have only two features, and because of that you are not you are not able to clearly separate the data points. But in this case, as the dimensions is more, we can clearly separate the data points. And in some cases we don't have the higher feature, so we cannot have more dimensions. So in that case, what we will do is, so if a data set has a minimum dimensions, minimum features, we will try to use some mathematical functions called as kernels. So these kernels are the mathematical functions that will try to increase the dimensional space. So this smaller dimensional space can be converted into a larger dimensional space. So this two-dimensional space can be converted into a three-dimensional space, and so on. So once you do that, you can easily classify the data points using some plane. So if you have a two-dimensional space like this, so it is just a two-dimensional space, right? So it just have x-axis and y-axis. So in that case, so I'll just draw x-axis and y-axis. Let's say that we have y-axis here and the x-axis here. So this is a two-dimensional space, and if you have a two-dimensional space, you can easily draw a straight line which can separate the data points. But if it is a three-dimensional space, we need to draw a plane. If it is 4 dimensions or 5 dimensions, we have to use a hyperplane. Okay, so that's what is called as a hyperplane, a plane which is in multiple dimensions. So hence we generally call this line as a hyperplane. Okay, so I hope you understand why we call this as a hyperplane, because we basically use it in a multiple dimension in most of the cases. So, and for this we use something called as kernel, which are mathematical functions to increase the dimensionality, right? So I hope everyone is clear up to this point. And now we are going to see how a SVM model can determine a new data set. If you take a new data point, which data groups does it belong? So we are going to discuss that. So let's say that we have two features, x1 and x2, and we are trying to plot the data points in these two features in a graph. Okay, and let's say that we have 2 points. So the first point is represented as p1, which is in red color, -3, 0. So this is the coordinate of this point. So x1 is so this -3 is the x1 coordinate, and 0 is the x2 coordinate. Okay, so it's just like x and y axis. So and then we have the second point as p2, which is represented as this green colored dot, which is the coordinate of this p2 is 3, 3. Okay, so we have this two data points, and now we are going to draw a hyperplane which can separate these two points. So as this is a two-dimensional space, we can just use a straight line, and we know that the equation of a straight line is y is equal to mx plus c, right? And now we are going to see how a hyperplane or how a line can separate these data points. So let's say that the slope of this line is minus 1. So let's take this blue color line, which will act as our hyperplane for our support vector machine classifier. And let's say that the slope of this line is minus 1 and the intercept of this line is c is equal to 0. So we know that the equation of the line is y is equal to mx plus c, and m is the slope and c is the intercept, right? So slope is nothing but it basically tells you what is the orientation of your line is. So if you have a line like this, so let's say that we have a line like this, so this line would have a slope of plus 1. So a slope of plus 1 basically means if x1, so let's join these points. Okay, so let's join these points. So slope of 1 plus 1 represents if x1 increases by 1 unit, then x2 also increases by 1 unit. So if you have a line which is in this particular direction, it would have a positive slope. Okay, but if you have sorry, just a second. So in other case, if you have a line like this, so line like this blue color line, which is in the opposite direction to what we have seen before, so this kind of line has a negative slope. So let's say that the slope of this line is minus 1. So let's consider this, and then let's say that the intercept is c is equal to 0. So you can find the intercept using this origin point. So we know that the coordinate of this particular point is 0 comma 0, right? If you take those values 0 comma 0 and substitute here, okay, so if we put y is equal to 0 and x is equal to 0, you will get your c is equal to 0, right? So your intercept value is 0 if your line starts like this. So let's say that we have a line which starts from this particular point and it is like this. So in that case, let's say that this coordinate, this point is 2. Okay, so let's say that this is 2. So in that case, this particular green line has an intercept of 2. So it is basically the intercept value is equal to y value when your x value is equal to 0. Okay, so you can remember that. So if you take this, if you substitute your x is equal to 0, in that case your intercept is equal to y. So we know that we can find this intercept value, right? So similarly, for this green line, the intercept value can be 2, but in this case, for this blue color line, the intercept value is 0 as this passes through the origin. Okay, so that's what you need to understand. So we have two data points, P1 and P2, minus 3 comma 0 and 3 comma 3, and then we have a hyperplane represented by this blue colored line, and the equation of this line is y is equal to mx plus c, where m is the slope of the line which has the slope of minus 1 and the intercept c is equal to 0. Now what I'm going to do is I'm going to take these two parameters. So this slope and intercept are the two parameters of my line, right? And I'm going to take these two parameters and I'm going to store it in a variable called as w. So let's call this w as the parameters of the line. You can think about this as the weight that we talk about in models. So we know that we have weights and bias in our models, right? So let's say that these two parameters m and c, the slope and intercept, is our weights, and you can represent this m as m comma c, which is minus 1 comma 0, right? Because we have given the value for slope as minus 1 and intercept as 0. So basically w will be a vector or an array with the values minus 1 comma 0. So now what we are going to do is, so I'm taking these 2 points, and now I'm going to take the transpose of this w. So the w is minus 1 comma 0. So I'm taking the transpose of this w and I'm multiplying it with x. So x is nothing but my point. So the point here is minus 3 comma 0, right? And now I'm just multiplying this. So this is just like a simple matrix multiplication. And the reason I'm taking transpose of w is that we know that the shape will mismatch for matrix multiplication. If you want to carry out a matrix multiplication, the number of columns in the first matrix should be equal to the number of rows in the second matrix, right? So if you look at this, the shape of this matrix is 2 comma 1. So 2 rows and 1 column, and the shape of this matrix is 1 comma 2. So 1 row and 2 column. So the column of the first matrix should be equal to the number of rows in the second matrix, and that is the reason we are taking this transpose. If you don't take this transpose, you cannot multiply this, right? So that's the reason we are taking the transpose of this w. So we are taking the transpose of this w vector, and then we are multiplying it with x, and if you do that, you will get the value of w transpose into x as 3, right? So we can say that for all the points which lie in this space in the left side of this blue color line will have a positive value. Now let's consider this P2 point. If you take this point, and similarly if you try to take the transpose of this w and multiply with x, and in this case the x is this P2, 3 comma 3. If you multiply this, it will be minus 1 into 3, which will be minus 3, and 0 into 3 is 0. So you will get w transpose into x as minus 3, which is a negative value. So the main inference that you can infer from here is, for all the points which lie in the left side of this hyperplane, W transpose into X value will be a positive value. Okay, as you can see here. Whereas for all the points which lie in the right side of this blue colored hyperplane, W transpose into X value will be negative. So this is how our support vector machine classifier will try to classify the data points. So it will try to multiply the data point with the parameters of the line. So W basically is the parameters of the line, which is M and C parameters of this blue color line. Okay, so it will try to multiply this data point value, which is minus 3 comma 0, so data point or coordinate value with the parameters of this line. And if you get the value as positive, and it can say that it lies in this space, and if the value, the product of this W transpose transpose of W and X is negative, it can say that that data point lies in this space. Okay, so you can try this for different data points. You can just take some data point here. So let's say that this data point here is minus 2 comma 0, or else you can take a data point here like minus 2 comma 1, any data points which comes under this space. So all the for all the data points, you will get the W transpose X value as positive values, and all the values in this side which comes in this space will be negative. Okay, so this is how it will try to classify our data points. If the value is positive, then it will say that the data belongs to this group of data. If the value is negative, it will belong to this group of data. Okay, so this is how it will try to classify our data points. Now we need to understand few more things. So in this case, this W transpose X will act as our label. So if the label is positive, then this is a red color data point. If the label is negative, then it will be this green color data points, right? But this hyperplane won't pass through the origin all the time. So in some cases, so let's say that we have this green color data points and red color data points, and this hyperplane exactly passes through this origin. And in some cases that won't be the case. So let's say that we have data points. You can see here that the data points have been shifted towards the right. So you can just compare these two data points, and we have the hyperplane here, and this hyperplane does not pass through the origin, and there is some distance between this coordinate axis and this line, and this will be your B value, which is called as your bias. So if your hyperplane passes through that origin, you can say that your label will be W transpose into X, and this value will be positive or negative for one group of data and for the another group of data. And in some cases, if you have a bias value, you will have the label value as W transpose X plus B, where B is your bias value, and this will be your label. Okay, so this is what you need to understand, and in most of the cases we will be having both weight and bias for our model. So this is what you need to understand. And so this is how the equation of this particular straight line looks like: W transpose X plus B, which is similar to Y is equal to mx plus C format, right? So it is similar to it. And one more thing, so it's not that if a point lies in the left side, it will be positive, and if it lies on the right side, it will be negative. So that is not a general case. If you see that we have a hyperplane in this direction, right? So if the hyperplane is in this direction, you will get all the points, so all the values as positive for left side points and all the values for right side point. But in case, let's say that we have a hyperplane that is in this direction. So if you have a hyperplane in this direction, it will be just inverted. So all the data points which lie in this side will get a positive value, and all the data points which lie in this point will get a negative value. So it is just vice versa. So I'll just remove this. So one thing you need to understand is, if it is in this direction, yeah, then in that case, so for all the data points in the left side, the value of W transpose X will be positive, and for all the data points which lie in the right side, the W transpose X value will be negative. If the hyperplane is in this direction, if it is in the opposite direction, then it will be the opposite case. Okay, so that's what you need to remember. And in most of the cases, the hyperplane may not pass through the origin, and in that case, the label will be W transpose X plus B. So this is another thing you need to understand. Now, so we know that we have these two kind of data, so red colored circles and blue colored circles, and we are going to draw a hyperplane, right? But we can draw different hyperplane in this space. So this can be one hyperplane, and this black color line is another hyperplane, and this orange color line is also another hyperplane, right? So all these data points can classify these data points, or they can separate these two data points. But we need to understand which is the best hyperplane, right? So that is our important goal. So in machine learning, this is how we deal with. There can be multiple solutions, but we need to figure out which is your best model. So what is the best parameters for our model, right? So we need to figure out that. So that will be our next step. So we are going to figure out which is the best hyperplane. So this is where the margin and support vectors comes into play. As I've told you before, for a subprotector machine model, this margin space should be maximum so that it can make good prediction. So it can have a good cushion value, right? So we will try to maximize this margin value up to a certain extent. So we cannot keep on increasing this margin value, but this margin value should be maximum, for making good predictions, right? So now we are going to understand how we can increase this margin value. So let's discuss that, and we can call this as the optimization part. So we are optimizing our supported machine model in order to get better parameters value or better hyperplane. So as I've told you before, there can be any number of hyperplane, but we need to choose the best one. So that's what we are going to do now, and we know that in order to have the best hyperplane, the margin space should be high. So let's discuss that. So let's say that we have two groups of data, green color data points and red color data points, and I'm having a hyperplane which is represented by this W transpose X plus B. So we know that if we have both weight and bias value, we can represent the label as W transpose X plus B, where this label can either be positive or negative, right? So if this label is positive, we can say that that data point lies in this group. If the this particular value W transpose X plus B is negative, we can say that it belongs to this green color data point, right? So now I'm going to draw this margin lines. So we know that this we have already discussed what is meant by support vectors. So support vectors are the data points which lie closer to the hyperplane. So if you look at this data point, this point, this green color point and this red color point lie closer to this blue color line, and hence we can call these data points as a support vector, and we can draw a line on them. So if you measure this distance, okay, so just a second, if you measure this distance will be your margin space or margin distance. Okay, so let's say that this particular line, the coordinates of this particular line is represented by x1, and the coordinates of this line is represented by x2. Okay, and if you try to find this x1 minus x2 value, that will be your margin distance. And once we find this margin distance, we will try to increase this value, this margin distance value. And we know that the equation of this hyperplane is W transpose X plus B, which will be our label. So this label is nothing but either a positive value or a negative value. So it can be anything. It can be -1, -5, -6, so on, or it can be +1, +5, +6, or so on. So we are not interested in the magnitude, but we are just interested in whether that value is a positive value or negative value, because this is just a classification task, right? So we just need to find whether it is positive or negative. And we know the equation of this blue color line is this, and let's say that the equation of this red color line is given by this red colored equation, which is W transpose x1 plus b is equal to 1, and W transpose x2 plus b is equal to -1. Okay, so we know that for all these data points, if we multiply the W transpose with the x1, so x1 is nothing but the coordinates of the points present in this side plus the bias value, you will get positive values. So let's for simplification purpose, I'm taking the value as 1, but this is not the case. So this value can be 1, 2, 3, or so on, but the only main thing that we can tell us it will be a positive value, right? Whereas for this data points, when you take W transpose and multiply it with x2 and add it with bias value, you will get a negative value, right? So let this negative value be 1. So let's just take simple values for simple calculation purposes. So this is how the equation of these two line looks like, because we know that for all the data points on this side we will get a positive value, for all the data points you will get a negative value. So basically what we are doing is, so I'll just go to my previous slide where we try to do that. So as you know that we have tried to multiply this W transpose with the x value, right? So x is nothing but your coordinate. So in this case, what we are basically doing is we are trying to project this point onto this blue color line. So this is just like a projection of vectors. So in our mathematics module, we have discussed about projection of vectors. This is simply that we are just trying to project this red color data point in this line, and we are trying to find it. So that's what is mentioned by this product W transpose into x. Okay, and that's what we are doing here. So the only difference is that we have some bias value. Okay, so this is the W transpose x1 plus b is equal to 1, W transpose x2 plus b is equal to -1, and this x1 minus x2 is your margin distance. So how you can find this margin distance is, if you have two lines, so let's say that we have two lines, this green color line and red color line, and we want to find the distance between them. So how you can find the distance between them is, you can subtract these two equations. So if you subtract these two equations, you will get the distance between them. So it's just math, basic algebra. So every one of us have studied this in our high school, right? So we will try to do some elimination process where we will try to find the value of the variable. So I'm just taking these two equations. These two equations are the equation of the line, green line and the red line, and I'm trying to separate this equation from this equation. Okay, so this is your red colored equation and this is your green colored equation, which corresponds to the green colored line and the red colored line. So I'm just subtracting this. So this W transpose x2 will take a negative value, this B will also take a negative value, and this minus 1, so this minus and this minus will be get multiplied, it will be a positive, right? So what happens is, I'll just mention this here. So there will be a negative value here and negative value here as well, and this negative will be turned to a positive, right? Because we are just multiplying it with negative value. Now if you do that, so you will get the equation like this. So W transpose x1 minus x2, this B and B will get cancelled because we have plus B and minus B, so we are just basically subtracting the equation. So you will get a 0, so this B and this B will get cancelled, and 1 plus 1 is 2, so you will get W transpose x1 minus x2 is equal to 2. And we know that this x1 minus x2 is the margin distance, and this is what we are interested in. So we need to remove this W transpose T. So we cannot simply take this to this side, so we cannot do that. So this is not numerical value, but this is just like a vector. So in that case, what we will do is we will take the norm of W. Okay, so you can see here, so we need to divide the equation on both the sides by norm of W. So this is like magnitude of a vector. So if you consider this W as your vector, we want to divide it by the magnitude of the vector, and in that case this W transpose will cancel with each other. So that's the case. So let's write this like this. So we are dividing both left hand side and the right hand side with this norm of W, and in that case what happens is this W transpose and also this W norm will get cancelled, and the final equation you will have is x1 minus x2 is equal to 2 divided by norm of W, so which is nothing but the magnitude of W. Okay, so this will be your margin distance. So this is very, very important for us, so you need to remember this. So we have the x1 and x2 value, x1 minus x2, which is our margin distance, and this margin distance is given by 2 divided by norm of W, and our goal is to maximize this margin value. Okay, so now let's see how we can maximize this margin value. So that's what we are trying to do here. So we are trying to optimize a support vector machine model so that it can have a maximum margin value. Okay, so we have seen previously, right? So this label can have either positive value or negative value, right? So we can simplify this and write this like this. So yi, so yi, let yi be the label of each data points. Okay, so this yi, the label will be minus 1 if this W transpose into x1 plus B is less than minus 1. Okay, so if it is a negative value, so this basically means everything is a negative value. If negative value, this yi will take the label value as minus 1. If the value is greater than 1, so if this particular value is greater than 1, then we will take this as plus 1. So this is just like label encoding, because like for some data points the value will be minus 1, so for some data point it can be minus 5, minus 10, and so on. So what we just need to simplify this, and we are just creating two labels as minus 1 and plus 1. So if the label is less than or equal to minus 1, which basically means if the value, this W transpose x1 plus B value is negative, then we need to give the yi value as minus 1 if the W transpose x1 plus B value is greater than or equal to 1. So this basically means that if the value is greater than 1, we need to give the yi value as 1. So we have two labels. So if the yi value is 1, then it comes under this data points, and if the yi value is minus 1, we can group them in this data point. So this is just simplifying the labels for our data points. Okay, and now we know that we have the margin. So x1 minus x2 is equal to 2 divided by norm of W. So our goal here is to have this maximum margin, right? So we can write this as, we should have the maximum value for 2 divided by norm of W, which is our margin, such that my yi should be minus 1 when this particular value is less than minus 1, and my yi, which is the label value, should be plus 1 if my value is greater than 1. So this is the important thing that we need to remember. Okay, so I'll just put this in a bracket. So this is very important for us. Okay, so you can just take a note of this if you want. Okay, so we are just trying to maximize this margin value such that my support vector machine model makes good predictions, where the prediction is if the W transpose into x1 plus B value is negative, I want the label value should be minus 1. If the W transpose x1 plus B value is greater than 1, then I want my label value to be plus 1. Okay, so this is what we can do. And now we are just going to rewrite this particular equation. So we are just going to rewrite this in a better sense. Okay, so maximum margin without overfitting. So just forget this statement. Let's try to understand what we have here. So this is the margin value we have, right? So we have explained this two equations. So I want a maximum value such that I get labels like this. So maximum value of 2 divided by norm of w. So the other way of writing this is minimum value of norm of w divided by 2. So instead of saying I want to maximize the label, I want to maximize the value of 2 divided by norm of w, what I can say is I want to minimize the value of w divided by 2. Okay, so I'm just taking the reciprocal of this part. So instead of saying this, you can say that I want to minimize this value, because we know that it's not easy to maximize some value when we are doing or when we are training a machine learning model. So if you remember in our previous logistic regression, linear regression models, we will try to minimize our loss function value, right? So similarly we will try to minimize this value, and if this value is minimum, then that means this value is maximum. What is this value? This is nothing but our margin. So the basic idea is to increase this margin, so increase this margin space. So how we can do this? Either by increasing this value, or we can decrease this value. So we are minimizing this value. Okay, so that is what represented here. And now you can see this new term here. So C into summation of epsilon I. So what this basically means is C is the number of errors, and epsilon I is the error magnitude. So we know that our goal is to maximize this margin value, right? But we cannot keep on increasing this margin value. As I have told you before, if you remember, I have already mentioned you that we cannot keep on increasing this margin value. So there should be a limit, because if you keep on increasing, then your model might overfit. So we don't want overfitting problem, right? So when overfitting occurs, all the training data points will be classified properly, but your test data points won't be classified properly, because your model won't get a general idea. It will try to overtrain from the data set. So we don't want it. So what happens when you overfit is, if you have the data points in this cases, let's say that we have red color data points and the green color data points, and one red colored point lies closer to this green color data point, and one green color data point lies closer to this red color data point. So these two are like outliers in a data set, right? So if you don't include this error part, then your model cannot find this error. So it will try to overlook them. It will try to overfit to the data point. So we don't want that. So in that case, what we will do is include this error part. So what I'm basically doing is I am allowing the model to make some errors, to make some mistakes. So this C is the number of errors that my model can make, and this ei or epsilon I value is the error magnitude. So error magnitude is nothing but what is the distance between this red colored line, this margin line, and this red colored data point, and what is the distance between this green colored data point and this particular line. So these are errors, right? So our model cannot classify these data points correctly, but that is fine, because if you try to overtrain your model, then that's not something that we want, because it can make a lot of mistakes in our test data. So we will let our model to make some mistakes, so that it cannot make overfitting problems. So we will try to minimize this norm of w by 2 value. Along with, we will give some tolerance for error, which is represented as C into summation of epsilon I, which is the total error magnitude, where C is the number of errors and the epsilon I is the error magnitude for each data points. Okay, so this is how you can maximize your margin without overfitting. So this is how your support vector machine classifier will work. So it will try to find this margin. So it will try to find this hyperplane, and it will try to maximize this margin. So instead of writing this maximizing 2 by norm of w, we can say that we want to minimize this norm of w divided by 2, and I'm allowing it to have some errors so that it doesn't overfit. Okay, so this is how a support vector machine model works. So it will try to multiply the w transpose with the particular coordinate, and it will try to find whether that value is a positive or negative. So this is how the equation looks like. So w transpose x1 plus b, if it is a negative number, it will take the value as -1. If it is a positive number, then it will take the value as +1. So this is how labeling basically works in a support vector machine classifier. And I hope everyone is thorough with this particular part. And if you have any doubts, please mention in the comments. Okay, in the 7th module of our hands-on machine learning course, and this 7th module is all about building machine learning models from scratch. In my previous videos, I have explained you what is the intuition and math behind a support vector machine classifier, and in today's video we are going to discuss what is meant by kernels in support vector machine classifiers, and what are the different types of kernels that we have in SVM classifiers. Okay, so that will be the agenda for today's video. So let's get started. I'll just give you a quick recap of what we have seen in the support vector machine classifier. So we know that support vector machine is mainly used in both classification as well as regression task, and between the two, it is predominantly used in classification problems where we will try to classify the data points into different groups, and in that classification also it is mainly used in binary classification. Binary classification is a problem where we will classify the data into two groups or two classes. So here you can see, let's say that each circle and square represents a data point, and all these blue color circles represents one group of data or one class of data, and all the red colored squares represent another group of data. So if you have a data set like this, you can use a support vector machine classifier in order to group these data points based on their classes. So the main thing about support vector machine is that, so you will have a hyperplane. So you can see the black colored line here, and this line is called as the hyperplane, and this hyperplane separates your data points into two classes, and then we have the support vectors. So support vectors are the data points which lie closer to this hyperplane. Okay, so these are called as support vectors, and you can have multiple support vectors in a data set. So these two blue colored circles which lie closer to this hyperplane are called as support vectors, and also these three red colored squares are also called as support vectors. So these are the support vector of this class of data, and these two circles are the support vectors of this kind of data. So it lays closer to the hyperplane, and the distance between, so if you draw a dotted line between these support vectors and these support vectors, this distance is called as the margin, and your hyperplane lies exactly at the center of this margin, and this margin should be as far as possible. So the margin distance should be as great as possible, and we have discussed why is that. So in my previous video I explained all those things, and so once we create this hyperplane and the margin, when you have a new data, so let's say that this green colored square represents a new data point, and if we try to plot this data point here, we can visually see this and say that this is a type of this red colored squares, right? So this is how a support vector classifier can classify a new data point on whether it is one group of data or it is the second group of data, depending on finding this. And in my previous video where we have discussed about the math behind the SVM classifier, I have explained you how does a SVM classifier can find that among which group of data this new data point goes. How does it find that mathematically? So we have discussed all those things in the previous videos. Now we need to discuss about the SVM kernels, which is another main thing. So the importance of SVM kernels is that, so this is an example of a linearly separable data. So that's what I have mentioned here. So this data can be separated by a straight line, and hence it's called as a linearly separable data. But in real life, we won't get many data points and many data sets which can be linearly separable. So this is where kernels are used when we have a non-linear data where the data points cannot be separated by a straight line. So I'll just give you a definition for this SVM kernel. So kernel functions generally transforms the training set of data so that a non-linear decision surface can be transformed to a linear equation in a higher number of dimension spaces. It returns the inner product between the 2 points in a standard feature dimension. So this is the definition for SVM kernels. You don't have to read this second statement right now. So once we go through all the slides in this video, you will understand this second statement, but for now focus on the first statement. So kernels are nothing but mathematical functions, or you can say that these are mathematical formulas, and the kernel importance of kernel functions is that they are used to create a multi-dimensional space. So let's say that we have only two features in a data set. So let's x1 and x2 be the two features that we have in a data set, and the blue colored circles represent one class of data, and the red colored triangles represents other other type of data. And we cannot separate these two kinds of data by a straight line, right? So in the previous case we have just used a straight black line in order to separate the data, but in this case we cannot do that. Because of the kind of the data that we have, so they are not linearly separable. So this is where we need kernel functions. When we apply this kernel functions to this data set, this particular data set can be converted into a data set with multiple features. Now you can see here we have x1, x2, and the third feature x3. So in order to create this extra feature, we use this kernel functions, which are nothing but mathematical formulas. So once you do that, you can, when you now plot the same data points in a three-dimensional space, you can actually create a plane which can separate these two data points, which is called as the hyperplane. So that's what mentioned here. So in this case, you cannot create a linear decision surface. So if you see this circle, we can say that it is a decision surface. If something comes inside the circle, we can say that that is an example of a triangled data point. If it comes out, we can let's say that it is a blue colored circle. But we don't do that in a SVM. So in SVM, we need a linear decision boundaries. So in order to create that, we cannot create a linear surface in this particular two-dimensional dimensional space, so we will convert it into a higher dimensional space, and then we can separate the data points using a linear surface like a plane. So that's what is mentioned in this first statement. So kernel function generally transforms the training set of data. So it is basically used to manipulate and transform the training set of data, which is our data set, so that a non-linear decision surface. So you can consider this circle as a non-linear decision surface, because we cannot use a straight line in this case. So if you just draw, I'll show you. If you draw a straight line like this, so you will just get 50% accuracy in this case, because no matter, even if it is an example of this triangle data point, the SVM model will say that it is an example of a blue colored square and so on, because it will just have 50% accuracy. The reason is that in the previous case we can clearly separate the two kinds of data, whereas in this case we cannot clearly separate the two data points, right? So two classes of data, so we cannot use a straight line in this case. So we will transform it into a higher dimensional space where we can clearly make an hyperplane that can separate the data. So this is the importance of kernels, and how we will do that is by creating some inner products. So let's try to understand what this second statement means. So I'll the different, so in SPM kernels we have different types of kernels. So the examples are linear kernel, polynomial kernel, radial basis function, and sigmoid kernel. So these are the four important types of kernels that we have in SVM, and all of these kernels work the same way. So the only difference is that they are different mathematical formulas, but the working and the functions that they do is basically the same. The only difference is they contain different mathematical formulas. So that's the difference. So what we are going to do right now is we are going to understand how this kernel functions works and how this kernels can create a new feature for a data set. So that's what we are going to understand. So once we understand that, I'll give you all the formulas that we need for this four kernels. So that is what we'll be doing in this particular video. So I'll just give you an example of how this kernel functions work. Let us say that we have a data set, and this data set contains only one feature, and let's call this feature as x, and these are all the different values for this feature x. So as you can see here, all the values are represented in green color and red color. Let us say that all the green color values represents the class 1 data points, and all the red colored values represents the class 2 data points. So these are the two types of data that we have. So now let's try to plot this data points in an axis. So you can have a x-axis. Let's say that this green color line is our x-axis, and in this x-axis value I'm going to plot all the features. So you don't need a y-axis because you don't have the y-axis coordinates, right? So you just have only the x values, so you can plot all the values in a single axis, which is our x-axis. So this first point represents -x, the second point represents -5, this is your -4, and the first red colored point represents -3, -2, and so on. The same order that we have our data is plotted here. Okay, so now let's say that we want to draw a line that should separate all these data points into two groups. So all the green color data points should be grouped under one section, and all the other red color data points should be segregated in the other part. So if you try to draw a line here, we cannot say that this line separates all the green color data points and all the red color data points. You cannot say that, because in this side there is both red color and green color data points, right? Whereas in the previous SPM, the one we have seen here, if you just see this hyperplane, this black color line separates the two types of data, right? But in this case it cannot be done, because if you draw this line at this side, there is both red colored data points and green color data points. So no matter what line you try to draw, so if you draw here, then also it is a problem, because now I'll just remove this particular line. So if you draw this line also cannot separate all the green colored points and the red colored point, right? So this is the problem that we have when we have a small number of features. So in this case we have only one feature, right? So if you have multiple features, then there is a possibility that we can separate this data point. So that is the importance of kernels. So whenever you don't have the necessary features, you cannot classify the data points, you cannot separate the data points, and that is where kernels are used. Now let us say that I'm taking all this feature x and I'm going to create a new feature. Let's say that let's see how we can create this new feature. So I'm taking all the values of this feature and I'm just squaring this. So I'm just taking x square. So this is the first row represents my x value, and the second row represents x square value. So I'm just taking the square of each of these values. So we know that 6 square is 36, 5 square is 25, 4 square is 16, and so on. So these are all the negative data points, and these are all the positive data points. So if you take square, you will get the values like this. So 4 square is 16, 3 square 9, 5 square 25, 6 square 36, and so on. So I'm taking x, and I'm also taking the square of x. Now I'll take the first row of values, that is my x values, as my x-axis value, and this x square value as my y-axis value. So we know that green color data points represents the first class and red color data points represent second class. But I have created a new value which is my x square value. If you try to plot this, if you try to plot the x versus x square values, where I'm taking all the x values or the first row of values in my x-axis and all the x square values I'm taking it in my y-axis. If you try to do that, and now if you try to plot, we will get a scatter plot like this. And if you see here, now we can easily draw a line that can separate the two class of data, right? So if you draw this hyperplane, if a point comes in this part, we can say that it is class 1 data, because we know that all the green color data points lies above this hyperplane. If a data point lies below this hyperplane, then we can say that it is a class 2 data points. Now let's say that we have a new data point and we don't know what that particular data point is. So I'll just change this color. So let's say that we have a data point that lie here. So in that case, we can say that this is an example of class 1 data point, because this lies at lies above the hyperplane. So what happens is, if you just give some values for this, let's say that we take this particular value 5. So if you have a new value, so I'm taking new value for this feature x. So what I would basically do is, if I have a new value like 5, I will just square that value. If I just square that value, I will get the value as 25. And if you plot that, it will come in this space above the hyperplane. Then I can say that that data point belongs to the class 1 data, which is green colored, is as represented here. Let's say that we have the value as 1 or 1.5 and so on for our x value. So in that case, again, I will take the x square, and I'll try to see where the plot lies. And once I find where the plot lies, whether it lies above the hyperplane or below the hyperplane, I can clearly say that which class does it belong to. So that is the importance when you have two feature or two dimensional spaces. So in the previous case, if you remember, we add only one feature, which is our x. So we cannot draw a higher dimensional diagram or a plot. So this is a 1D plot. So in this case, we cannot draw a straight line that separates the data. But when you have another feature, when you have additional feature, you can easily draw a straight line, which will be our hyperplane that can separate the data points. So this is the advantages of having more number of dimensions. So this is not just for one dimensional space and two dimensional space. It's not like that. In some cases, you may have four dimensional spaces, which means basically you have four features. Let us say that there is a data set which contains four features. But even though it contains four features, sometimes we may not be able to draw this line that separates the data point. So in that case, what we will do is, we will try to increase the dimensional space further. So we can create 5-dimensional spaces, 6-dimensional spaces, 7, and so on. So when you do that, you can create an hyperplane that separates the data. So this is how kernels works. So kernels are basically the mathematical functions that allow us to get all these features. So in this case, the extra feature that we get is x square, right? So similarly, we will get different terms using the kernel functions, and once you have that, you can increase the dimensionality of your data, and then you can easily draw a hyperplane which can be used to classify the new data points. So this is basically our SVM classifier kernels work. Okay, so I hope everyone is clear up to this point on our kernel works. And now let's try to understand what are the different SVM kernels that we have. So I've already told you, so we have linear kernels, polynomial kernels, radial basis function kernels, and sigmoid kernels. And this radial basis function kernel is also called as Gaussian kernels. Okay, and each of these kernels have different mathematical functions, and these are the different mathematical functions for all the kernels. So you can take note of this. So we won't be going in detail about how we get this formulas and all. You can just remember this. Okay, so let's say that x1 and x2 are the two features that we have, and let k be our kernel function. So I'm having a function which depends on x1 and x2. So the basically the linear kernel is represented by x1 into x2. So we know that data set may be considered as a matrix, right? So this is just like matrix multiplication. So we are taking the transpose of first feature, because then only we can multiply the two matrices. So we know that in order to do a matrix multiplication, the number of columns in the first matrix should be equal to the number of rows in the second matrix, right? So that is one of the basic things that we have learned. So this is just a matrix multiplication. So this is how we can represent linear kernels. So the linear kernels in the sense is the one we have seen before, where you can just draw a straight line and you just have only two features. And if you see this polynomial kernels, so in the case of linear kernels, you just need this two features alone, x1 and x2. In that case, you can just classify the data points into two classes. If you just see here, let's go to the first example that we have seen. So let's say that we have the x-axis and y-axis like this. So let's draw the x-axis and y-axis here. We can say that this is our x1, the first feature, and this y-axis represents our x2, which is our second feature. So in a linear kernel, you just need these two features, x1 and x2, and within that you can draw a linear structure like a straight line to separate the data points. So that is represented by the linear kernel. So and this is the formula for it. Okay. And when it comes to a polynomial kernel, this x1 and x2 alone is not sufficient. So we need more features as we have seen before. Okay, and this is the formula for this x1 transpose x2 plus r the whole power d. So this d basically represents the degree of your polynomial equation. So when you plug in the values for this particular function and you expand this, you will basically get a polynomial equation. Okay, and this d represents the degree of the polynomial equation that you get. So when you do this polynomial kernel implementation, basically what you will get is, let's say that we have this x1 and x2 as our features, and we are unable to separate the data points using a line when we have the two features alone. So when you implement a kernel function, a polynomial kernel function, what happens is that you will get new features such as x1 square, x2 square, x1 into x2. So these are the new features that you get. And if you we can easily find the values of x1 square, x2 square, and x1 x2 based on the x1 values and x2 values, right? So previously we have seen that we have the x values and we have squared the x and we got x square, right? So similarly we will try to create new terms such as x1 square, x2 square, and x1 x2. And when you have these three-dimensional plot, you can easily segregate this data. So this is how basically a polynomial kernel function works. So if it is a two-dimensional space or three-dimensional space, you will get different plots. If it is a five-dimensional space, you will again have multiple values. So in this case we have x1 square, x2 square, x1 x2, right? So similarly, if you have a five-dimensional space, you will have two additional features, which will be a combination of these features. So that is what is represented as inner product, as we have seen in the definition of SVM kernels in the previous part of this video. So basically we will get multiple features when we use a polynomial kernel function. So similarly we have radial basis function kernel, which formula looks like this. So we take the exponential of this terms, and then we have a sigmoid kernel. So sigmoid kernel function is similar to the sigmoid function that we have discussed for a logistic regression. So it is just like the same formula. So these are the different kernels and the main kernels that we have in support vector machine classifier. Okay, so now you might have one question that in which case I have to use which type of kernel, right? So you may have that question. So which kernel to use at which particular aspect? So basically we will try to use a linear kernel when the number of features that we have in a data set is I. So let's say that you already have about 20 features in your data set. So in that case, you can just go ahead with linear kernel because you have sufficient number of features. But let us say that you have only a less number of features in a particular data set. In that case, we may use a polynomial kernel in order to increase the number of features, or in order to increase the dimensional spaces, so we can create a hyperplane which clearly separates the data points. So similarly, you can also use radial basis function when you have a very low number of features. So there is not a general rule of thumb on when to use which. So the basic intuition or basic inference that you can remember is, if you have many features, you can basically go with a linear kernel, and if you don't get a good accuracy score with linear kernels, you can try the different kernels like polynomial kernels and radial basis kernel and so on, because the kernels which we are choosing is completely based on the data set that we have and the nature of the data set that we have. So different features in a data set have different relationships among them. So all those things comes into play when we are choosing a kernel. So you basically can try the linear kernel. If the accuracy is not good, then you can go on with the other types of kernel. So that's what I would advise you. Okay, so if time permits, let's deal with this kernelizations in a more detail in a later part of this particular course. But for now, understand that these are the four important kernels that we have, and these are the mathematical functions of this kernels. So basically what a kernel does is, it will try to increase the number of features that we have, so that it can increase the dimensional spaces where we can draw a hyperplane that can separate the data points into two classes. So that is how a basic kernel works, and these are the different types. So I hope that everyone is clear up to this point. And the next part of the video, we can move on to the hands-on part where we can try to build this support vector machine classifier from scratch. The 7th module is all about building machine learning models from scratch. In my previous videos, I have explained you what is the intuition and math behind a support vector machine classifier, and in today's video, we are going to discuss what is the loss function for a support vector machine classifier. Okay, so that is the agenda for today's video. And for SVM classifier, we have a different kind of loss function called as inch loss, and we will be discussing about this inch loss in detail in this video. So let's get started. So I'll just give you a quick recap of what we have seen in the previous videos of SPM so that you get a better understanding of the loss function. So we know that support vector machine is mainly used in both classification and regression problems, but it is predominantly used in classification problems, and that too binary classification, where we will try to classify the data points into two classes. Here we have the two types of data we have are these blue colored circles and red colored squares. So let's say that all these data sets, data points represents one kind of data, and all these data points represents another class of data, and we are building a hyperplane. So this black colored line here represents our hyperplane, and this hyperplane separates these two data points. So this is our support vector machine classifier, and you can see the data points which are close to the hyperplane. So these data points are called as support vectors. So you can see these three red colored squares and these two blue colored circles. So these are called as a support vector. So these are nothing but the data points which lie closer to the hyperplane, and this distance is called as margin. So if you draw a dotted line along these support vectors, if you measure this distance, this is called as a margin, and this margin should be as long as possible. Okay, so this margin distance should be greater, and we have discussed why it should be a greater distance in the previous video, right, in our math video. So if you haven't watched those videos, you should watch that. Okay, so we have a hyperplane, and then we have a support vector, and the distance is called as margin. So this is the example of a linearly separable data where we can separate the data using a straight line. In the case of non-linearly separable data, we use something called as kernels. So we have also discussed about this kernels in the previous video. Now once we create the support vector machine classifier that can separate these two data points, when we give a new data point, if we see this visually, we can say that this green colored data point, new data point, lies among this data point. So we can say that it belongs to this type of data, not this one. So this is how support vector machine classifier works. It tries to find among which groups of data does the new data falls in, and using that it can classify the data point as whether class 1 or class 2. So this is how a simple support vector machine classifier works. So we have already seen the math behind this. So if we call this x1 minus x2 as our margin distance, so these are the equations of our line. So this blue color line represents our hyperplane, and this is the equation of our hyperplane, where w is our weight and b is the bias. So these two are the parameters of our support vector machine classifier, and these two are the equations of this margin lines. Okay, so this green color equation is the equation of this green color margin, and this is the equation of this red color margin. So this is the margin distance. So we have already seen that this margin distance can be calculated using this particular value, which is 2 divided by norm of w. So this is your margin. So we have discussed how we get this particular value. So we try to in order to find this distance, we will try to subtract these two equations. So this green colored equation and red colored equation. So we have discussed that in our math video, right? So our goal is to maximize this margin distance so that our support vector machine classifier can create a clear segregation between the two types of data. So that's the idea. When you have a larger margin, then the data are clearly separable. So that's the reason, and this margin should be as great as possible. So this y I cap is the label predicted by your model. Okay, so we will give the label as either 1 or -1, where if the value you find from this w transpose x1 plus b is if it is -1, it comes under one group. If it is +1, it is in the other group. So we are basically trying to classify the data points, and when you substitute the value of x and you multiply it with weight and add it with bias, you will get some value, and this value can be anything. It's not like it should be either -1 or +1. So it is not the case. It can be any value. So if it is generally less than -1, we will take the label as -1. If it is greater than +1, then we will take the label as 1. So it is just like label encoding. Okay, so you will get any values, but we will try to see whether it is a negative value or positive values, and -1 and 1 are your labels. Okay, so this is the math behind it. So we need to increase this margin so that we can get a prediction like this, whether it belongs to the class 1 where the label is -1 or the class 2 where the label is +1. So we have seen all these things before, right? And there is another type of aspect to this support vector machine. So you can see this two types of structures here, two types of diagrams here. So this is both are examples of the support vector machine classifier. The only difference is that there is no data points within this margin, right, in the first case, whereas in the second case there are some in this particular margin space there is a red color data point which is a class 1 data point, and in this there is a green color data point. So we call the first type of problem as odd margin, where we will try to create a margin where no errors are there, whereas in this case, if a data point lies here, if a red color data point lies here, the model tend to make some errors. So this is called as a soft margin. So if we always follow odd margin, there is a problem of overfitting. So we will try to give some relaxation for our model where it can make some errors. So these are the errors made by our model. Sometimes even though the it is a green color data point, but if it lies in this region, the model may classify it as red. So there will be a basically a error in this case. So these are example of soft margin where we will try to give some relaxation to our model where it can make some errors. Whereas in the case of hard margin, there should not be any errors. So we face this kind of problems, and this loss function comes into play only in the case of soft margin support vector machine classifier, because hard margin basically means that our model is making 100% accuracy, and we don't need loss function in that case. So we will basically use this loss function in the soft margin cases. So you should remember this aspect as well. Okay, now let's discuss the basic now definition of loss function. Let's try to understand about loss function, and then we can move on to inch loss, which is the specific loss function for support vector machine classifier. Okay, so we have already discussed about this loss function. So this is the definition of it. So loss function basically measures how far an estimated value is from its true value. Okay, so estimated value is nothing but the value predicted by your model. Okay, so when you train your model, let's say that you have trained your model and you are giving a new new input, and you want to predict some value for this new input. So your model will make some prediction. So we will try to find the difference between the estimated value or the predicted value and the true value. So when you do that, and that particular value is called as your loss function. So for any model, the loss function value should be as minimum as possible. This is because low loss function means there is a very small difference between the true value and the predicted value, which basically means our model is making almost accurate predictions, right? If the loss function value is more, it basically means that there is a huge difference between true value and the predicted value. So the loss function value should be minimum. So, and the other important aspect of loss function is that it is very helpful to determine which model performs better and which parameters are better. So this is a very important aspect, which is choosing the parameters. So in order to choose the best parameters for our model, we need this loss function measurement. Because so what we will basically do in gradient descent is that we will try to give some parameter values, parameters in the sense weight and bias value, to our model, and then we will try to check this loss function. If the loss function value is more, then we can say that these are not the optimum parameters, these are not the best parameters of our model. Let's say that we are giving a different parameter value, different weight value and bias value to our model. In that case, if we get a minimum loss function, then we can say that our model is making good predictions. Okay, so that is the importance of loss function. So it is basically used in order to find the difference between estimated value and the true value, and its importance is that it is used to find which parameters are the best, or which parameters are the optimum for our particular problem. Okay, so this is the general loss function that we deal with. So this is called as a squared error loss. So loss is equal to 1 by n summation of n yi minus yi cap. Here yi cap is the value predicted by your model, and yi is the true value. Okay, so y, you can also call this as yi at, and this will be your predicted value, and yi is a true value. So this is called as a squared error loss, and we have used this kind of loss in linear regression problems. And in the case of logistic regression, we used a different form of this loss function called as a cross entropy loss, right? In the case of support vector machine, we won't be using this kind of loss function. We use a loss function called as a inch loss function. So the reason we are using inch loss is that, as I told you before, we want to increase this margin space. So that also plays a very important role. So you need to make good predictions, you need to make accurate prediction, and along with that you should try to maximize your margin distance. So I think you remember, so this is your margin distance, so x1 minus x2, if you remember. So this is your margin distance. So we will try to find whether our model is making accurate prediction, and also we will try to maximize this distance. And whenever there is this margin related case, we will go with inch loss. Okay, so now let's discuss about what is meant by this inch loss and how this is useful. So I'll also explain you how you can calculate this inch loss when it comes to a support vector machine classifier. Okay, so inch loss is one of the types of loss function, as I've told you, and it is mainly used for maximum margin classification model. So support vector machine is actually a classification model. We know that it is a classifier. So it is used in regression as well, but we are mainly focusing on classification, right? So maximum margin classification. So we know that this margin value should be very large, right? So that the SPM classifier can segregate the data points clearly. So we are focusing on increasing this margin space, and this is where inch loss will be very useful for us. And now let's try to understand about this inch loss. So inch loss incorporates a margin or a distance from the classification boundary into the loss calculation. So even if new observations are classified correctly, then they can incur a penalty if the margin from the decision boundary is not large enough. So let's try to understand these two statements. First of all, we need to understand the statement classification boundary. So the classification is boundary is nothing but your hyperplane. So your hyperplane is the one which classifies the data points, right? It tries to see on which side of the hyperplane the data point lands. So the classification boundary is nothing but your hyperplane. So this inch loss, this kind of loss function incorporates a margin. So margin is nothing but the distance between the two margin lines, which we have seen before, right? So it incorporates that value as well, the margin distance as well, for this loss calculation. So even if new observations are classified correctly, so even though you make correct predictions, your model, so what this inch loss will try to do is, even though the predictions are correct, it will try to find the distance between the particular data point and the hyperplane. So it will try to find whether the data point is close to the margin or not. So it is basically telling us that so let's consider this. Let's say that there is a green color point somewhere, and it will try to find whether it is a green colored or a red colored point. So even though it is correct, it will try to find this distance from this hyperplane. So once it finds it, it can tell whether the margin distance is more or not. So that is the important aspect of it. Okay, so even though the predictions are correct, it needs to see whether the margin is high or not. So that is given in the second aspect. So inch loss basically takes two details into account. One is whether the data points are classified correctly, and the second point is whether the margin distance is high or not. Okay, so let's try to understand this. So this is the equation of a inch loss function, and this is the diagram. So I'll explain you what this diagram represents. So first of all, let's try to understand this formula. Okay, so this is how inch loss is generally represented. So loss L basically represents inch loss here. So inch loss is equal to maximum of 0 comma 1 minus yi of w transpose xi plus b. Okay, so this w transpose xi plus b is nothing but your y cap, your predicted value. Okay, so you have this y cap, right, or y at. So I'll just go here. So this is your y at. So this is nothing but the value predicted by your model. So this value will be either -1 or 0. If it is a negative value, it will be taken as -1. If it is a positive value, we will take it as +1, right? So this is your predicted value, and the value for this y is nothing but w transpose into x plus b. Okay, so that's what we have written here. So this basically means 0 comma 1 minus yi. So yi is your true value. So true values, it can be either 1 or -1. So which is nothing but the two types of classes that we have. Okay, and this w transpose xi plus b is your yi at, which is your predicted value. Okay, so and now we need to understand when should we use 0 and when should we use 1. Okay, so basically when your model makes correct classification, when it makes correct prediction, you will take the value as 0. So you will take this value as 0, and you will minus this particular value, so yi, which is true value into predicted value. So this is basically nothing but 0 minus true value into predicted value. So when you make correct classifications, when you make wrong classification, this equation becomes 1 minus yi into yi at. Okay, so 0 should be considered when the model make correct predictions, and 1 should be considered when you make wrong classification. So the basically idea here is that When you make a wrong prediction, your loss function value will be I. When you make a correct prediction, your loss function value will be 0, which is minimum. Okay, so this basically tells us that when you make a wrong prediction, the loss function value will be I, and when you make a correct prediction, your loss function value will be small. So that is what is represented by 0 and 1. So we will consider in these cases. So 0 for correct classification and 1 for wrong classification. I'll also substitute some values and explain you how this works. So now let's try to understand this. This will make a more sense to you. So we are taking the distance from the boundary here. So we have the margin boundary, right? So this is the distance from the boundary, and in the y-axis we are taking the penalty. Penalty is nothing but your loss value, your inch loss value. So here, so all the points in your right side represents correctly classified points, and all those in the left side represents incorrectly classified points. And we are basically trying to plot the inch loss versus the distance from boundary. Okay, so if you just come here, you can see this line represents your inch loss value. So when you make an incorrect prediction and distance bound from the boundary is high, you will have a very high inch loss. When you make a good prediction, when you make a correct prediction, so correctly classified means your data point is classified correctly. So even though you have correctly classified in this particular region, so you can see this region from here to here, we have some inch loss. So this basically means that even though you make a correct prediction, the distance from the boundary is very small in this region, right? So this is the zero distance from the boundary. Okay, so in this particular region, the distance from the boundary is very small. This basically means the margin is very small. So in that case, you will have some inch loss function. Whenever your loss function is minimum, then we can say that our model is predicting correctly. So if you see the values after this point, your model is making correct prediction, and also the distance from the boundary is kind of increasing, right? So this is the positive x-axis, and in this region the distance from the boundary increases. So this basically means the model is predicting the values correctly, and also the data points lies at a greater distance from the boundary. So that is what is mentioned here. So even if new observations are classified correctly, they can incur a penalty if the margin from the distance boundary is not large enough. So you can consider the data point from this point, the 0 point and this dotted line. So this is what represented here. So all the data points in this region are classified correctly, but they don't have a higher margin distance. So that's why they have some inch loss here. So if you see this flat line, this basically means is it has almost a 0 inch loss. Okay, because they are at a greater distance from the boundary. When you make an incorrectly classified data point, when the data point is classified incorrectly, in that case you will obviously have a higher loss function, right? So this is what you need to understand. So whenever you make a wrong classification, the inch loss will be high, and whenever you make correct classification with a high distance from the boundary, your inch loss will be very low. So but even though you make correct classification, and if the distance from the boundary is small, then you are going to have some inch loss. So that is what we need to understand here. Now let's try to understand how this value turns out. So we will give some values for our yi and yi cap, and we will try to find this loss function with this inch loss function value. Okay, so let's do that. So we know that this is the formula for the inch loss, right? So 0 comma 1 minus yi into w transpose xi plus b. So this is basically your predicted value. So this value can be 1 minus 1 minus 2 minus 3, any values, right? So this yi can be only two values. It is 1 or minus 1. So yi is nothing but your true labels. Okay, and we know that we will take this 0 and 1. We will take 0 for correctly classified data points and 1 for wrongly classified data points. So let's take two cases: misclassification, correct classification. In this case, the model is not making accurate predictions, it is making some wrong classification. Let's say that we know that yi is the true value and yi cap is the predicted value, right? So let's say that the true class to which the data point belongs to is 1. So the true label is 1, but let's say that our model is predicting the value as minus 1. So this basically is a wrong classification, right? So you can also see this. So when the true value is minus 1, the model is predicting the class as plus 1. So this is basically a misclassification. So if our model is predicting correctly, both the values should be same. So the y cap value should be the same as yi value, but it is not this in this particular case. So we can call this as misclassification. And let's try to plug in the values in this loss function formula. So we know that this w transpose xi plus b is basically your yi cap, right? So I'm going to substitute the values here. So this is misclassification. So the classification is it is making wrong classification. So we will take this value as 1 and not 0. So 0 should be taken for correct classification, and hence we are taking 1. So I'm taking 1 minus yi into yi cap. So 1 minus 1 is my yi value and my I cap value is minus 1. So if you substitute it, you will get 1 minus 1 into minus 1. So this minus into minus is plus. So the loss function value is 2, which is a higher loss value. So if you come to this particular example, you will get the values the same too, because it's the true value is minus 1 but the model is predicting plus 1, right? And this is a wrong classification, hence the first term becomes 1. So 1 minus minus 1 into 1, so this is also basically 2, which is a I loss value. Now let's see this for correct classification. So yi is my true value and my true value is 1 and yi cap is the predicted value, and it's basically the same as this yi. So my model is making correct classification, right? So this is also the same. So if the true value is minus 1, the model is also making correct prediction, which is minus 1. So in that case, the first term will have the value 0 and not 1. So 1 should be taken for misclassification and 0 should be taken for correct classification. We know that. So we will take the first term value as 0 and not 1. Okay, so this will be basically like this. So now we are substituting the same. So 0 minus yi is my 1 and yi cap is also 1. So 1 into 1. So you will get 0 minus 1. So minus 1. So we know that minus 1 is a very small number, right? Whereas a plus 2 is a large number. So this basically has a higher loss value, and whenever you are making a correct classification, you are getting a low loss value like minus 1. You can do the same in this case also. So this is basically 0 minus minus 1 into minus 1. So minus 1 is plus 1, and so here there is another minus, so you will basically get 0 minus 1, and again the loss function value is minus 1, which is a low loss value. So the idea behind this is, when your model is making misclassification, you will have a larger loss value, and when your model is making correct classification, you will have a low loss value. Okay, so this holds true for that margin distance as well. So you can also try the different values in this case. So as I've told you, even if it makes correct classification, it also takes into account the distance from the boundary. Okay, so you can just basically give some values, like instead of minus 1, you can give values like minus 3, minus 2, and so on. So in that case, your value will be highly negative, a large negative number, which basically means the loss function is further smaller. So whenever your distance from the boundary is larger, in that case you will get a very minimum loss function. Okay, so that's what you need to understand. So if you make a correct classification, and let's say that the value, so the true value is minus 1, and let's say that the value predicted by our model is minus 0.25 or something like that. So in that case, you won't have a very small loss function value, you will have a slightly bigger loss function value than this. Okay, so this is what you need to understand about Inge loss. So when we are making correct classifications, we will have a minimum loss function, and for misclassification we have a high loss value. And the main and important thing is that even though it makes correct classification, the distance from the boundary should be large. Okay, so this is the important takeaway from this video, and I hope everyone is sure about this, and everyone clearly understood all the things covered in this video. And in the next video, we will be discussing about how we can use gradient descent for support vector machine. And once we done that, we can move on to the hands-on part, where we can build this support vector machine classifier from scratch in Python. This 7th module is all about building machine learning models from scratch. In my previous videos, I have explained you what is the intuition and math behind a support vector machine classifier, and we have also discussed about the loss function for a SVM classifier. So in today's video, we are going to discuss what is the gradient descent for support vector machine classifier, and what are the different formulas that we have for gradients for a SVM classifier. So this will be the agenda for today's video. So I will be giving you a quick recap of what we have discussed about support vector machine and so far, and after that we can go in detail about this gradient descent and what are the gradients formula for support vector machine. Okay, so let's get started. So we have already discussed that a support vector machine model is used in both classification as well as regression problems, but it is predominantly used in a classification problem, and that too a binary classification problem, where the model will try to classify the data points into two groups. If you see this diagram, we have two kinds of data points. So one group of data points is represented as blue colored circles, and the other group of data points is represented as red colored squares. So if you use a support vector machine classifier, it will try to classify these data points into groups as we have. So how it basically works is, it will try to create a hyperplane. So you can see this black colored line here. So this line is called as hyperplane, and this hyperplane separates these two types of data points. Okay, and there is another important term that we have in support vector machine classifiers, and that is support vectors. So you can see this data points. So these two blue colored circles and these three red colored squares. So these are the data points which lie closer to this hyperplane, and these are called as the support vectors. So the data points in a data set that lies closer to the hyperplane are called as support vectors, and if the position of this support vector changes, the position of the hyperplane also changes. So the position of the hyperplane basically depends upon the position of the support vectors. Okay, and if you draw a dotted line along these support vectors in both sides, this particular region is called as the margin, and your hyperplane lies exactly in the middle of this margin. Okay, so these three are the important terms when it comes to a SVM classifier, and this margin should be as long as possible. So if you have a greater margin distance, that means your hyperplane can correctly segregate the data points. So it can clearly define some segregation between the data points. If the margin distance is low, then it means that the hyperplane does not know a clear distinction between these two data points. So we always try to increase this margin space. Okay, so that's one of the main thing about support vector machine classifier. So once we train this SVM classifier, if you give a new data point, it will try to see in which side of the hyperplane the new data point is coming. So once it realizes it, it can classify whether that point belongs to the first group of data points or the second group of data points. So we have discussed how the SVM classifier mathematically finds this in our mathematical intuition videos. I hope you have watched that one. So if you haven't watched those videos, you should surely check out that. So I'll give the link for those videos in this particular video description, so check that out. So this is how a support vector machine classifier can find among which groups a new data point lies. Okay, so this is the basic intuition of a SVM classifier, and mathematically, so these are the important formulas that we have. So let's say that we have two groups of data points here. So one group of data points is represented as red colored circles, and then the other group is green colored circles, and these are the equations of the lines that we have. So this blue colored line is our hyperplane, and this is the equation of our line, where W and B is our parameters of this line. So W is basically the weight and B is the bias. So these two are the model parameters. So the parameters of our SVM classifier, and this is nothing but this is similar to the equation of a line, which is y is equal to mx plus c. Okay, and these two are the equations of this margin lines. So if you take this distance x1 minus x2, so this is your margin distance, and if you want to find this distance, you can easily subtract this green colored equation and red colored equation. So when you do that, you can find this particular distance, and this distance is given by this factor. Okay, so we will basically try to increase this margin size. So 2 divided by norm of W is what is the margin distance. So I have explained you how we derived this particular formula or function in my mathematical intuition video. So this is our margin distance. So we always try to maximize this margin distance, so there is a clear distinction or clear segregation between the two groups of data that we have. Okay, and this yi cap is our label. So here the label will be either -1 or +1. So if the model tries to multiply the input factor with our weight and bias, so it basically tries to multiply it with weight and add some bias to it, and it will try to find the value, whether the value is greater than -1 or it is whether the value is less than -1 or it is greater than +1. So these are the two possibilities. If the value is less than -1, in that case we take the label value as -1, and if the value is +1, and the label value will be +1. So these are the two labels that we have. So the model will try to find this label value, and this is how it segregates these two data points. Okay, so these are the two groups of data points that we have. So this is how this is the mathematical intuition of a SVM classifier, and also we have discussed about the loss function, right? So we know that the loss function for a SVM is an inch loss. So inch loss is given by this particular equation. So I have explained this in my previous video. So basically it is represented as maximum of 0,1 minus yi of W transpose xi plus b. So this W transpose xi plus b is nothing but your yi cap. So the label that you are predicting. Okay, so we have already discussed about this definitions and all in my previous video. I'll just explain you about this particular formula. So we take the value, first term value as 0 when the model makes correct classification. If the model makes wrong classification, the value will be 1. So these are the two values which we should choose from for this first term. So if the model makes correct prediction, the value is 0. If it makes wrong prediction, the value is 1, and then we will subtract this term from this value, either 0 or 1. So basically what we get is, if the model make wrong prediction, then the loss function value will be higher. If the model makes correct prediction, then the loss function value will be minimum. So we basically will try to minimize our loss function value. So a low loss function value basically tells you that your model is making almost correct predictions. Okay, so we have discussed about this graph and all these definitions in my previous video. I don't want to go into that again. So this is the inch loss. So this loss function is very important for us in order to build our gradient descent algorithm. Okay, so now let's discuss about the gradient descent that we have. So when we build a gradient descent, we will try to plot between the cost function and the weight and bias of the model. Okay, so basically the loss function is when you compare the true value and the predicted value of one particular data point. So we will try to find that difference, and that difference is your loss function. So that is what basically loss function means. So we will try to compare the value of the true value and the estimated value. So what is the difference between them? So when you do that for the entire data points, so let's say that we have 500 data points. If you try to find the true value and the predicted value for all these 500 data points separately, then each of this value is called as loss function. When you try to find that particular difference for the entire data set, so the true value and the predicted value for this entire data set, and you take a score, and that will be your cost function. So the cost function is basically the average of all the loss function for all the data points that you have. Okay, so cost function is the parameter that we need in order to build this gradient descent. So here we will take cost function in our y-axis and weight in our x-axis. So these are the two axes that we have. So the idea of gradient descent is to find the best parameters. So here the parameters are nothing but weight and bias. So how we do that is, so basically if you have a minimum cost function, that means your true value is close to your predicted value. So that means your model is making almost accurate prediction. If your cost function is I, that means there is a huge difference between the true value and the value predicted by your model. So our ultimate goal is to reduce this cost function. Okay, and how we will do that is, we will try to change the value of weight and bias. So we will try to change the value of these parameters, and at each step we will try to find the cost function. Okay, so we will initially or we will randomly initialize some value for our weight. Okay, so let's say this is a random initial value for our weight, and for this particular weight value, let's say that the cost function at this point, so this means the cost function is I, right? Because this point lies in the top region of this cost function y-axis. So we can say that here in this case the cost function is very high. So we need to reach to this particular point. So at this point, if you just come to the corresponding y-axis value, it will be very less, right? So at this point the cost function value is very minimum. So this point is called as your global minimum point. So if you take the weight value at this global minimum, you will get a minimum cost function. Okay, so we need to reach to this point from this point. So we will randomly initialize some value for our weight, and we will constantly change this weight value in order to minimize this cost function. So this is the idea behind the gradient descent, and gradient descent is one of the most important optimization algorithms we have in machine learning. Okay, so we have discussed a lot of times about gradient descent. I hope you are very thorough with gradient descent as of now. Okay, so we will try to regularly change this weight value, and we will try to minimize this cost function at each step. So this is how gradient descent works. It will try to add some change to our weight value and bias value so that the cost function changes. So this is the basic working of a gradient descent. And how this gradient descent does this is basically by using derivatives. So it will try to differentiate the cost function with respect to weight and bias, and this is how it can minimize this cost function. Okay, so this is the mathematical aspect of gradient descent. And this, when you plot this cost function and weight, you will get a curve like this, a u-shaped curve like this, or you can call this as a convex curve. Okay, so the idea is to, like, wherever you are at initially, so initially you may have a higher weight value. In that case it might be at this point. So wherever you start at this curve, you have to reach this global minimum. Okay, so that's the idea of gradient descent. So no matter what is the weight value, it will end up at this particular global minimum. Okay, so here we have plotted for cost function and weight. Okay, so it is a two-dimensional structure, and if you do this for both weight and bias, so we know that the two parameters that we have for SVM classifier is the weight and bias. And if you try to change both this weight and bias value and compare it with this cost function, you will get a three-shaped curve like this. So this is just a representation. So we basically try to change the weight value and bias value repeatedly so that we get a minimum cost function. So we will if a particular weight value and bias value as a minimum cost function, so that will be our global minimum, and that will be our optimum parameters. Okay, so our goal is to get this optimum parameters values. Okay, so this is how the definition for gradient descent looks like, and this is the formula for gradient descent. Let's try to understand this. Gradient descent is an optimization algorithm used for minimizing the cost function in various machine learning algorithms. It is used for updating the parameters of the learning model. So we have already used this gradient descent in our linear regression and as well as our logistic regression. Now we will be using this in our SVM classifier. Okay, so it is an optimization algorithm. Optimization in the sense it will try to improve the efficiency or the accuracy of our SVM classifier model. And how does it does is by basically updating your parameters of the learning model. Parameters is nothing but your weight value and your bias value. So this is how the formula for gradient descent looks like. So W2 is your updated weight, new weight, and W1 is the previous weight. So updated weight is equal to previous weight minus learning rate into djw by db. So let's try to understand what does all these terms mean. So basically W is your weight and B is your bias, we know that, and L is your learning rate. So learning rate is nothing but how much change do you want to give to your weight and bias. Okay, so I'll just go to my previous slide. So we know that we will randomly initialize this weight value, right, and we will change our weight value. So this is our changed weight value, right. So learning rate is nothing but how much change do you want to give to your weight or bias. Okay, so it is basically the magnitude of change that we are giving to our parameters. So we will try to give some change to your weight regularly, right. So this is your learning rate value. So that is represented by this L, and dj by dw is the partial derivative of cost function with respect to with respect to weight. So that is given by this dj by dw, and dj by db is partial derivative of cost function with respect to b. So what does this basically say is, so dj by dw represents how much your cost function changes when your weight changes. Okay, so that is represented by this term, and dj by db basically represents how much your cost function changes when you change your bias. Okay, so if you come to this graph again, so we are changing the weight value, right. So the weight value changes from this point to this point. So this is the change in the weight, and for that you will try to find what is the change in the cost function. So this particular part, so we will try to find that value. So for change of weight for this magnitude, the change of cost function is this. So we will try to take the derivative of this, and that is represented by dj by dw. And if we do that in terms of bias, it is called as dj by db. So this is the partial derivative of cost function with respect to w and with b. So this formula for gradient descent won't change. So only the formula for dj by dw only. So this is called as gradient. So you can call this as either gradients or derivatives. Okay, so this gradients value changes for different models. So we need to understand what is the formula for this, and this is the formula for updating the weight. So as I've told you before, W2 is your updated weight, W1 is your previous weight, and B2 is your updated bias, and B1 is your previous bias. Okay, so this is the formula for updating the weights, and these two are dj by dw and dj by db are your gradients formula. Okay, and let's now try to understand what is the formula for these two terms. So when we think about gradients for SVM classifier, there are two conditions. So first condition says if yi into wx plus b is greater than or equal to 1. So we know that w is our weight, x is our input feature, okay, and b is your bias. So in our data set we have input feature, or we can say this as the column. So we have multiple columns in our data set, right. So this will be our input feature. So we will try to find this value and we will multiply it with this yi. So yi is nothing but your label. If this value is greater than 1, we have different formulas. If or else in other condition where the value is less than 1, in that case we have different formulas for our derivatives. Okay, so these are the two formulas. So when we have this kind of a condition, we get the dj by dw value as 2 lambda w, and your dj by db value will be basically 0. When this condition is not satisfied, we have the other condition. So in this case the formula will be dj by dw is equal to 2 lambda w minus yi xi, and dj by db is equal to yi. So this is the formula that you get. So how you basically get this formula is, we need to differentiate this particular. So this is our Inge loss, right. So we need to differentiate this particular equation, particular formula in terms of weight, and then with in terms of bias. So that's what we have to do, and when you do that, you will get the formula like this. Okay, so this so we don't have to go in detail about the derivations and all, so that's not required right now, but we need this formulas alone. Okay, so these are the two conditions that we have, and the formula in each condition. And once we find these formulas, we will be using this in our updating weight formulas. So you will substitute this particular formula in this, and when you do that, you can find the optimum parameters. So these are this is how the gradient descent works for a support vector machine classifier, and these are the formula for your gradients when it comes to a support vector machine classifier. Okay, so in my next video, let's try to build this support vector machine classifier from scratch in Python. So in that case, we will be using all these formulas. So all this updating the weight formulas and all the gradient formulas and all, we may use a different form of this particular formulas. We may not use the same format, we may use the different formulas. So let's discuss about that in later, but this is the theoretical aspect of these gradients, and this is how the formula looks like. Okay, so actually I have to explain one more thing. So we have a new variable called as this lambda, right? So this lambda is basically called as lambda parameter, and the real name for this lambda parameter is the regularization parameter. So what this regularization parameter basically does is it will try to give some importance to the misclassified data points. Let's say that we have trained our SVM classifier, and our support vector machine classifier sometimes can make mistakes, it can make wrong classifications. Okay, so we know that it classifies between two groups, right? So it may make some misclassification, and this regularization parameter will try to give some importance to our misclassification. So the final goal that we want, or the final objective that we want with our SVM classifier, is that we should have a maximum margin and we should have a minimum misclassifications. Okay, so we know that the margin distance should be greater when it comes to SVM classifier, and we should not make any misclassification. So that is given by this regularization parameter, which is represented by lambda, and this is why this lambda comes into play when we use a gradient descent formula. Okay, so that is the importance of this. And when we build our model, we will manually give some value. So we will give some value for our learning rate as well. So for learning rate as well as this lambda parameter, we can manually assign some values. So that is all about this gradients formula, and I hope everyone is clear up to this point. If you don't understand how we arrive at this formulas and all, it's not a problem. So in my next video, let's understand in detail about how we can build this from scratch in Python. In the 7th module of our hands-on machine learning course, and this 7th module is all about building machine learning models from scratch. So in my previous videos, I've explained you what is the intuition and math behind a support vector machine model, and how you can reduce the gradient descent for a support vector machine model. And in today's video, we are going to discuss how we can build a support vector machine classifier model from scratch in Python. So this is the agenda for today's video, and in case you haven't watched the previous videos on SPM, I suggest you that you watch all those videos. I'll give the link for those videos in this particular video description. You can check that out. So let's get started with today's video. So I have given the equation of the hyperplane here. So we know that the main component of a SVM classifier is the hyperplane. So we will try to build this hyperplane that separates the data points into two groups, and this is the equation of the hyperplane. So y is equal to wx minus b, where w is the weight of our model and b is the bias of our model, and x is our input feature and y is the label that we are going to predict. Okay, so this equation is similar to the equation of a straight line. So our goal when we use a machine learning model is that we will try to build this equation, build this function in Python. So once we do that, we need to find the best values for our weight and bias. So the process of finding this best value or optimum value for weight and bias, which are the parameters of the model, is called as optimization. And for this optimization purpose, we will be using an algorithm called as gradient descent. So we have discussed about this gradient descent a lot in our previous videos, and I hope that you are clear about what is this gradient descent and how this gradient descent works. So I have given the definition for gradient descent here. Gradient descent is an optimization algorithm used for minimizing the loss function in various machine learning algorithms. It is used for updating the parameters of the learning model. So this is the definition of this. So as I've mentioned here, it is an optimization algorithm. Optimization in the sense we will try to optimize this support vector machine classifier so that we can get better predictions. Okay, so optimized model in the sense our model should have the best parameters value, that is the best values for weight and bias. Okay, so what we will basically do is we will randomly initiate some value for weight and bias, and we will check how well our model is performing. So we will compare the values predicted by our model with the true values, and we will see how many errors our model is making. So based on that information, we will try to optimize our model using gradient descent. So how we will do that is we will try to find the loss function for different weight value and bias value. So if for a particular weight value and bias value the loss function is minimum, then we can say that our model is making accurate prediction. So our goal is that we have to minimize this loss function in every step. So we will randomly initialize some value, and we will reiterate or we will make the model to go through the data again and again, and this process is called as reiteration. So in each step we will try to change the value of weight and bias, and we will try to find the loss function value. So this is how gradient descent basically works, and by doing this you will get the optimized or the best values for your parameters, and this is the formula for updating your weight and bias. So the first equation is used in order to update your weight value, and the second equation represented here is used to update your bias value. And you can read this formula here. So w is equal to w minus alpha into dw, where w is the w in this left hand side is your updated weight, and w in this right hand side is your previous weight. And you can see this alpha, so alpha is your learning rate. So learning rate is nothing but how much change do you want to give to your weight or bias. Okay, so as I've told you, in each step we will change this weight value and bias value, and this learning rate is like the magnitude of change you want to give to your weight and bias. And the dw is dw and db are the derivatives. So we have already discussed about all these things. Okay, so I'm just giving you a quick recap of all those things before getting started. So dw is the dw and db are the derivatives, and we have separate formulas for dw and db as well. So I'll just show you here. So we have discussed all these things in my previous video. So these are called as the gradients. So we have a condition here. So this, if this condition is satisfied, we take this as our dw value and this as our db value. If this condition is not satisfied, then we will take this particular function or formula as our dw and this as our db values. And this is the same formula in order to update your weight and bias. So we have discussed all these things. Okay, and here I have given the definition of a learning rate. So learning rate is a tuning parameter in an optimization algorithm that determines the step size. Step size is nothing but how much change do you want to give to your parameters. Okay, so at each iteration we're moving towards a minimum of a loss function. As I've told you, our goal is to minimize this loss function. So minimum loss function means the value predicted by your model is close to the true value. So that means you have a minimum loss function, which means that your model is making accurate prediction, which is what we want. Okay, so our goal is to minimize this loss function, and for this we implement this gradient descent algorithm. Okay, so this is how we are going to build this SVM classifier. So first of all, we will try to build this hyperplane equation, and then we will try to build the gradient descent equation. Okay, so let's get started. And the first step that we are going to do is import the NumPy library. So this is the only library we will be using in order to build this algorithm or this SVM classifier. So I'll make a text here as importing the dependencies. So let me make a text here as importing NumPy library. So let's import NumPy as np. So most of you, would be having experience working on NumPy library. For those who haven't heard about this, so NumPy library is used in order to make arrays. So we call this arrays as NumPy arrays, and we are importing this NumPy library in the short form as np. Okay, and now let's build our SVM classifier. I'll make another text here as support vector machine classifier. Okay, so you can see the equation of this SVM classifier. So in my previous videos I have we took the bias value as positive, but in some cases we take this bias value as negative. So I'll explain you that. So let's say that we have two cases. So this is the first case. So we have two kind of data points here. So the green colored circles represent one type of data and the red color circles represent another kind of data. So in this case you can this distance is called as our bias value. As you can see here, this is in the negative side of this x1 axis, and in this case the bias will be negative if we have a hyperplane like this. So in this case this is another hyperplane, another data set. In this case the bias value is positive because it is towards the positive side of the x1 axis. So we will generally take the bias value as negative. So that's why we are taking bias values as negative, because like this is the equation we generally use. Okay, so we have to write this equation, this y is equal to wx minus b equation. So we need to build all this weights, bias and all those things, and after that we will build this gradient descent. Okay, where we will try to include all these formulas in our code. So let's see how we can do that. So how we will create our SVM classifier is that we will create a class. So let's name this class as SVM underscore classifier. Okay, so SVM classifier. So you need to mention parentheses here. So first of all, we need to understand what is meant by this class. So this class in Python is generally used for creating objects. So here we are creating an object called as SVM classifier, and class is used to create a template for this particular object. Let's say that we want to build a car. So this car, you can consider this particular car as an object, and before building this car, you need a template for this, right? So whatever the object or whatever the machine you are building, you need a template for this, and you can consider this template as the class. So we are creating an SPM classifier, and we need to give some template or prototype to this object, and we will include all those template in this class. So this is the importance of class, okay, in Python. So within this class, we can mention different functions. So first of all, let's try to create the skeleton for this SVM classifier. Okay, so skeleton in the sense we are going to see what are the functions that we are going to need. So the first function that I'm going to create is the init function. So this init function is basically used to declare some parameter values, hyperparameters. So we have seen this learning rate, right? So learning rate is one of the hyperparameters for our model. And then we have other hyperparameters like number of iterations and so on. So we will use this init function in order to create this hyperparameters. So I'll explain you in a minute what is meant by this hyperparameter. Just hang in there, okay? And the next function that we are going to create is our fit function. So I'm creating a fit function, and the third function that we need is define. So def, this def stands for define, and this is the keyword in Python in order to create functions, okay? And each of this define represents each function. So totally we need a fourth function for this SVM classifier, and the third function will be update weights function. Update weights. And the last function that we will need is the predict function. So define predict. So these are the four functions that we have, and let's try to understand what is the purpose of all these four functions. First, we have this init function. So init stands for initiation. So first of all, we will try to initiate some parameters for our model, and after that, we have fit function. So in this particular fit function, we will try to fit the data set to our model. Okay. So once we complete this SPM code, what we will do is we will use the code in order to find whether a person has diabetes or not. So we have already worked on this diabetes data set. So it contains multiple columns, and finally we have this outcome column here. So this outcome column is your target column, where if the value is 1, that means a person has diabetes. If the value is 0, that means the person does not have diabetes. Okay, and all the other columns, so all the columns except this output column, are called as the input features. So you can consider all these columns as from A to H. So you can consider all these columns as your x-axis value, and your I column as your y-axis value. So it is just like taking the x-axis value and y-axis value and fitting it to a line. So that is the purpose of this fit function. So we will create a function so that we can fit our SPM classifier to the data set that we have. In this case, the data set that we have is this diabetes data. So you can use any data set. So in this case, we are going to consider this data set, and now we will build this fit function where we can feed the data set to this particular function. Once we do that, it will try to fit the data set to the SPM classifier that we are building. Okay, so that is the purpose of this fit function. And then we have the update weights function. So as I've already told you, we will randomly initiate the weight value and bias value, and after that we need to reiterate over the data. So the model goes through the data again and again, and in each step we will try to update the weight value and bias value. Update in the sense we will try to change the weight value and bias value by a certain magnitude. So that is done by this update weights function. And finally we have this predict function. So the reason for having this predict function is that once you train your model, if you give new values, let's say that we are giving all the values from this A to H, pregnancies, glucose level, and so on up to this age column, our model should predict whether that person has diabetes or not. So it should give the value as either 1 or 0, 1 being a person with diabetes and 0 being a person without diabetes. So our model has to predict the outcome, right? And we need this predict function in order to find that output. So these are the four functions that we need. So the first function is for initiating parameters, second function is for fitting the dataset to our model, third function, which is update weights, is used for updating the weight and bias through gradient descent, and finally the predict function is used for predicting the target column. Okay, in this case whether the person has diabetes or not. So it can be any data set of your choice. Okay, so these are the functions that we have, and I'll just make some comments here so that it's clear for you. Okay, so this function is used for initiating the hyperparameters. So the hyperparameters that we have are learning rate and number of iterations. So let's come to that later. So I'll just make another comment here. As this is for fitting the data set to SVM classifier. So this is one of the important functions that we need. And then we have the update weights function, which is used to function for updating the weights or the weight and bias value. Okay. So this is where we will use all these equations. So the equations and the formulas we have. So we will use this gradient equation and updating weight functions in this particular part. Okay. So in this update weights, and finally we have this predict function, and the purpose of this predict function is to predict the label. Okay. So the label being 1 or 0. So predict the label for given input value. Okay, so input value will be all those things. So except this output column, we will give all other values, and our model will predict what is the output, whether it is 1 or 0, which is basically a person with or without diabetes. Okay, so these are the 4 functions that we need. So we have the skeleton ready, and now we can complete each of this function separately. So in this case, we are going to have 3 parameters. Okay, so we will be creating our learning rate, number of iterations, and lambda parameter. Okay. So before that, we need to give an inbuilt parameter in all this case, which is called as self. Okay, so you can include this self in all the functions that we have. Self and predict is also self. So the reason we have this self is that, so let's say that we are implementing this SVM classifier. Let us say that we have completed this SVM classifier, and now we want to use it in order to train a particular data set. So in that case, what we will do is, so I will create a variable like model. So in this model, I will call this SVM classifier class. So I will write this as SVM classifier. Okay, and I'll mention my parentheses there, and within this I will give some parameters. Okay, and this is called as instance. So this model is called as the instance of this SVM classifier, and this self takes the value of this instance. So this self basically means the term model. Okay, so whenever we are implementing this SVM classifier, once we complete this class, we will call an instance of this model, and this instance is represented as self within this particular class. So when we use a model from sklearn, also we will try to create an instance of some model. So in sklearn, you have different models like logistic regression, linear regression, support vector machine, etc. So when we are calling those models, those like machine learning models, we will create some instance, and this instance is represented as self within this class. Okay, so that is the importance of having this self parameter in all the functions. So it is like one of the inbuilt things that we have to do. Now we need to mention the parameters that we want to declare. So there are 3 parameters in this case, and they are learning rate, number of iterations, and the third is the lambda parameter. Okay, so these are the 3 parameters that we need. So let's try to understand this. So learning rate is nothing but the amount of change you want to impart to your weight and bias. So as I have explained it before, so we have the definition for it also. And then we have the number of iterations. So number of iteration basically tells you how many times you want your model to go through the data. So we will be giving the number of iterations value as 100 or 1000 or 10,000. So basically, like if you give the value of number of iterations as 1000, so what that means is your model will go through the data 1000 different times, and each time it goes through the data set, it will try to change the weight value and bias value. So that is represented by this number of iterations, and we have discussed about this lambda parameter in our previous video. So you can see this lambda value here. So this is called as the regularization parameter. Okay, so I have explained you the importance of this lambda parameter in my previous video, so I don't want to go through it again and again. Okay, so these are the 3 parameters that we have, and we give the learning rate value as 0.01 or 0.001 and so on, and lambda parameter will also be like a 0.01 and so on. So you can manually tweak all these values and see how your model is performing. Okay, and you can give number of iterations as 100,000 or 10,000, any number you want. Okay, so these are the hyperparameters that we have, which you can manually give. So these three parameters are called as hyperparameters, and weight and bias, this W and B, are called as your model parameters, because these are the parameters of your model. So these are internal parameters, but these parameters work beyond the model or outside the model. So we manually give this value, but we cannot manually give the values for weight and bias. Hence, these are called as the model parameters, and these are called as the hyperparameters. Okay. So now we need to initiate all these parameters. So how we will do that is by mentioning self dot learning rate. So self dot learning rate is equal to learning rate, and self dot number of iterations. I'll explain you what happens here exactly. So just a minute. So self dot number of iterations is equal to, again, number of iterations, and self dot lambda parameter, which is basically the regularization parameter, is equal to lambda parameter. So lambda is a keyword in Python, so it represents another function. So we cannot write only lambda. So hence I'm naming this as lambda parameter. Okay, so lambda parameter. So this is how you can initiate the hyperparameters. So what basically happens here is when we call this SVM classifier. So as I've told you, let's say that we have completed this SVM classifier, and now I want to call this. So I'll create an instance as model, and I will write model is equal to SVM classifier, which is basically the name of the class that we have created. So SVM classifier. And within this parenthesis, we need to give all these three parameters. The parameters are learning rate, number of iterations, and lambda parameter. So I will write all those things. So I'll just copy all those things from here. So what we will do is, so while calling this in this parameter, we need to give the learning rate value. Let's say that the learning rate value is 0.001, and let's say that the number of iterations, so the number of times we want our model to go through the data set is 1000. So the model will go through the data 1000 times, and the lambda parameter is, it can be 0.01 or any number. So we will give all those values. So model is equal to SVM classifier, and these are the parameters. So you can see here self dot learning rate. As I've told you, this self is nothing but the instance of your model. In this case, the instance is nothing but this variable called as model, right? Now, when you mention self dot learning rate, what it basically means is model dot learning rate, which is equal to 0.001, and self dot number of iterations is nothing but model dot number of iterations, which is given by this 1000, and finally self dot lambda parameter is model dot lambda parameter, which value is 0.01. So that's what we are doing here. So we need to initiate this parameter like this, and we will give all those values while we are calling this model, while we are implementing this model. Okay, so this is how we will do it. Now we can go on to the next function, and this next function is a fit function, right? And the purpose of this fit function is to fit our dataset to our SVM classifier. So for that we need two variables, so self dot m and self dot n. Self dot n is equal to x dot shape. So before that, we need to give two parameters in this fit function. So the two parameters are x and y. So self is the parameter which we give as an inbuilt function. So self, and then we have x and y. So x is nothing but all the input features. So all the input features are from a to h. Okay. And so this represents your x-axis value, or basically the x value, and your outcome column represents your y value. So we need to mention x and y. So when we call this fit function, we will feed this data set, this x and y data set, to our model, and that's why we need to mention x and y in our fit function. Okay, so now we need to understand what is meant by this m and n. So your m basically represents the total number of data points that you have, and n represents the total number of input features that you have. Okay, so let me mention that in some comments here. So m is your number of data points in your data set. Okay, so number of data points, and you can also call this as number of rows. And now let's try to understand what is our n. So I'll just copy this and I'll paste this here, and this will be your n. So let's try to understand what is this n value. So n value is basically the number of input features that you have So number of input features, and in other words, it is nothing but your number of columns. So let's try to understand this. So we have a data set here, right? So we have taken a sample data set here and it contains some amount of data. Now let's try to find how many rows are there. So this particular data set contains about, I think it contains around 700 data points. So yeah, it contains about 769 data points. So what basically it means is we totally have 769 rows, and each row represent the data for each individual. Okay, so this means this is the data from 769 different people, and we call all these rows as individual data points. Okay, so that is represented by your value m. Okay, so m basically is your number of data points or your number of rows, and n is the number of columns that we have. Okay, so we don't take this output column. So excluding this outcome column or the target column, how many columns that you have? So totally we have, so totally we have 8 columns, right? So all these 8 columns is your number of input features. So totally we have number of 8 input features, and the total number of input features is n. Okay, so in other words, you can say these are the number of columns. So the reason we want to find this is, so we have already discussed about this weight, right? So number of weight that you have in a particular model is equal to the total number of input features that you have. So in this case, you totally have 8 input features, right? So don't consider this outcome column. This is target column. This is different. This is y value, right? So your number of weight value. So if you have 8 different input features, so in this case you have 8 different weight values for your model. So in case, let's say that you have 20 input features or 20 different columns, in that case your model have 20 different weight values. So basically weight is like an array. Okay, so this particular, so weight is an array, and this array contains the number of values, which is equal to the total number of input features that you have. So it is basically equal to the number of columns that you have in your data set. Okay, so that is the importance of finding this number of columns in a data set. So m represents the total number of rows, and n represents the total number of columns. And the reason for finding this n is we need to know how many weight values are there. Okay, so that's why we are finding this particular n value. So you can find this by x dot shape. So x dot shape is nothing but what is the shape of your x. So if you consider this, so this is our x, right? So it will the shape of this particular x will be 769 into 8, where 769 represents the total number of rows, and 8 represents the number of columns, a to h. Okay, so that is what we will get from this x dot shape. So this x dot shape will give you an output of 769 into 8, and m will take the value as 769 and n will take the value as 8. Okay, so that is what we are basically doing. We are trying to find the number of data points and the total number of input features that you have. Now the next step that we are going to do is we need to initiate the weight value and bias value. So initiating the weight value and bias value. So as I've told you earlier, first we will give some random value for our weight and bias. So what value we will generally give us, we will just give the value as 0. So we will do that using the same method. So I'll mention self dot w. Okay, this basically represents model dot w is equal to np dot zeros. So this is why we need the numpy array. Okay, so just a second. Yeah, so np dot zeros. So and the shape of this array should be self dot n. So what we are basically doing here is I'm initiating the value of this w, which is my weight value, and I'm creating it as a numpy array, because we know that weight is basically an array, and the number of values in this array is equal to the total number of input features, which is n. So that's why we are mentioning this self dot n. So I want to create a numpy array, and all the values inside this numpy array should be 0. So that's why I'm mentioning np dot 0. So np dot zeros is a function that will create you a numpy array, and all the values will be 0 in this numpy array, and the shape of this particular array is n. Okay, so as I've told you, this basically means it will try to find how many columns are there in a data set, and based on that value it will create as many weight values, and all the values will be 0. So that this is how we will initiate weight value, and then we need to initiate the bias value. So self dot b, so b is our bias value, and we will just give the bias value as 0. So the one main thing you need to note here is weight is generally an array. Okay, so it contains multiple values, whereas bias is a single value, is it is like a single real number value, whereas weight is an array. So that's why we are initiating the bias value as just 0, but we are initiating the weight value as a numpy array because it is basically an array. Okay, and then we need to mention this x and y. So self dot x is equal to x, and self dot y is equal to y. So x is nothing but all these 8 columns from a to h, and y is our outcome column. Okay, so we will feed this data set to our model in a later part of the code. So this is how you can initiate weight and bias value, and this is how you can represent this x and y value. So x is all my input features and y is my output column. So once we initiated all these values, now what we need to do is build our gradient descent algorithm. As I've told you, so we need to build this equation, and after that we need to find the optimum values for weight and bias, right? So first we will initiate the value. So in this case, we are initiating with the value 0, numpy dot zeros, and for bias we are just taking 0. So after that we are going to build this gradient descent. So what we will do is we will take this initial value and we will try to make some prediction, and this gradient descent we'll try to compare the loss function for different weight value and bias value. Okay, so if you remember, we have discussed this in the previous case. Okay, so I'll just take this particular slide. So let's take this cost function. So cost function and loss function are not something very different. So if you take the difference between the true value and the predicted value for one single data point, that is called as the loss function, and if you do that for the entire data set, it is called as cost function. So that is the difference between it. Okay, so we have the cost function in the y-axis and weight in the x-axis. Let's say that we are initiating some random weight value. So in our code, we have initiated the random value as 0, right? So this is our random initial value, and let's say that for this particular weight value we have an higher cost function. Okay, and this is the point. So this point is called as global minimum, and at this point, if you consider the weight value at this particular point, your cost function value will be minimum. So you can just take the corresponding y-axis value. So it is very minimum, right, compared to this particular value where the cost function value is minimum, and our goal is to minimize this cost function. So we will try to change the weight value regularly until we reach this global minimum. Okay, so that's what we are doing here. So we will take a random initial value and we will implement this gradient descent in order to reach that global minimum where the loss function or the cost function value is minimum, and that's what we are going to do here now. So I'll create a text here as implementing gradient descent algorithm. Gradient descent algorithm for optimization. So optimization in the sense we are going to find the optimized value for our weight and bias. Okay. So for this we need to create a for loop. So let's create a for loop as for I in range number of iterations. So we need to mention it as self dot number of iterations. Okay, so basically what this means is, as I have told you before, we need to give some number of iterations for our model. So in this example, we took the number of iterations as 1000, right? So it means your model will go through the data 1000 times, and each time it will try to impart some change to this weight value and bias value. So that's what we are going to do in this particular for loop. So when I mention this number of iterations, so this value will be 1000 in this case. So you can give any values, 1000, 2000, or anything. So your for loop will run 1000 times, and each time it will try to update your weight value and bias value, and that's what we are going to do now. So I'm going to call this self dot update weights function. Okay, so update weights function. So this update weight function is what we are going to build now. So first of all, I'm trying to initiate the hyperparameters like learning rate, number of iterations, and I'm also initiating the lambda parameter, which is my regularization parameter. So after that, I'm creating a fit function in order to fit my x and y to my svm classifier, and I'm trying to find the m and n value, where m is the number of data points and n is the number of columns that we have, and then we are initiating weight value as a numpy dot zeros. which is basically a numpy array with all the values as 0 and bias value as 0. After that, we are implementing the gradient descent, where we are creating a for loop with the number of iterations mentioned by the user. And within this for loop, we need to update weight. So what we are doing is we are updating the weight each time the for loop is running. In other words, each time the model goes through the data, it will try to change the weight value and bias value so that we get accurate predictions from our model. Okay, so that's what we are doing here. And now we can come to our update weights function. Okay, so we have created this update weight function, and now we need to build this update weights function. So the first thing I am going to do here is y label. I'm going to create a variable called as y label, and this label is equal to np.var self dot y less than or equal to 0. I'll explain you in a minute what we are basically doing here. -1 comma +1. So you can just call this part as, label encoding. So I'll call this as label encoding. So we know that we have the y-axis value. Your y-axis value is nothing but your outcome column or target column, where 1 represents a person with diabetes and 0 represents a person without diabetes, right? So this is the label we generally deal with in machine learning. We take the label values as either 0 or 1, right? But if you remember the things we have discussed in my previous videos, support vector machine will try to find whether the label is +1 or -1. Okay, so if you come to this particular slide, so what we will basically try to do is we will try to find this y cap value. Y cap value is nothing but your label value, and this label value will be either 1 or -1. If the value is +1, then we can say that a new data point lies, or the new data points belong to this group of data. Or else if the label value is -1, we can say that the new data point lies to this green colored group of data. Okay, so generally support vector machine works like that, whereas in the case of logistic regression, we take the label values as 0 or 1, right? And it is the general way of having label values in any data set, so it's either 1 or 0. But support vector machine, we will give the label values as +1 or -1, because it is the convenient way for it. So you will basically get some negative value or positive value. Let's say that you are getting the label value as -1, so then it will try to say that it belongs to this group of data, this green color group. And if the value is +1, it will tell that it belongs to this group of data. So we need to do that label encoding. So what I'm doing here is, if the label value is 0, I want to convert all the values to -1. Okay, if the label, or else in other case the label value will be 1. Okay, so that's what we are mentioning here. So I'm trying to look at the y-axis value, and what I'm telling here is, if the value is 1, you don't need to give any change. If the value is 0, you need to convert it to -1, so that we can have convenient labels for our SVM classifier, because 0 and 1 does not work well with SVM. So we need +1 or -1 for our SVM, and that's why we are using this np.var. So what this np.var function basically tells us, it will try to find this condition. So in this condition, the condition here is y should be less than or equal to 0. So if y is equal to 0, then we can say that we want to convert all those values by -1, or else the value can be +1. Okay, so that's what we are doing here. We are basically label encoding. So we are converting all the zeros as -1, and all the +1 will stay as +1. Okay, and now we are going to create another for loop, and this for loop is for index comma xi in enumerate self.x. Okay, so let's try to understand what is what we are trying to accomplish in another for loop. So for our gradients, we have two set of formulas, right? So I have showed you already. So we have discussed about this in our previous videos. So we have a condition. So this condition has to be satisfied. So yi into wxi minus b. If this value is greater than or equal to 1, we take these two formulas for our gradients. Or else, if this condition is not satisfied, which is the condition given here, so in that case, the formula will change slightly. So this will be the formula for my dw, and this will be the formula for my db. So we have a condition, and we have two sets of formula, and now we need to include this condition. So yi basically means the individual yi values, which is either 1 or 0. Okay, and xi represents individual rows. So we have to take this individual label value either 1 or 0, and now we have to take this individual row value, and now we need to multiply it with the weight and subtract it with the bias value, and then we need to multiply it with the yi value. If that particular value is greater than or equal to 1, then we have this formula, or else on the other condition we have this formula. Okay, and this is what now we are going to do this in this particular for loop. So I'll explain you what does this enumerate function does, but I'll just complete this next line of code. So this is for carrying out my condition. So my condition is that is equal to y label. Okay, so y label of index. So y label of index is nothing but your yi. Okay, so this yi is what I am representing as y dash label. So y underscore label is nothing but this value. So if you remember, like I've taken all these values and I've converted all the zeros into -1, and +1 stays as +1, right? So this is my y underscore label. The only difference is that all the zeros will be converted to -1. So that is my y label. So it contains all the label values, and I'm taking all the values individually because my condition wants all the individual label values. So yi, right? So that is what I am doing. So y label index into, so we need to multiply it with np dot dot. So this is just like a dot product of w and x. So xi and self dot w. So self dot w, which is the product of my weight and my xi value, minus self dot b, and this should be greater than or equal to 1. So this is my condition. So this line is nothing but the condition that I have explained you here. So I have taken this condition and I have represented it here in Python. Okay, so condition is equal to y underscore label index. So I'm taking all the individual labels and I'm taking the corresponding xi value. So xi is nothing but all the input features, and here we are multiplying xi and w, and then we are separating by the bias value, right? So that's what we are doing here. So we are taking the numpy dot. So this is like a matrix product. So xi comma self dot w minus self dot b. So it is just the same equation, and this should be greater than or equal to 1. Okay, so what we are basically doing is, in this case, so let's come to our data set. Let's say that we have this sixth column. So in this case, what I will do is I will take the yi value. So this is my yi value now. So the yi value is 1, and this y underscore label index will take the value as 1. Okay, and I'll take the xi value. So xi values in this case is all these 8 values. So I will take all these values and I will multiply all this xi value with my self dot w, subtract it with my self dot b, and then I will multiply it with y underscore label index, which is the value is 1. We know that, right? And I will check whether that value is greater than or equal to 1. So this is my condition. So now the reason we are using this enumerate function is, so enumerate is an interesting function that we have in Python. So let's try to understand what does this enumerate function does. So I'll explain to you in a simple way. So I'll create another cell. In this case, let's create a list as my list. So we are creating a list here basically, and let's say that this list contains the values like 10, 20, 30, 40, and 50. Okay, so these are the 5 values in my list. Just a second. Okay, so now what I'm going to do is, for I'll name this as, I don't want to interpret this interrupt this particular code. So I'll name this as for I comma my list I in enumerate my list. So the reason I'm just doing this is in order to explain you the importance of this enumerate function with this for loop. Okay, and I want to print I and my list. So enumerate is basically like a counter. It will count how many times a particular operation is carried out on a list. So I'll run this. Let's see what are the values that we are getting. Okay. So just a second. I just wanted to change one thing. So for I comma my list I in enumerate. Okay. So my list I, just a small change. Now let's try to understand what this enumerate does. So we are creating two variables for this particular for loop. One is I and the second is my list I. Okay, so what I want to do is I want to take this list and then I want to print the index of the number and its particular value. So the index of this 10 is 0, the index of this value is 1, this is 2, and so on. So we know that in Python indexing starts from 0, right? So the first value will have the index as 0, the next value is 1 and 2 and so on. So now I want to get the index value as well as the particular element value. So if you see here, the index of this value 10 is 0, and for 20 the index is 1, for 30 index is 2 and so on. So I want to take both index value and the element value, and you can do that by this particular enumerate function. So if you do that, this particular I, the first variable, will get the index of the values, and the my list I will get the corresponding element value 10. So that's what we are doing here in this particular case. So I'm creating two variables here. So I'm creating the first variable as index and the second variable as xi. Okay, so when I do this, what happens is, let's say that I have this x. So I'll just remove this for some time. So this is my x now, right? So when I carry out this for loop along with the enumerate, so what happens is, first of all, it will go through this. It will try to find the index of this particular data point, and it will try to take all this value. So all this values is nothing but xi, and the corresponding index will be 0. So as we have seen here, so when you run this for loop will go through the entire data set. So it will go through all the rows, and it will try to get the index of the particular row and all the values in that row. So this index basically will take the value of that index, and xi will be all the 8 values for individual rows. Okay, so that's what we are trying to do here. And in order to find that index as well as the value, we use this enumerate function. So it is not, I think there is a spelling mistake here, so we need enumerate. Okay, so this is the function we need. So it basically gives you the index as well as the element of that. So enumerate actually works as a counter. So it is not like it gives the index of the value, but it is just like a counter. But we can use it in this case as well in order to get the index as well as the element. Okay, so the reason I want to get all the xi values individually is that I want the y label value and the xi label value, right? So I want to take, so if you come to this formula, so we have this yi. So yi is nothing but all the individual y values, and xi is nothing but all the individual x values. So I will take all this x value, and then I will take the outcome value, right? So outcome value will be either 1 or -1. So I need to do that. So for that particular reason, and I'm finding the index of a particular row, and then I'm finding the xi of that particular row, and I'm doing this particular condition. Okay, so once we satisfy this condition, we can build our gradients formula. Okay, so we have the if condition here, right? So if this condition is satisfied, if this condition is true, I want this particular formula for my gradient. So that's what I'm going to do now. So if you don't understand few things, don't worry. So once I complete the code, I'll just give you a quick recap of how things happen here, and in that case you can understand everything completely. Just wait for all the things to complete. So now I'm going to create a if condition. So if condition is equal to true, so this basically means if this particular condition is satisfied. So I'm taking the same variable condition. If this condition is satisfied, then I want the gradients formula to be, or the derivatives formula to be, so you can call them as both. So they are nothing but gradients or the derivatives. So these are nothing but my dj divided by dw. So this is nothing but how much your cost function values change if your weight changes. So dj by db represents how much your cost function changes when your bias change. So that is the importance of these two values. So here the formula is 2 into lambda into weight, right? So we need to write that. So let dw be our gradient for weight, and dw is equal to 2 into self dot learning parameter. It's lambda parameter. Okay, so it's lambda parameter into self dot w. So this is nothing but my this particular formula. So dj by dw, which I have represented just as dw, is equal to 2 into lambda into w. So that's what I have written here, 2 into self dot lambda parameter into w, and my db value is just 0, right? So you can see the formula here. So dj by db is equal to 0. So if this condition is not satisfied, we need this particular formula. Okay, now let's include that formula as well. So if the condition is satisfied, we have this particular equations, and if this condition is not satisfied, which is represented by else we have dw is equal to 2 into self dot lambda parameter and into self dot w minus np dot xi comma y label index. Okay, and your db value will be y label index. Okay, so this is nothing but the formula that we have if the condition is not satisfied. So dj by dw in this case is 2 into lambda into w minus yi into xi, and dj by db is yi. Okay, so I'll just make a text here as, or else a comment as gradients. Okay, so this part of the code is to build the gradient. So I'll just mention this as gradient. So gradients are nothing but your dw value and the db value, which we need for our gradient and descent model. Okay, so we have dw and db value, right? So we can find this value by this particular formulas. So we have two set of formulas for dw and db. So if the condition is satisfied, this particular condition is satisfied, we take this formulas, and if this condition is not satisfied, we will take this particular formula. And the reason we are running this in enumerate is we will take all the data points individually. So we will take the y underscore label. So we take the label values and the corresponding xi, which is the input features value, and then we will try to find this condition is satisfied or not. So if this condition is satisfied, we have these two formulas for dw and db. If this condition is not satisfied, we will take the formulas as dw and db. Okay, so now once we have this, we need to build these two formulas. So we have this is the final gradient descent formulas for updating the weight and bias value. Okay, so now we need to write these two formulas. Now all the things are very easy from now on. Okay, so these are basic things. So I will just come out of this iteration. So make sure that you are not in the sales iterations. So it should be in this particular line. So self dot w is equal to self dot w minus self dot learning rate. So whenever you are mentioning the parameters within this class, you need to mention self. So that is the importance of it. So self dot learning rate into dw, and for updating the bias, it's the same. So self dot b is equal to self dot b minus self dot learning rate into db. Okay, so just a second. So this is the formula for updating our weight and bias value. So this is our gradient descent. So w is equal to w minus learning rate into dw, and the dw value is given by these two equations. Okay, and now we finally completed our gradient descent, and now we can write the function for predict. Okay, so for this I'm going to create a variable called as output. So now what happens is, once this gradient descent is completed, you will get the best weight value and your best bias value. Okay, so we get optimized values for our weight and bias. Now you have this equation y is equal to wx minus b. So initially we took the values for w as numpy zeros and b as a single zero number, right? So and after that we will run our gradient descent in order to find the best value for weight and bias. Now we have the best value for weight and bias, and now if you give the xi value, your model can predict the y value, whether the value is -1 or +1. So it can make that predictions, and that's what we are going to do in this particular predict function. So output, so we are creating a variable as output, and np dot dot. Okay, so np dot dot x comma self dot w. So we need to mention another parameter here. So predict x. So the reason is, so when you give a new x value, so when you give all this value, your model can predict what is the outcome. So you need to give this x value to this predict function. So that way we need to mention it here. Okay. So x self dot, so self dot w x comma self dot w minus self dot b. So this is nothing but the equation of your hyperplane. Okay, so wx minus b. So that's what we are mentioning here. So as w and x are nothing but arrays, so they are not single numbers. So we need to multiply it using np dot dot. So this is just like matrix multiplication. Okay, so output is equal to np dot dot x comma self dot b minus self dot b, and we have the predicted labels. So the value you will get won't be either +1 or -1. So the value can be anything. So the value you get can be +1, +4, +5, or it can be -3, -6, -1, and so on. So it can be any values. Now we need to round those values. So I'll create another variable as predicted labels, and now I'm going to round all the values. So if we get a negative number, then we will say that that particular value is -1. So I'll just complete this, and then you will understand what I'm doing here. So predicted labels is equal to np dot signs, np dot sign of output. Okay, so what we are doing is, as I've told you, in logistic regression, when we do this predict function, it will output the value as either 0 or 1. So the value will lie between the 0 or 1. But in this case, the value you get using this particular formula won't be either 0 or 1, or it won't be either +1 or -1. So this value can be anything. So it can be any positive number or any negative number. So we need to generalize this. So if it is a negative number, so it can be any negative number. It can be -1, -3, -6, -10, -100, any number, and so on. So if it is a negative number, then we need to say that that value will be -1. If the value, this particular output value is +1, so it can be +1, +5, +10, +100, so on. In that case, we will take the value as +1. So that's what we are doing that by np dot sign. So the reason is that in SVM we are interested in whether that label is positive or negative. If the label we are getting is a positive value, then it is one group of data. If the label we are getting is negative, then it represents another group of data. Okay, so that's what we have mentioned here. So you can refer this particular equation. So yi, so if this value is less than or equal to -1, in that case we will take that as -1. If the value is greater than or equal to +1, we will take that as -1. So it doesn't mean that your label has to be +1 or -1. So it can be any values, but we are interested in whether that value is plus or minus, whether it is a positive number or a negative number, and we can find that using np dot sign. So when you use this np dot sign, it will go through this output value. If it is a positive value, it will output the value as +1. If it is a negative value, it will give the output as -1. Okay, so the final value, so this predicted labels, so this particular array will contain all the values as +1 or -1, whereas output can contain any values. So this particular list can contain any values, but this predicted labels will contain the value as either +1 or -1, because we are just considering the signs. And now we just have only one more thing to do. So that is, if you remember previously, we have converted all the zeros as -1, right? So, and we didn't make any changes for 1, but we have changed all the values of zeros as -1, right? And now we need to revert this particular change. Now we need to take this and we need to change all the -1 back to 0. So that's what we are going to do now. So I'll call this as y at. So this is my final predictions. Okay, so this should contain the values as either 0 or 1, because these are the two true labels that we have. Okay, so y at is equal to np dot where. So I'm just reverting that particular change. Predicted labels, and it should be less than or equal to -1, 0, comma 1. So basically what I'm doing is, if that value is equal to or less than -1, I want to change it to 0, or else it should be 1. So what I'm basically telling here is, so all the values which is -1 should be changed to 0, and all the +1 can stay as +1. So we are just removing this particular change that we have done here, because our original dataset contains the values as either 1 or 0. And if you don't do this, if you don't revert back this change, then your accuracy score won't be working properly. So you don't need the labels to be +1 or -1. So you need the labels to be 0 or 1. So that's what we are doing here. So this is our final step, and finally we can return our y at value. So finally we can return y at. So when you run this predict function, it will try to return you this y at value, which will be either 1 or 0. So this is our entire code. So I mean, I know that you may not understand few things, but I'll just give you a quick recap of all the things that we have done here, and now you can understand all the things that we have done. Okay. So first of all, the idea here is we have the equation of the hyperplane, which is y is equal to wx minus b, right? So that is what we have mentioned in this defined predict. So np dot x comma self dot b. So this is nothing but w into x minus self dot b. Now we need to find what is the best value for our weight and bias, and for this purpose we need to build our gradient descent formula or gradient descent algorithm. And this is the formula for updating our weights, which is w is equal to w minus alpha into dw, where alpha is your learning rate, and the formula is same for bias as well. Now we know the formula for dw and db, right? So the only challenging part is that we have a condition here. So if this particular condition is satisfied, we can take these two formulas. If this condition is not satisfied, then we need to take these two formulas. So that's what we are basically doing here. So first of all, I have imported my NumPy library, the basic thing, and then I'm creating a SVM classifier. So this is my support vector machine classifier model, and I have four functions here. So first is my init function, and then we have our fit function. The third function is our update weights function. Finally, we have predict function. So the purpose of this init function is used to initiate some parameters. So the parameters that we are initiating are learning rate. So learning rate is nothing but what is the amount of change do you want to give to your weight and bias when you are running your gradient descent. And number of iterations is the number of times you want your model to go through the data, and lambda parameter is your regularization parameter. So we have initiated all these parameters here. Self is nothing but the instance we are creating. So in this case, the instance is nothing but model. So there we can give any values for our learning rate, number of iterations, and lambda parameters, and then we have initiated all these parameters. So the second step is fitting our data set to our classifier model. Okay, so we need x value and y value. So the x value will be all the 8 columns, all the input features, and all the y value will be this particular output column. Okay, so this is our second function, and we are trying to find the value for our m and n. So m is nothing but the total number of data points. In other words, it is the total number of rows that we have, and n is the total number of input feature, or in other words, it is nothing but the number of columns. So the importance of n value is that the number of weight values you have for a model is equal to the number of input features that you have. In this case, you have 8 input feature from this pregnancy column to this age column. So totally you will have 8 different weight values. Okay, so this is how we will initiate weight value and bias value. So weight will basically be a numpy array, and we will initiate with all the values as 0 in the shape of n. So n is nothing but the total number of columns, and as I told you, the number of weight is equal to the total number of columns that you have, and bias is nothing but we are initiating with 0. So x is my input feature, y is my label. And once we initiate all these parameters, we need gradient descent in order to optimize our model, in order to find the best value for my weight and bias. For that, I'm creating a for loop, and this for loop runs for the number of iterations we have mentioned. If you have mentioned the number of iterations as 100, it will run for 100 times. If you mention it as 1000, it will run for 1000 times. And each time this for loop runs, it will change the weight value and bias value. And that is done by this update weights function, which is our third function. So now we can come to this third function, and now the interesting thing that we are doing is we are converting the labels. So we are converting all the label value 0. If the label value is 0, we are converting it to -1, and all the +1 will stay as +1. Okay, because the labels are convenient in this way for support vector machine, because it will try to find whether the label value is +1 or -1. So it doesn't care whether it is 1 or 0, but it wants to know whether it is +1 or -1. So that is the next step, and then we are using this enumerate function. So the reason for this is in order to carry out this condition, and I have shown you what is the importance of enumerate. It will take a list, and it will try to give the index of a value and the value. So we have 5 elements here. So if you want to enumerate this list, it will take this first value. So it will give the index of this first value, which is 0, and the value itself, which is 10. Okay, so you will get the index and the corresponding value. So we want the index of the data point and the corresponding xi value. So if you go to this data point, the index of this first row will be 0. Okay, so index value will be 0, and the xi value will be from 6 all the way to this 50. Okay, so this is my index and xi value. And once I have this, I can run this condition. So this condition is nothing but the one which we have mentioned here. So we are creating this condition, and if this condition is satisfied, my dw, my gradient formula is 2 into lambda parameter into self dot w. Okay, if this condition is not satisfied, the dw and db value changes. And once we have that, we can implement this gradient descent, the updating weights and bias value functions, and we have represented it here. So this is nothing but w is equal to w minus learning rate into dw. This is b is equal to b minus learning rate into db. So the gradient descent updating weight formulas. And finally, once all these parts are completed, we will get the optimized weight value and bias value. In other words, your model will get the best weight value and bias value. If you consider this weight value and this bias value, what it means is your model can make accurate predictions. So it basically means there is not much difference between the true value and the predicted value. So that is what is done up to this particular mark. After that, you have this equation now. So you have the optimum value for this w and you have the optimum value for b. And now if you give a new value, if you give a new x value, it will try to find the label and it will be stored in this output. The main thing you need to remember here is this output need not be either +1 or -1. So it can be any values. So it can be any positive values, it can be any negative values, but we are interested in whether that value is either positive or negative, because this is a classification task, right? So this is not a regression task. We want to find whether the person has diabetes or not. So this is a classification task. And for this, I'm going to use this np.science, and it will, if the value is negative, it will output the value as -1. If the value is positive, if the value is 1 or +5 or +6, the output will be, final output will be +1, and all those +1 or -1 will be stored in this predicted label. So this is my labels which contains either +1 or -1. Finally, I have this y at, so I am reverting the change that I have done before. So all the -1 will be changed back to 0, and all the +1 will be the same +1. So that is what is done by this np.var, and this is my final output, final predicted value. Okay, so this y at, so this is y at is nothing but y cap that we generally write in a convention. So this is my final predicted value. So this will be either 1 or 0. So this is my prediction, where 1 being a person with diabetes or without diabetes. So this is how you can build a support vector machine classifier from scratch in Python. So now you can use this particular code, this particular SVM classifier for any data set. So in this case, we have a diabetes data set, right? So in my next video, I'll explain you how you can implement this support vector machine classifier, how you can use this particular code in order to find whether a person has diabetes or not. So you can use any data set in order to find that particular predictions. Okay, so in this case, we will take this particular data set alone. You can also try this with a different data set. So this is how you can build your SVM classifier from scratch in Python, and I hope you're completely thorough with all the things that we have covered here. So if you don't understand few things, you can mention me in the comments, and I'm sure that if you don't get a few things, you will understand it completely in the next video, where we will take this particular dataset and we can see for ourselves how this particular code works. And this seventh module is all about building machine learning models from scratch. In my previous videos, I have explained you how we can build a support vector machine classifier from scratch in Python. And in today's video, we are going to see how we can implement this SVM classifier that we have previously built. Okay, so that is the agenda of today's video, and I'll just give you a quick recap of what we have done in the previous video so you get the hang of it. Okay, so first of all, we are just importing the NumPy library. So this is the only library that we will be using in order to build our SVM classifier, and here we are creating our SVM classifier as an object, and for that we are using a class. So class is basically like a template in order to create an object, and here the object that we are creating is a SVM classifier. Okay, so in this SVM classifier, we are having 4 functions. So the first function that we have is the init function, which stands for initiation, and then the fit function, and the third function is update page function, and finally we have the predict function. So these are the 4 functions that we are building. Okay, so the purpose of this init function is to initiate the parameters such as the learning rate, number of iterations, and lambda parameter. Okay, so learning rate is the amount of change you want to give to your weight and bias. So when we are implementing gradient descent, the model goes through the data multiple times. So it goes through the data again and again, and each time it goes through the data, it will try to impart some change to the weight and bias of our model. So weight and bias are nothing but the parameters of our model, where W is our weight and B is our bias. Okay, so we will initiate that learning rate. So it is nothing but the amount of change you want to give to your weight and bias. And now we have the number of iterations. So number of iterations is the number of times you want your model to go through the data. If you set your number of iterations to 100, it means your model will go through the data 100 times. If it is 1000, it means the model goes through the data 1000 different times, and we will give these values while we are implementing the SVM classifier. Okay, and then we have the lambda parameter, which is called as the regularization parameter, and I've explained about this in our gradient descent for SVM classifier video, so you can refer that one. So these are the three parameters that we are initiating in this init function. So this is the first step of our SVM classifier model. And then we have the fit function. So this is the most important function that we need. So the purpose of this fit function is to fit the data set that we have to our SVM classifier. Okay, so here X represents the input feature and Y represents the target that we are going to predict. So as we know that this is a classifier model, it will try to classify the data points into two groups. So here the target can be, it will be either 1 or 0. So 1 represents one group and 0 represents another group, and X is our input features. So in this case, we are going to take the diabetes data set for the prediction. And if you see this data set, so there are totally 9 columns. Okay, so out of these 9 columns, the last column is the outcome. So 1 represents people with diabetes and 0 represents non-diabetic people. So this is our target column, and the remaining 8 columns from this A to H, all these 8 columns are called as the input features. So these 8 columns will be considered as X, and this last outcome column will be considered as RY. So we need to give this X and Y separately to our fit function in order to fit our SVM classifier to this data set. So that is the purpose of this fit function, and we try to find the M and N. So M is nothing but the total number of data points that we have in our data set, and N represents the total number of columns that we have. So columns of the X. Okay, so we don't consider this particular Y column. So excluding this Y column, we have to find how many input features are there. So these 8 columns are called as the input features, and that is represented by N. So in other words, you can say that M is the total number of rows you have, or the total number of data points, and N represents the total number of columns that you have. So you can find that by using this X dot shape. So X is nothing but all these 8 columns, as I've told you before. Okay, so all these 8 columns, and we need to find the shape of this X. So shape of this X is nothing but the total number of rows that we have and the total number of columns that we have. So this particular data set contains about 769 rows. Okay, so you can see here, so 769 rows, which means 769 different people. So each row represents the data from each individual person, and so totally we have about the data from 769 different people, and totally we have about 8 columns. So X shape will be about 769 into 8. So M will take the value 769, which is the total number of data points. In other words, it is the total number of rows, and N is the number of input feature, or the number of columns, which is 8. So it will be 769 into 8. So the reason we are finding M and N is that the total number of weights you have in your model is equal to the total number of input features that you have. So in this case, in this diabetes dataset, we totally have 8 input features, or we can say 8 columns. So you will have totally 8 different weight values. So basically, weight will be an array which contains 8 different values, and bias is a single value. So you can consider weight W as an array, whereas bias is a single number. So we will initiate the values. So the next step is initiating our weight and bias. So we are initiating it. So we are initiating weight as a numpy array with all the values as 0, and the shape of this numpy array is N. So N is nothing but the total number of input features, and then we are initiating the bias value with 0, and we are just representing our X and Y, where X is the number, where X is our input feature and Y is our target, which has either 1 or 0. And now we are going to implement this gradient descent. So what we are basically doing here is we are randomly initiating some weight and bias, and when we implement gradient descent, the purpose of gradient descent is to find the optimum parameter values, the optimized value for W and B. Okay, so that is the purpose we are using this gradient descent, and the gradient descent will try to see for which weight and bias value the loss function value or the cost function value is minimum. So that is the goal of this gradient descent, and for this we have some formulas. So this is the formula for updating the gradient descent, weight and bias using gradient descent. And so W is equal to W minus alpha into dW, where alpha is your learning rate, which we will give to our model, and the dW and dB represents the gradients. You can call them as gradients or derivatives, and we have also separate formulas for dW and dB, and we have discussed them. So that is our next step, where we are implementing this gradient descent within this for loop. So in this for loop we are giving the number of iterations. So as I've told you before, if you give 100 number of iterations, that means your gradient descent uses it to go through the data 100 different times. So your model will go through the data 100 times, and each time it goes through the data, it will update your weights. Update the weights in the sense, it will try to change your weight value and bias value, so that you can get accurate prediction, and which in turn give you a minimum loss function and cost function. So that's what happening in this particular for loop, and we have to now build the function for this update weight, and that is our third function. So we are defining the update weights function, and the interesting thing that we are doing here is we are encoding our label. So we know that the labels are in the form of 1 and 0, where 1 represents people with diabetes and 0 represents people without diabetes, right? But in SVM, the model try to find whether the output is either +1 or -1. So it is convenient for us to have the labels as +1 and -1. So what we are basically doing here is we are converting all the values of 0 as -1. Okay, so that is the next step. So all the 1 will stay as 1. So that is the thing which we are doing in this particular line of code. And then we are building our gradients. So gradients is nothing but the dw and db. So these are nothing but dw is a differentiating cost function with respect to weight, and db is differentiating cost function with respect to bias. And then we have a condition, so we have to satisfy this condition. So if this condition is satisfied, then we have to use these two formulas. If this condition is not satisfied, we have to use this formula. So we have two set of formulas. So if the condition is satisfied, if the condition is true, we have to use this one. If the condition is not true, we have to use this one. So we have discussed all about this in our gradient descent video. So what are these formulas for dw and db and so on. So this is our dw and db, and finally we can use it in our gradient descent formula. So the updating weights formula that I have written here. So w is equal to w minus alpha into dw, and b is equal to b minus alpha into db. So that's what written in these two lines. Okay, so yeah, so these two lines where we are trying to update our weights and bias each time the model goes through the data. And finally we have this predict function. So the purpose of this predict function is, let's say that we have trained our support vector machine classifier, and when you give some data, let's say that we are giving this particular data. So we know that this is our x, right? So these are our x, input features. So if you give these data alone, it can predict whether the label is either 1 or 0. Okay, so it can tell you whether that person is diabetic or not. So this is the reason of building this predict function, where it will try to predict the value of y, whether the output is either 1 or 0 from the value of x. Okay, because now we have the optimum value of weight and bias, and then we just substitute those values in this particular equation, and we will try to find the value of y. So the final output can be any number. So it can be -3, -4, -5, or it can be +1, 3, 4, any number, so on. So the main thing that we are interested in is, as it is a classification problem, we will try to see whether the outcome, the final output, is a positive value or negative value. So we need to find whether the outcome that we are finding here is a positive value or negative value, and for that we use this np.sign. So numpy.sign function, which will give you -1 if your output is a negative number, and it will give you +1 if your output is a positive number. So because we just need to find whether it is a positive or negative. So that is the next step, and the final step is that we are going to convert this -1 to 0. So the reason is that if you remember, previously we have converted all the labels, right? So we have converted all the labels from 0 to -1. So we need to revert this change. So we need to change that back to how it was previously. Then only we can do some evaluation on our model. So we have to get the data in this structure. So the labels will be -1 and +1 in this predicted labels. So we are using this np.sign, right? So all the values will be in the form of +1 and -1, and now we need to convert all the values of -1 to 0. So that's what we are doing it. So all the +1 will stay as +1. So we are just reverting back the change that we have did in the first place. So that is our last step. So y at is our final outcome. So it will contain the values as either 1 or 0, where 1 being it can be a person with diabetes and 0 can be a person without diabetes, and finally we return this particular value. So I have made a small error in the previous videos. I have mentioned a parenthesis here, so this parenthesis should not come here. So that's one of the error I made in the last video, so you can just remove that. I have made that change in my Google Colab file, so it won't be there, but just take note of it. So there should not be this parenthesis here. Okay, so this is how we can build our SPM SVM classifier, and now we are going to use this diabetes dataset in order to make predictions. So we will use this dataset to train our SVM classifier, and once we train this model, we will try to predict whether a person has diabetes or not. So that is the agenda that we are going to carry out in this case, and this is basically the same procedure that we have done for our diabetes prediction project. So if you have seen my machine learning projects playlist, we have already worked on the diabetes prediction project, but in that case we have used the support vector machine classifier that is available in sklearn library, which is ready-madely available. And in this case we are going to use the SVM classifier that we have built by our own. Okay, so if you have already watched that particular video, you can skip to the last part of implementation, or else you can watch this complete video if you haven't watched that. Okay, so it will be almost the same thing except for the final implementation. So if you have already watched that, please skip to the last part, or if you haven't watched that video, or you want to have a revision, or you want to if you wanted to see this again to get a better understanding, you can watch this video completely. Okay, so now we can move on to the implementation part. So the first step is we need to import some dependencies for our data processing and predictions. So I'll just make a text here as importing the dependencies. Dependencies is nothing but the libraries that we need, and the first library I'm going to import is pandas. So we have already imported numpy library, so we don't need that now. So I'll import pandas. So import pandas as pd. So the use of this numpy library is that it is used to create numpy arrays. So sometimes we will be working on arrays, so that is the reason we are importing numpy array, and we need pandas library for its data frame. So this panda library is basically used to create data frames, and data frames are nothing but structured tables. So the data set that we have is in the form of a CSV file. So you can see a diabetes.csv. So it is not easy to do some analysis and processing from the CSV file. So we will load the data from the CSV file to a pandas data frame, and that's why we need this pandas library. So this is the second library that we need, and then I'll import from sklearn.preprocessing import standard scaler. So we need the standard scaler function in order to standardize the data that we have. So the data that we have in a data set is in a different ranges. So totally we have 8 columns, and each column will have values in different ranges, and it is better to standardize all those values. So that is the reason we are using this standard scaler function. So this all comes under the data pre-processing part. And then I'll import my sklearn dot model selection. From this I'm going to import my train test split function. So the use of this train test split function is that it will split your data set into training data and test data. So we will usually train our machine learning model with the training data, and we will evaluate our model with the test data, and your train test split function will automatically split the data set that you have. So you don't need to do that manually. And finally I'm going to import my accuracy score from sklearn.metrics. Import accuracy score. So this is used to evaluate our model. In other words, it is helpful to find how many correct predictions our model is making and how many wrong predictions the model is making. Okay, so the next step is data collection and analysis. So I'll just make a text here as data collection and processing. So you can find this diabetes dataset in Kaggle. It is also available in sklearn's library. I'll also give the link for this dataset file in this video description. You can download it from here. So you can, if you are new to Collaboratory, just go to this files and you can upload your dataset from here. Okay, so you can give this upload to session storage, or just right click here, you will find this upload option, and through that you can upload your dataset file. So this is a pretty small file. So this is diabetes.csv, and we will be working on this particular file now. So the next thing I'm going to do is I'm going to load the data from the CSV file to the pandas data frame. So I'll just mention this here, loading the data from CSV file to pandas data frame. Okay, so that is our next step, and I'll name this data set as diabetes data. Okay, diabetes data is equal to, we are going to use pd.readCSV function. So PD represents pandas, as we have imported pandas in the short form as PD, and read CSV function will read the CSV file and it load it to a pandas data frame. Okay, so we need to mention a single quote here. So within this quotes we need to paste the location of this file. So you can find this option symbol here. So from there, copy the path of this dataset file. Okay, so your path will be copied and you need to paste it here. So you can press shift plus enter to run this cell and go to the next one. Okay, so this will load the data from the CSV file and it will create a new data frame called as diabetes data. Okay, and now let's try to get the look of this data. So now we are going to print the sample of this data set. So what I'm going to do is print the first 5 rows. So these are the basic things that we do with all the data set in order to get some idea about how the data set looks like, what are the different values that we have. Okay, so we are going to print the first 5 rows of the data frame. So here the data frame is nothing but diabetes data, so we have named it like that. So I have to mention the name of the data set, which is diabetes data dot add. So this add function will give you the first 5 rows that you have in your data frame. So these are the different the 5 rows that we have. So we have different columns like pregnancies, glucose, blood pressure, skin thickness, insulin, BMI, diabetes pedigree value, age, outcome, etc. Okay, so these are the different columns that we have, and the name of this data set is PIMA diabetes data set. Okay, so you can also search for it. So these are the 5 columns that you have. So you can also look at this values and see what are the different ranges the values are present. And now we are going to check how many number of rows and columns that we have in our data set. So this step will be finding the number of rows and columns. So we need to do all this before feeding the data set to our model. Okay, so in this data set, so number of rows and column, how you can find that is mention diabetes data, the data frame name dot shape. So here you shouldn't mention the parenthesis. So it will give you the total number of rows you have and the columns you have. So the first number represents the total number of rows and the second number represents the total number of columns. Okay, so we have 769 rows, which means 769 different data points or the data from 768 different people, and finally we have 8 different columns. So these are 9 columns. So these are the 9 columns that we have, and the final column is a target column, outcome. So here 1 represents people with diabetes and 0 represents people without diabetes. Okay, and we can also do some analysis here. So the next step will be to get the statistical measures of the data. Getting the statistical measures. So I'm just going through this fastly because we have already discussed about this. I don't want to waste much time here. So diabetes data dot describe. So this describe function will give us some important statistical measures of our data set. Okay, so you can see, so we have all the columns here, and the first value we have is the count. So how many values we have in each column, and the mean. So what is the mean value of this entire column? So we have mean value for all the different columns. So what is the standard deviation, what is the minimum value, what is the 25th percentile, 50th percentile, and 75th percentile value, and maximum value. So these are some statistical measures you can get using this describe function. And I'll do one thing here. So diabetes data outcome dot value counts. So here we are going to see how many 0 values are there and how many 1 values are there. Okay, so value counts. So I'm taking this outcome column and I'm counting how many values are there. So totally we have 500 values for the value 0, that is people without diabetes, and 1 for the label 1 there are about 268 different people. So this is the data distribution in the outcome column. Okay, so I'll just mention a text here as, so 0 represents people without diabetes. Okay, so we can call this as non-diabetic people, non-diabetic, and let's say that 1 represents diabetic. Okay, so this is our next step. Now what we can do is, so now we are going to separate our features and target. So we know that the first 8 columns are input feature and final columns are target column. So input feature in the sense, so once you train your model, if you give all this input feature, you can find the final outcome column. So that's the idea. So we are going to split the first 8 columns and we will separate this target column. So that is the next step, and I'll just make a text here as I'll just make a comment. Let's not make a text. So I'll just write a comment here as separating the features and targets. So target is our outcome column. So I'm going to create an array as features. So features is equal to diabetes data, and in this diabetes data I'm going to drop one column. So I'm going to drop the outcome column. So columns is equal to outcome comma access is equal to 1. So this particular drop function is used in order to drop a column. So in this case we are going to drop this outcome column. So we are going to take this diabetes data frame, and I'm going to drop the final column, which is the outcome column. So the other columns will be my input features, and I'm going to store this outcome column in a different array. So and then I'm going to create. So you can see here, so we are using this drop. So this drop function is available in our pandas library. So we know that this diabetes.data is a pandas data frame, and we are using this pandas function in order to drop the column, and we are going to drop the outcome column here. Okay, so that's why we are giving the value as outcome for this column, and axis is equal to 1. So whenever you're trying to drop a column, you need to give the value in your axis as 1. Okay, so we know that outcome is a column, right? So we are giving the axis value as 1. If you are removing some rows, you need to give the axis value as 0. So that is the convention that we use. And the next thing we are going to do is we are going to load, or we are going to save all the outcome in a different variable. So all the x values, all the input features will be stored in this features array, and all the target or all the outcome will be stored in this target array. So target is equal to diabetes dataset. So you need to mention the name of the column that you need. So we need this outcome column. So what we are basically doing here is we are removing the outcome column, storing all the other values in this feature, and we are taking this outcome column and we are storing it in this target. Okay, so you can also try to print the features. So I'll print my features, and I'll also print my outcome. Sorry, it's target. So we have named this as target, right? So we need to mention target, so you can print this. So you can see here this particular features contain all the values except for the outcome column, but this target contains all the values in the outcome column. Okay, so now the reason is that as we have discussed with this fit function, right? So yeah, in this fit function we will give all the x and y separately. So your x is nothing but your features and y is your target. So that's why we are splitting it. And there are a few more processing things we need to do. So now what we are going to do is we are going to standardize the data. So we know that the data is in different ranges, right, in each column. So we are going to standardize all these values. So the next part is data standardization. So data standardization. So I'm going to create an instance called as scalar, and in this instance I'm going to load my standard scalar function. Okay, so standard scalar. So if you remember, we have imported this standard scalar function from sklearn.preprocessing here. So we have used this, imported this standard scalar function, right? So we are going to load that standard scalar into an instance called this scalar. So this is just like a variable. I'm loading this standard scalar function into this instance. I load this, and now I'm going to scalar dot fit. So we don't need to change the target column. Okay, so you know that we have two arrays, right? So one is features and the one is target. So we don't need to change the target column, as this is a binary column, so it contains values with either 1 or 0. So we don't need to do any changes here. So we just need to standardize all the values in our features. So what we will be doing here is I'm going to standard.fit feature. So we will fit this features array to this standard scalar function, and then we will transform this data. So scalar.fit, and I'll create another array called as standardized data. Standardized data is equal to scalar dot transform. So we need to fit the data to the standard scalar, and then we need to transform this data. So features. Okay, so that's what we are doing. So first we are loading the standard scalar function to this scalar instance, and we are fitting the features array to this scalar function, and then we are transforming. So I'll Run this. Now you can print your standardized data. So you can print this, so you can see the feature values here. So all these values will be standardized in a different manner, which almost will be in the similar range. So there are a lot of things that happens in our standardization procedure. So we have already discussed about this in our data pre-processing module. So the basic thing is we don't want the data to be in different ranges, so it will be difficult for the model in order to find the patterns within them. So we need to convert all of them into a similar range and structure. So that is the reason of this standardized standardizing the data set. So next what I'm going to do here is I'm going to create another array with the same name as features, and I'm going to load all the values of this standardized data to it. So it's just like renaming it. Okay, so I don't want the name to be standardized data, so I'm just renaming it to features. So that's what we are doing here. And we know the target column, we have already made the target column. It's just like redoing the step: diabetes data and outcome. So we have already done this here, so there is no need to do this here, but the idea is to have these two in the same cell. So we are creating again features target. The only difference is that this features will be in the form of a standardized format. So I'll just print my features and targets now. Features, and let's print our target. Okay, so now the features value should be standardized, and then we have the target column either 1 or 0. We know that 1 represents people with diabetes and 0 represents people without diabetes. Okay, so now what we are going to do is we are going to split this data set into training data and test data. So this is another important step we need to do. So once we split this data, we can move on and we can feed this data set to our model. So we will use the training data to train our model and test data to evaluate our model. So these are some basic steps that we have to do in every machine learning projects that we do. So I'll make a text here as train test split. So basically what we are going to do here is split the data into training data and test data. So now I have to create 4 arrays. So these 4 arrays are xtrain, xtest, ytrain, and ytest. So I'll explain you what all these arrays mean. So let me complete this line of code. So we are going to use the train test split function. Okay, so we have imported this train test split function from sklearn dot model selection. So you can see here, so we have imported this train test split function from sklearn dot model selection library. So within this we need to mention some parameters. So I'll mention my features, target, test size is equal to, I'll give my text size as 0.2, and random state as 2. Okay, so let's try to understand what we are doing here basically. So now we want to split this features and target into training data and test data. So the purpose of doing this is we have to train our SVM classifier with the training data that we have. So once we train that model, we need to test our data, or we have to evaluate our data with a different data set. So that's the reason for splitting this. So your xtrain will contain all the training data features, okay, and your ytrain will contain the corresponding labels. So it will contain the labels for all the data points in your xtrain, and your xtest will contain all the test data features. So all the features will be separated into 2 groups, so xtrain and xtest, and all your outcome or target will be split into ytrain and ytest. So ytrain contains all the labels corresponding to xtrain, and ytest contain all the labels corresponding to xtest. So we are basically splitting this features and target into training data and test data, and for this we are using this train test split function, and within this we need to mention some parameters. So parameters are nothing but features and target. So the reason we are doing is we need to split this features and target, right? So that's the reason we are mentioning them here. And then we have the test size is equal to 0.2. So 0.2 means 20% of test data. So test size is equal to 0. So 0.2 means 20%. If you mention it as 0.3, it means I want the 30% of the entire data set to be my test data, and the remaining 70 will be my training data. In this case, 0.2 means 20% of the entire data set. So 20% of the 760 data points will be my testing data, and the remaining 80% of 760 data will be my training data. So it is the general value you use. So we generally take 10% or 20% of the data as a test data, which is used for evaluation. And then we have the random state. So random state is not that much important. So this is basically to reproduce the code. So let's say that you are working on the same project, and let's say that you want to split the data set in the same manner that I am splitting my data set. So in that case, you can give the random state value as 2. So if you give the random state value as 2, your dataset will be splitted in the same way that my dataset is getting splitted. If you give the random state is equal to 3, 4, or any other number, your dataset will be splitted in a different manner. So this is just basically to get the same type of split that we are doing. So this is our next step. So I'll run this. So once we do this, so you can also try to print the shape of all these values. So features dot shape, and xtrain dot shape, and xtest dot shape. So let's run this. So features is our original data set, the features of our entire data set. So it totally contains 768 values. Out of that, 80% will go to your xtrain, which is 614 data points, and 20% goes to your xtest, which is 154 data points. So the next step is training our model. So this is where we are going to implement the SVM classifier that we have built here. Okay, so let's do that now. So this part is training the model. Training the model. And the model we are going to use is the support vector machine classifier. So I'm going to create an instance, and I'll name this as classifier. Okay, classifier is equal to, so in this I'm going to load my support vector machine classifier that we have built. So you can see here we have built the support vector classifier, and we have named this class as svm underscore classifier, right? So we need to call this one. So make sure that you have you run this particular cell. So I have already run these two cells. So if you don't run the cell, this won't work. Okay, so you have to run that particular cell before implementing this particular one. So classifier is equal to svm classifier. So this is the classifier that we have built, and within this we need to give some parameters. The parameters are nothing but the parameters that we have initiated here. So we need to give our learning rate, number of iterations, and lambda parameter. So lambda parameter is our regularization parameter, right? So we need to give all these three values and make sure that the spellings are same as we have mentioned above. So first is our learning rate. So learning rate is equal to, so you can give any values. So I'll just give my learning rate as 0.001, and I'll give my number of iterations as 1000. So it means my model will go through the data 1000 times. And finally my lambda parameter. So lambda parameter is equal to 0.01. So you can just change this values slightly and see how your model is performing. So you can manually tweak these values. Let me give all these values. So let's say that these are my values. So try different values and see how your accuracy score, what is the accuracy score you are getting, and so on. Okay, so I'll run this one. Okay, so we are basically loading our SVM classifier to this instance called as classifier. Now we need to train our support vector machine using this classifier. So this part is training the SVM classifier with training data. So here we are going to call the fit function that we have built. Okay, so you can go here. So this self is nothing but we have created an instance called as classifier, right? So classifier, our self within this class. So this self is nothing but the value of classifier. In this case, the instance that we have is the word classifier, right? So self will take the value as classifier, and we are going to call this fit function, and within this we need to give two values. One is x and y. So in this case, x is nothing but our x train and y is our y train. So we need to give this values while we are calling this function. So fit. So how we can call this is, we know that we have loaded this svm classifier so into the instance called as classifier, right? So you can mention classifier dot fit. So this is the fit function that we built, and within this we need to mention x train and y train. Okay, so I'll run this. So this will train my support vector machine classifier model. Okay, so Let's see. So this will take a second or two. Just wait for it to complete. So after that, so once your protected machine classifier is trained, now we can evaluate our classifier. Evaluate in the sense we can try to find how many correct predictions it is making and how many wrong predictions it is making. So this part is model evaluation. So the training part is done, and the next step is model evaluation. And in this step, we are going to find the accuracy score of the model. So I'll explain you what this accuracy score means. So first, let's try to find the accuracy on the training data. I'll create an array as extrain prediction. So extrain prediction is equal to classifier.predict. Predict, and within this we need to give extrain. So what we are doing here is, so we know that now our classifier, our subprotected machine classifier is trained because we have used this fit function in order to fit this data set to our model, right? So what happens in this case is, as I've explained you before, so all the steps that we have mentioned in this fit, gets carried out. It will try to find what is the m and n. In other words, it will try to find how many total number of data points that we have and how many input features that we have and so on, and it will try to initiate the weight value and bias value, which are basically zero. After that, it will try to implement the gradient descent in order to find the optimum values for weight and bias. So that's what happens when you call the fit functions. And finally, we can use this predict function. So we have this predict function, right? And the purpose of this predict function is, when you give some value, when you give some new input features value, it will try to predict whether the outcome is either 1 or 0. So that's what we are doing here, and that's why we are calling this predict function now. So classify.predict, and I'm giving this extrain. So what happens here is, now as our model is trained, if you give this extrain, it can try to predict the labels. It can try to predict the target for all these values, and that's what we are doing in this predict. And now we need to compare the values. So this extrain prediction will basically contains all the predicted values or all the predictions made by your model, and we need to compare this with the true labels. True labels is nothing but your y train. Okay, so this extrain prediction is the values predicted by your model, and it will be compared to the true values, which is y train. So let's do that, and we can do that by using the accuracy score function. So we have imported the accuracy score function from the sklearn.metrics, right? So we are going to use that now. So extrain prediction, and let's name this as training data accuracy. Training data accuracy is equal to accuracy score, and within this we need to mention two things. One is y train and the other one is extrain prediction. Okay, so what we are doing is, so this accuracy score will compare y train and the x train prediction. So we know that y train contains values as 1 or 0, and x train prediction will also contain values as 1 or 0. So it will try to compare these two values, and it will try to see how many correct values it is getting and how many wrong values it is getting. So numpy object is not callable. Okay, so we made, okay, so I think, so I didn't run this particular cell after removing this parenthesis. I told you that there should not be any parenthesis here, right? So that's the problem. I'll just restart and run all the cells. So all the cells should be run again. So now we won't get this particular error. So you can see this. So we have removed that particular parenthesis, right? So after that, we didn't run that particular SPM classifier. So that's why we are getting this error. Now things will work fine. Okay, so now we can try to print this accuracy score. So I'm going to print my accuracy score on training data. Accuracy score on training data is equal to my training data accuracy. So this will basically contain a value. So let's try to understand what is this value. So accuracy score in this case is 77, 0.7768. So 0.77 basically means 77%. So what it means is, out of 100 predictions that you are going to make, your model will make correct predictions for about 77 values or 78 values. Okay, so that is meant by this accuracy score. So if you get an accuracy score of 0.85, it means 85 percentage of your values will be predicted correctly. So in machine learning, like if we have correct predictions for 70 or more than 75 percentage, we can say that it is a good accuracy score. There are also techniques to improve this accuracy score. We will be seeing this in a later part of this course, but for now understand that this is how we can find the accuracy score of our model. So now what we have to do is, we need to do the same thing but for the test data. As I've told you before, we will train our machine learning model, our support vector machine model, with the training data, and we will test it with test data, right? But in this case we have tested it with the training data itself. Now we have to evaluate our model using the test data. Okay, so I'll just copy the code here, and we have to use this x test. Okay, so the model has already seen the x train and y train. So this is like the model has already seen this particular data, x train and y train, and it is making predictions on it, but the model did not see the x test data and y test data. Now we need to give this x test to our model, and we will try to predict the labels, we will try to predict the target, and we will try to compare it with the true labels, which is y test. So that is our next step. So I'll just copy this x test. So we need to replace some things here. So we have to replace the x train by x test, and this will be our x test prediction, not x train, x test, and this will be my test data accuracy, my test data accuracy. So classifier.predict test accuracy score will be y test and y test prediction. Okay, so we are just doing the same thing. The only difference is that in this case we are using the test data. So I'll run this. Y test is not defined. Okay, so we made a spelling mistake here. Okay, so let's run this, and now again you can print the accuracy score. So in this case we are going to print the accuracy score on test data. Okay, so I'll copy the test data accuracy score, and let's see what is the accuracy score we are getting for test data. So in this case the accuracy is 0.75, which means it is almost 75 percentage. So the accuracy on training data is 77 percentage, and the accuracy on test data is 75 percentage. Now you may wonder, what is the reason that we are trying to find the accuracy score on both training data and test data? The reason is that when your model is overfitted, your training data accuracy will be very high and your test data accuracy will be very low. Let's say that in some case you may get a training data accuracy of about the 77 or 78, and your test data accuracy may be 40 or 30 percentage. So that means your model is overfitted. So we don't want that particular problem. So overfitting happens when you are accuracy, the accuracy score on training data is very high, whereas the accuracy score on test data is very low. So we don't want our model to overfit, where will overtrain on the particular training data set. So we don't want that to happen. How we can find whether our model is overfitted or not is comparing the accuracy score on training data and test data. So that's why we are trying to find the accuracy score on both these data set, but the accuracy score on the test data is the most important one. Okay, so this is how you can evaluate our model, and we are getting an accuracy score of about 0.75. And you can, what you can now do is, you can use the support vector machine classifier that is present in the svm library, so the sklearn library. So as I've told you, I have already made a video on diabetes prediction, the same data set that we have, and in that case we have used the SVM classifier from the sklearn library. And if you use that particular model also, you will get almost the same accuracy score. Okay, so there won't be any much change. You can also try that. So you can also try to use that sklearn .svm classifier, or you can also refer that video where we have used that particular model. So what I'm saying here is, the accuracy score won't change much. So because we have actually built the same model, right? So that's the reason. And now finally what we are going to do is, we are going to build a predictive system. So this is the most interesting thing of all. So what happens here is, we are going to build some code here. So in this case, when you give some input features, when you give all these x values, your model will try to find whether that person is having diabetes or not. So it will basically try to predict whether the value is either 1 or 0, and from that we can know whether that person is diabetic or not. So this particular part is building building a predictive system. Okay, so I'm going to create an array called as input data. So in this you can give the input features, and using this data your model can predict whether the label is either 1 or 0. So now we need to do some processing. We need to change the data to numpy array. Okay, so when you mention the values in these parentheses, it basically means it is a tuple data type. So we need to convert it into numpy array. So numpy, because the processing is easier in the numpy array. So these are just small things. So I'll name this as input data as numpy array is equal to np.asArray. So this as array function will convert the tuple into numpy array. So within this parenthesis, we need to mention input data. So input data is nothing but this particular values. So input data, so we can fill all these values at a later time. So first of all, let's complete this code. So now we need to reshape the array. Reshape the array. So input data reshaped. So the reason we are doing this particular thing is we are just going to give one value. So we are just going to give the value for one particular row, and we are trying to find the target column. So our model doesn't know that. So for that particular reason, we need to reshape the array accordingly. So it will be we need to I'll just paste copy and paste this dot reshape. So this reshape function will reshape the array, and I'll give it as 1 comma minus 1. I'm not explaining a lot of things in this particular case. So I have explained all these things detailedly in that particular diabetes prediction video. I'll also give the link for that video in this video description. You can also refer that one in order to get a detailed explanation. So next we need to standardize the data. The reason is, so while we train our data, we have standardized it, right? So we have converted this data, we have used the standard scalar function, right? So if you give this data now, our model doesn't understand anything. So the data should be in the same format we have used it for training. So we need to standardize the data the same way we have standardized this particular data. So we have fitted the features and then we have transformed it, right? Now we also need to transform all the data that is present in this input data. Okay, so let's copy some value. So I'll just open my dataset in a notepad file. I'm going to copy some value. So I'll just copy this value and I'll paste it. So this is the value we have copied, right? So you can see that the label we are getting here is 1. So 1 means people with diabetes, and when we try to predict it, the model should give the value as 1. So that's the idea. So and I'll paste all the values here. So now the values is in this format, and we need to standardize all these values before feeding it to our model. So this will be standardizing the input data. Standardizing the input data. So let's call this as standard data. Standard data is equal to scalar dot transform input data reshaped. Okay, so this scalar is nothing but we have loaded the standard scalar function here, right, to this scalar instance. So we are calling that particular function data dot reshaped, and you can also try to print this particular standard data. So you can see how this data looks like. And now we are going to use the prediction function that we have built. So let's create a variable as prediction. So prediction is equal to classifier. So classifier is nothing but our SVM classifier, the classifier that we have built dot predict. So we have built the predict function, right? So predict, I'm going to predict the standard data. Okay, so this will give you the output as either 1 or 0. So you can also try to print this, print prediction. Okay, so let's run this. Now our model will try to predict the value of target or the value of y given the input data. Okay, so let's run this. We know that the particular target for this particular input, which is 1, so our model should predict the value as 1. So let's run this. So there is some array reshape. Okay, again a mistake. So it should be reshaped scalar. Okay, I made another small error. So scalar, I hope there is not any other mistakes. Okay, so you can see here, so this is my standard data. So my this particular input data set is now reshaped, and now our model has predicted the value as 1 basically means people with diabetes, and we know that the label is also 1 year. So if you can also try different values and try to see whether our model is predicting correctly or not. The thing is, it won't predict correctly for all the data points, as we have the accuracy score of about 77 and 75 percentage. So out of 10 values you are predicting, you may get correct prediction for almost 7 or 8 values. So you can also try to copy different values and try to predict the values in this case, where 1 represents people with diabetes and 0 represents people without diabetes, and we can also create an if condition to print that. So what I'm going to do is, I'm going to say that prediction. So we know that prediction is the value predicted by our model, and this value is in the form of a list. You can see here, so this one is enclosed in a list. So square bracket means it is a list, and this list contain only one value. So I'm going to call this prediction list, and prediction of 0. So prediction of 0 basically means the first value. So we know that prediction is a list, and if I mention a list name enclosed a 0 within the square bracket, it means the first element in that particular list. So I want to basically I'm just calling this particular value, and I'm checking whether that value is equal to 0. If that value is equal to 0, we want to print that the person is diabetic. Okay, in case this condition is not satisfied, else is nothing but that value will be 1. So else I want to print the person is okay. So 0 should be the person without diabetes, right? So the person is not diabetic, and else the person is diabetic. Okay, so basically what this means is, so we are trying to predict the value whether it is either 1 or 0. If the value is 0, we want to print that that person is not diabetic, or else if the value is 1, we want to print that that person is diabetic. So let's run this, and you can see here, so if your label is 1, it will print this particular statement, the person is diabetic. And if you copy and paste some different values and try to, let's say that we are getting a value as 0, so in that case this particular code will say that that person is not diabetic. So this is a simple if condition. So basically what we are doing here is, so we are giving some input data and we are just doing some processing. So we are just converting into numpy array in this particular line, and we are reshaping it to tell our model that I want to make prediction for only one data point, and then we are standardizing the data the same way we have standardized our training data. After that, we are making the prediction. If the prediction value is 0, I want to say that that person is non-diabetic. If the value is 1, I want to say that that person is diabetic. So this is the idea here. So this is how you can do the data processing on your diabetes data set, and this is how you can implement your SVM classifier that we have built. So you can also compare the accuracy score to the SVM classifier that is available in the sklearn library and see for yourself. So this is how you can implement this, and we are going to do one more thing. So I have already explained this in my linear regression and logistic regression code, where so we have this pretty large cell, right? So which contain all the code. So we don't want to write this code every time we are implementing SVM classifier. So what we will do is, we can copy this entire code and we can create a Python file. So once you do that, you can just call that SVM classifier every time you want to use it. I'll just show you. So I'm going to copy this entire cell. So I'm going to open my notepad plus plus. So this notepad plus plus is a very useful application. You can install it in your system. So I have copied my entire SVM classifier code. So this is my subprotected classifier model, and I'm going to import my numpy library here. Import numpy as np. So don't forget to include this particular line, because in some cases we are using the numpy library. Okay, so if you don't import this particular code won't work. So you can find this file option in notepad plus plus. You can give save as. I'm going to save this file in my desktop as SVM. Okay, so I'm going to save this as SVM, and in the save as type, I'm going to save this as a Python file. So you cannot do this in a normal Notepad file. So that's why we need this Notepad++ application. So you can see this Python file. Okay, so now the extension will be .py, and we can save this in our dataset. Sorry, in our desktop. Okay, so now this will be in the form of a Python file, and now what I'm going to do is, so I have another code. It's basically the same thing. So the same thing that we did for our diabetes dataset. Okay, so everything is the same. Now I'm going to upload my dataset file, my diabetes.csv, and I'm also going to upload my support vector machine classifier file. Okay, so you can see this svm.py file, the one which we have built in our Notepad++. So I have imported the NumPy and other libraries. Now what I'm going to do is I'm going to call this SVM classifier. So instead of writing this code every time you want to implement it, you can save this in a simple Python file, and you can call this file. So you see the name of this file, it is SVM. Okay, so what you can do is I'm going to write here as from SVM import SVM classifier. Okay, so this SVM classifier is nothing but the classifier that we have built. So first you need to mention the name of the Python file. So the name of the Python file is SVM, right? So svm.py. So mention that here, and mention the class that you want to import. I want to import this SVM classifier that I built. Okay, so this is how you can import your SVM classifier, and you can run this particular cell. Okay, so you can run all the cells except for one. So everything is the same that we have did before. So we need to come to this training the model. Yeah. So now in this case, so here we need to put this SVM classifier. So from SVM we have imported this SVM classifier. So in this classifier I'm going to write this as SVM classifier. So this is nothing but the model that we have built. So let's run this. It is actually the same thing. Let's see. So our model is getting trained, and we are getting the accuracy score and the prediction. And also the reason we are doing here is I don't want to have this code every time I want to implement this SVM. So you can just build a simple Python file where you can include all the codes that we did for our SVM, and you can just import that particular SVM file, and you can use this multiple times, right? So this is for that particular purpose. So now we can call this SVM classifier, and we can try to make our predictions. Okay, so this is how you can save the code for your particular model. So we have did the same for our linear regression, logistic regression. We have seen how we can do this for SVM classifier. Okay, so that's it from my side, and I hope you have completely understood how the SVM classifier works and how we can implement this SVM classifier from scratch in Python. And if you have any doubts, please mention in the comment. Module is all about building machine learning models from scratch. In my previous videos, I have explained you what is the intuition and math behind the models such as linear regression, logistic regression, and support vector machine classifier. We have also seen how we can build these models from scratch in Python. So the fourth model that we are going to discuss is a Lasso regression model. Okay. So in this video, let's try to understand what is the intuition behind Lasso regression, and in the upcoming videos, we can discuss about what is the math behind this model and how we can build this model from scratch in Python. Okay, so let's get started with this intuition part. So let's first of all try to understand the very basic aspects of a Lasso regression model. So Lasso regression is an example of a supervised learning model. So we know that machine learning is basically divided into two types. One is supervised learning and the other one is unsupervised learning. So the difference between them is when we take a supervised learning approach, we use labeled data set. Whereas in the case of unsupervised learning approach, we use an unlabeled data. Say for example, let's say that we want our machine learning model or deep learning model to look at an image and say whether that image represents a dog or cat. So in this case, what we will do is we will feed the machine learning model with lots of images of dogs and cats. So when we use a supervised learning approach, we will label all these images. So we will give the label as dog for all the dog images, and we will give the label as cat for all the cat images, and the model will try to find the relationship between the label and the corresponding images. So it knows now how a dog would look like and how a cat would look like, and when you give a new image, it can tell you whether that image represents dog or cat. Whereas in the case of unsupervised learning approach, we won't label this data. So we basically give only the images. So this data is called as an unlabeled data. So the model will try to group the data based on their similarities. So this is the difference between supervised learning and unsupervised learning, where you give the labeled data to your supervised learning model, and you give a unlabeled data set to your unsupervised learning model. So this is the difference between them. So Lasso regression is an example of supervised learning model, and it is an example of a regression model in particular. So we know that supervised learning is divided into again two classifications or two types. One is classification models and the other one is regression models. So this Lasso regression is an example of a regression model. So the example that we have seen here, so in this case the model will try to classify the images as either dog or cat. So there are basically classes, or you can think about a model that can predict whether a person will get a job or not. So these are classification problems where the model has to classify the data, whereas the regression tasks are those where the model has to determine some value. So if you say that you want to build a machine learning model that can predict what is the salary that a person can make. So in this case, the model tries to find some numerical value, right? So in this case, the numerical value is the salary. So this is an example of a regression model, or you can try to build a model that tries to predict what is the temperature for this particular day. So these are regression problems where it will try to find some numerical value, whereas classification generally, classify the data points based on classes. So Lasso regression is an example of regression model. And the full form of this Lasso regression is least absolute shrinkage and selection operator, hence the name Lasso. Okay, so we will try to understand in the later slides what is meant by this shrinkage and so on. And the final important aspect of Lasso regression is that it uses regularization techniques called as L1 regularization in order to avoid overfitting. Okay, so these are some of the main aspects of Lasso regression. So the one main thing that you need to understand is it tries to avoid this overfitting using L1 regression. So it is basically built on top of a linear regression model. But in order to make accurate predictions, we try to use this regularization. So further we can decrease this overfitting so that we can make accurate predictions. So these are the important basic aspects of Lasso regression. So it is a supervised regression model, and this is the full form for it, and uses a L1 regularization. So there is also another type of regularization called as L2 regularization. And when you use L2 regularization, then that kind of regression model is called as ridge regression, and when you use L1 kind, it is called as Lasso regression. So that is one thing that you can remember. But for now, let's try to understand about this L1 regularization and Lasso regression. So before going into Lasso regression, we need to understand about linear regression a bit, because as I've told you, a Lasso regression model is built on top of linear regression. So with the only difference is that we want to avoid this overfitting problem by means of regularization. So let's try to understand about what is meant by this linear regression. So let's say that we have a small data set. So this data set contains the years of experience of different people and what is the salary that they are making. So let's say that these are the data for software engineers. Let's say that a person with a 0 years of experience make 2 lakh salary, and a person with 2 years of experience makes 4 lakhs of salary, and so on. So this is the data that we have, and based on the trend that we have in this data, we want to determine what would be the salary of a person with 3 years of experience. So this is what we are interested in. So let's try to understand how we can determine this. So you can easily find this particular value. So what the salary of a person with 3 years of experience. So you can determine that by just plotting this data points. So the first data point that you are going to plot is 0,2 lakhs. So if you do that, so let's say that we have the years of experience in our x-axis and the salary of the person in rupees in y-axis. Okay, so if you take this first data point, so it's 0,2 lakhs, so the point will come here, and the second data point is 2,4 lakh, and it will come here, and these are the plot that we are getting. So now you can try to fit these data points to a normal straight line. Okay, so you can try to use a line or a curve, but this is a very simple data which can be fitted to a straight line. So you can see here, so almost all the data points are closer to this line. So this model, this line is called as your linear regression. So whenever you can fit your data to a simple normal line, it is called as a linear regression model. And now when you have constructed this particular line, if you want to find what is the salary a person with 3 years of experience can make is, so you can come to this x-axis and you can draw a dotted line from this 3. So this 3 represents a person with 3 years of experience, right? So you can just draw a dotted line and you can see at what point this dotted line meets this blue colored line. So this blue colored line is a linear regression model, and you can try to find the corresponding y-axis value. So it is coming somewhere here, right? So the value will be around 6,50,000 per year. So when you have a value of x-axis, now you can predict what is the value of this y-axis can be. So given the years of experience of a person, now you can determine what is the salary they can make. Okay, so you can also try to find the equation of the line, which will be like y is equal to wx plus b. So this is similar to the equation of a straight line, which is y is equal to mx plus c, where m is your slope and c is your intercept, right? So here weight w is similar to the slope that you have, and bias is similar to the intercept that you have. Now, this is how generally machine learning works. It will try to find that relationship between x and y. Here, the relationship is represented by this particular equation, y is equal to wx plus b, and this w will have some value and b will have some value. So this is what we will try to do in machine learning. So we will try to find this equation that can relate x and y. So when you have that equation, you can plug in some values of x and you can get the corresponding values of y. Let's say that we get some values for this w and b, and when you plug in the value of 3 in the place of x here, so you can multiply that 3 with the weight and add it with bias, and you will get what is the salary that the person is going to make, and it will be around 6,50,000 per year. So this is what we will try to do in machine learning. So we have a data set and we will try to find the relationship between them. So once we find this relationship, when you give a new data, the model can tell you what is the y would look like. So this is how any machine learning model works. And so as as I've told you before, this lasso regression is built on top of this linear regression. We use the same equation y is equal to wx plus b. So the only difference is that we use a regularization term. Now let's try to understand why we need this regularization. So this is a very simple data point, right? So these data points can be joined by a simple straight line, but it won't be the case in in every real world data set. So real world data set will be very complex. So you can see the data points in this case. So you have multiple data points here. So let's say that all these data points are represented by this violet colored points. So these are our data points, and we want to draw a curve that can best fit to the data that we have. Okay, so here we have three kinds of curves. So the first, the red color curve represents third order polynomial fit. So what this basically means is you get this red colored curve by using a third order polynomial equation. Okay, so if you want to know about this polynomial equation, so this is how a first order polynomial equation looks like. So you have some x and you have some y, and this y depends on the value of x. Okay, so y is equal to ax plus d, and the second order polynomial equation will look like y is equal to ax square plus bx plus d. Okay, so here you have x squared term in the second order polynomial equation, and in the case of a third order polynomial equation, you have the equation as y is equal to ax cube plus bx square plus cx plus d, and so on. So this is something that we have learned in our simple algebra classes during our school time. So this is how polynomial equation looks like, and when you draw a curve using this third order polynomial equation, the curve will look something like this red colored curve represented here. Okay, so there will be a slight rise and slight fall in the curve that we have, and this depends on the data point that we have. Okay, so you can see here, so the data points are at this region at this particular place, and now it is in the lower region, and so on. So hence the curve slightly rises and falls and so on. So when you take a fifth order polynomial fit, again what happens is the number of terms you have in your equation increases. So the fifth order polynomial equation will look like, it will have the x power 5 term, x power 4 term, and so on. So the curve will be more complex, and there will be more rise and more visible rise and fall here. So the fifth order polynomial fit is represented as the blue colored curve here. So you can see that here. Whereas the ninth order polynomial fit again will contain more number of terms in that particular equation, and you can see clear rise and fall in the curve, right? So the green colored model. So let's try to compare these three curves. So the red color curve has slight rise and fall, and fifth order polynomial fit, the blue color curve, has again more rise and fall, whereas this ninth order polynomial fit has a very high rise and fall. So we call this ninth order polynomial fit, this green colored curve, as a overfitted model, because it tries to overfit to the data point that that we have, whereas the fifth order polynomial and a third order polynomial tries to fit to the data points generally. Okay, so it tries to make some generalization. So there is a rise and a fall and so on, but the rise is not as much as given in this green colored fit or the ninth order polynomial fit in this case. So this is what we call as overfitted model. Okay, so we don't want our machine learning models to overfit to the data point. So what happens is when overfitting happens, the accuracy on your test data will be very low, whereas the accuracy on your training data will be very high. So we don't want that to happen. So we want our model to do well on the test data as well. So this is a problem of overfitting, and this is where we need regularization techniques in order to overcome this overfitting problem. So before going into that, let's try to understand more about these equations. So here y is your dependent variable, so and x is your independent variable. So in the previous case where we have discussed, so your years of experience is the independent variable, or in other terms it is your x value, and salary is your dependent variable because salary of a person depends on the years of experience, right? So you can call your y as dependent variable because it is dependent on the value of x, and you can call this x as independent variable because it doesn't depend on any factors. And a, b and c are your coefficients. So these are similar to the parameters that we have, the weight and bias that we have. So a, b, c and coefficients, and d is your constant term. So constant term is similar to the bias that we have in our model, the last b term. Okay, so this is the equation that we have. And what is the inference we can get is, as the complexity of the model increases, it tends to overfit with the data. So we have seen in this case, so a ninth order polynomial fit have multiple terms when compared to a fifth order or third order polynomial fit. So the complexity of the model increases. So what happens is the model tends to overfit to the data. But in case you have a simpler model, then we don't have the problem of overfitting and so on. So this is why we need regularization to happen so that our model doesn't overfit. So when your model overfit, we don't get good predictions from our model. So that's the reason for preventing this overfitting from happening. So this is one aspect, and there is another thing we need to discuss before we move on to regularization. So that is, so in this case we just have only one x value, right? So you can think about this x as the salary of a person, and sorry, the y as the salary of the person, and x as the years of experience. So here basically what we are telling is y depends on the years of experience. But what happens is in real life, the salary a person can make depends on multiple factors, not only on the years of experience, but also on what is the performance on their previous job and what is their academic performance. And a lot of things depends on this, right? So what happens in real life is your y will be dependent on several x values, not only one single x value, but several independent variables. So that is where we use a multiple linear regression when we have more than two variables. Okay, so multiple linear regression is a model for predicting the value of one dependent variable, which is your y, based on two or more independent variables. So you will have x1, x2, x3 and so on. Okay, in that cases, instead of a line, we may need a plane to fit to our data. Okay, so let's say that we have a simple linear regression. So we call a linear regression a simple linear regression when your y depends on only one x value. Let's say that the example that we have discussed before, where we considered the salary of a person depending on the years of experience. So here x1 will be your years of experience, and w1 will be the parameter of your model, which is nothing but the slope of the line, and b is your bias value, the intercept of the line. Whereas let's consider another example. Let's say that in this case y represents the price of a house, and we want to predict this price of the house, and generally a price of a house depends on several factors. So let's say that this x1 represents the number of rooms in a house, and x2 represents what is the size of that house, and x3 represents what is the crime rate that are happening in that particular area. So all these factors determine what is the price of the house can be. So in real life, in a lot of data that we deal with, this y, this dependent variable or the target variable, depends on multiple features. So we call this x1, x2 and x3 as our input features, and there will be a lot of input features. So there can also be cases where you have 10 input features, or even 20, or even 100 input features. So this is where again we get the problem of overfitting, as you have more dimensions. So dimensions are nothing but the x1, x2 and x3. So when you have multiple dimensions, when you have more number of features, then again your model tend to overfit because the complexity is again kind of increasing. So this is why we need regularization techniques in order to prevent this overfitting from happening by just simplifying the model. Okay, so now let's try to discuss about this regularization. Regularization is used to reduce the overfitting of the model by adding a penalty term to the model. Lasso regression uses L1 regularization technique. So this is about regularization and lasso regression. So as I've told you, the main purpose of this regularization is to reduce your overfitting or to prevent your overfitting from happening. So how it does it? It will try to add a penalty term to your model. Okay, and like when you add this penalty term, some of your parameters, like in this case we have seen this w1 w2 w3 so on, right? So some of the parameters can get eliminated. So like eliminated in the sense the value will become zero. Let's say that we have this w2, and when you add some penalty term, if the penalty term is I, let's say that this w2 term becomes zero. So this 0 into x2 will be 0. So again, we have one term less in the previous case. So you will have only this w1 x1 and w3 x3 plus b. So this term will be 0. This w2 x2 term will be 0. Again, you are simplifying the model. So that's the idea. So the idea here is to add a penalty term to the model, and this type of regularization is called as a L1 regularization technique. As I've told you, if you use a L2 regularization, then that is called as a ridge regression, but let's discuss about that in a later time. So now the area of interest is only lasso regression. So what happens is the penalty term reduces the value of the coefficients or eliminate few coefficients so that the model has fewer coefficients. As a result, overfitting can be avoided. As we have discussed, as the complexity increases, there is a high chance of model getting overfitted. So we want our model to have lesser terms. So when you have a higher degree polynomial like 6th order polynomial equation or 7th order polynomial equation, the penalty term will try to reduce the value of the coefficients. So coefficients are nothing but a, b, and c. So these values will try to get minimized so that we can get a more generalized model, and this process is called as shrinkage. Okay, so we are trying to shrink the value of the parameters or the coefficients that we have in our model, and hence we get this name least absolute shrinkage and selection operator. So there are methods on how we can shrink this coefficients values, and we will discuss about this in our mathematical video. But for now, understand that the main idea, the main intuition here is that we need to try to minimize the coefficient values so that we can get a more generalized fit. So if you see this red color curve, so this red color curve is more fitted to this data, but this green colored curve is more of a generalized one. It doesn't change with each data point that we have. So when you, let's say that we have a regression model that were fitted like this red colored curve, and when you add this penalty term, when you add this L1 regularization, you will get a more generalized term like this green colored curve. So this is the idea behind this. So the idea here is to use the same linear regression model that we have, with only a change is that we try to add a penalty term. So where we will add this penalty term is that we will add to try to add this to the cost function of the model. So when you add when you add this penalty term to the cost function, your gradient descent changes, and the main work of this gradient descent is to find the best value of the parameters, this w1 w2 and so on. So how basically the gradient descent works will change, and you will get a better parameters value that doesn't overfit to your data. Okay, so this is where this lasso regression is also helpful for us. So we call, or there is an important concept in machine learning called as feature selection. So feature selection is nothing but when you have 10, 20 or 30 features in your data set, all the 10 or 20 features are not important for us. Only 5 features may be important. So in the case of house prices, so only a few features may be important for us, but there can be many features that are present in the data set. So this process is called as feature selection, where we will try to select selected features, the important features on which the value of y depends on, or in other words the price of the house depends on. So this is where lasso regression is also helpful for us. So when the penalty term is I, when this lambda term is very high, so in that case what happens is some of the this parameters value, so this w1 w2 w3 are called as your parameters, and some of this value tend to move towards 0. So let's say that this w2, as I've told you, let's say that this w2 value becomes 0. So in that case this term will be replaced by 0. Okay, so let's say that this w2 is equal to 0. Now this term will be 0, and you will get a more simpler model. So what happens is when you have multiple features, it will try to shrink the values of these parameters, and as a result of this, when you have a higher penalty value, most of the features may get 0. You will get a very simple model, and this is how you can overcome the problem of overfitting so that you can make accurate prediction. So this is about lasso regression, where we will try to simplify our model by adding this penalty term so that we can get better accurate predictions. So that's it about lasso regression intuition, and I hope everyone understood what is meant by this lasso regression and what is meant by this L1 regularization. So we will be discussing more about this L1 regularization and what is the mathematical model of this particular model, and we will be discussing about that. And after that, we can move on to the hands-on part where we will try to build this lasso regression model from scratch in Python. Seventh module is all about building machine learning models from scratch. So in my previous video, I have explained you what is the intuition behind a lasso regression model, and in today's video, we are going to understand what is the math behind lasso regression and how it is different from a linear regression model, and how does the cost function looks like for a lasso regression. So these are the things that we will be covering in today's video. So let's get started. So I'll just give you a quick recap of what we have discussed so far about lasso regression. So we know that it is a supervised learning model where we use labeled data set. So it is not an unsupervised learning where we use unlabeled data. Okay, so we use labeled data set, and it is an example of a regression model. So we know that there are two types of supervised learning. One is classification, where we will try to classify the data points into classes or types. Say for example, we will try to classify the images into dogs or cat, or we can try to classify whether a person will get a job or not. So those kind of problems are called as classification problems, whereas regression problems are those where we will try to find some value, some continuous value. So it can be like a predicting what is the salary that a person is expected to make. So that kind of problems, or what is or predicting the temperature of a particular day. So these are regression problems where we are interested in finding some continuous numerical values. So these are examples of regression problems. So lasso regression is an example of a regression model, and the full form of lasso is that least absolute shrinkage and selection operator. So this is the full form of this word lasso, and the main difference from lasso regression and linear regression is that it is basically built on top of the linear regression model, with one change that it uses this L1 regularization technique in order to avoid overfitting. So we know that overfitting is the problem which occurs when the model overtrains on the training data, where that basically the accuracy on the training data will be high, whereas the accuracy on the test data or any other data will be very less. So this happens because the model doesn't generalize the situation, it doesn't generalize the problem, but it tends to over train with the training data. So that is one problem we need to avoid, that is called as an overfitting, and this lasso regression uses this L1 regularization in order to overcome this. So this is the purpose of having this lasso regression model, where we want to avoid this overfitting when compared to normal regression problems. So these are some basic things that we have discussed before, and we have also discussed what is meant by this regularization. So this is the definition for this. So basically regularization is the technique mainly used in order to avoid or reduce this overfitting problem. So how does this regularization do that is by adding a penalty term called as lambda to the model. So to be more precise, so we add this penalty term to the cost function of the model. So we will be discussing about that in the later slide. So what is the cost function of this lasso regression, and where do we add this penalty, and so on. So for now, understand that regularization adds this penalty term to the model. So how this penalty term works in order to reduce overfitting is that it tries to reduce the value of coefficients. So coefficients are nothing but the weights you have in your model, the parameters of the model, which are nothing but are weights. So it tries to reduce the weight value, or in other words, we can say that it tries to push the weight value towards 0. So what happens is when your model is simplified, or when your model doesn't have many terms and many dimensions, so in that case it doesn't tend to overfit. So the fit will most probably be an optimum fit. So that is the reason. So the penalty term reduces the value of coefficients or eliminate few coefficients. So eliminate few coefficients in the sense some of the weight values may become 0, so that that particular term will be 0, and so on. Okay, so that the model has fewer coefficients. As a result, overfitting can be avoided. So we can consider this third order polynomial equation. Let's say that this model is overfitting. So you can see the red color curve here. So we can call this red color curve as overfitted model, because there is not a regular trend in the curve, right? So this curve increases suddenly and decreases suddenly based on the data points that we have. Whereas if you see this green colored curve, it is more of an optimum curve. So we can see a generalized trend where it kind of increases slightly and then decreases, and so on. So this is an example of an optimum model. So what happens when we use this L1 regularization is that, let's say that the model tries to, or this L1 regularization tries to reduce this b value close to 0. So let's say that this b value becomes 0. So when we multiply this 0 with this x square, this whole term becomes 0, so there won't be this second term. So the model will be more simplified, and we can avoid this problem of overfitting and so on. And this process is called as shrinkage, because we are basically shrinking the weight value and so on. So we also call this as sparsity, where we try to create sparse model in the sense a model which have less number of weight values. So that is called as shrinkage, and hence the Lasso regression gets the name least absolute shrinkage and selection operator. So now what we have to do is we have to understand how a linear regression model works. So if we can understand that, we can later understand about the cost function of Lasso regression, and everything will make sense. Okay, so first of all, I'll explain you how a linear regression tries to predict the values. So what happens is we know that the equation of a line is y is equal to mx plus c, right? So instead of m, we will be taking the slope as w, which is basically the weight. So it is similar to the slope of the model, and b is nothing but it is similar to the intercept of the model. So b is called as bias. So generally, how we will train a machine learning model is that, so it will randomly get some weight value and bias value. So in our cases, we took the initial value as 0 for both our weight and bias. So if you have seen our videos on building models from scratch in Python. So while writing the code for the linear regression and logistic regression model, we give the initial value as 0 and bias value also as 0. So in this case, let's say that we are randomly assigning some parameters. W is equal to 3, which is the slope of the line, and b is equal to 2, which is the intercept of the line or the bias of the line. Okay, so this is the random assigned parameters. Now what the model will try to do is it will try to find, or it will try to predict the output value based on these parameters, and it will try to check whether this value is close to the true value or not. So that's what basically happens. So let's try to understand this with an example. Let's say that these are the data points that we have. So we have some x value and we have some y value. So you can consider this like x may represent the number of years of experience of a person, and y is the corresponding salary that they make. So you can see here that there is a linear relationship between x and y. What I mean is, if x increases, y also increases. If x decreases, y also decreases. So this is what we call as a linear relationship. And let's say that we want to fit a line using these parameters. So let's say that we are drawing a line, and this line will be y cap is equal to 3x plus 2. So 3 is nothing but our weight value, which is similar to the slope, and this b is equal to 2, which we have written here. So this is the same format as y is equal to mx plus c, which is the equation of a line. So now what we are trying to do is, so let's say that we have this x values. So the x values are 2, 3, 4, 5, 6, 10, and this is the true y value. So 10, 14, 18, and so on. So if x value is 2, then y value is equal to 10. If x value is 3, y value is equal to 14, and so on. So this is our true y value. Now what we will do is, so we have this equation, right? So this is the equation that we have made using this randomly assigned parameters 3 and 2. So now what we will do is we will substitute the value of 2 in this equation, and we will try to find the value of y cap. So if you substitute the value of 2 in this equation, you will get 3 into 2, which is 6. 6 plus 2 is 8. So similarly, you can plug in all the values, and you will get the corresponding y cap values. So what is this y cap or y hat is that it is the predicted value. So this is how a model tries to predict the values. So it will try to assign some parameters, and based on these parameters, it will try to find y based on the input feature values. So this is our y true value, and this y hat is our predicted value. Now the model has to know whether this particular equation, so this is an example of a linear regression model. So it needs to see whether this model is making accurate predictions in the sense whether these two values are close to each other. So you can see that there is a clear difference between these two values, right? So these are not the same values. So if a model is accurate, in that case the y at value and the y value will be very close to each other. So then we can say that the model is making accurate predictions and so on. So now we need to understand how the model can determine whether the performance is good or not. So this is where loss function comes into play, or we call this as cost function. So we have this x, y, and y cap, and we will try to basically find the difference between this y and y cap or y at. Okay, so this y is nothing but our true value represented here, and y cap is our predicted value. So what is the difference between cost function and loss function is that if we try to find the difference between only one data point, so let's say that we have this first data point, right? If we try to find the difference between this y and y cap for only this data point, then it is called as the loss function value. If you try to find the difference between these two values for all the data points, and you take a mean of that, in that case case it is called as a cost function. So this is one main thing that you need to remember. Loss function is nothing but the difference between y hat and y for single data point, whereas cost function is the difference between y cap and y hat for all the data points that we have. So we will individually find all the differences, and we will try to sum it up, and then we will divide it by the total number of values we have. So here n represents the total number of values. N is nothing but 1, 2, 3, 4, 5. So totally we have 5 values here. So here the n will take the value as 5. So we will try to find the difference between each values and square them, and we will try to divide it by n. So this is also called as mean squared error. Okay, so this is an a loss function which is in the form of mean squared error value. Now we can easily find this. So you just need to substitute the values. So first we need to find the difference between y and y cap for this first value, which is 10 minus 8. So we have 10 minus 8 and we have to square it. So the reason we are squaring is, so if you don't square the difference, then what happens is like the negative error and the positive error get cancelled each other. So we don't want that. So say for example, in this case we have 10 as our true value and y cap value is 8. So in this case, let's say that our y value is 14, whereas our y cap value, let's say that it is 12. So in the first data points, the difference between them is plus 2. So in the second data points, let's say the difference between the y and y cap is minus 2. So if you don't square this plus 2 error and minus 2 error will cancel out each other, and the model will say that the predictions are accurate, but that is completely wrong, right? So we need to take into account both positive errors and negative errors. So that is why we sign the difference between them in order to neglect that sign error and so on. So that is why we need to square them. So we have this 10 minus 8 whole square and 14 minus 11 whole square and so on. So we are finding the difference between each data point, y and y cap value, and after that we are dividing by 5, which is our n value, which is nothing but the total number of data points that you have. So if you substitute all the values and calculate it, you will get the cost function as 18. So the main thing that we need to remember here is, if the loss function or the cost function value is high, in that case we can say that the model is not working well. If a model is working well, or if the performance of the model is good, in that case the cost function value will be very less. So this is because when the difference between the true value and the predicted value is very small, the difference is not much, right? So in that case the cost function value will be very minimum. So your cost function value will be high only in that case when the difference between y and y cap is very high. Okay, so the main goal is here is to minimize the cost function value, which tells us the model is making good predictions. So here the cost function value is 18, and the magnitude of this cost function is relative. So if you see this y and y cap value, so just compare the magnitude of this this cost function value and this y value. So you can just take a square root of this, because we are squaring the value, right? So if you take this a square root of this 18, so we will get something like 4 point some values and so on. So the magnitude of this cost function is around 4. So you can compare the magnitude of that 4 with y. So in this case we have the values in the range of 10 to 20, right? So for values in 10 to 20 range, a cost function value or a error value of 4 is quite high, right? So we can say that this model is not working fine. So if the cost function value is low, we can say that the accuracy of the model is high. So the one main thing that you need to remember is the cost function should be low for your models. If you it basically tells your model is working well if the cost function value is less. So that is the main inference that you need to get here. So this is how a linear regression will try to find the cost function and try to minimize it. Now we need to understand how does a Lasso regression model does it. So everything is the same when it comes to Lasso regression when we compare it to a linear regression up to this particular part. So it will try to find the y cap value in the same way. It will try to assign the weight value and the bias value, and it is the same equation. So the equation of the linear regression model, which is y is equal to mx plus c or y is equal to wx plus b, which are both the same. So everything is the same up to this part. So the only difference is that we don't use this cost function. So 1 by n summation of yi minus y cap I. So we just add another term to this. So that is the difference between linear regression model and Lasso regression model. And the reason for adding another term is to reduce this overfitting issue. So this is where the cost function of Lasso regression comes into play. So the only difference is that we add this penalty term to the cost function of the model, and we will try to sum up the values of the weights that we have. So if you look at this equation, so j is our cost function. So generally we represent cost function as j and loss function as L. So you can see the value is j, which is our cost function. So in this case, m is the total number of data points that you have, and n is the total number of input features. Okay, so in the previous case, we have considered n as the total number of values, but in this case, let's say that m is the total number of data points and n is the total number of input features. Input feature is nothing but your x value. So in this case, you can see that here we have only one x value, right? So only one group of x value. So we have only one input feature and one target column and so on. So in some cases, you will have multiple x values. So let's say that we have, we are predicting the salary of a person based on various parameters like what is their years of experience, what is the college they have studied, what is their academic performance, and so on. So in these cases, you have multiple input features, right? Whereas in this case, we have only one input feature, which is x. So that is what this n is about. So it will take the total number of input features. In other words, you can remember this as the total number of columns that you have in your data set, and you can consider this m as the total number of rows in your data set. So I hope everyone is clear about this m and n. So m is the total number of data points and n is the total number of input features. Now y and y cap are the same. So this is the true value, yi is the true value for, and yi cap is the predicted value. So we will try to find the difference between true value and the predicted value for each data point, and we will try to square that difference and we will try to sum it up. Okay, so before dividing it by m, what we will do is we will add it with the product of this penalty term and the parameters of the model. So in this case, in the previous case that we considered, the parameter that we add, the weight that we add is 3, right? So what we will basically do here is, in this case, we add only one input feature, which is x alone. So there will be only one weight value, and another thing is the total number of weight values that you have is equal to the total number of input features that you have. So in the previous case, so if you see here, we have only one x value, right? One x group of values. So you have only one w value. If you have multiple input features, so the number of weights will be equal to the total number of input features that you have. So that is another thing which I hope everyone knows this. So in this case, what happens is, in the previous example that we considered, we have about 5 number of data points. Okay, so this m will take the value as 5 and n will take the value as 1, because we had only one input features, and hence we will have only one weight value, which is nothing but 3, the randomly assigned weight value. And after we find this difference and square it, we will multiply the penalty term and this weight value. So we can manually change this penalty term. So this lambda is called as a regularization parameter, or the lambda parameter. Okay, so while building the Lasso regression model, we can see how we can assign the values to it. But for now, remember that we will multiply this penalty term with the weight that we have, and then we will add it to our cost function. After that, we will divide it by this m, which is the total number of data points that we have. So this is our cost function in this case. So the only difference between this cost function and the cost function we have in the linear regression is that we add a penalty term to the same cost function that we have in order to reduce this overfitting issue, which will basically try to reduce this weight value. Okay, so I'll give you another example. So in the previous case, we have only one input feature, right? So we can consider another example. So this is the Boston house price data set. So in our channel, we have already worked on this project where we will try to, determine, or we will try to predict the price of house based on various input features. So these are the different types of input features that we have. So we can see the last column, price column. So this is nothing but the price of the house in $1,000 or something. So this is our target column. So we need to predict this particular value. So, and all the other columns are called as the input features. So if you see here, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So we totally have 13 input features in this case. So what we will do basically here is, so in this case, the total number of m will be more. So the data set contains around 500 data points. Here I have shown you only the first 4 data points. Okay, so this m will take the total number of data points, and we will try to find the y cap value as our linear regression would do. So we will initiate some weight value and bias value, and we will try to find this y cap value, and after that we will separate each of this y cap value with the corresponding this y value. So this is my y, which is my true target column, the true price of the houses, and y cap is the predicted price for the houses. So we will try to find the difference between them and add the penalty term. Now the main thing you need to note here is, let's say that we totally have 13 input features. So in that case, your model will have 13 weight values. So as I've told you before, the total number of input feature, or in other terms, the total number of columns that you have is equal to the total number of weights that you have. So you don't, I mean, like, you shouldn't see this target column. So neglect this target column and see other columns, and the number of weight is equal to this total number of columns. So what it basically tells is, so let's say this crime has a weight value of about -2, and this zone has a weight value of +2, and so on. So it basically tells you how much a column is important for predicting the price. If you see this crime rate, so we can say that if the crime rate in a particular area is very high, in that case the price of the house goes down because people don't want to buy houses in that area. So we will this particular column will most probably have a negative weight value. If you see this this room, so RM basically represents the room in a house and so on. So if the total number of rooms is very high in a house, then that price is going to cost more, right? So this will have a positive weight value. So this is what the weight value signifies. So it will tell how much important a particular column is. So if you have 13 input features, then in that case you will have 13 weight values. So we will try to find the difference between y and y cap, and we will have this penalty term. Okay, and what we will do is we will try to add all the weight values. So we will try to add all the weight values here. So that is what represented by this summation. So n is the total number of weights that we have, and we will try to add all the weight values for this particular data set, and we will try to multiply it with the penalty term and add it to the normal cost function that we have, and then we will divide it by m. So you will have some cost function value. So the main thing about lasso regression, which we have discussed before, is it tries to push the weight value towards zero, right? It will try to minimize the value of weight, or it will try to eliminate some weight value. So how all these things comes together is by means of gradient descent. So the reason we are using a different cost function is that, so it will change our gradient descent gradients. So that is the reason. Like, we know that gradients is nothing but how much your cost function changes when your weight changes and so on. So when you use this kind of a cost function, the final result is that your gradient descent will try to push the weight value towards zero. So if a particular column is not at all important, okay, so in that case that particular weight value will become zero, so that column will be completely neglected. So you can also consider that this as a kind of an automatic feature selection, where the model try to neglect the features that are not important for our prediction. So that is another main advantage of lasso regression, where it can automatically determine whether a particular feature is important for the output variable, which is my price, or whether it is important or not. If it is not at all important, if it is not related to the price of the house, then in that case the weight value will become zero for that particular column, and that particular column will be neglected. So this is how everything comes together. So we will basically have this cost function, and because of having this kind of a cost function, this penalty term will try to push the weight value towards zero, so that you have minimum weights and minimum input features to your model. So this is how a lasso regression basically works. This is how the math behind lasso regression basically works. So in the next video we will try to understand how the gradient descent works, especially for a lasso regression model, and what is this formula and the derivations for this gradients for this lasso regression. Then we can understand how this weight value is pushed towards a zero. Okay, so that's it from my side for this particular video, and I hope everyone is clear about the topics that we have covered here, and I'll see you in the next upload, where we can discuss about the gradient descent for lasso regression. The module is all about building machine learning models from scratch. So in my previous videos I have explained you what is the intuition and math behind a lasso regression model, and in today's video we will be discussing what is the gradient descent for lasso regression and how gradient descent works for lasso regression. So once we understand all these things, in the next video we can move on to the hands-on part, where we will try to build this lasso regression model from scratch in Python. Okay, so let's get started. So I'll just give you a quick recap of what we have seen in the intuition video and math video of lasso regression. So we know that lasso regression is a supervised learning model where we train with the labeled data set, whereas in the case of unsupervised learning model we train with the unlabeled data, and the lasso regression is one of the examples of supervised learning models, and it is a regression model. So further, supervised learning can be classified into two types. One is classification and regression, when you are trying to predict the class of a data point or the type of the data point, so that is called as a classification problem. But whenever you are trying to predict some numerical value, some continuous value, so it is called as a regression problem. Let's say that you are trying to predict whether an image represents a dog or cat, so that represents a classification problem. Whereas in case you are trying to predict what is the salary a person is expected to make, so in that case salary is a numerical value, right? So this will be a regression problem. So lasso regression is a regression model where it will try to predict some continuous value, and the full form of this lasso regression is least absolute shrinkage and selection operator, because this lasso regression model try to shrink the weight values and thereby try to eliminate those values which are not important for the final predictions. So it can also be used as an automated feature selection technique. So that is why it gets this name of least absolute shrinkage and selection operator. And the main thing about lasso regression is that it uses L1 regularization in order to avoid overfitting. So overfitting is the issue that we get in machine learning models when they overtrain on the training data. So in that case they only have good performance, good accuracy on the training data, data, whereas if you test the model with new test data, then the performance of the model will be very poor. So that is called as an overfitting issue, and this is overcome by the lasso regression using the L1 regularization technique. So we have also seen all about this L1 regularization in the previous video. So the only difference is that, so to a normal regression model, we add a penalty term called as lambda. So this penalty term tries to eliminate a few weight values that are not significant. So let's say that we have 10 input features in our data set. Let's say that we are trying to predict what is the salary a person is going to make based on certain input features. So these input features are nothing but what is their academic performance, what is their job performance, and all those things. So some features may be important for our final predictions, and some input features may not be important. So the lasso regression, so this particular L1 regularization tries to eliminate those input features by pushing the value of the weight towards zero. So let's say that we have an input feature for the name of the person. So we know that a person won't get a job based on his name, right? So what happens is the lasso regression model will try to push the weight of that particular name column towards zero. So what happens is that particular column will become a zero. So the idea here is to in order to reduce the complexity of the model. So that is all about this regularization, and particularly L1 regularization, we use this penalty term in order to either eliminate coefficients or to shrink their values in order to avoid this overfitting. So you can see the example curve here. So the red color curve represents overfitting because it changes regularly with all the data points. So there is not a general trend. Whereas if you see this green color curve, there is a general trend. So first of all, it increases and then slightly decreases and so on. So there is a trend, whereas you cannot find the trend in the red color curve. So this red color curve is a overfitted model, whereas this green color curve is an optimum model. So that is all about this regularization, and its main purpose is to avoid overfitting. And we have also seen the cost function for the lasso regression model, which is given by this particular equation. So this is similar to the mean squared error that we add for our linear regression loss function. So the only difference is that we add this penalty term, which is lambda, which is our penalty term or our regularization parameter, into our weight values. So the number of weight you have in a model is equal to the number of input features. So let's say that we have a data set, and this data set contains about 10 columns. Out of these 10 columns, one is the output column, which we are trying to predict, and the other 9 columns are our input features column. So the number of weights you have is equal to the number of input features that you have. So in case you have 9 input features, in that case you will have 9 different weight values. So that's what the importance of weights. So this wj is basically an array. So wj represents each weight value in that particular weight array. So you can see here, so m represents the total number of data points, or in other words, the total number of rows you have in your data, and n represents the total number of input features. So, or in other words, the total number of columns you have in your data set except the output column. And yi is the true value. So the true value which is present in our data set, and yi cap is the value predicted by our model. Okay, so and lambda is our penalty term, and w is the parameter of the model. To be precise, it's the weight of the model. So what we will do is we will use our model in order to make some predictions, and those values will be stored in this y at. Okay, and after that we will try to find the difference between y and this y at, and it will give us give the cost function for our model. So cost function basically tells you what is the difference between your true value and predicted value. So that is the importance of this cost function. So the reason we are discussing about this cost function is it is very important for us in order to implement gradient descent. So gradient descent is based on the cost function of a model. So that's why we need to discuss about this cost function. So now we can move on to the gradient descent part. So basically how a gradient descent works is, so you can take the weight value in your x-axis, and you can take the cost function in your y-axis. So how we will generally proceed in machine learning is that we will randomly initiate the parameter values. Okay, so let's say that this is our randomly initiated initial value for this weight. So this can be any value, and for this particular value, let's say that our cost function value is at this point. So you can see here this is the upper part of this axis. That means the cost function value is very high. So it means your model is not going to make good prediction. So it is going to make some errors. So that is what is signified by this position of this weight. So if you choose the weight at this point, your cost function will lie at this point. So what we need to do is, so from this point we need to reach to this lower part of this curve. Okay, so when you plot a weight and cost function, so you will get a curve like this. So it is called as a bell-shaped curve. So we need to reach this point. So this point is called as the global minimum. So what this signifies is, so if you choose the weight at this particular point, you will have the minimum cost function. So our goal in machine learning is to minimize this cost function. So which means our model is performing well, or in other words, the model is not making any errors or so on. So we need to reach to this global minimum from this initial point. Okay, so that's what we are interested in. So we implement a gradient descent algorithm where we will try to keep on changing this weight value. So you can see now the point is here. So what this basically means is we are gradually changing the weight value, and now we are choosing the weight value from at this particular point. So you can see here now what happens, your cost function decreases. So we will do this repeatedly in order to reach this point. So if you start from a random initial point, your gradient descent works in order to reach this global minimum. So if you consider a weight at this point, so your gradient, the first model, so I'll just show you. So what happens, let's say that we are taking the weight value at this particular point. So in that case, your cost function may be at this particular point. So this gradient descent again will try to come to this global minimum starting from this point. So it will try to come to this particular point. So this is how gradient descent works. So no matter at what part of the curve you work on, it will try to reach this global minimum, and this is the working of a gradient descent. So we have discussed this multiple times in our models. So this is how gradient descent, if you want to visualize in a three-dimensional space. So I've just shown this in a two-dimensional space where we have weight alone, whereas in the case of three-dimension, it may look like this kind of a curve. So what happens is we take this both weight value and the bias value, and then we will try to apply this gradient descent in order to find the optimum value of weight and bias. So the main goal of this gradient descent is to get an optimum weight value and bias value. So when you have the optimum weight value and bias value, so your model is going to make good prediction. So that's the idea behind a gradient descent model. So I'll just give you a definition for this gradient descent. So gradient descent is an optimization algorithm. So we are going to optimize our machine learning model, which is used for minimizing the cost function. So this is our final goal, which is to minimize the cost function. So minimum cost function means there is not much difference between the true value and the predicted value, which means that your model is making correct predictions. So minimizing the cost function in various machine learning algorithms, it is used for updating the parameters of the learning model. So parameters of the learning model is nothing but my weight and bias. So this is the the formula for a gradient descent. So you can see here. So this W2 is my updated weight and W1 is my initial weight. So if I come to this particular point, so if you see this, so this is my initial weight, and the second circle is my updated weight. So that's what is represented in this particular equation. So you can see here, so this W1 is my initial weight and W2 is my updated weight. So I will take my initial weight and I will separate it with this term L into dj divided by dw. So what this basically means is L represents the learning rate. So learning rate is nothing but how much change do you want to give to your model. So you can see this gradient descent curve. So you can see, so we are starting from a point and we are reaching this particular point. So we are changing the weight value, right? So this learning rate is nothing but how much change do you want to give to your weight value. So that is represented by L, and you can see here. Okay, so L is our learning rate, and dj divided by dw is nothing but the partial derivative of cost function with respect to w. So we are finding the derivative of the cost function. So we have already seen what is the equation of the cost function, or what is the formula for cost function for Lasso regression. So we take that cost function and we derive it in terms of w, in terms of weight. So what this basically tells you is how much your cost function changes if your weight changes. So again, I'll go to this curve. So I'm starting from my initial random value of weight, and I'm changing the weight value. Right now my cost function changes. So if I take this, so this is my initial cost function value. Okay, so this point is my initial cost function value, and once I update the weight, the updated weight, so now the cost function will kind of decrease. So you can see, so this is the difference, right? So this basically tells you how much your cost function changes when you change the weight value. So this is nothing but the slope of this particular curve. Okay, so that is represented by this dj divided by dw. So this is what we use in order to minimize the cost function by changing the weight value. So this is the first equation in order to update our weights, and the second equation is for updating the bias value. Okay, so a model will have multiple weight values, so you can consider a weight as a list of values. So which is as I've told you earlier, the number of weight values you have in a model is equal to the number of input features that you have. So it is basically an array, or you can consider it as a list of values, whereas bias is a single value, so it is a single real number value. So that is one main thing that you need to remember, and this is the formula for updating the bias value, so which is basically the same thing. So W2, which is the updated weight, is equal to initial weight minus learning rate into dj divided by dw, and B2 is equal to, so which is my updated bias, is equal to initial bias minus learning rate into dj divided by db. So you can also call this dj by db and dj by w as, so these are called as my gradients, these two terms, dj by dw and dj by db. So these are called as gradients of my model, or you can also call these as derivatives. So the only difference is that we will have different formulas for this dj by dw and dj by db. Okay, so that is the next thing that we are going to discuss. So in Lasso regression, this is a bit tricky. So we have two cases for our gradient for weight. So this is my djw by db value, which is my partial derivative of cost function with respect to w. So we have two cases. If your weight value is greater than 0, in that case we use this equation. In case your weight value is less than or equal to 0, we use this particular equation. So the only difference is that in this case we take a positive penalty term, and in this case we take a negative penalty term. So that's the difference. So what is the significance of this positive weight and the negative weight is that, so if let's say that we are trying to predict the price of the house. So we have features like what is the number of rooms we have in our house, what is the size of that house, and what is the crime rate in that particular area, and so on, right? So if we consider about the relationship between the total number of rooms in a house and the price of the house, there is a linear relationship between them. So there is a positive correlation, which means if the total number of rooms increases in a house, then the price of the house increases, right? So logically we can say that. So in that case, that particular column, so the number of rooms column will have a positive weight. Okay, so this basically tells you the weight value tells you how much important does a particular column is to the output variable. So in case you consider the total number of crime rates that is happening in that particular area, so what happens in that case, people don't want to buy houses in that area. So this will negatively or inversely affect the price of the house. So in that cases you will have a negative weight value. So positive weight value will basically tell you, so that particular feature is desirable for our output column, whereas negative weight value tells us that if this value increases, the final output decreases. So that is the importance of weight value, and so on. Okay, so and whenever you have a positive weight value, you have this positive penalty term, and whenever you have this weight value is either 0 or less than 0, which is basically a negative number. So this is positive number, this is negative number, so you have to take minus lambda. Okay, and the dj by db value is the same for both the cases, so it won't change. Okay, so dj by db is equal to minus 2 divided by m summation of yi minus y cap. So where y cap, or this y at, is my value predicted by our model, and y is the true value. Okay, so we take the summation of it and we plug in the values, and you will get this dj value and dw value, again dj value and db value. So once you get this value, you can put all these values in this equation, which is my gradient descent updating weights and bias value equation. And once you do this, you will get the most optimum weight value and bias value. So these two are my perfect weight value and bias value for my Lasso regression model. So these are the things that you need, and the final equation that we need in order to build our Lasso regression is the equation of the straight line, which is y is equal to wx plus b. So as I've already told you, Lasso regression is actually built on top of the linear regression. So the only difference is that how gradient descent works for linear regression and Lasso regression. So we have the extra penalty term when it comes to Lasso regression, but we don't have this penalty term in the linear regression. So the reason for adding this penalty term is in order to reduce the overfitting problem. So how we will approach this Lasso regression is that, so these are the equations that you need in order to build your Lasso regression model in Python. So what we will basically try to do is, so we will have our data set. So we will have both x and y, where x is your input features and y is the output variable we want to predict. So this will be given from our data set. After that, we will try to initiate some random values for this weight and bias. So we generally initiate the values with 0. So w2 will be an array which contains all the values as 0, and bias will be a normal value. So it will be the value will be 0 in the case of bias. So first of all, we will try to initiate weight value and bias value. So once we do that, we will try to plug in this value in this equation. So after that, we will try to make prediction and we apply this gradient descent algorithm. So now it will try to go to that global minimum part where it is the optimum weight value and bias value using these two equations. Okay, and once we do that, we will get the optimum weight value and bias value, and we can substitute that value in this equation. So now you have a different x value, we can get the y value. Say for example, if you want to predict the price of the house, so you can give all the input features, and now based on this learning, so learning is nothing but finding this optimum weight value and bias value. So based on this value, our model can give you what is the price of the house is expected. So this is how the gradient descent for Lasso regression works. And the main importance of this gradients is that this penalty term will try to push the value of the weight and weight value towards zero. So which we have already discussed, because the purpose of this is to decrease the complexity of the model. So whatever may be the weight value, if it is greater than zero or it is less than zero, so its goal is to push the value towards zero. So if like how we do it is like so the importance of this gradients equation is that to make the model understand which column is important and which column is not important. So if you see, this xj is nothing but the individual columns that we have. So it's okay if you don't understand all the terms in this equation, so you will understand it better once we are implementing this hands-on in Python. So in that I will show you the data set as well as how this equation works and so on. So it will give you more clarification. So the only thing here that you have to understand is the Lasso regression model. This penalty term tries to push the weight value towards zero. Okay, so that will reduce your problem of overfitting. So this is all that we need. So first of all, we will initiate our weight value and bias value, and then we will implement our gradient descent in order to find the most optimum parameters of the model. And after that, we can use this linear regression equation in order to find the final output. So this is what we are going to be doing in our Python. So we will basically write all these formulas in Python, and we will create a class called as Lasso regression, and we can use that particular Python class in order to make predictions using the Lasso regression model. So that's it from my side. I hope you understand all the things that is covered in this video, and in the next video I'll explain you how we can build this system in Python. And this seventh module is all about building machine learning models from scratch. In my previous videos I've explained you what is the intuition and math behind a Lasso regression model, and how we can determine the gradient descent for a Lasso regression model. And in today's video, we will try to apply all of those things that we have learned. And in this hands-on part, we will try to build this Lasso regression model from scratch in Python. So this is the agenda for today's video, and let's get started. So I'll open my Google Collaboratory. So I hope everyone knows about Google Collaboratory, and this is where we will do all the coding part. So as you can see here, I have already connected my system, and I have made some statements and text about this Lasso regression model. As I have explained you in the previous videos that a Lasso regression model is built on top of a linear regression, and hence we use the same equation, which is the equation of a line, which is y is equal to mx plus c. So the only difference between the linear regression and Lasso regression lies in its gradient. So we will discuss about all of those things. Okay. So for now, understand that it is the equation that we use here is same as the equation of a linear regression, which is the equation of a straight line, which is y is equal to mx plus c. So instead of m and c, we will use w and b. So m is nothing but the slope of the line, and c is the intercept of the line. So we will replace that slope m by weight w, and intercept c by bias b. So we have the equation y is equal to wx plus b. Okay, so now let's try to understand what is meant by this y and x. So y is a dependent variable because it depends on x, and x is the independent variable. Okay, so let's consider an example. So we are trying to find the salary of a person based on their work experience. In that case, x is nothing but your work experience, and y is the salary of the person. So we can say that the salary of a person depends on what is their work experience. So this is why we call this y as a dependent variable, because it depends on x, whereas x is an independent variable, and we are trying to find that relationship between y and x. So the function of a model, or the role of a model, is to find the best value for this weight and bias so that it can make accurate predictions. So once we build this model, if we give this x value, the model should predict the y value. So that is the idea behind this, and the main role of a model is to find this parameters, which are weight and bias. Okay, so that is about this equation of a line, which we use for this Lasso regression, and this is the gradient descent part. So we use this gradient descent in order to find the optimum value for this weight and bias for this w and b, and that is the role of this gradient descent. So you can see the definition of a gradient descent here. Gradient descent is an optimization algorithm because we are basically optimizing the model for better parameters. Okay, so optimization algorithm used for minimizing the loss function in various machine learning algorithms. It is used for updating the parameters of the learning model. So loss function is nothing but it tells you how much your true value and the predicted value differs. So it is nothing but the difference between those two values. So what is your model is predicting and what is your is your true value. So that is called as the loss function. So if we take the difference between the true value and the predicted value for all the data points that we have in a data set, then it is called as a cost function. If you try to find the difference between the true value and the predicted value for only one data point, it is called as a loss function. So I hope everyone understand this, and I have already made a video on these things as well, so you can also refer my loss function video so you can find details there. Okay, so the main goal of this gradient descent is to minimize this loss function. So minimum loss function, what tells us is, so if you have a minimum loss function for a model, then we can say that the true value and the predicted value are very close to each other. So you can say that your model is making good predictions and it is accurate, or the performance of the model is good. So that's what we want. So the gradient descent will try to minimize this loss function by finding the optimum value for weight and bias. So this is the role of a gradient descent, and this is the formula we use in order to update the weights and bias. So what happens in a machine learning problem is that when we feed a data to a machine learning model, it goes through the data again and again. So we can say that, let's say that we are, want our model to go through the data 1,000 times. So we will mention that. So let's say that we will mention that number of iterations is equal to 1,000. So in that case, the model will go through the data 1,000 different time, and each time it will try to, change the weight and bias value, and it will check whether the model is predicting correctly or not. So that is why we use this formula W is equal to W minus alpha into DW, where W in your left hand side is the updated weight, and the W in the right hand side is your previous weight. So we will take this previous weight and we will subtract it with the product of alpha and DW. So alpha is nothing but your learning rate. So you can see the definition also here. So learning rate is nothing but what is the change that you want to give to your weight or your bias. So it is nothing but the change you want to impart to your parameters. So you can see the definition here. Learning rate is a tuning parameter in an optimization algorithm that determines the step size at each iteration while moving towards a minimum of a loss function. So we will try to reach a global minimum in gradient descent. So we have also discussed about this multiple times. Okay, so let's say that we have gradient descent, and when we are plotting this gradient descent, we will take cost function in our y-axis and weight in our x-axis. So we are going to take different weight values, and we are going to see for which weight value we have the minimum cost function. Okay, so when you plot the cost function and weight, you will get a U-shaped curve like this. So this is example of a convex curve, and let's say that we are randomly initiating some weight value. Okay, so we have randomly given some value for our weight, and for this particular weight, your model has a cost function which is at this point. You can see here that at this point the cost function value is very high. So our goal is to reach to this point. So what this point signifies is, at this point, if you choose the weight value at this particular point, you will have a very minimum cost function. So that is what we want. So we want to minimize our cost function. So we need to come to this point from this point. So this is why we use gradient descent. So each step we will try to change our weight value, and we will try to see how much our cost function changes until we reach this global minimum. Okay, so this step size is nothing but your learning rate. So how much change do you want to give to your weight value or your bias value? So this is how a gradient descent algorithm works, and that's what we have mentioned here. Okay, so alpha is nothing but your learning rate. You can see the definition here, and this is the first equation is the formula for updating the weight, and the second formula is for updating the bias value. Okay, and you can see the gradients formula here. So in the previous videos we have discussed about this detailing, so you can refer that video in case you haven't watched those. Okay, so in that I have explained you what is meant by this gradients. So you can see here dj by dw. So this is what is represented as dw here, and so basically dj by dw tells you how much your cost function changes when your weight changes. So if you come to this gradient descent, so as you can see here, so in each step we are changing the weight value, right? So we have changed the weight value by this particular magnitude, and for this magnitude we will try to see what is the change in the cost function. So this is called as your gradient. So this gradient is required for us in order to make good updations, in order to arrive at optimum weight value. So this is the formula for this dw. So this dw is nothing but your dj divided by dw. So for weight we have two cases. So like we take the weight value and we will see whether that weight value is greater than or less than 0. Okay, so if this particular weight value is greater than 0, we will use this equation. If the weight value is less than or equal to 0, we will use this second equation. So the only difference is that we add a penalty term. So if the weight value is greater than 0, we should add this penalty term. If this weight value is less than 0, we will subtract this penalty term, which is our lambda parameter. Okay, so here you can see here yi is your true value and yi cap or yi at is your predicted value. So we will try to find the difference between them for all the data points, and we will try to subtract them and take a summation of it and add some penalty value. So this is how we get this dj by dw. So the only difference is that if the weight is greater than 0, add penalty. So if the weight is less than 0, we should subtract that penalty term. And bias is the same for both the cases, so it doesn't care whether the weight is greater than 0 or less than 0. We have the same formula. Okay, so this is dj by db is for this particular term, alpha into db. Okay, so this is the value of db, and we will manually give the value for this learning rate and our penalty term, which is lambda. So let's see how we can build this lasso regression model now. So the only difference is that we have this penalty term in lasso regression, which we won't have in a linear regression model, and that is the difference between them. So now what we are going to do is we are going to build all these equations in Python, and we are going to create a lasso regression model. So that is the idea behind this. Okay, so let's see how we can do this. So just a second. Okay, so first of all, I'll make a text here as importing the dependencies. So we won't be using libraries. So I'll be using only the NumPy library. So importing the dependencies, and here I'll import NumPy as np. Okay, so let's run this, and now we can create a class for lasso regression. So I'll create another text here, and I'll name this as lasso regression. So we are going to create this lasso regression model, and how we are going to do this is by creating a class. So I'll make a comment here as creating a class for lasso regression. Okay, so class is the keyword that we need to use for Python, and class, we can name this class as lasso underscore regression. Okay, so once we complete this, we will compare the performance our model, the model that we have built, and we will also compare what is the performance of the lasso regression model that we have in sklearn, which is ready-madely available. Okay, so now we are going to create this class. So now let's try to understand what is meant by this class. Some of you may know, and some of you might not know what is a class. So I'll explain for those people who doesn't understand clearly what is meant by this class. So let's say that we are building this lasso regression model, so we don't want to write this code every time we want to use lasso regression. So in this case, what we will do is we will try to create a template for this lasso regression. So this lasso regression is now called as an object, and let's consider this example. So let's say that we want to build a car. So in order to build a car, you need a template, you need a blueprint for it. Okay, so this class is nothing but the blueprint. So in the example that I've given you, the car is the object, and the template or the blueprint that you have for your car is called as your class. So we are going to create an object called as lasso regression, and the template for this lasso regression will be made using this class. Okay, so once we do this, we can use this lasso regression code multiple times without writing this code again and again. So we are basically creating an object called as lasso regression, and this class is the template for it. You can understand in that way. So we need to mention some functions for this class. So we need 4 functions. So I'll just mention the comments and the respective functions. So the first function that we need is the initiation function. So I'll make the comment here as initiating the hyperparameters, and the keyword in order to write a function is def, which stands for define. So define, so you should mention 2 underscores in it, and again 2 underscores. So this is for initiating the parameters of the model. So this is our first function, and the second function that we need is the fit function. Okay, so and this particular function is for fitting the data set to the lasso regression model. So this is a second function, and I'll name this as def fit. So this is my second function. So what we will basically do is, once we complete this code, we will fit this model with the data set that we have. So that is the reason for creating this fit function. And the third function that we need is the gradient descent function. So the updating part of the gradient descent function. So as I mentioned earlier, so we can update the weight and bias using this two formulas. So that's what will be your third function. So this is the function for updating the weight and bias value. Okay, so we can name this as update weights. So update weights. So this is our third function, and finally we need the last function, the one more function, which is the predict function. So the role of this function is to predict the target variable. So when you give the value of this x, this function will give you the value of y. So that is what we are going to do, and this function is for predicting the target variable, and let's name this as def predict. Okay, so these are the four functions that we have. So the first function we have is the init function, which is used in order to initiate some parameters, the learning rate, the number of iterations, and the lambda parameter. Okay, and the second function that we have is the fit function, and the role of this fit function is to fit your data set to your Lasso regression model. And the third function we have is the update weight model, update weight function, which is used to update your weight and bias value. Okay, and the last function, the fourth function that we have is the predict function, and the role of this predict function is to predict the value of y given the value of x. Okay, so that these are the four functions that we need. So I'll just name this as update weights. So now we should give some parameters to these functions. Okay, so the first thing that we need to mention is the inbuilt parameter, which is your self. Okay, so you should mention this self in all your functions. So define, so this will be your default first parameter, and yeah, update weight self, and finally for this also we should mention self. So let's try to understand what is meant by this self now. So once we complete this Lasso regression code, what we will do is we will try to call this Lasso regression class or Lasso regression object. So how we will do this is, so we can create a variable called as model, and once we complete this, so we should call this function, which is Lasso underscore regression. So Lasso underscore regression, and we will mention the parenthesis here. So once you complete all this code, so we should fill in all these functions. So we have a lot of code to write within this function. For now, let's say that we have completed this code. So after that, we will try to train our model. So while training that model, you need to load this instance to a variable. So let's say that we are creating a variable called as model, and we are loading an instance of this Lasso regression to this term called as model. So once you load that, what you will do is, so we will write as model dot fit, and within this we will give the x train and y train. So this is the fitting part. So for this only we are creating the fit function. Okay, so now as you can see here, we have an instance called as model, right? So this model is your self. So like within this code we should mention this instant as self. So what happens, like model dot fit will be considered as self dot fit. So that's what happens. So like this self is nothing but the instance that we are creating for our model. So that is the role of that. So you can just think about this self as the instance that we are going to create after completing this. So we don't require this right now, so I'll just delete this. So we should mention the self as the first parameter for all the functions that we have within this class. So that is our next step. Now let's try to mention the parameters that we need. So in this init function, we should mention three main parameters. They are learning rate, and the second parameter will be number of iterations, and the third is your lambda parameter. So lambda parameter is nothing but your penalty term which we need for our Lasso regression model. So lambda parameter. So these are the three parameters that we need to initiate within this init function. Okay, so learning rate is nothing but, as I've told you earlier, what is the change do you want to give to your model when we are applying gradient descent, and number of iterations is how many times you want your model to go through the data. So that is given by number of iterations, and lambda parameter is your penalty term. Okay, so these are the three things that we need, and now we are going to initiate it. So how you can initiate it is, you need to mention self dot learning rate, Okay, so this self is nothing but the model, the instance name that we are giving in the later part. Okay, so we can just think about this as model dot learning rate. So this is how we can initiate the values. So self dot learning rate is equal to learning rate, and the second parameter is, we know that, number of iterations, right? So self dot number of iterations is equal to, so you should just write the same thing, number of iterations. And the third parameter that we have is self dot lambda parameter. Okay, so I think I made a mistake, a small spelling mistake. So lambda parameter, lambda parameter is equal to, again, lambda parameter. Okay, so what happens is, when we are implementing this model, or when we are creating this, or calling this Lasso regression model, we will manually give some value for this learning rate, number of iterations, and lambda parameter. So we can give that model when we are using this particular model. So we don't need to manually give the values now, but in the later part of the code, while we are implementing this, we will give these values. So this is the next part, which is initiating the parameters. So the next thing that we have to do is write a function that can fit the data to your model. Okay, so this is the next thing. So for fitting the function, you need x data and y data. As I have shown you before, that while we are fitting this using model.fit, we need to give x train and y train, where x is your independent variable and y is your dependent variable. So what happens during this fit function is that your model will try to find the relationship between this x and y. Okay, so it will try to find the optimum values for w and b using this gradient descent, and all those things happens in this fit function. So basically, when you are running this fit function, you should give that function both the x value and the y value. So those will be your parameters. So self comma x comma y. So these are the two parameters that we need to mention along with the self parameter. And here we need two things. One is m and the other one is n. Okay. So m is nothing but, it is the number of data points that you have in your data set. So number of data points that you have in your data set, or in other words, you can also say that this is nothing but the number of rows, and n is nothing but your number of input features. And we can also say that this is nothing but the number of columns that we have in our data set. So let's try to understand this. So we need to these two values. So the data set that we will be using in order to implement this is the salary data that we have. So I'll try to open this in a notepad file. So you can see here we just have two columns. So this is a very small sample data. It contains about 30 data points. So the value in the first column contains the years of experience, and the second column contains the salary. Okay, so what it means is, like, if a person has 1.1 years of experience, it means like they can make a salary of about 39,000 per month or so on. So this is the salary and years of experience data that we have. So from this data, we need to determine what is the total number of rows we have and what is the number of columns. So the reason is that, so you can see that we have some weight value here, right? So weight value and bias value. So a model as, like, let's say that your data set in this case has only one input feature. So this years of experience is your input feature. So what input feature means is, like, based on this input feature, we can find the target value, which is our salary. So in this case, so this salary is my target column, and this years experience is my input feature column. So the number of weights you have in a model is equal to the number of input features that you have in your data set. So in this case, you can see here we have only one input feature column. So your model will contain only one weight value. So let's say that we are predicting the salary of a person based on the input features, like what is their years of experience, so what is their academic performance, and what is their CGPA, and so on. In that case, let's say that we have three input features. So in that case, your W, so you can see this W here. So it will contain three values. So this W. Okay, so what you need to remember here is the number of weights you have in your model is equal to the total number of input features that you have, and bias is just a single number. It is a single real number, whereas this, you can consider this weight as an array which contain multiple values. So if you consider this data set, we just have only one input feature, which is our years of experience. So in this case, it will contain only one weight value. So in other case, it will be a list of values which will contain multiple values, which is equal to the number of input features that we have. So we need to determine how many input features are there. So that is given by this n. So n basically represents the number of input feature, or in other words, it is the total number of columns except the salary column, because this is the target column. So we shouldn't consider this target column, we should consider only the input features. So n will be the total number of input features, or in other words, you can say it is the number of columns, and m is the total number of data points that you have. So the number of data points is nothing but we totally have 30 data points from year to year. Okay, so there are totally 30 lines, which means 30 rows are there. Okay, so we need to find these two values from a data set. So so that will be our next step here. So we need to find the value of this m and n. So how you can do that is, so we know that x is my input feature. So when we feed the data set to our model, what we will basically do is we will separate this input feature and we will separate this target column. So we will feed this separately to our model. So your years of experience will be your x value, so the x that we have mentioned here, and the salary will be the y value that we have mentioned here. Okay, so now we should basically try to find what is the shape of this x. So if you find the shape of this x, you can determine the value of m and n. So let's see how that works. So self.m comma self.n is equal to x.shape. Okay, so we will basically, before feeding the dataset to the model, we will drop this target column. Okay, and it will just contain the first column values, and the shape of this first column is nothing but 30 into 1, because we have 30 rows. So that is how we will represent the shape of a matrix, right? So the first value represents the number of rows, and the second value represents the number of columns. So if you try to remove the salary column, so I'll just open this in my Excel file. It is more easier to understand. So let's say that we have the data set here, and I'll try to delete this second column, and now I have only one column here. Okay, so I have only this years of experience column, and it totally contains about 30 columns. So this 31 is nothing but the first column is your column name, so we can ignore that. So totally we have about 30 columns, or 30 values here. So there are totally 30 rows and one column. So the shape of this x will be 30 into 1. So this is my x now, where I have removed the target column, which is my y. So the shape of this x is 30 into y, where the first value 30 is your total number of data points, or the number of rows which will be given to this m value, and n is nothing but the total number of input feature, or in other words, what is the number of columns that you have in your x, and that will be your n value. So you can find this m and n value by calling this x dot shape, where x is your the input data set. Okay, so removing this target column, so that is my m and n. So the next step that we will do is we will try to initiate the parameters and this x and y. So you can see that we have two parameters which are weight and bias, w and b. So we will try to initiate it. Let's see how we can do that. So it is so as I've told you before, we will randomly initiate some value for our weight and bias, as I mentioned here. So how we will basically initiate the values, we will give the value as 0. So I'll say that self dot w is equal to np dot zeros self dot n and zeros. Okay, and self dot b, now we are initiating our bias value, which is 0. So what we are doing is we are creating an array for this weight. So as I've told you earlier, weight won't be a single number. So this weight will be an array, or you can consider this as a list which contains the number of values, the number of weight values that you have is equal to the number of input features. So we should create this weight as an array. So that's why we are creating this weight as a numpy array, where all the values of this numpy array will be 0. So that is the use of this np.zeros function, and the shape of this array should be self.n. If you look at this data, so we have removed the y part, and now this is my x, and this x contains 30 rows and one columns, right? Where 30 is my m value, which is the total number of rows, and n is my number of columns. Here the number of columns is 1. So this particular array np.zeros, if you give the value as self.n, so in this case the value of this n is nothing but 1. So it will create an array which contain only one value. Okay, so you will basically have only one weight value here, because we have only one column. So some dataset which contains a lot of input features. So let's say that we have a dataset which contains 10 input features and one target column. In that case, what happens is your n will take, so you can see here, so in that case, if we mention x dot shape, your n will take the value as 10. So if you mention the value as 10 here, so what happens, we will get a numpy array which contain 10 values as 0. So in this case the value will be 1, and yeah, because we have only one column. So That is why we are using a numpy array and we are creating all the values as 0. So we will initiate the values with the 0. So this is the general convention that we use. So instead of randomly initiating values, we give all the values as 0. And as I've told you earlier, bias is a single number. It is not an array, it is just a single real number. Okay, so this is how you can initiate the weight value and the bias value. And then we should initiate the x and y value. So self dot x is equal to x, and self dot y, which is your target variable, is equal to y. So the next step is, just a second, okay, self dot y is equal to y. So the next thing that we are going to do is, so we are good with this weight value, bias value, and so on. So we have randomly initiated this weight value. So the role of our model, the function of this model, is to find the optimum values for weight and bias. So it will basically start from the value 0 for weight and bias, and it will work its way all through in order to find the optimum value for this weight and bias, and that is done by this gradient descent. So we need to write these two functions along with this gradients formula in order to build this. Okay, so that is our next step, which is implementing gradient descent algorithm. So I'll make a comment here as implementing gradient descent algorithm for optimization. Optimization is nothing but finding the optimum value for weight and bias. Okay, so for this I'm going to create a for loop. So for I in range, number of iterations. Okay, so if you remember, we have initiated this hyperparameter value called as number of iterations. So this is nothing but how many times you want your model to go through the data, and each time it will change your weight value and bias value, right? So let's say that we are mentioning the number of iterations as 100. So in that case, this for loop will run 100 times, and your gradient descent will try to change the weight value and the bias value for 100 times, and it will try to reach that optimized value. In case you mention this number of iterations as 1000, and then 1000 times this for loop will run. So that is the idea for it. So this number of iterations is nothing but the parameter that we initiated here. So for I in range, so each time the model runs through this for loop, it should update the weights. So for that we will call this function update weights. So this we are calling this function within this function. So you can see here this update function is one of the function that we have in this class Lasso regression, right? And this fit function is again the function that we have within this Lasso regression. So now we are going to call this update weight function. So what we are basically doing is we are calling the function that is already present in that particular class. Okay, so this Lasso regression already contains this update weight function, and we are calling the same function here, which comes under this fit function. Okay, so what happens now is, so each time this for loop runs, it will try to update the weights. So it will try to change the weights and bias value, and that is what is done by this update weights. So now we need to build the function for this update weights, and that is our next step. As you can see here, the role of this is to update this function is for updating the weight and bias value. Okay, so let's try to do that. So for this, first we need to build the linear regression equation. So I'll just name this as linear equation. So linear equation is nothing but the equation of the straight line, because we know that Lasso regression is based on the equation of the straight line, which is similar to the linear regression model. So the linear equation of the model. So now I'm going to create an array called as y prediction. So this y prediction is equal to self dot predict. So self dot predicts self dot x. So before explaining what is meant by this particular line, let me complete this predict code, because we need this predict code here. So this predict is nothing but your final model. Final model is nothing but wx plus b, that will contain the optimized weight value and the optimized bias value. So that is your predict, and for predict you need this x value. Okay, so like let's say that in this init function we are having three parameters, so that's why we have mentioned learning rate, number of iterations, and lambda parameter. So whenever we are fitting the model, we need x and y. So we will fit the model based on this x value along with the y value, and this update weight function, so we won't use it beyond this particular class. So this update weight is used within this class, so we don't need to mention any parameters other than the self, and we will use this predict function out of this class as well. So what happens is, once the model is trained, once you get the optimum value for weight and bias value, if you give a new x value, it will try to give you a y value. So that is what is done by this predict. So we can write this predict as return x dot self dot w plus self dot b. So this is nothing but the equation that we have here. Wx plus b is nothing but it is represented as x dot self dot b plus b. So this is nothing but the equation of the straight line. So what happens is, so we are initiating the weight value as 0 and the bias value as 0, right? And we are running this for loop. So what happens when we are running this update weight function? We are creating an array. This array is nothing but the values predicted by your model based on your initiated weight value and bias value. So the initiated weight value and bias values are nothing but just zeros, right? So what happens is, like, this w will take the value as 0 and this bias will also take the value as 0, and that will be, this w will be multiplied this with this x, and this term will be added with this bias value. Now you will get a value which will be 0, right? Because both w is 0 and bias is 0. Now this value will go to your y prediction because we are calling the predict function here. So what happens is, we are giving the x value, and based on the x value we are trying to predict the value of y using the equation of the straight line. So now what happens is, we are just trying to predict the y value using the initiated parameter. So the reason we are doing here is, so we know that this is not the optimum parameter value. 0 and 0 is not our optimum value. So what we will try to do is, we will take this prediction made by our model, we will find the difference between this y prediction and the true label, which is my y. So the true label in this case is nothing but your salary column. So you can see the salary column. So this is my true value. Now the value predicted by my model, which is stored in this y prediction, will be subtracted with this salary column. So this is our next step. So once you find the difference, you can implement this gradient descent in order to carry out the thing. So if you see this gradient descent equation, so you have this particular term, right? So y minus y I cap. So this is the part which tells us what is the difference between my true value and the predicted value. So now what the gradient descent model will do is, if the difference is too high, it will try to change the weight value and the bias value. So it will try to repeat this process so many times until it reaches the most optimum value, which is my global minimum, as we have seen here. So the global minimum, so it will try to start from the random weight value and the bias value. It will try to compare the predicted value and the true value that we have, and if the cost function is high, and then it will try to change the weight value and the bias value, and this step will go on. So that is this step. So we are taking the initiated weight value and bias value and predicting some value and comparing it with the true value. So that is what happens here, and that is why we need this predict function now in order to make the prediction with the initial values. So the next thing that we are going to do is write this gradient descent, sorry, the gradient formula. So these are called as your gradients, this dj divided by dw and dj divided by db. So once we write these two equations, we can write this updating weights equation. So the after that the code is complete. Okay, so let's see how we can do that. And so this part is for finding the gradients. So gradients are nothing but dw and db. So dw is nothing but dj divided by dw, and db is nothing but dj divided by db. So these are nothing but derivatives, partial. You can consider this as just basic differential calculus. So we are differentiating cost function in terms of weight here, and we are differentiating the cost function in terms of bias here. So that is the difference between them, and let's see how we can do that. So for I in range self dot n. So let's try to understand the equation of this gradients first. So you can see here, we should multiply the xi with the yi and yi at. So I think there is an error here. So here there should be xj. Okay, so I missed this. So you can see there's xj here, right? So this xj should be present here. So I'll just open my ppt. Yeah, so this is the correct equation. So you can see here, we should find the difference between yi and yi cap, and we should multiply it with this xj. Okay, so I forgot to include that xj here. So this is the right equation. So the only difference is that you should include a xj here. Okay, so xj is nothing but different columns. So in this particular data set, we have only one column. So this is my xj value. Okay, so in case you have multiple columns, so the first time you run this for loop, You can see here. So the first time you run this for loop, we will take the first column and then we will take the second column and so on, because each time we need to take that column and do some processing. So or else I'll complete this code and explain you what I'm doing. So just a second. So for I in range, so here we need to include a condition. So you can see here, if the weight value is greater than 0, we should use this equation. If the weight value is less than 0, we should use the second equation. Okay, so for that we are going to create an if condition here. If self.w I is greater than 0, in that case your dw will be, I'll mention this as dwi. So instead of mentioning j, I'll just mention I, so we don't want any confusion. So I'll just mention this as I. So wi, I'll explain you what all these things mean. So first of all, I'll try to complete these two equations. So this is -2. Okay, so let's write this as -2, and within this parenthesis I should mention self dot x, and we should slice this now. I dot self dot y minus y prediction, and with this we need to add the lambda parameter, which is self dot lambda parameter, and we should divide this entire thing by m. So this is my first equation. Okay, so if you just see this equation here, so this is what I have written here. So there is a mistake here, which is like we should include an xj here. So that is the difference. So xj represents each column that you have in your data set. So first we have this 2. So you can see that we have a -2 by m term. So we have this minus and 2 here. So this should be multiplied with this term, and this entire thing should be divided by m. So m is nothing but the total number of data points that you have in your data set. Okay, so that is your m. So this is like finding the mean of the entire thing. So as you can see here, we should multiply the xj with this yi minus yi cap. So this yi is my true value and yi cap is my predicted value. So if you see here, I have this self dot y here. So self dot y is nothing but, if you consider this data set, this is my y. So we have the true value. So this is my true value, and we should subtract it with the predicted value. So y prediction. So if you remember, we have created this array, right? So this is nothing but the value predicted by our model based on the assumed weight value and the bias value. So we should find the difference between them, and we should multiply it with each column of this x. So in this case, we have only one x column, so it is not an issue. So it will just multiply it with only this one column. So in case you have multiple columns in your data set, so your yi minus yi at will be multiplied with each of this column separately. So that's why we need this for loop. So the reason you need to understand this, like, we are not making this code for this data set alone. So we are making this code for a generalized term so that you can use this for different data sets. Okay, so that's why we are just making some like generalization. So I can just remove this m, and I can just mention that it is 30, because I know that there are totally 30 data points, but we are generalizing it because we need to use this to other data sets as well. So that's why we are making this generalization and so on. So in this case, we have only one column, whereas generally you will have multiple columns in your data set. So each time this for loop runs, so the first time this for loop runs, the first column, so when you run this, let's say that when this for loop runs for the first time, this I will take the value as 1, and this I will take, as we know that it will take the value as 1. So when you mention x, this column comma 1, it means it's just slicing the data frame that we have. So it will take this first column and it will multiply it with y minus y prediction. So the second time this for loop runs, so it will take the value as 2. So this is nothing but the second column in your data set. So that is what mentioned by this x colon comma I. Okay, so this represents each columns that we have in our data set. So we should find the difference between y minus y prediction, and we should multiply it with each column of the x that we have, and after that we should add this lambda parameter. So you can see this lambda here, and as if you remember, we have initiated this lambda parameter, and we will give this give some value for this lambda parameter when we are calling this Lasso regression model. Okay, so this is the first equation that we have. So I'll just check once whether this is correct. So it's if self dot w is greater than or equal to, or like if it is greater than 0, so dwi, so just give a space here. So dwi is equal to minus 2 into self dot x I dot self y prediction plus self dot lambda parameter. Okay, so there it should be self dot m, because we are using this within the class of Lasso regression, right? So it should be self dot m, and then we should include a else condition. So else condition is nothing but when the weight value is less than or equal to 0. So we shouldn't, like, we don't have to mention this, because one condition is weight is greater than 0, so automatically the other condition is weight is less than or equal to 0, so we shouldn't mention this, so we don't have to mention that. So else it will be, the same thing, but in this case we are going to use, yeah, so this should be a negative sign. Okay. Okay, so just a second. So we have this if condition and the else condition. So we know that if the weight value is greater than 0, we should use this equation. If the weight value is less than or equal to 0, we should use this equation. The only difference is that here the penalty term is positive, and in this case the penalty term is negative. Okay, so yeah, so that's what we have written here. So minus 2 into x into this y minus y prediction minus self dot this lambda parameter divided by this self dot m. So this is how we can write this gradients formula. And the last thing that we need to include with this gradient is dj divided by db, which is my gradient for bias. Okay, so I'll just mention here that, okay, so there is one more thing that I have to do. I think I have missed that one. So we should, I'll just name this as gradient for weight. So before creating this dw, so we should initiate this as an array. So dw is equal to np dot zeros self dot n. Okay, so we are creating a numpy array with all the values as 0. After that we are implementing this. Okay, so like the reason we are using this n with the weight is, as I have told you earlier, the number of weights is equal to the number of input features, and we know that n is the number of input features that we have. So that's why when we are working with this weight, it should be the same shape as the n. So that's the reason we are mentioning this n all the time. So in this case we have only one input feature, so we will have only one weight value, and this dw will contain only one weight value. So in case you are having, let's say you are having 5 input features, so in that case your weight will be a list. So this weight will be a list which contains 5 values, and this dw will, this for loop will run 5 different times, because we totally have 5 columns, right? So that's what I mentioned it, because this particular thing is individual columns of this x. Okay, so I hope everyone is clear up to this point. Now we should, we have just completed the gradients for this weight. Now we should write the code for this gradient for bias, which is dj divided by db, which is very simple. So minus 2 by n summation of this yi minus yi cap. Okay, so come here, and so the indentation is very important here. So make sure that you are making the indentation correct. So this dj should be the same as you have for your for. Okay, so you can see the number of dots here, which is 4. Okay, so this is where we need to write it. So db, so db is equal to minus 2 into np dot sum self dot y, sorry, so it's y prediction. Okay, and this thing should be divided by self dot m. So this is the formula that we have here. Okay, so you may think there is a summation symbol here, right? So we don't need to mention this, because this self dot y is not a single value, so it is all the salary values. So this all this true salary values will be, we totally have 30 values, right? So all these values will be subtracted from the predicted value, which is my y prediction, which will again contain 30 values. So each of these values will be subtracted, so you don't need to mention this summation. So that's why we are using this np dot sum. Okay, so after that we should, multiply it with 2, and we should divide it by self dot m, because we have this minus 2 by m term here. So this is how you can build this dj divided by dm. So I'll just check this once whether the indentations are correct. So all the define should be, in the same indentation, and we have this for loop within this indentation. Okay, so this for loop comes under this define, and we have this if condition and else condition within this for loop, and this db should be in the same line as your dw and in this particular for loop. Okay, so the indentations are correct. We can move on to the next part, which is, so we have completed this, right? So dj divided by db and dj divided by, w and db are fine. So now the last thing that we are going to do is we are going to write this updating weight and bias formula. So once we do this, the code is ready. So this is for updating the weights and bias. So I'll just come here and I'll also, include a text here as gradient for bias. Okay, so this is the gradients we are finding for bias, which is nothing but my dj divided by db, and this part is for the gradient of my weight value. Okay, because we have the if condition here, whether the w is greater than 0 or less than 0. Okay, so the next step that we are going to do is updating the weight value and bias value, updating the weights and bias. Okay, so it is nothing but self dot w is equal to self dot w minus my self dot learning rate into my dw. Okay, and the self dot b is equal to self dot b minus self dot learning rate into dB. Okay, so this is nothing but this formula. So we have this formula, right? So W is equal to W minus alpha into dW, and B is equal to B minus alpha into dW, where alpha is my learning rate that we have initiated here. So that's what I have mentioned here. So W is equal to W minus learning rate into dW, and B is equal to B minus learning rate into dW. As we are using this within the class, we should mention this self. So when you run this, your weight value will be updated again and again each time this for loop runs. So okay, so when when this particular for loop runs, it will call this update weights function, and this update weight functions will run, and the number of time this for loop runs is the number of iterations that we are mentioning. So it can be 100 or 1000, any number that we are specifying, and when this runs, each time it runs, we will get the updated weight value and bias value and so on. So once all these things are completed, we will get the most optimum value for this weight and bias. So that is the next step, and when we get this weight and bias value, and finally we already created this predict function. When let's say that we have the best value for weight and bias, let's say that the weight value is 10 and this bias value is 5. So those value will be plugged in here, and when you give a new value for x, in other words, when you give the new value for years of experience, our model based on this equation can determine what is the salary of the person, which is y. So this is how this entire thing works. So I'll just give you a quick recap of what are all those things that runs. So like the first step is creating this Lasso regression class, and within this we have totally 4 functions. So these are the 4 important functions that we need. So the first function is the init function, second function is the fit function, third is the update weight functions, and finally we have this predict function. So what happens is we will manually give the value for this learning rate, number of iterations, and lambda parameter. So that part will be done while we are calling this Lasso regression. After that, when we call this fit function, we will provide the model with the values of x and y. So in this case, the values are these two values, x and y. Okay, years of experience is your x and salary is your y, where this first column is my input feature and this column is my target. So we will give this x and y, and we do that. This model will initiate the value of weight as zeros and as well as the bias as 0. And for this weight value and the bias value, we will try to find the y prediction using the predict function. Okay, so you can see the predict function here, and based on this value, we will get some predict function, right? So those value will be subtracted from a true value so that we get the cost function. Okay, and this is where the gradient descent comes into play. So the gradient descent will run the number of times that we have mentioned in that number of iterations parameter here. So each time it runs, it will try to find that gradients dw by db. So this db is nothing but the change that you want to give. So how much your cost function changes when your weight changes. So when you step down through this curve and so on, because we want to reach this global minimum, right? So that's what happens in this particular step where we are implementing this gradient descent. So within this for loop, we are calling this updating weights, and each time this for loop runs, your weight will be updated one time and again. So each time it will update the weights, and we have the function for this update weights, where first we are trying to find the value based on the initiated weight value and the bias value. After that we are creating this gradient. So we are initiating this gradient with numpy dot zeros, and after that we are creating another for loop, and this is where my I will substitute my gradients function, my dj divided by db and dj divided by dj divided by dw and dj divided by db value. So that is mentioned here. So after that you will get those two values, and after that you can substitute this values in this particular equation, which is w is equal to w minus learning rate and b is equal to b minus learning rate into db, and so on. So once all these things are completed, you have the best parameter values, so the best values for weight and bias, and this will give you the most accurate prediction when you use your models. So that will be plugged in here. So w and b, after this code is completed, and when you call this predict function and you give a new x value, so this predict function will tell you what is the value of y based on this equation. So this is how lasso regression works. So we initiate the parameters, and the model will randomly initiate weight value and the bias value. After that it will try to run this gradient descent, where the weight as well as the bias value will be updated, and finally this is the code for it. And finally, once we get this optimum value, we can predict the value of y based on the value of x. So this is how lasso regression works. So in the next video we will try to implement this lasso regression. So we will take a data set and we will try to build this lasso regression and see how this works, and we will compare the performance of this lasso regression, the one that we have built, with the lasso regression that we have in our sklearn library. Okay, so I hope everyone understood all the things covered in this video.